they come in and it's true.
Hmm. The real do like a 180 with the maths too. The maths was a bit sus.
Yes, sir.
Wasn't
Yeah.
only the maths too, because like the bio paper, they didn't change up the format, but they bring a lot of niche topics, and that's what they kind of do with all the papers.
That niche testing is really dumb.
One
I
question,
agree.
sir. Sorry to interrupt, but after the logic gates and the transformers and everything, would we be doing the atomic?
Yeah, we could do that.
Okay.
So I feel like I want to focus on electrical parts of physics today and nuclear. With nuclear, real easy, guys. Nuclear is so easy, it's crazy. Extremely easy. That's so easy. The electrical parts of physics just confuse some people, and it's one of the harder ones for sure. Did anybody here learn about Lenz's law and Faraday's law?
Faraday's, yeah, not lenses.
Okay, so basically, anytime you induce a current, as a result of a change in magnetic field, the current in the coil, it would want to create a magnetic field in the opposite direction to oppose the change in magnetic flux. And that's Lenz's law. So Lenz's law says that if you induce a current via a change in magnetic field, the coil that gets the induced current is going to want to generate a magnetic field in the opposite direction to oppose the change in magnetic field. Kind of like inertia in mechanics.
Still have a borrow brain for physics and stuff.
Nah, I can't borrow my brain. Need my brain.
Genius.
Yeah, Christian?
So you in the electrical part of physics that dealing with specifically like heat capacity and stuff, or you do that already?
No, we did that yesterday. No, not yesterday. We did that day before yesterday. That's still on physics.
Okay.
For the thing with the transformer, is that like when the EMF is induced via mutual induction?
Yeah, correct. So in a transformer, you have the primary winding, which is a bunch of wires looped in a coil, and that will be wrapped around the soft iron core. Well, we typically use soft iron core because it has a low permeability and it would allow the magnetic flux to be channeled through it. And then in the other side, in the secondary winding, you have a coil of wires as well. And essentially, when you run an AC current through the primary winding, it's going to generate a change in magnetic field, and that's going to cut the secondary coil. And if you have a change in magnetic flux cutting a current carrying conductor, it's going to generate a current. It's going to induce a current in the secondary coil. And depending on the turns ratio, the EMF would be higher or lower. We look at all of that today. Don't worry. It sounds complicated, but I don't think it is complicated. Much more time than me, buddy. Yeah, power in is equal to power out. All right. I think I'll go make it for the 12 hours.
Yes, sir.
Sí se
For sure.
puede.
Yes, sir.
I don't.
Sure.
You have to know yourself. Eh? If you know you can make it, don't push yourself to a crazy degree. I'm gonna check the YouTube channel.
Yes, I need my sleep. I need
So
my
you're
sleep.
giving me any breaks?
Yeah, I'll give all your breaks.
So the latest I will stay up to is like about 11 and then I clock it out. Because I had to
Okay.
get sleep.
No problem. All right, we're ready to start, right?
Yes, sir. Are we run it?
Here, when I'm done with the electrical physics as well as nuclear physics, we're going to look at the January 2026 paper, the full paper, okay?
Sure.
Then we're going to do the June 2025, and then we could look at any other topics you all want in extreme detail, of course.
So I was now going to ask you if you could go over 2025 paper.
Yeah, we'll do that. All right. So, like I say, all I had to put on the camera for today, right? Just putting that out there. I gotta put on the camera today. Or if you want to fully benefit now, if you understand what I mean.
Yes, sir.
All right. So the first we're gonna look at is electrostatics. So I have my notes right here. Give me a second. But yeah, some energy, you know. I gotta give me energy and thing, you know what I mean? So
Yes, sir.
don't be moving there and thing. All right. So people here, anybody here do chemistry as well?
Yes, sir.
Yes, sir.
Yes, sir.
Did you know that all elements are made up of atoms, and in an atom you have a what? What do we call this? This is what?
A nucleus.
Nucleus. Nucleus.
Yes. In the nucleus you have protons and
Neutrons.
Neutrons.
Trons.
and in this case, this is our shell, this is our orbital. Since it's the only shell we have, it's called the valence shell. Now, in the shells, you have what?
Electrons.
Electrons.
Trons.
A lot of electrons.
So here what I'm saying, right? Here what I'm saying. If you were to rub two materials together, some of the electrons from one material could be transferred to the other material. Now, let me ask you that question. If something is gaining electrons, do you think it's becoming more negative or more positive? It's gaining electrons.
Negative, sir.
For those
More
of you guys that don't know, electrons are negatively charged. Negatively charged. Cool. So if something gain electrons, it becomes, what would I say? Would I say positively charged or negatively charged?
Negative.
Negatively
Negatively
charged.
charged.
Negatively charged.
Right. And question, if one material is losing the electrons to give it to the other one, then the material that is losing the electrons becomes what?
Positive.
More positive.
Okay, is everybody okay with that concept so far?
Yes, sir.
Yes,
Yes,
yes, sir.
Right. So, like I said, electrostatics is the study of charges at rest. Okay, we know that. So, what is it that you really have to know? Well, I just explained what you had to know. When you rub two materials together, some of the electrons can be transferred from one to the other one. Does anybody here know about the electrostatic series or the triboelectric series?
Yes.
Okay, I'll no peak, boy. I'll no peak. So, like, let me give you an example, right? So, we have a glass rod here. We have a silk cloth. As you can see, where is the electrons leaving from? The electrons are leaving from where?
The glass rod.
The glass rod. Because
Yes.
when you rub the glass rod on the silk cloth, the negative electrons from the glass rod will go into the silk cloth.
Correct. And if the glass rod is losing electrons, it's going to become positive. The silk cloth is now gaining electrons, so it's going to become negative. And as a matter of fact, don't we have more negative charges than positive charges? Well, let's see that.
Yes, sir.
Yes, sir.
Yeah, we have 4 negative charges and 3 positive charges. So it's our net charge of negative. Cool. And if one now becomes positively charged and the other one becomes negatively charged, you'll have what develop in between them. If you have oppositely charged things, what's going to happen?
Forces of attraction.
Force of attraction.
Exactly.
It's what
Now,
attracts.
now you guys can take a screenshot of this, right? So I'm going to give you a quick example. Say I had vinyl and I rubbed vinyl against wool. Tell me, which one is going to lose the electrons? Is it the wool or the vinyl?
What?
So if you notice, everything to the top has a weaker tendency to gain electrons. So if it has a weaker tendency to gain electrons, then it might quicker what?
Give up.
Might quicker give up electrons. Cool.
Might
And everything to the bottom has a stronger tendency to gain electrons. So it quicker accept electrons. So since wool is quite over here, wool is going to give the electrons to the what?
To the vinyl.
To the vinyl.
Exactly. So when I rub vinyl against wool, the electrons from the wool are going to go to the vinyl. So the wool would now become more charged.
Negatively charged?
No, the wool is given
Positive?
electrons. The wool is given
The wool will
electrons.
become
Positive
positively charged.
And since the vinyl is now gaining more electrons, it's gaining more electrons. What's the answer?
It could be negatively charged.
It's gonna be negatively charged.
Great. So just to summarize that, if something is given electrons, it's going to become what?
Positively charged.
Positively charged.
Positively charged. If something is given away its electrons, it's becoming less negative. If you're becoming less negative, you're becoming more what?
More positive.
Positive.
Exactly. So if you're giving up electrons, you're gonna become positive, and if something accepts electrons, it's gonna become negative. Cool. So when we're talking about charges, you need to know this main formula over here. Q is equal to IT. Tell me fast. What does Q represent? What does Q represent?
You charge?
What's your charge?
Charge.
What do we measure charge in?
Coulombs.
What does I represent?
Current.
Current.
What does T represent?
Time.
in seconds.
I'm in seconds.
Now, some
Time
of you
and
guys
seconds.
may not know this, right? But when we talk about charge, we're really talking about the amount of electrons. You'll see what I mean shortly. So charge is measured in coulombs, and 1 coulomb is equivalent to 6.25 by 10 to the power 18 electrons. So back what I was saying, right? Charge is just a measure of the number of electrons. When you charge your phone, electrons from the charger is flowing from the charger to your
Phone.
Exactly. So when you put your phone to charge, electrons are being pumped from your charger to your phone battery. So charge is just a measure of how much electrons something could store, in case you didn't know. If something could store charge, you have a battery and you also have capacitors. If all you do unit 2 physics, you could deal with that a bit more. Right. So the main formula you should be familiar with is Q is equal to what?
IT.
IT.
Is equal to IT. Cool. All right. Let me do a quick question. Right. So during a certain lightning strike, a current of 5 by 10 to the power 4 amp flows for a time period of 0.15 milliseconds. Calculate the quantity of charge of the lightning strike. So they mention in current and they mention in time. What formula to use?
Q equals IT.
Q equals IT.
Right. What's the current?
So 5 times 10 to the power 4.
What's the time?
0.15.
Right. Now a lot of you guys are going to go into the exam and put 0.15, plug that into your calculator, and you're going to get it wrong.
No, you have to.
You need to look at the prefix. You need to look at the prefix. What is the prefix there?
Milliseconds.
Milliseconds. So if it's milli, guys, if all you need to take a screenshot of this, no. You need to know your prefixes. Right? Cool. You need to know your prefixes. All right. So I am not going to write 0.15. I'm going to write 0.15 by 10 to what power? Since it's milli, it's going to be what power?
-3.
Exactly.
-3. So
Plug in.
which means milli is 3, right?
7.5.
Milli means 10 to the power -3. Milli means 10 to the power -3.
Okay.
All right. So plug that into your calculator. Let me know what you guys are getting.
7.5.
What are you guys getting?
7.5.
7.5.
7.5 what? 7.5 what?
Column C.
Coulombs. Good. And if I wanted to find the number of electrons, I would have to multiply 7.5 by what? So if you guys remember, if you guys remember, hear this, right? I would have mentioned it here. 1 coulomb is equivalent to how much electrons?
6.25 times 10 to the 18.
The power of 18, yeah.
So if we have a charge of 7.5 coulombs and I wanted to find the number of electrons, wouldn't I just multiply this by 6.25 by 10 to the power 18?
Yes.
Because in 1 coulomb, you have this amount of electrons, but we have 7.5 coulombs. So you multiply to find the total amount of electrons you have. Which brings me to another formula. Q is equal to NE. You know about this formula or no?
No.
Nope.
Nope.
No.
Okay.
No, sir.
What do you think
Yes.
Q represents?
Charge.
Quantity.
Charge.
Quantity of charge.
Q is charge, right? What does E represent?
Electron.
Electrons.
Electrons.
Electron.
Electrons, charge of our electron. And what do you think N represents?
The amount of electrons.
Number of
Number
electrons.
of electrons.
Number of electrons. So if you wanted, you could have divided both sides by E, and you could find for the number of electrons given a charge and electrons. Okay, cool. So we'll look at this shortly. But remember, Q is equal to IT. Q is equal to IT. Guys, I always measure time in what? What do I measure time in?
Seconds.
Seconds.
I am Makila. I am on YouTube, you know. I don't know what people on TikTok. I am on YouTube. My YouTube channel is Math Vibes. I'm live on YouTube right now. Okay. All right, let's tackle this question quickly. So any volunteers? Quick. We're moving on speed today.
Yes, sir. Yes, sir.
All right, so Nikolai, the makers of a cell phone have upgraded its battery capacity from 4,320 coulombs to 9,000 coulombs. So guys, since I upgraded the capacity, it could now store more. It could now store more of what? Store more what?
Quantity.
Yeah.
More charge.
More
It could now
electricity.
store more electrons. More electrons, right? It could now store more electrons. And then they say, Nikolai, a charger delivers 0.6 amps. How much more time will it take to charge a new battery than the old? So do you have any suggestions, Nikolai?
Using the formula Q is equal to IP.
Right, we could use Q is equal to IT. Nice. What else you want me to do?
Substitute.
Divide both sides by I.
Well, we could substitute first. Nikolai, tell me what to do.
Only I put in the charge. We have the charge. We have the coulomb.
So what do you want me to plug in for charge?
The difference.
The difference, yes. Guys, if we want to find how much more time it will take to charge a new battery, and we would just have to find for the difference in charge,
Yes, sir.
Yeah.
Yes, sir.
because and the difference is what's going to change the time.
Yes, sir.
So Nikolai, what is the change in Q?
I got 4,680.
It got 4,680.
Yes, sir.
Right, so we can now plug that in for Q. So we'll say 4680. What's the current?
0.6 amps.
Right, by time. If I want to find for time, what will I do?
Substitute for T. Make T the subject by dividing by 0.6.
Both sides by T.
So Nikolai, I wouldn't say substitute, but you said the correct thing in the second part there. You would divide both sides by 0.6. And so what is 4680 divided by 0.6?
I got 7,800.
What you get?
7,800.
And that time will be in what? Somebody tell me fast.
Second.
Seconds.
If I ask you to convert this to hours, what are you going to do? If I ask you to convert it to hours, what are you
By
going to
60.
divide by 60?
60
no,
multiplied.
Divide by 360.
Nah, 3600. 3600.
Yeah, 3600.
If you are confused, right? How much seconds you have in a minute?
60.
60 seconds.
So in 1 minute, you have 60 seconds. In 1 hour, how much minutes you have?
60 minutes.
60 minutes.
60 minutes.
So if I multiply 60 by 60, what will I get?
3600.
3600.
So in 1 hour, we have 3600 seconds. If I wanted to convert that to hour, I divide that by 3600. Nice. So let me know if you guys okay with this question.
Yes, sir.
All right, cool.
Sir.
All right. I'm going to go into the well. I'll just wing this because I'm taking too long. All right, so here we're going to say, right? Typically, if two things are oppositely charged, what would happen if two things are oppositely charged?
They'll attract.
They would,
It's an attract.
They will attract each other.
Right, they will attract each other. Let's consider we had a positive charge there and a negative charge here. Okay. Could anybody tell me what an electric field is quickly? I'll start you off. The electric field is the area around which what?
Electric charge express electric force or something.
Okay, so
Electromagnetic force.
The region around an electric charge where another charged particle would experience a force.
correct. So over here you can see that we have two differently charged particles, a positively charged and a negatively charged. Now, obviously, since they have different charges, they're going to be attracted. But how? Is the positive going to move to the negative or vice versa?
So an
From the
opposite
positive to the
opposites
negative.
attract.
Right. Positive is going to go to the negative.
Opposites attract.
Right. So positive goes to negative. So how would I draw this arrow? Would I draw this arrow like this or would I draw it like that?
Outwards.
I would draw it outwards because if I were to
Outwards.
complete this, if I were to complete it, you can see that it has to go to the negative.
Yes.
How would I draw this? In what direction?
Inwards.
Inwards.
Because if I were to complete this, guys, if I were to complete it, wouldn't the positive go towards the negative, like so?
Yes, sir.
Yes, sir.
Yes.
Is everybody with me?
Yes, sir. I like this way you explaining it. My teacher did use north and south.
No, that's for magnets. We look at that just now. Right now, we are dealing with electrostatics,
Okay.
which is the study of charges. Right?
Okay.
Cool. So you have a positive charge and a negative charge. Does everybody understand this?
Yes, sir.
Yes, sir.
Yes,
Okay.
sir.
So
So
what
if-
is the definition? What's the electric field?
All right, let me take a screenshot, right? An electric field is defined as the region around which a charged particle or object within which a force would be exerted on another charged particle or object. So let me explain, right? Over here, you see, now we have two differently charged particles here.
Yes, sir.
Are you seeing the field lines?
Yes, sir.
For those of you guys that don't know, these are the field lines. So once you have two differently charged particles very close to each other, it's going to develop field lines, and the field lines will tell you how the attraction is. And so when I ask you about electric field, I'm just saying it's a region around a charged particle or object within which a force will be exerted on another charged particle or object. Because it makes sense. If you have two differently charged particles, you'd experience a force of attraction. The area around which they experience this force is just the electric field. Quickly, if you had the same charge, what would happen?
They will repel.
They repel each other.
Each other.
They repel each other. Okay, cool. All right, so guys, quickly, if I just had a positively charged particle here, I would draw the what direction would I draw the arrow in? Would I draw it away or coming in?
Away.
Away.
Now this makes sense because if I have a negatively charged particle close by, wouldn't it go from positive to negative?
Yes, sir.
Right. So
Yes, sir.
if we're talking about a positively charged particle, the field lines extend outwards. Consequently, if I had a negatively charged particle, the field lines are going to go how?
Inwards.
You go inwards.
Inwards.
It would go inwards. And why would it go inwards? Well, wait, I make a mistake there. Yeah. Because again, doesn't it go from positive to negative?
Yes.
Yes, sir.
Yes, sir.
Okay, so is everybody with me up to this point? Or you're confused?
Yes, sir.
Yes, sir.
Okay, good. Let's tackle this question now. So define the term electric field. Anybody want to tell me what the electric field says?
Sir, I would like to go.
All right, Renisha, talk to me fast.
Okay, so the term electric field is defined as a region around charged particle or an object within the force that would be exerted on the other charged particles or objects.
That's correct. I want to make it a bit simpler for you guys. the region around two charged particles where forces of attraction or repulsion felt. I think this is a bit easier to remember. So it's just a region. Okay, if you have two charged particles, guys, if you have two charged particles and you can either have repulsion or attraction,
Yes, sir.
right? So all you had to say is just a region around two charged particles where the forces of attraction or repulsion will be felt. Repulsion will be felt. It don't have to be hard. It don't have to be hard. Right? Try to understand anything as opposed to just memorizing. Do that.
Yes, sir.
Okay, good. So over here, what charge does this look like? Somebody tell me, what charge does this look like?
Positively charged.
Positive charge.
Positively charged. Because
So
there's
they
only positive signs inside of the circle.
just positive signs. So they're saying draw arrows to indicate the pattern and direction of the electric field in the region surrounding the sphere. So guys, I'm really trying to move with pace today. Because we have real work to do. So I'm going to draw the arrows going inwards or outwards?
Outwards.
Outwards.
Sir.
Are we getting these marks?
Yeah.
Yes, sir.
Yeah. In the name of Jesus.
Yeah.
Right,
Amen.
we're getting these marks. Nice. So far, they have 4 marks in the bag, you know. You have 4 marks in the bag. Real easy 4 marks. Alright, things gonna get a bit more complicated now. So a smaller uncharged metal sphere Q is suspended by a cotton thread and brought closer to the positively charged particle as shown in figure 9. Draw the distribution of charges on sphere Q. Now they're telling us that sphere Q is what?
Negatively
Uncharged.
Negatively charged.
Let us say negatively charged.
It said uncharged.
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 And you had to be careful, you know. It told us it was uncharged.
Uncharged metal sphere.
Right. So if it is uncharged, then the number of positive charges and the number of negative charges are going to be what?
Equal.
Yeah.
Equal.
And why does this make sense, chat? Well, if you had 5 positive charges and you had 5 negative charges, the mask will have a big question. What's 5 minus 5?
0.
Zero. So that is why I was saying the positive charges need to be equal to the negative charges. So the net charge would be equal to 0. So they would cancel off now.
Oh, that's right. That makes sense.
Yeah, makes sense. So here we're going to do, right? A lot of you guys might be tempted to just do this. Like, okay, some of you might just put 3 positive charges. Or any, it can put any amount, right? It can put any amount. Celine, try not to draw on the screen, please. Celine, it will fall out, you know. You can't just be writing on your screen just so. So, if it is uncharged, wouldn't it look like this? Well, I drew it wrong on purpose, right? Let me just mix it up. Let me scramble it. Okay, does this look uncharged?
Yes.
Yes, sir.
Why is it uncharged? Somebody explain that to me. Why is it uncharged?
The same amount of negative and positive.
Positive and negative.
Right. We have
They
3
are
positive.
equal.
We have 3 positive and we have 3 negative. So we have the same amount. But let me ask you a question. Are you think that correct?
No.
No, sir.
Nah.
No, sir.
No.
Yeah.
No, that's not correct. Let me explain. Over here, it is what? What is the charge for this?
Positive.
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 Right. So you're gonna have electrostatic induction happening here. Let me explain. So over here, it's a positive charge. Like this is definitely positively charged, very strongly positively charged. So it's going to induce a pull on the what charges? What charges is going to want to come closer to the
Charges.
Negative.
Negative.
So this is not correct. If you draw this wrong, you're supposed to draw it like this. Everybody
So
understand
now-
this or not?
Yes, sir.
Yes, sir.
And why is that happening? Well, it's positively charged. It's going to want to attract the negative charges. But because there's a space in the middle, all that could happen is the negative charges would settle on this end. So as you can see, we still have the same amount of charges. It's just, you just have a charge separation. That's what you call it, a charge separation. So let me know if you understand.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Consequently, if this was negatively charged, right? Negatively charged sphere, and I bring a uncharged sphere here, what would settle on the left-hand side?
Positive charges.
Positive charges.
Positive.
Right.
Positive charges.
Nice. We're cooking, guys. We're cooking. So far, there are 6 marks in the bag. How are you feeling about that?
Good.
Good.
Feeling
Then
great.
good.
All right. An earth wire was briefly brought into contact with sphere Q, as shown in figure 10, and then removed. Okay, so let me explain. So remember, we had drawn 3 negative charges here and 3 positive charges here.
Yes, sir.
Yeah.
That's what we had do. And they said a what wire was brought into contact with sphere Q.
The earth
Earth
wire.
wire.
Earth
Earth
wire.
wire.
Now, on this side, we have a delta positive charge. It is a very weak positive charge, right? It's a very weak positive charge, but a positive charge nonetheless. Now, let me explain that again, right? Do you guys understand that the net charge of this particle is 0?
Yes,
Yeah.
sir.
Yes,
Yeah.
sir.
Yes, sir. Yes, sir.
But here what I'm saying, where are all of the positive charges condensed? It's condensed on which side?
The right
The
side.
right-hand side, sir.
Right hand side.
Right hand side. So on this side, you're gonna experience a very weak quote unquote positive charge. And if you attach that to the ground, I want you guys to understand this. Earth acts like an infinite reservoir of electrons. So if Earth is like an infinite reservoir of electrons, then and this side is positively charged, then what's gonna happen?
The electrons will start moving
The
towards
electrons will
us.
be attracted to that side.
Yeah. Nikolai, let me know if you understand.
Yes, sir.
Yes, sir.
I should have like a better explanation to this side here. So before contact, sphere Q has negative charges on the left and positive charges on the right. So Q is polarized but uncharged. That's the proper terminology. It's polarized. What does that mean? Polarized so kind of sounds like what? Polarized kind of sounds like what?
Pole and south.
Equal.
It kind of sounds like pole, polarized, pole. And when you think of pole, and think of like North Pole and South Pole,
Yes, sir.
Yeah.
it's a similar concept
Yes,
happening
sir.
here. If you think about this as the Earth, you have the negative, quote unquote, negative pole here and the positive pole. They're separating. So we say that this sphere is polarized, but it is
Uncharged.
it's uncharged. It's uncharged.
Uncharged.
Cool.
So can I take a screenshot of this part here?
By the way, guys, if all I have my 17-hour marathon notes, everything is there, right? I was given all that for a reason. That document is amazing. That document is all you need to know. That document is amazing. I really take my time on make that. All in one night. But yeah, Renisha, I'll get a screenshot, Justin. So here what? Because Q is polarized to the right side, it acts as if it's what? On the right side, it's acting as if it's what?
Positive.
Positive.
Positively
Positive.
charged.
And here I'm saying the earth wire acts as an infinite reservoir of electrons, approximately 10 to the power 24 electrons. It's a really big number, is it not? 10 to the power 24.
Yes, sir.
And so if this side is acting as positively charged, and again an infinite amount of electrons here, in a brief time they're in contact with each other, the electrons from Earth is going to flow into the
Positive side. The
Positive side.
Positive.
The positive
positive
side.
side. So here what? After contact, you're actually going to end up with what's in the sphere?
Negative.
Negative.
Negatively charged.
Negative.
Hello? It freeze?
It's so frozen.
Oh my god, I thought it was me. I think it's Sue.
Yeah, I thought it was me too.
I thought it was me too.
Yeah,
Frozen.
why?
What's going on?
It is Wi-Fi.
Way.
Wait, Nikolai still get cut off, yes?
I sure it's the end. They cut him and cried.
Oh God, why all this so?
That might be true because I know in some parts, TNT cut out this thing, the current would cut for like certain hours and certain areas.
When? For
Just
today?
not cutting now.
Today?
I know it was between. I know, like, yes, that's why I said different areas had different days and times. So I don't know.
Crazy.
Most likely.
Why? When we have physics, why?
Yeah, why?
Oh,
It could have
Okay,
been
come
math,
back.
but
Okay, I'll
why
be back.
now?
Wait.
but
Too much of you guys have your camera on. The internet bandwidth can't handle it.
Oh, okay.
Yeah,
oh,
that's happening.
okay.
That's what happening, right? So like, Nikolai, you can leave your camera on. Nikolai is my son, guys. He has to have the camera on. You know what I mean? Yeah. Right. I upgrade this Wi-Fi, you know, I paying more money. Should I be able to take it, but can't take the jam.
Yes, sir.
Small.
So I seen the full bars.
All right. So yeah, I'll with my rights.
Yes,
Yeah. So like this side over here is positively charged. So after contact, we're gonna flow into the sphere.
Negative charge.
Negative charges.
Negatively charged particles.
Right. So watch. And they said it was brought in brief contact. So only a few electrons are going to flow into sphere Q. But after we remove it, after we take it, after we remove the contact, this sphere now becomes what?
Negatively charged.
Negatively charged.
Negatively charged.
Negatively charged.
It becomes
Right.
neutralized.
It would not become neutralized. Let me ask that question, right? It was uncharged before, but because electrons are gonna flow into it, now you have some extra electrons, so some extra negative charges. So the net charge is what? Since it has more negative charges and positive charges.
It will be negatively
It'll be
charged.
negative.
Negatively charged. Negatively charged. So they want us to describe what happens in the wire and state the final charge on Q. So does anybody want to give it a I can't explain it here, but let me hear if you could explain it.
So I could try.
Give it a try.
Okay, so since the wire is a earth wire, it's like a grounding wire, that means that the electrons from the earth could go inside the Q. So Q can become more negatively charged.
Wait, but why? Why is it going from the earth to Q? You had to tell me why.
It connected, I guess.
Alright, so if you don't mention the charge separation, you're gonna lose our marker.
Okay.
So Shivesh, you had to talk about the positive charges are to the right, and so therefore sphere Q is polarized. Because it's polarized, it has a very weak positive charge. And so that's going to cause the electrons from Earth to flow into the sphere Q. You have to mention that.
Right, because opposite charges attract each other.
Yes.
Okay, I understand.
So I'll put on the ideal answer here. So Shivesh, give the ideal answer a read.
When the earth wire touches sphere Q, electrons flow from the earth to the right side of the sphere Q because it is electron deficient. When the earth wire is removed, the extra electrons remain on Q, therefore sphere Q becomes negatively charged.
So what do I mean by electron deficient? Shivesh, are you seeing any negative charges on this side?
No, sir.
No, so that's what I mean by electron deficient.
Yes, sir.
So is anybody confused to the ideal answer?
So by chance, how do you know that the charges that coming from the earth negative?
Oh, that's a known fact. That's a known fact. That's like a fact.
So that never changes.
No,
Okay,
that never
sir.
changes. That never changes. Yeah.
So
Wait. For those of you guys that are okay, when I talk about current is just the flow of what? Current is the flow of what?
Electron.
Electrons.
Electrons.
Right. anytime you have a difference in anytime you have a potential difference, you have current flowing. So you see how over here is like positively charged with it. See how over here is like quote unquote positively charged and here's negatively charged. Electrons will start to flow because of the potential difference. And like I say, Earth is an infinite reservoir of electrons. That's always the case. Mariana, see you raise your hand. Talk to me.
Right. So, the electrons in the neutral, like the ball, right, the sphere, is it possible that they travel to the other positively charged thing and leave it completely unknown? Never.
Nope.
Okay. And
Let me
then,
ask you a question.
is it possible?
Wait, let me ask you a question. Are these two in contact with each other?
No.
No.
No. If two things are not in contact with each other, I like to use the word starts with I. That's the word I'm looking for. I. In what? In
Induction.
induction. Right? So Mariana, the spheres are not in contact with each other. So no.
Okay. And then, is it possible for electrons, like in the grounded, the wire to go down?
Nope. Let me explain why. So Mariana, you understand why there's a charge distribution on that?
Yeah, I understand why they separate.
They separate because you have a big positively charged sphere over here. So it's going to attract all of the negatively charged particles to the left side of sphere Q. So this side over here is electron deficient. It becomes polarized. Why am I saying that, Mariana? You see any electrons on this side?
No.
No. And so on this side, it experiences a what charge then? Quote unquote, it experiences a what charge?
A positive charge?
Yeah. So this side is positively charged. And so if it's positively charged, what is it going to attract?
Negative charges. Electrons.
Yes. And the negative charges are electrons. So hope you understand this.
Okay.
And electrons always flows to the positive. Because, yeah. So do you guys understand that or not?
Yes, sir, I
Yes, sir.
understand.
Yes, sir.
Kinda. Okay, which parts are losing it from? Okay. So do you guys understand that this side has no negative charges, right?
Yes, sir.
Yes,
Yes,
sir.
sir.
If it has no negative charges, it's going to act as a on this side, it's going to act as if it's what?
Positive.
Attracting?
Positively charged. It's going to act as though if it's positively charged. So let me ask you a question. If something is positively charged, right? What is it going to attract?
Negative
charges.
electrons.
Negative electron.
They wouldn't say negative electrons. That come like a double negative because electrons are
Okay.
understood to be negative.
Well,
Very good.
negative.
And from the Earth, we have a near infinite supply of electrons. So you're gonna have electrons from Earth going where now? Since this is acting like it's positively charged, electrons are gonna flow from ground to where?
Sphere Q.
charge.
Yeah, to the
Exactly. Are you understand this or no?
Yes,
Yes.
sir.
Yes, sir.
Yes, sir.
Right. So over here is acting like it's positively charged. Why? Because that big sphere over here, that big sphere over there is causing the negative charges settle on this side, and obviously would repel the positive charges. So it's forcing them to settle on this side. So it's making that sphere Q polarized because you have a negative pole and a positive pole. And so this side is acting as if it was positively charged. And so if it's acting like if it's positively charged, would it repel electrons or would it take in electrons?
Taking.
Right. And the Earth
Taking.
supplies what? What does the Earth supply?
Near infinite.
Negative.
It supplies
Negative
electrons.
Electrons.
Right. So you're gonna have electrons from the Earth flowing up the wire, and it's gonna go into which sphere?
Spare Q.
Sphere Q. And so after I remove the wire, you notice that in sphere Q you have what? What was on there before?
More
More negative
more
charges.
negative charge.
Exactly. Watch, we have two negative charges now, and we understand why. Because when there was in contact, electrons from the earth went up the wire and went into the sphere. So, again, this is the answer. When the earth wire touches sphere Q, electrons flow from the earth to the right side of sphere Q because it is electron deficient. Because of the charge separation, remember, all the positive charges on this side, so it acting as if it's positively charged. And if it's positively charged, then the electrons from Earth would want to go up the wire and go into into the right side of the sphere. Because the right side of the sphere is acting as if it's
Positive.
Positively.
Positive.
exactly.
positive.
And so some electrons from Earth is going to remain in sphere Q. And so when you remove the wire, some of the electrons are going to remain, and that's going to make it negatively charged. So do we understand that?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, cool. Cool. So let's take a screenshot. Right, I'll add the screenshots.
Yes, sir.
No, not yet, sir.
And if you want, don't forget I'm live on YouTube. Or you can go on YouTube and take a screenshot too. But YouTube you could like go back. All right? Don't forget that. All right. We're gonna move on. We're going pace today, guys. Pace. Right. I need a volunteer to help me with this question. I need a volunteer.
Me, sir.
All right. Talk to me. Christian, give it a read.
The battery in an electric car can be charged by passing a current of 11 amperes. Calculate the charge stored in the battery.
Wait, so before you say anything, somebody said on YouTube Live, would the electrons travel down the wire instead? No, it would not. The whole reason why the electrons traveling up the wire. Okay, somebody explain it to me. Why you think the electrons traveling up the wire?
They
Because
are
the
attracted to
The
the
right side
positive
of the
charges.
sphere is positively charged.
Because the right side acting as if it's
Positive.
Positively
So
charged.
therefore, that's why the electrons from the earth wire will go up into spare Q to
exactly.
put more negative charges.
Now, if it was the other way around, nothing will happen. Nothing will
You move
happen.
down.
No, nothing will
Oh, okay. Yeah,
It
you
will
bring up
go
a good point.
down.
Yeah.
It will
It
go
would go
down.
down.
It will go down.
It would go down.
Yeah,
It would
if
go
it
down.
was the opposite way,
Oh,
if
because
it
it's
was the opposite way, it would have
Yeah.
gone down instead of go up. It would have gone
And
down.
so when I remove the wire, I would be missing some electrons. So the net charge of the sphere would be what?
Positive.
Positive.
Positively charged.
Positively charged. So let me run that back again. If it was the other way around, and this was negative, then this side over here acting like if it's what? This side over here acting like what?
Negatively charged.
Negatively
It's
charged.
negatively charged.
Negatively charged,
It
right?
will go down the, yeah.
It will go down.
Right. And when you remove the wire, that sphere is going to be missing some electrons. So it's going to have a what charge?
A positive charge.
Positive.
Positively
Positively
charged.
charged.
Yeah. So hopefully you understand that.
Yes,
Yes,
sir.
sir.
Yes, sir. Understand. Thank you so much.
Not a problem. Right. And if I ever say something that sounds kind of sus or like correct me, I love that. I love to see. I don't just want to teach all them maths and physics, you know. I want to like mold you guys into adults that could think with your own brain as opposed to just listening to people. So much people are just listening to people, right? But if you could think, you could oppose authority and you could make a change. You know what I mean? So I like what I see. So Christian, Christian, what formula do you use here? I see in current and I see in time.
Q equals IT.
Right. Now here what? Some are gonna go into the exam and are gonna do this. And I'm telling you it's wrong. Some are gonna say 11 by 8. That's wrong. Why is that wrong, Christian?
Because
Christian, why is that wrong?
the table values.
This is not the SI unit for time. What is the SI unit for time?
Seconds.
So I don't multiply 8 by what?
5600.
What is 8 by 3600?
Um, 28,800
28,800.
seconds.
Right. So here what, guys? In any question, well, here what, there's like an exception. When you're doing the lenses questions, you can leave the lengths in centimeters, that's fine. Just make sure you have the same units across the board. In gas laws, the only thing you gotta be wary of is the temperature. When you're doing the gas laws, the temperature had to be in what? The temperature. Kelvin. And in generally speaking, in any other question, if you see a prefix, don't forget to write the prefix, right? You see milli 10 to the power -3, so on and so forth. And if you're dealing with a question and they give you time in hours, you have to convert it to seconds because we just work in the SI units, right? So 28,800. What is 11 by 28,800?
316,800. 316,800.
And let me ask that question. That would be in what? What would that be?
Would it be coulombs?
It'll be coulombs.
Sir, I'm lost.
Somebody said they lost. Okay,
Yes, sir,
so
me.
in the question, they told us that a car. Okay, I'm gonna just say this, right? And it's gonna sound kind of bad, but if you expect to come to this session and just master physics, no. Like this session is for people that was revising and doing their work. So like if you all prepare early for tomorrow now. If you didn't do anything in physics and they come here, you'll benefit, may not, but they wouldn't benefit to a great degree. Because I kind of banking on you guys to know some of the formulas at least. You understand what I mean? You don't know some of your formulas. But I'll explain it back. In the question, they're saying a battery in an electric car can be charged by passing a current of 11 amps through it. So they're giving us current. Current is I. They're giving us current. And they want us to calculate charge. Charge is Q. And they're telling us stored in the battery after 8 hours. So the person that's confused, as you can see in this question, they're giving us current. We have to find for Q and we're given time. Is there any formula that you know that has Q, I, and T in it?
Yes, sir.
A formula have Q, I, and T in it.
Current.
Nah, Q is equal to IT. Q is equal to IT.
IT.
Right, Q is equal to IT. Anytime you see charge, current, and time, Q is equal to IT. So, Tamale, what's the next thing I did? They gave me time in hours. Is that the SI unit for time?
No, sir.
No, the SI unit for time is what?
Seconds.
Seconds. So I have to. So in 1 hour, we have how much seconds? Can you hear?
1 hour.
Okay, so in 1 hour, we have 60 minutes and we have 60 seconds. 60 by 60 would give us 3,600 seconds.
3,600.
Right. So if we know it have 3,600 seconds in 1 hour, and we have 8 hours, I'll have to multiply 8 by 3,600. So 8 hours is equivalent to 28,800 seconds. So here what? Again, you see in charge, that's what the way to find for. They're giving you current and you have time. You have to use Q is equal to IT. Q over here represents charge. And so it's going to be the current. What's the current? Tamale, any question? What was the current?
So current is what we're finding?
No, they want us to calculate the charge, Q.
Charge. The current is 11.
11 is the current. And what was the time we just found?
28,800.
Right? And when you plug it into a calculator, you'll get the answer. That's simple. Q is equal to IT. Remember that formula.
Okay.
Q is equal to IT. So Tamale, what does Q represent? Q represents what?
Current.
Nah, Q does not represent current.
Charge.
Charge.
Oh,
Q
charge.
is charge.
Sorry.
That's okay. Right? Q is charge. What does I represent?
Current. Current.
And T represents?
And T is time.
Time in seconds.
Already, time had to be in what?
Seconds.
Question: if I see microseconds, I gotta multiply by what?
By
But times 10 to the
10
power
to
6.
-3.
-6 micro.
-6. All right.
Yeah, micro. Milli is what? Where's milli?
-3. Times 10 to the power
-3.
All right, so you gotta be careful, right? You gotta be
So
careful. You gotta
it's
be careful.
10 to the power of -3.
Wait, so let me just verify something. Yeah, I know micro is 10 to the power -6. Ole, please take a screenshot. Don't forget this, please. Micro is 10 to the power -6. Milli is 10 to the power -3. All you need to know this. Need to. All right. All right, cool. So that was our 4 marks. I think I'll again our 4 marks in the exam.
Yes, sir.
Yes, sir.
All right.
Yes,
Part
sir.
two. Part 2. Somebody read part 2 for me.
Calculate the resistance of the battery given that the voltage used is 220 volts.
All right, so Nikolai, here what, right, Nikolai? You're seeing resistance. So that's R. Seeing that. And you're seeing voltage. What are you thinking about? Which formula are you thinking to use?
Power? No.
Nah.
V is equal to IR.
All right, what is V is equal to IR called?
Ohm's law.
Ohm's law.
Right, and Nikolai, let's see if we could use this formula. To use this formula, V is equal to IR. I need to know 2 other variables. So over here, Nikolai, they're telling you what the voltage is. What is the voltage?
220 volts.
They're telling you that the voltage is 220 volts. And they want us to find the what?
The resistance, which is R.
Right, so I'm putting a question mark by this. We have the voltage. Nikolai, do we have the current?
Yes, sir. We do.
What's the current?
11 amps.
11 amps. So I have the current, I have the voltage, right? So Nikolai, could I make R the subject of the formula?
Yes, sir. By divided by I.
Yeah, yeah.
Volt.
By dividing by I throughout. And by the way, guys, you see this V is equal to IR? This is called Ohm's law. Do you all know about Ohm's law?
Yes, sir.
Sure.
Yes,
Sir,
sir.
isn't power is P equal to IR as well, or no?
Nah.
Power is equal to V times I or V squared divided by R. So yeah.
If you're talking about resistive losses, it's P is equal to I squared R.
Oh, okay.
Aren't there 3 formulas, right?
Yeah, so power is equal to VI, P is equal to I squared R. And what's the other formula you're thinking about?
V squared divided by R.
P squared divided by R. Wait, no, wait. No.
V squared divided by R.
Yeah.
Yeah.
We typically do use this formula, right? But here what I'm saying, if you were to make I the subject of the formula for over here, well, you can make a direct substitution and get this formula. If you were to use these 2 formulas here and you made a substitution, you can get the V squared on R. But we typically don't use our formula.
Okay.
Like I do my bachelor's in electrical engineering. Like I never use this formula. I never use our formula in my life. Yeah. I use I squared R though. We use I squared R all the time to find resistive losses. Cool. So Nikolai, R is going to be equal to, why isn't I writing?
Is it in
R
right?
Yeah. V is 220. Where's I?
11 amps.
Alright, so what you got?
I got 20.
20 what? 20 what?
Ohms.
Right. Would you guys have gotten any 3 marks?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Right, so here what I'm saying. You're looking to see what you have. In this question, we want us to find resistance. So I'm putting that down one time. I'm putting down R. And next thing they tell me voltage. And well, in the last question, I know they give me current. So what formula has R, V, and I in it?
V is equal to I.
Ohm's law. So that's all I want you to be thinking. Look at the variables you have and ask yourself, what formula do I know has these in it? Okay, cool. right? What should I do next? Okay, let me explain transformers, and should I do that next? Yeah, I can do that. All right, so let me give a little introduction to this, right? So, do you guys know what a direct current source is?
Yes, sir.
Yes, sir.
Yes, sir.
All right. I should probably explain what is conventional current flow and electron flow. So let me show you something, right? So I'm going to draw a little circuit here. I have a resistor, right? I have a bulb here. All right. So if you see the longer terminal represents the what?
Positive
Positive
battery.
side.
Positive charge.
Yeah, positive charge.
Right. And this terminal represents the what?
Negative.
Negative charge.
Negative charge.
Right. Now you see this symbol over here? This symbol over here telling you that you're dealing with a DC source, and specifically a battery. Now, we're going to look at conventional current flow first. Conventional current flow tells us that the current flows from where to where?
Positive to negative charge.
Positive to negative.
Positive to negative.
Right, positive to negative. So let me run that back again. The longer terminal is positive, shorter terminal is negative. And if we're talking about conventional current flow, which is what we're going to be dealing with unless they explicitly state electron flow, it'll be from positive to
Negative.
right. Are you guys with me there?
Yes, sir.
Yes,
Now
sir.
let me ask you guys a question. Will the direction of the current ever change?
No.
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 No, sir.
No. It will only change if you do what with the battery terminals.
Yeah, switch it.
If I switch it. But under normal operation, will the direction of the current ever change?
No. No, sir.
No. So when I say, so let me explain something, right? When I say DC, I mean direct current, implying that the direction of my current does not change with respect to time. It's a fixed direction. Now, quickly, guys, I'm going to switch the terminals. Let's observe the effect that has on the circuit. So, tell me, guys, what terminal this is? Positive terminal or negative terminal?
Negative.
Negative.
What terminal is this? Positive or negative?
Positive terminal.
And does this represent a DC source or an AC source?
DC.
AC, specifically from a
Battery.
battery. All right. So now, look at this, right? Remind me, in conventional current flow, the current flows from where to where?
From positive to negative. Positive to negative.
Let me ask you guys a question. What happened to the direction?
It changed.
It changed.
But it only
Went in the
changed.
opposite direction.
But it only changed because where you do?
Yes,
You
so.
flip the battery.
Flip the battery.
Good. So that is DC, direct current. So let me give you guys a little definition for direct current. So I have a proper definition here. Direct current. DC current is current that always flows in one direction. That's all. Right? As you guys would have saw, you had to directly flip the terminal for the direction to change. Are you doing that under normal circumstances? When you put your battery in your remote,
No, sir.
when you put your battery in your remote, you just interfere with the battery after until it's dead,
Nope.
Until it did.
right? Well, obviously when it's dead, you gotta change it, right? But under normal circumstances, a battery provides a current in one direction. It provides a flow of current in one direction, from positive to negative. And that, my friends, is conventional current flow. So, if direct current is in one fixed direction, what do you think AC is?
Alternating current.
Alternating current.
Alternating current.
And what does alternating suggest?
Okay, going
It's
any
not
Direction.
changes direction.
Right, the symbol is given by a sine wave. Would you guys have seen this before?
Yes, sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
That's it.
Alright, well, you've seen it now. Comparable again. So, okay. Let me just say this is 120 volts at 60 hertz. Okay. Do you guys understand this? Okay, I'm telling you that an alternating current is typically represented by a sine wave. And why am I saying that? Well, if it's alternating current, it suggests that as time passes by, my current what?
Moves.
Moves back and forth.
It changes direction. The current moves. The current changes direction. So I'll try to show you what I mean by that. I'll try to show you what I mean by that.
Negative half cycle and positive half cycle.
Yes. So I just gotta make a common circuit here, like we would see at home. Don't you guys literally just screw a light bulb into like a fixture and the light is come on?
Yes, sir.
Yes.
Yes, sir.
Yeah. Right. So here we're saying, right? Let me just say at a time of 5 seconds, this was the direction of the current. All right. Stay with me. And let's just say we have some other time here. Probably a time of 7 seconds. Do you think the current will be flowing in the same direction at
Yes.
7 seconds?
No.
No.
No. No. The direction of the current could switch. And so if the direction of the current switches, I hope you understand why we call it alternating current, because the direction of the current, what?
Changes direction due to time.
Changes direction.
Not due to time. Right? You'd say that for alternating current, the direction of current changes with respect to time. So
Okay.
that's alternating current. So let me explain that one more time. Guys, if it's alternating current we're dealing with, will the direction of current remain the same?
No, sir.
No,
No,
sir.
sir. No, sir.
No, it would not. No, it will not. And so let me ask a question. I'm going to tie in this into it. We had the positive terminal here, and we had the negative terminal here. So didn't current want to flow in this direction?
Yes, sir.
Yes, sir.
When I switched the terminal, what happened?
It went in another direction.
Went in the next direction.
Went in another direction, or policy and I went in the other direction. So here's what I'm saying. In this instance in time, if we were to treat this as terminals, what would I call this terminal at this snapshot in time?
Negative.
Negative terminal.
And this would be the what terminal?
Positive.
Positive terminal.
Because conventional current flow tells us that current flows from
Positive to negative.
Positive to negative.
Good. So here what? In the other snapshot in time, you notice that the current is going in what?
The reverse direction.
Negative, positive.
Negative to positive.
So let me
From
make a
negative to positive.
let me make a little note here, right? So at this point in time, this terminal is acting like a negative terminal, and this terminal here is acting like a what?
Positive.
Positive terminal.
Positive.
Positive.
Okay. So in this point in time, this terminal is acting like a what?
Positive.
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 And this one acting like a what?
Negative.
Negative terminal.
Well, let me ask a question, right? Do you think that's a physical thing that happens, or do you think it's just as a result of the type of currents being supplied?
And respect to the
Result.
time.
The type of current.
it's the type of current.
Exactly, it's the type of current, right? I'm not here switching this back and forth. It happens automatically because, okay, when you guys, if any of you do electrical engineering and thing, and you look at generators, most generators create alternating currents. You know why? Because if we want to generate a current, you must have a change in magnetic flux. And if you have a change in magnetic flux, automatically that will produce an alternating current. Because in alternating currents, the direction of the magnetic flux, like if you use the right hand grip rule, you'll see that the direction of the current changes every time the current changes. I will discuss that just now. But what I'm trying to say is, if you have a change in magnetic field, you'll also have a what current?
A change in the current.
Exactly. I'll explain it just now. But hopefully you understand this.
Yes,
So
sir.
if we're dealing with alternating current, the terminals are effectively switching automatically, in a sense. So let me show you guys something quickly. So if I were to draw a graph here of voltage versus time, do you think the polarity would change?
No.
Okay, you're probably wondering, sir, what do you mean by polarity? If I'm calling this 5 volts, if I switch the terminal, what do you think I'm gonna call that?
5 volts.
5 volts.
Negative.
I was saying negative 5 volts. If you switch the terminal, it's gonna be negative. It's gonna be negative. But let me ask you a question. When we're dealing with direct current, does the polarity ever switch? Like, okay,
No.
tell me guys, when you put your battery in your remote, is about take the battery out and switch it?
No.
No, sir.
No. So does the polarity ever change? Does the polarity ever
No,
change?
don't change.
No,
No,
sir.
sir.
No. So like, if it's 5 volts, it will remain 5 volts no matter how much time passing by. This is what a direct current graph looks like. Now, as you can see, it's a straight line. And why do you think it's a straight line?
Because it remains constant.
It
It never
remains
changes.
positive.
It does not. The polarity of the battery never reverses, so it remains at 5. However, if we're talking about an alternating current, what do you think happens to the polarity as time changes?
It
Switches
changes.
from positive to negative.
So between negative and
changes.
positive.
Alternate.
Yes! I don't know if I've seen it in Overwatch. Over here, that was like the effective terminals, and over here, these were the effective terminals. And so, as you can see with our alternating current waveform, as time changes, the polarity changes. And so, the voltage would change from positive to
Negative.
Negative.
and negative to positive, and vice versa. So,
Yeah.
So it's like
Just-
the sine graph.
exactly.
So I was gonna say that's how the graph is, but never mind.
Yeah, this is how the graphs look. So, I'm going to try to explain it one more time. If we are talking about DC, we're talking about direct current. Does the direction of the current ever change?
No, sir.
No,
Nine.
No,
sir.
sir.
No, it does not. It does not change. And if that's the case, then will the polarity of the battery ever change?
No,
No,
sir.
sir.
No, sir.
No.
No. So if it's 5 volts, it will remain at 5 volts as time passes by. If I had switched the polarity and it was at negative 5, then it would just stay at negative 5. You understand?
Yes, sir.
Yes, sir.
Yes, sir.
It never changes. Watch. As time passes by, if you realize it's still what?
5.
It's still
Five.
five.
It's still 5.
But okay, let's look at this scenario. In this scenario, okay, remember, alternating current. What changing with respect to time here?
Current
Polarity.
flow.
Polarity.
The direction of the current. As time progresses, the direction of the current changes. And if the direction of the current changes, it suggests that the polarity what? The polarity is how the terminals are.
Switching.
It's switching. So watch. At this point in time, it's 5, and at this point in time, it is
Minus 5.
Minus 5.
Negative 5.
So hold on.
Negative 5.
Direct current, direction of current doesn't change. Alternating current, direction of current changes with respect to time. That's simple. That's simple. Right? So if all you want, or you can take a screenshot. So for direct current, the DC, the current always flows in one direction. For alternating current, the current changes direction periodically.
So during the time where the thing switching, right? Or does it switch so fast that like what is it that no current is like momentum like I don't know how to explain what I want to ask.
Okay, I know what you're trying to say. It depends on the frequency at which it switches at. So like the faster the frequency, the shorter the wavelength or the periodic time for the waveform. If the frequency is like, if it switches at a very slow rate, then if it switches at a slow rate, then the waveform is going to have a very large wavelength. And let me see if I can show you something fast, right? Let me see if I can show you something fast. And I think this will blow your mind. I think this will make so much sense. Because I think I know what you want to ask, man. You ask him, sir, what happened in between? Like, does it just not
Yes,
not come on? Should have a. Let me show you something cool, right? Let me make a quick circuit. Right, what does this represent?
Alternating
Right.
current.
Alternating current.
Right.
Alternating current.
I'm gonna put a light emitting diode. Probably saying, so why are you gonna put a light emitting diode? You'll see why. Probably power resistor. Do you guys know what light emitting diode does?
Not fair.
What does a light emitting diode do? Say that again.
Sir, another light emitting diode would have the cathode and the anode based on its connection in the breadboard. It would but it will show the light after current pass through.
What we
Sir,
said.
also, quick question. Wouldn't that light emitting diode like blow if you don't put a resistor?
Yeah, we'll go if you
So,
do power resistor. Okay, come on a second.
This is real cool, so.
Yeah, it is very cool.
Excuse me, what app is this?
This is every circuit.
Does this app is this app on Android for Android phone as well?
Yep.
Okay. Gonna download that, yes?
sir, have you ever used KiCad before?
Yes. I have KiCad downloaded on my laptop. I use it for electrical engineering.
Oh yeah, to make PCB designs, right?
Yeah. I don't know why I don't want to work. Give me a second. Like, this is a very basic, it's like a very basic software, right? Like, if you have like a more robust software, like what's the name of that one, movie? Like, you'd be able to actually change the amplitude of the alternating signal, but I'm not seeing the ability to do that over here. I'm not seeing that over here, which is really bad. So I'm not sure if it will work. Wait, not sure what happened. I'm gonna try to. Okay, that's really weird. I don't know why I'm behaving so.
Sir, how?
Give me a second. Alright, so this is how. Alright, so let me explain something. So a light emitting diode only allows. Okay, the diodes, right? Diodes only allow current to flow when they're forward biased, so like in one direction. If you switch the terminal, it's not going to light. So let me see if I can share that quickly. I really don't use this software, you know. I really don't use this one. Give me a second. So when I switch this, I think the LED will light.
No, it wouldn't.
No, sir.
No,
Wouldn't light.
reverse.
It wouldn't light. But I want an alternating source. I don't know why it be even so. Don't want to say the word I want to say. They're not letting me change the voltage of the alternating waveform. Don't know why they're not letting me do that.
So could you think of the diode as the arrow which should the one direction?
Say that again?
Would you think of the diode as where it should the triangle in one direction?
Yeah, you can think of it like that.
Sir, wouldn't the Zener diode allow for a part of a backward bias for reverse bias within the circuit?
So like xenon diodes, you know about all right, so different diodes have like different they have different
Like the
like the
PD, the
voltages
depletion layer? Oh,
like the voltages that they drop is different. So they have like different breakdown voltages and different dropping. They have different voltages. Like they drop different voltages across them. I'm not sure
yeah,
why
like
this working.
germanium and silicon, right?
Yeah, but I'm not sure why that's not working. I don't
Yes.
use this app, guys. I don't use this app.
One
But like,
question.
okay, wait, let me try to explain it to you. Okay, Mariano, let me try to explain it to you here, right? So between these cycles, let me explain what's happening. So it would start off at 5, and then the amplitude of the voltage is going to start to decrease. So Mariana, at this snapshot in time
Yes,
here,
sir.
it is at the current is let me just say the current is 5, right? Let me do a graph. Wait. Okay, let me do V. Do you understand that when I completely switch the polarity, what happens to the direction of the current? When I completely switch the polarity,
It switches
One goes up
also
and one.
because
it switches right now. Here's what's gonna happen in the middle. Over here, it's 5 volts, right?
yes, sir.
Over here, it's a little less than 5, a little less than 5,
Mhm.
and over here it's at what?
0.
Right? And then it's changing direction now, and it completely changes direction at -5. So what I was trying to show you with the LED is that it would like blink, like the brightness would increase and it would decrease.
Mhm.
But it wasn't working. It wasn't working. Because like, okay, as time passes by, what's happening to the voltage here? Well, for this half cycle, what's happening to the voltage?
Decrease.
Decreasing.
It decreases until it hits 0, and then it goes below. And this would be when the polarity is completely switched with the maximum amplitude, and then it would come back up. If the app was working, right? You would have seen that the LED, the light emitting diode, would have gone bright, it'll come off, and the whole process would have repeated itself. It'll be like blinking, dependent on the frequency of the alternating waveform. Yeah.
Okay, so then at 0, is it that no
It's off.
current or
No current.
it's
No
just
current.
off?
No current.
Okay.
No current. Because guys, if it's over here, then what's the voltage? What is the voltage?
0.
0.
0. Remember, V is equal to IR. If I make I the subject of the formula, that's going to be V over R. If V is 0, what's the current?
0.
0.
0.
Yeah.
Mhm.
Yeah.
Okay.
Hope you understand. Okay, cool. So does everybody understand direct current and alternating current?
Yes, sir.
So, but one question though.
Talk to me.
What the diode I know you said that it will be blinking when it decreases as it hits 5 and it continues going down, it will blink. But when it hits -5, would it be bright as well or would it stay off?
Okay. Depending on how you position it, like you see the positive half cycle over here?
Yeah.
All right, this is the only cycle it's going to be on for. As soon as it dips below negative, it's going to be off.
Okay, that makes sense. Okay,
Then it's
cool,
going to
cool.
come over here. Because it needs to be in a certain direction. And do you guys know that there's like a certain threshold with which a light comes on? Like a light doesn't come on at any specific voltage. It has like most LEDs come on at like 3.3 volts.
Yeah, I think so too.
Yeah. All right. So are you surely understand direct and alternating current?
Yes, sir.
Yeah, sure.
Okay, cool. I want to discuss Faraday's law now. Nikolai, I see you have your hands raised.
Yes, sir. One question, sir. I know you talked about the different diodes, right? And I know from what I did in school, and we draw like one. So like the other different diodes, would they have the same concept, or each of them will have a different way of
Same
how
concept.
one
Same
concept?
concept. Same concept. Same concept. All diodes allow current to flow in one direction. Yeah.
Okay.
Right. So let's look at Faraday's law. And I'm going to draw a basic transformer here. So what does Faraday's law says? It says that the rate of change of magnetic flux is directly proportional to the magnitude of the induced EMF. Okay, it sounds complicated, but stay with me, right? So Faraday's law says that the rate of change of magnetic flux is directly proportional to the magnitude of the induced EMF. So from that, here we're saying, right? If there's no change in magnetic flux, will an EMF be produced?
No, sir.
All right, let me say it back again because I know lots of you guys are confused. Okay, somebody that is confused, I want you to read that for me. Read that for me.
The rate of change.
Wait, Christopher, I know you're not confused. Mariana, read it.
The rate of change of magnetic flux is directly proportional to the magnitude of the induced EMF.
Okay. Do you know about magnets?
Yeah.
Okay. Do you know that if I run current through a wire, a magnetic field is going to develop around it?
One.
Nah or yeah?
Yeah.
Right, so let me show you something, right? So do you know what your right hand grip rule, Mariana?
Nope.
Oh, okay.
Mm-mm.
Alright, so let me try to explain this to you guys, right? So let me use the same circuit I used above. Okay, so Mariana, can you see that in this circuit, we have the current flowing in this direction?
Yeah.
Okay. Here's what I'm saying, guys. Anytime you have a current in a wire, around the wire, you're going to have a what?
A magnetic field.
Mariana, if you didn't know, now you know.
Mm.
And so, okay, let me try this. Okay, so like, you never hear about the right hand grip rule before?
Nope.
All right, so here what? Your thumb tells you the direction of the current, and your fingers, okay, your
Mhm.
fingers, what we're saying, right? Like, okay, your thumb is the direction of the magnetic field, and your fingers, how they curl around would indicate the current.
Okay. So, like, if the magnetic field is left, my thumb will point left, and then the rest of my fingers is the magnetic field.
Yes,
That is it?
yes, that's what I mean. So, like, let me give you a quick example, right? So, can you see that in this wire over here, we have a current passing through the wire?
Yeah.
So, around the wire, what did I draw?
Arrows going the other, well, going around it.
Right. That is actually a magnetic field. So, the right-hand grip rule could be used vice versa, as you'll see when we do the 2017 question with Lenz's law, but it could be used vice versa. Let's use it in this context, Mariana. So in this context, your thumb represents the what?
The current flow.
Okay, and your fingers, what do they represent?
The magnetic field.
So let me show you what I want you to do, right? Point your camera and I want to see your right hand. I want to see your right hand. Let me see your right hand.
Oh, I'll put my LZ. Okay. Right hand.
All right, so here what you do, right? I want you to point your finger in the direction of this current over here. You have your camera mirrored.
Hang on this. Double
Okay.
pressure.
All right, cool. And I want you to observe how your finger is curling. So like rotate your finger, like rotate your hand.
Like so?
Yeah. Right?
Okay.
Now I'm gonna be seeing it a bit different, right? Because you have your camera mirrored. But what I am actually seeing, I'm actually seeing this. So
Oh.
Mariana, when you rotate your hand, your fingers are curling in what direction? Clockwise or anti-clockwise? So like,
Clockwise?
does this look like clockwise?
No.
Nah. I would not be clockwise. I'll be anti-clockwise.
Anti-clockwise.
So Mariana, let me run through the process one more time. So over here, the current is going in this direction from left to right. So that's what my thumb is pointing to. And my other fingers are going to curl and they're going to indicate the direction of the magnetic field. So when I line up my thumb with the direction of the current and I twist my hand, guys, what does this look like? What does this look like? It looks like this. This is clockwise or this is anti-clockwise?
Clockwise?
Clockwise. Nah, that's not clockwise.
Is it clockwise?
That's not clockwise.
It's maybe to your camera said, sir.
Guys, if you guys have your camera mirrored, it'll be a problem. Okay, like watch. So like watch. Like watch.
So that'll be anti-clockwise.
Yeah, it's
following the
anti-clockwise.
direction of the circle, sir.
Yeah,
Anti-clockwise.
anti-clockwise. It's anti-clockwise. It's anti-clockwise. Now, if I were to switch the direction of the current, do you think it would still be anti-clockwise?
No.
No, sir.
No. So here, what? Let's try to switch it and see what's going to happen. Let's do that quickly, guys. If I have a camera mirrored, please change it to like how I would see it, because that gonna cause some real confusion to everybody that looking, because they're gonna be seeing you pointing in the other direction. All right. So here, what to do? You're going to take your thumb and you're going to point it in the direction of the arrows, because these would represent the direction of the current. And we are trying to see what the magnetic field would look like around it. So Nikolai, wait upon the camera. Nikolai, you there?
Yes, sir.
I point the camera. So Nikolai, I want you to point your thumb in the direction of the current.
Sir, wait, my camera looking like it inverted. We just
Okay, that's fine. That's fine. So Nikolai, well, for me, it's in this direction. It's in this direction, right? Guys, literally, you're just putting your thumb in this direction. That's all you're doing. That's all you're doing. Right? In this direction. And Nikolai, I want you to curl your fingers. Curl your fingers. Like so. And if you're having a hard time seeing it, Nikolai, what you could do is you could take your hand and keep it facing you, right? And so Nikolai, as you can see, it's going in the opposite direction. Okay, like it's real hard to teach virtually, but
I think
your camera mirrored.
Yes, I think your camera mirrored
yes,
because
sir, your camera kind
Yes,
of
sir.
mirrored.
up to that.
you know, like until you could read the text.
Yeah.
Yeah.
Yeah, so then it wouldn't be mirrored.
So you just had to imagine yourself backwards.
Come on a second. Let me
I'm
actually
sorry,
let me
put it in the right direction.
mirror my video preview. Okay.
Mm.
Now it should. Am I right? So like now you shouldn't be able to read the text.
So
Now
it's
say the
It's
same.
the
That's
same.
how you can see it.
I like to see it now.
Yeah.
Say the
Okay.
same for me. I don't know.
Yeah, I guess so.
Yeah, I can see
Yeah,
the
I
text
can
in the
read it
little.
too.
Yeah, so it never changed.
Okay. It never changed, right? Okay. Here what? An easier way to explain this. Let me show you an easier way to explain this. A much easier way to explain this.
So
Let's look at a current going into the paper and a current coming out. So you see X. What does the X represent?
well, it going in.
And this represents a
Coming
current.
out.
So here's what I want you guys to do. This should be a bit easier for you all to understand. So stay with me. So you're gonna take your finger and you're gonna point it at the X. What does that look like, guys?
Clockwise.
Clockwise.
So that looks like anti-clockwise to me.
You sure? You sure? Watch. Watch.
So yours is anti-clockwise, but
Yeah.
on our side it's clockwise.
Clockwise.
When we doing it,
No,
it's clockwise. But
I
when
get
you doing
clockwise.
it,
Like
it's anti-clockwise.
watch. This is like okay. So this is 12. 1. It's clockwise.
Nah,
So
clockwise.
you definitely mirrored it.
I just
That's
mirrored.
anti-clock.
Okay, like I just mirror the camera. Let me unmirror it. Give me 1 second. Okay, so I'll unmirror it.
So
I don't know what's going on. Like I don't know what's going on.
Because he's doing
I figure
in his
unmirrored was
so
the
he's
same
seeing
thing.
the clockwise and we're going to
Yeah,
see
what?
the answer.
Here what? I'll just do it for yourself, right? Do it for yourself. Do it for yourself. Do it
Sorry.
like just take your finger, right, guys? Take your finger, point it towards the screen, right? Point it towards the screen. Like, okay, let me show you what I'm trying to do, right? Like literally just do this. And like
Right.
wherever your fingers curl,
No,
wherever
it's
your finger,
clockwise.
No, it's clockwise.
It's
like okay,
clockwise.
wherever your fingers curl, just 3 arrows in that direction. That's like the best way I could probably explain it visually.
Yeah, but I was going to ask if you want to use like pictures of somebody thumb, like a hand or something, so to point in the direction of the current and everything.
Well, when this is a thumb here, and your fingers would be curled in this direction. Are you seeing it or not?
Yeah.
Yes, sir.
Yes,
Yeah.
sir.
Yes, sir.
Yes,
I
sir. We've seen it.
understand.
All right. And so if the current is going out, where would my thumb be? Wait,
On the opposite side.
Pointed outward.
Anti-clockwise.
all right, watch. So you see how my fingers are curling?
Yes, sir.
Yes,
Yes,
sir.
sir.
What am I gonna do?
Anti-clockwise.
Anti-clockwise.
Anti-clockwise. ACW.
So let me ask you that question, right? If the current is going in, then I could probably represent that in a 2D way like this. But if the current is going out, okay, let me ask you that question, right? Over here, the current is going in, and over here, it's going out. So is it going in the same direction? Is the current going in the same direction?
No.
No, sir.
No, because watch. Over here, the current going in, right? Current traveling in this direction, going in. And in the other one, the current going out. So let me ask you that question. What did I do? Watch. So I changed the direction or what?
All I seen
And
is white, sir.
The current
sir,
flow.
Oh, okay. Yeah, seen it.
Yeah, seen it now.
so I changed the direction of the current, and as a result of changing the direction of the current, what changed?
The
The
direct.
direction of
Direction.
the
But I think you're in real trouble, boy. Yeah, so because I changed, okay, because I changed the direction of the current, what changes as a result?
The magnetic field around it.
The direction of the magnetic field.
Right.
Flow.
That's what we're going for. That's what we're going for, right? So because I changed the direction of the current, the magnetic field changed. That's the main thing I want you guys to take away from this. Are you guys getting these results?
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
Okay. All right. So let me summarize that. This is real headache to teach away. Like these things, God, when we had to do right hand rule and left hand rule, oh my, I don't know.
We adapt, sir. We adapt.
Yeah, boy, we adapt.
They can't try the thing.
I'll draw it. What?
Like draw a hand and like with that circle and we're gonna like for anti-clockwise and clockwise.
It's a very poorly drawn hand. But like, and this is the thumb. Yeah. So like, if the current is going in, your thumb needs to be pointing towards where?
The outside?
Towards the if it
Towards the
going
paper.
towards the paper.
Towards the paper. And if it's going out, your thumb needs to be pointing where?
To you.
Towards
To
yourself, yeah.
To yourself.
Right. And wait, where come on?
Oh.
Right. Ollie, this is like the easiest way I can think of showing all of this. Like, Ollie, just grab a paper, right? Grab a paper. Grab a paper. Grab a paper. Come on. Grab a paper, right? And stop share again. Here, on, grab a paper, right?
Sir.
Remind me. If it have a dot, that tells us the current is what?
We're outward.
Coming out.
Out.
it
Coming
goes
out, right? So here I want Ollie to do. All I want you to do, take your thumb and point out, right?
Yeah.
You see how your fingers curling? You see that? Oh, let's see now, right?
Yes,
Let's see how
sir.
you
Yes, sir. Anti-clockwise.
Yes, sir.
all you're gonna do is just by your fingers curl, you can draw that arrow. And from there you figure it out. What is this?
Anti-clockwise.
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 Right, that's right. Just show you. This is the first time. This is anti-clockwise, right? If you see an X, what I mean?
Current
Current
going
going
out.
in.
Current going in.
Going out. And
Right. So let me just write it, right? So if you see a dot, it means that the current is what?
outward.
Going
out.
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 And if you see an X, it means that the current is what?
Going
in.
in.
Okay, good. So Alia, boy, my phone for long. I really mystery people on TikTok, boy. Right. So as you can see here, the current is going in. So where's my thumb going to be pointing?
Into the paper.
To the
To the
paper.
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 Can you guys see that my fingers are curling in a certain direction?
Yes, sir.
Yes,
Clockwise
sir.
direction.
So all I'm gonna do, just like
Find
draw.
out where your finger is going.
Yeah, that is all. Are you understand anything?
Yes, sir.
Yes, sir. I understand the motion.
Yes, sir.
Yes, sir. Yes, sir.
So obviously, if the current is coming out, it's traveling in this direction, yeah?
Yes, sir.
Yes, sir.
Okay. Okay, cool. And over here, if the current is going in, if we going in this direction, and
Yes,
Yes,
sir.
sir.
Yes, sir.
long story short, if I change the current, what changes to the magnetic field?
The direction.
The
of the
direction.
magnetic field.
Direction.
Right. I wonder if people on YouTube getting that way.
Okay.
I don't know. They getting that.
So they even seeing what we're doing.
That would be bad if they're not. Somebody say we're doing Fleming's right hand rule. Oh no. No. This is the right hand grip rule, guys. Guys, this is the right hand grip rule. This is not Fleming's right hand rule. Oh my god.
Is that also called corkscrew? Like the corkscrew?
Yeah. So, guys, do we understand?
Yes, sir.
Understood.
Right. Okay, so you see in this instance how we use our thumb to indicate current and our fingers to indicate direction of the magnetic field.
Yes, sir.
You could use this rule, or like in reverse as well. You could use your thumb as the magnetic field, and you could use your fingers as the current. You'll see what I mean when we look at another question. But you could use this rule. You could use this rule reverse. But how are you feeling about this?
I feel like we need to do some questions, Johnny.
Yeah.
Okay, no problem. This is one topic that's really hard to teach for
Didi,
sure.
you can go in the living room. I need to charge my laptop.
All right, cool. So what am I trying to say here?
That man.
Well, Mariana, I want you to read back Faraday's law for me.
Yeah, please.
The rate
What
of
is
change of magnetic
What
flux is directly
I
proportional
can't
to the
do the next thing
magnitude
about
of
the
the
dog.
Wait,
induced
somebody
EMF.
is unmuted. Who is unmuted? Please mute them.
Yes, sir, no problem.
All right, cool. Yeah, Mariana, read it.
The rate of change of the magnetic flux is directly proportional to the magnitude of the induced EMF.
Okay. Do you know what magnetic flux is?
The change in the magnetic field around the cell?
Nah.
No?
So like, okay, let me show you something, right? This you're actually gonna combine a bunch of things here. Let me show you something. So let me just say this was the north and the magnet, and this was the south.
Hmm.
Let me just say that this was the south and the north. You with me?
Yeah.
How would the field lines for this look like? Remind me. Magnets go from what to what? Where to where?
The the north would be attracted to the south pole.
Right, north to
And then
south.
the
North,
south
north
pole.
to north to south, right?
Yeah.
So these are the magnetic field lines.
Mm-hmm.
So you're probably saying, so what is magnetic flux now? So imagine you had like a sheet of paper here, right? Or some area, right? Imagine you had some area. Wouldn't these field lines pass through this paper?
Yes,
Yeah.
sir.
Yeah. And so here's a way to think about it. So like watch. Tell me if you understand, Mariana. So the magnetic flux. So this is the paper I'm talking about. And these are the field lines. Can you imagine the field lines passing through the paper?
Yes, sir.
Can the rest of you guys imagine that?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So like all magnetic fluxes is just the measure of the total magnetic field. Total magnetic field that passes through a given surface area. That's all. That is what magnetic flux is. So I'll say it again. Right? So Mariana, can you see that the field lines are going to go from north to south because that's how magnets behave, right?
Yes, sir.
Right. And I want you to imagine that there's a 2D sheet of paper between the north and the south. Wouldn't field lines pass through the paper?
Yes, sir.
And so wouldn't this have a certain area?
Mm-hmm. Yeah.
So what I'm saying is the magnetic flux is just a measure of the total magnetic field lines that pass through a given surface area. That's all. So like you see how the magnetic field lines passing through the 2D sheet of paper?
Yes, sir.
Right. The amount of field lines passing through that paper is referred to the magnetic flux. So let's do a quick comparison. Just to make sure you have it like locked in. Tell me, which one would have a stronger magnetic flux? Scenario 1 or scenario 2? You tell me, scenario 1 or scenario 2?
Scenario 2.
Right. I'll call this 1, I'll
one.
call this 2. I'll call that 1, I'll call that 2. So tell me.
Scenario 1. Because it has
Right.
more.
Right. So guys, I'll say it again. Magnetic flux is just a measure of the total magnetic field lines that pass through a given surface area. So if there are more field lines passing through a given 2D area, well, obviously area is 2D, then it would have a stronger magnetic flux. Do you guys understand this?
Yes, sir.
Yes, sir.
So let's summarize what we just learned, right? Let's summarize what we just learned. According to the right-hand grip rule, if you change the direction of the current, so if you change the direction of the current, what changes as a result?
The magnetic field.
Magnetic field.
The direction of... Okay, do you guys understand this?
Yes, sir.
Yes, sir.
Mariana, do you understand this for sure?
Yes, sir.
Okay, good. And do you understand that magnetic flux is just the amount of magnetic field lines passing through an area?
Yes, sir.
Okay, good. So Faraday's law says that the rate of change of magnetic flux, okay, what does that mean? Rate of change of magnetic flux. That means how fast the what?
How fast the lines, like how many lines passing through the area? Like
So
how
like,
it changing?
yes, that is what I want to hear. That is correct. Now let me ask you a question, guys. I'm so good at this. If it's a direct current we're dealing with, will the magnetic field lines ever change? Like, okay, would
No,
the...
sir.
No. So Mariana, if
No,
we're dealing with
sir.
a direct current, right? So Mariana, if you have a current flowing through a wire, right? You have a current flowing through a wire, what would develop around the wire?
The magnetic field.
Good. And if the current is remaining the same, will the direction of the magnetic field ever change?
No, it won't.
No, it won't. However, Mariana, if you have an alternating current, right? Doesn't the direction of the current change periodically?
Yeah, yes, sir.
And if the direction of the current changes periodically, what would happen to the direction of the magnetic field lines?
They will change periodically also.
Exactly. So here what we're saying. If you have a change in magnetic flux, meaning that the direction changing, then if it cuts a coil, it will induce an EMF on that coil. Yeah. You want to see a practical example of what I mean?
Please, yes.
Okay, no problem. All your mind gonna be blown. So what I'm saying, guys, if you have a change in magnetic flux, when it cuts a conductor, it's gonna generate a what in it. It's gonna induce a what in it.
EMF.
EMF.
Right. If you didn't know, EMF is just voltage, right? EMF is electromotive force, which is voltage. So if there's a change in magnetic field, it's going to generate a...
EMF.
Right. And EMF is just what? EMF is just what? EMF is just what?
Voltage.
So look at what's gonna happen, right? Can you guys see that as I move the magnetic field lines changes?
Yes, sir.
Are you seeing it or no? I'm only for seeing it or no?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Are you seeing like the little compass is like it's changing, right?
Yes, sir.
Yes, sir.
So watch. Will you see that?
Yes, sir.
Yes, sir.
Yes,
So like,
sir.
so like Mariana, as the magnetic, as the magnetic flux changes and it cuts the copper wire, what's happening to the bulb?
It's turning on, like, and well,
It's
off
turning on,
or
right?
not.
It's turning on. But like, okay, if I just leave the magnet there, if I just leave the magnet there, right? I leave it there. Does it turn on?
No,
Because it's not turning on because okay, is the magnetic flux changing?
no, it's the same. So like
Is
they're
the
not
same?
generating any voltage.
Okay, but if I move it,
It's
watch.
changing.
I want a little zoom in, like watch. You see like little compasses? Watch. Until you can see that it's moving.
Yes, sir.
Yeah.
Yes,
So
sir.
the magnetic field lines or the flux. Okay. Okay, the magnetic field lines, it's going to cut the copper. And can we both agree that if I'm moving the magnet in the coil, then the coil is going to experience a change in magnetic flux? Because like, I mean, you can see it, right? What's happening to the magnetic field? Is it remaining the same or is it like changing?
Changing.
It's changing.
Engine, sir.
And that magnetic field is going to do what to the copper? It's going to do what to the copper?
Make an EMF voltage.
Does it even have to be
Well,
induced?
well, the magnetic flux is going to cut the coil. And because you have a change in magnetic field, you're going to have a change in magnetic flux. And so that change in magnetic flux, it induces an EMF. As you can see, watch, if I leave the magnet there, the magnetic field lines that cut the copper coil, is it changing?
No, sir.
No.
Let me know if you're seeing that. So the magnetic field lines, right? Is it changing there?
No, sir.
No, sir.
So Mariana, is there okay? What's the rate of change of magnetic flux here?
0. Well, it's not changing at all.
Exactly. So will it induce a EMF, a voltage?
No, it won't.
No, it won't. But if I move it slightly, what will happen?
It's generating the voltage because it's changing.
Right. People on YouTube, let me know if you understand that. People on YouTube, let me know if you understand that. Well, I hope they do. Hope they do. So that is why I'm saying that's what Faraday's law says. It says the rate of change of magnetic flux is directly proportional to the magnitude of the induced EMF. That is what it says. So again, guys, if there's no change in magnetic flux, will there be an induced EMF?
No.
No, sir.
No,
No,
sir.
sir.
No. So let's look at how a transformer works now. Let's do that. So guys, can you guys see that we have a coil here?
Yes, sir.
Sure, sir.
Okay.
Yes, sir.
Let's try hooking up this coil to a DC power source. Now I have it hooked up to a DC power source. Mariana, we just learned that if you supply a current through a coil or a current carrying conductor, then around the wire, you're going to have a what?
A magnetic field.
Right. So the magnetic field developed over here is going to cut this, right?
Yeah.
But is it changing?
No.
No, because it's direct current. Guys, if it's direct current, does the direction of the current ever change?
No, sir.
9.
No, sir.
No, it does not. So will the direction of that magnetic field ever change?
No, sir.
No, sir.
9.
No, sir.
No. So what would you guys say the rate of change of magnetic flux is?
0.
Zero. So if it's 0, will any voltage be induced on the secondary side?
No,
No,
sir.
sir.
9.
No, sir.
No. CSEC could ask all this, and they could ask you why don't we use DC power sources in a transformer? You'll have to explain that. However, if we had an alternating, if we had an AC power source, right? AC power source. Let me just say we have a time at 1 second. Let me just say at 1 second, This is what the magnetic field line looks like. Right? Okay, Mariana, at a time of say 2 seconds, will the field lines look the exact same way?
No, sir. Well, no, sir.
No, because in an alternating power source, what happens is the direction of the current?
It changes periodically. So
Right.
if
So
it changes
maybe
in 1 second, it'll change again.
maybe at 2 seconds, you know, the direction of the current probably change.
Mm-hmm.
So if it change now, guys, if it change, wouldn't this coil experience that change in magnetic flux?
Yes, sir.
Yes, sir.
Yes, sir.
Yes,
And
sir.
as a result, it's going to generate a what on the secondary side?
Yeah.
EMF.
A EMF. Yes.
EMF.
Yes. So let me try to understand that. Let me try to understand that, right? Let me try to understand that. So guys, if I have, let's do a quick summary, right? If I have an alternating current source, that means the direction of the current what?
Alternates.
Changes
Changes.
periodically.
Direction of current changes periodically. Okay, and if the direction of the current changes periodically, then what would also change?
The magnetic field.
Magnetic
Direction of the
field.
magnetic field.
Direction of magnetic. So if the direction of the magnetic field lines changes, right? Then you would have a change in what?
EMF.
Yeah,
Nah,
EMF.
a change in magnetic what?
Flux.
Clock.
Change
Yeah,
in
flux.
magnetic.
Field.
Because remember, isn't the flux just the area where the field lines cut in?
Yes, sir.
That's what the flux is, and all the flux is just okay. So like you see how we have the coils? You see how we have the coils?
Yes, sir.
The magnetic flux is just going to be how much field lines cut in the coil. So if the direction of the current changes, the direction of the magnetic field line changes, and therefore you have a change in magnetic flux. Do you guys understand what I'm trying to say on that?
Yes, sir.
Yes, sir.
So the magnetic flux is just where the field lines cut in the what?
The number of coils
Area.
in the transformer.
The coils.
Coil.
Right? Cool. And if you have a change in magnetic flux, you're gonna have what?
A change in name.
EMF.
You're gonna have an induced EMF.
Induced EMF.
Induced EMF in secondary coil.
And that's basically how the transformer works.
That is it. That is it. I know it sounds really complicated, but do you guys understand it to some extent now?
Yes, sir.
Yes, sir.
All right.
Yes,
So
sir.
okay, good.
Yes,
So
sir,
I have
to some extent.
to some extent. All right. So this coil over here is called the primary coil or the primary winding, and it just comprises of copper wire wounded about into a coil. You guys know what a coil looks like?
Yes, sir.
Yeah or no?
Yes, sir.
Yes, sir.
Yes, sir.
This over here is to denote a soft iron core. You typically want, because I'm asking that question, right? I'm asking, I literally have a transformer. Let me get a transformer. Let me get a transformer. I have a transformer right here. Surely the transformer. Oh, let's see the transformer. This is the transformer.
Yes, sir.
Right. So can you see that there's like this thing over here, right? Are you seeing that? There's this thing over here.
Yes, sir.
Yes, sir.
And you can see that there's like wire wrapped, like, okay, there's like a red one over here and a blue one over here.
Yes, sir.
Yes, sir.
All right, so this is a soft iron core. And the purpose of the soft iron core is to channel the magnetic field lines. Because I'm asking a question, right? You want most of the magnetic field lines generated by the primary coil to cut the what? You want that to cut the what?
Secondary coil.
Secondary coil.
Right. Do you want the magnetic field lines to just go all over the place?
No, sir.
No, sir.
You
No,
don't.
sir.
So this soft iron core has a very high magnetic permeability. So it's going to allow the magnetic field lines to be channeled through this. And so effectively, you see how we have the red and the blue?
Yes, sir.
Right. One of these will be the primary winding and the other one will be the what?
The secondary winding.
Secondary wire.
Secondary winding.
Right. I'm not sure if you guys could see it, but so like you see this soft iron core, it actually extends downwards actually. And this is like, so it's effectively like, I'm not sure if you all could visualize it. But essentially the soft iron core, it extends downward as well. And so here's what's gonna happen. When I supply an alternating current in the primary coil, what's gonna develop?
EMF.
Magnetic
flux or
A change in magnetic flux. A change in magnetic flux, right?
Yes, sir.
When I supply, like I literally have a plug over here. If I hook this up to the AC outlet in my primary coil, I'm going to have an alternating, well, it's going to have an alternating current, and as a result, it's going to give me an alternating, a change in magnetic field, which is going to result in a change in magnetic flux. And that is going to cut where? What is that going to cut?
The secondary winding. The secondary coil.
Exactly, it's going to cut the secondary coil. And that change in magnetic flux is going to be channeled through the what? What is it going to be? What is it going to be channeled through?
The soft iron core.
Exactly.
Iron.
The soft iron core. And so it's going to guide the magnetic flux to, well, it's going to guide the magnetic field lines to pass through the secondary coil. That is what it's going to do. So this is a transformer. And a transformer only works with what? Whatever
AC.
current.
AC power outlet. AC.
If I use DC current, will that generate a change in magnetic flux?
Nope.
No, sir.
No, because the current will be constant. It will be a constant current. Yeah. So for like actually seeing how these things work, right? Like not just on paper, like hopefully could like see it with your own eyes. Because a lot of things you do in school, they don't really see it. They just be seeing it on paper. And that's a problem. Okay, so I think I explained it. So this is the primary coil, this is the soft iron core, and this is the secondary coil. Right? Primary, secondary. Good. Now we need to look at turns ratio. Turns ratio. The turns ratio is just a ratio between the number of turns in the secondary over the primary. Question, when you look at this diagram, you see more turns in the primary or the secondary?
The secondary.
Right. Let me ask another question. If I have more turns in the secondary, then wouldn't that mean I'm gonna have a lot of intersections between the field line from the primary and the coils? Like what? Like if I were to draw a magnetic field here, and isn't it cutting the coils quite a lot of time? Like a lot?
Yes, sir.
And if it's cutting the coils a lot, then the EMF here is going to be very, very strong. So in the instance where the number of turns in the secondary is more than the primary, we actually call it a step what?
Step up.
We call it a step
A
up.
step up.
A step up. And the reason for that is because if you have more turns in the secondary, then
Than the primary, it will be a step up.
it will
And
be a
if you
step
have,
up.
There will be more in the
and
secondary.
if you have more coils in the primary than the secondary, it will be a step down.
But I hope all you understand why. It has to do with the interactions between the field lines and the coil.
Coil.
Yes,
Yeah.
sir.
Right, cool. So I'll take a screenshot of this. I think we kind of understand transformers good now. and we understand Faraday's law. And Mariana, I feel like you understand this a bit better.
Yes, sir. It's just that I did never hear about the right hand thing.
Okay, we use
Well,
that to determine the direction of the magnetic field lines for current carrying conductor, or vice versa. So we'll do a question like that in 2017. All right, so let's take a screenshot.
Yeah, sure.
Okay, cool.
Sir.
So Faraday's law of induction, it says the magnitude of the induced EMF in a coil is directly proportional to the rate of change of magnetic flux through the coil, which is what I would have wrote over here, just a bit differently, but it means the same thing. Right? But the point is, if we want to induce an EMF, it must have a change in what?
Change in the magnetic field, actually.
It must have a change in magnetic flux. And if for that to happen, you need the current to change direction. So I'll let you take a screenshot of this.
So I don't take a screenshot already.
You guys have a screenshot?
yes, sir.
Okay, cool. So here what? Let me do a question now. Do I have the past paper? So it goes up to 2016. Disappointing.
I think it's 2017 question one, sir.
That's paper one. One second. I gotta be in paper two somewhere. Okay, good. This is the question I want to discuss. Right, so let me tackle this question, right? An experiment in which a magnet was allowed to fall through a coil was conducted to test the concept of induced EMF. Now, guys, as the magnet is falling through the coil, isn't it going to cut the coil like the magnetic field lines? Isn't the magnetic field lines going to cut the coil?
Yes, sir.
Yes,
And
sir.
okay, if the magnet is falling, tell me, Mariana, will the coil experience a change in magnetic flux?
Yes, sir.
Yeah, because like, wouldn't the magnetic flux be changing like every time it move? It changing, you know? Every time it moves. That was the example I just show you over here. Watch. That's the same thing. This is induced EMF. So Mariana, you're gonna help me with this question, right? So they said using a scale of 2 centimeters to 5 milliseconds on the horizontal axis and 2 centimeters to 0.5 volts on the vertical axis, plus a graph of induced EMF versus time on the grid provided on page 5. So, Mariana, what am I going to plot on my y-axis?
The voltage.
On my y-axis, right?
Yeah, vertical is now y. So
Right, so let me explain something. Whichever one is mentioned first, that is going to go on the y-axis. So they want us to plot a graph of induced EMF, so that's y, versus time, that's going to go on the x-axis. Generally speaking, time always goes on the x-axis. So let me jump straight into this. Did anybody here learn lenses law in school?
No, sir.
Okay. All right. You guys know about inertia, right? Like
Yes, sir. Yes, sir.
Yeah, so like if I want to stop an object, I would need to enact a force in the opposite direction.
Yes, sir.
And like the greater the mass of the object, it would be what? It'd be easier to stop or harder to stop?
Harder to stop.
Right. Well, it's a similar concept here. Anytime you induce a EMF, the EMF, the direction of the okay, the direction of the current is going to be in such a way that is going to oppose the change in magnetic flux. So you'll see what's going to happen, right? You'll see. Just take my word for it, you'll see. You'll see what I mean. So, Mariana, I'm seeing some negatives on the y-axis. Okay. And time is what? We can't have negative for time. So, right, so that's the y-axis over there. 0 on the y-axis. What scale do we use on the y-axis?
They're 2 centimeter scale. So like every 5.
Now, every 2 centimeters is 0.5.
I thought you said. Yeah. Okay.
I'll show you again. Feel like this might work. So, Mariana, watch. On the vertical axis, they're saying 2 centimeters to what?
0.5 volts.
Right, so every 2 centimeters is going to correspond to what?
0.5 volts. So
Yeah. So, let me start. So, this would be 0.5. What would this be?
0.10.
Nah, 1.0.
Oh,
Because what's 0.5 plus 0.5?
1.
Right. What would this be?
Not bad. 1.5.
This would be?
2.
And this would be what?
2.5.
Everybody with more, like, they lost.
That's it.
Yes,
And,
sir.
and to get your marks in physics, you need to label the axes. So I'm going to put induced EMF
Oh,
voltage. Are you all with me? You understand that part?
Yes, sir.
Yes, sir.
Yes, sir.
Right. Now, Mariana, we had to label the bottom, right? So, Mariana, what do you think I'd say this is?
negative 0.5.
Right. Negative 0.5. What do you suppose this is?
Negative 1.
This is,
Negative 1.5.
and this is,
Negative 2.
right. Let's label the x-axis now. So on the x-axis, which is the horizontal axis, they're saying 2 centimeters to 5 milliseconds. Okay. So I'm going to label this what?
5.
It was 2, right? Yeah, 2 centimeters. I'll label this what?
10.
15, 20.
20.
And we have to label these axes. So this axis would be maybe time in what?
Second.
No.
No. Millisecond.
Yes. Time in milliseconds. I don't understand that, right? I know some of you guys will have put seconds, but as you can see, time is measured in what here?
Millisecond.
Millisecond.
Right, so Mariana, when I'm writing my points, I see the x first and the y. So my first point would be 0, comma what?
0.0.
Right, so that's my first point.
Okay. Oh.
All right. What's my next point?
5, 0.25.
Okay, so you understand that if like this is 0.5, then half of 0.5 would be what?
That would be 0.25.
Correct. It would more now.
Yeah.
Or the next one is 10, 1, 10, 1, 10, 1. What's the next one?
15, 2.
What's the next one?
22.5. Thirty,
Then the other one is what?
38 negative 7.5. We're going down.
So that would be right here. If you're confused, right? Remember, if the full thing is 0.5, then half of it will be what?
25. Well, 0.25, like a quarter.
So if this is 0.5, this will be negative 0.75 because I add 0.25 to it.
Mhm.
And then we had to do what?
35 to 2.
35 to negative 2.
Okay.
And then what?
Actually, 40 to negative 1.
Right? So 40 will be over here. A negative 1 will be where?
Right after 0.75.
Right.
So you put it on the same line.
So that again?
You put it on the same line as
Oh,
0.75.
right here. Okay, let me know if you guys understand everything that I did so far.
Yes, sir.
Yes, sir.
Okay. Is there anybody confused by this? People on YouTube, is anybody confused? Let me know if you guys understand this. So, have you guys ever seen a graph like this before?
Yes, sir.
Yes,
Yes,
it's
sir.
like
So,
No, sir.
No,
Okay.
sir.
Now, let me explain something, right? Since we have a change in magnetic flux, do you think this would have looked like a linear graph?
No.
No, sir.
No, sir.
No. So what kind of graph does this look like?
all this.
If you had to say, what kind of graph does this look like?
You saying that?
It looks like a sine graph. I'm not sure if you could see it. It's definitely a bit weird though. It's definitely a bit weird. Right? But let me connect the dots. Notice in the question, did they say anything about best fit?
No, sir.
No, sir.
No. So like what we're to do is this. Let me hope to
Your
draw
up
this.
curve.
Yeah. My God. This is a bad drawing. Oh yeah, I'm trying.
So Diana, thank you.
So it will be perfect, no?
Alright, let me know if you're okay with that.
Yes, sir.
Yeah.
Yes, sir.
People only understand this.
Yes, sir.
People on YouTube, let me know if you understand this. Let me check the YouTube people. Okay, cool. Use the graph to determine the induced EMF after 12.5 milliseconds. So 12.5 milliseconds will be where? In between what? In between what, Mariana?
Between 10 and 15.
Mariana, can you see that? Okay, 12.5. If I add 10 and 15, that's going to be 25. What's half of 25? Tell Mariana, what's half of 25?
12.5.
Right.
So,
So
yeah,
So here's what we're going to do. If they want us to figure out the induced EMF after 12.5 milliseconds, we're going to go on the x-axis, look for 12.5, which is right here, and we're going to see where it cuts the graph, and that's going to be our read off. So Mariana, at
Yes, sir.
12.5 milliseconds, what is the induced EMF? It's really hard to see. Let me see if I can.
1.75.
Nah.
No,
Okay, well,
gotta go up.
let me explain it. 1.5.
1.5.
Let me explain this again, right? So we're talking about 12.5 milliseconds. 12.5 is right here. We're going to draw a line. We're going to see where it cuts the graph. Cuts the graph here. So what's that?
1.5, sir.
Yeah, it's 1.5
One.
volts. Would you guys have gotten the mark?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Right? So then they're saying the time in milliseconds other than at the beginning of the experiment when the induced EMF was 0 volts. We want to figure out where it's 0 volts. So if it's 0 volts, then this will be the what intercept? The x-intercept or the y-intercept?
The x-intercept.
The x-intercept.
X-intercept.
So I believe if I drew this a little better, it'd probably cross the x-axis over here. Totally agree?
Yes, sir.
Yes, sir.
Yes, sir.
What are you looking like, guys?
So it would have been
25.5.
5.
No.
28, sir.
Here what, right? Here,
2.75.
wait, I'll tell you guys guessing. Here what you have to do, right? If the answer is in the middle of 25 and 30, all you have to do, guys, is just add 25 and 30 and divide it by what?
7.5.
2.
Right. So what is 55 over 2?
27.5.
27.5.
27.5.
Do you guys understand?
27.5.
Understood.
And that would be obviously milliseconds, right? So would you write 27.5 seconds?
No, sir.
No, sir.
No, sir.
No.
So let me explain the
Yes,
question
sir.
again. They want us to figure out the time where the induced EMF is 0 volts. So it's 0 volts over here at 0 seconds, obviously. And where else did it cut the x-axis? Over here. And okay, if you're confused, right? If you're confused, at this point, what is the induced EMF, guys?
0.
0.
0.
0, 0. So I hope we understand that. Right, so here's the part where you guys are going to get a little confused. I hope not to, but you will get confused. So Kevin, we have any Kevins in class?
Right, yes, sir.
Big up Kevin. Kevin Ramdial, as you want.
Yes, sir.
Right, so you will help me with the question, give it a read. And put on the camera one time. Put on the camera one time. Because you gotta use your right hand grip rule.
So I can't put my camera right now.
How come?
Camera give me trouble, sir. It's external from my laptop.
Okay.
Okay. Yeah. Kevin, a physics student, conducted an experiment to determine the effects of electromagnetic induction. He used the following apparatus: a coil made from fine wires, a sensitive galvanometer, connected wires, a bar magnet. Figure 1 shows the setup of the apparatus used by Kevin.
Alright, so here how this is going to work, right? Guys, as we know, if I have a magnet and I move it by a coil, it's gonna induce a what?
Voltage.
EMF. It's gonna induce a EMF because there's gonna be a change in magnetic field cutting the copper wire. Alright? Now here's what you guys don't understand. We know about Faraday's law, but you need to know about Lenz's law. So I'm gonna take the bar magnet and I'm moving it inwards. If I'm moving it inwards, okay, which side of the magnet goes in first?
North
side.
The north side. So here's what I'm saying. Lenz's law. The induced EMF will oppose the change in magnetic flux. Therefore, so a question, if the North Pole is going in, to oppose this change in magnetic flux, the current has to flow in such a way such that it creates a what here to oppose it?
A south.
I thought I
No.
was John.
Ollie. If it's a South Pole, will a South Pole with a
I North Pole create a
No,
different
it will
potential,
not.
John.
Not so, not
Wait,
so much.
Nikolai, will a South Pole resist the change in magnetic flux?
No.
No, sir.
Nah, Nikolai, we need to form a North Pole here. We need to form a North Pole over here because Nikolai, what will a North Pole do?
Repel.
Exactly. So Lenz's law says that the induced EMF will oppose the change in magnetic flux. Therefore, the direction of current needs to be such that okay, there has to be an easier way to say this. Let me find out the easiest definition I could find. Yeah. But like the point is, if the north side of the magnet is going in, then I need to create a current. Okay, however the current is flowing, it must generate a north pole over here to resist the change in magnetic flux. That's it. So like over here, Kevin, we need to effectively create a what side a what here? Our north pole or a south pole?
South Pole, is it?
No, not a south pole. Here, what? Let me write down a nice definitions of Lenz's law for you guys. I don't think you'll learn Lenz's law in CSEC physics though. When an electric current is induced by a change in magnetic field, the direction of the induced current will always be opposite the change that created it. So, when an electric current is induced by a change in magnetic field, the direction of the induced current will always oppose that change that created it. So, Kevin, if the north side of the magnet goes in, what pole would I have to create here to oppose that?
Oh,
It's a-
we got it. But a North Pole because like poles are trapped. I mean,
Exactly.
repel.
Exactly. Correct. So I will have to put over here will have to be a what?
North Pole.
Okay. So here's what I want you guys to do. So again, guys, Lenz's law says that if I'm inducing a current, then it's going to be like inertia. So the current that's induced over here will oppose the change in magnetic flux. So if I'm sending the magnet in from the north side, then to kind of oppose that, I would have to create a what magnet over here? A what pole?
Not.
Not.
Oh,
A North Pole.
because if it's not, what would it do to the magnet?
Repel.
It will repel it.
So here we're going to do, right? Like I tell you, that
that
right
holds
hand grip
it.
rule, the right hand grip rule works in both directions, works in both ways. So here what? In this instance, you're going to treat your thumb as the north. Your thumb always points in the direction of the magnetic field in this instance. So here's what. I want you to take your thumb and it's going to oppose this magnet over here. So it's going to be like this. Let me know if you guys with me.
Yes, sir.
Yes, sir.
Yes,
And
sir.
you're gonna curl your fingers. You're going to curl your fingers. And if you do it correctly, you'd realize that this is what it looks like.
Oh, yeah. Yes, sir.
Yes, sir. Anti-coupler.
Right, so let me explain it again. So what are we going to do? Again, Lenz's law. If I'm inducing a current, then that current induced will want to oppose, it will want to oppose this magnet over here. So at this point over here, you'll have to create a north pole because north and north would repel. And I want to oppose the change in magnetic flux. So I'm going to take my thumb and I'm going to align it over here. Because north, don't I want to repel this magnet over here?
Yes, sir.
Yes, sir.
Yes, sir.
Right. So you're treating the thumb as the north pole. And so I put my thumb in this direction because I literally want to oppose this, and I'm treating my thumb as the north. So you're gonna take your hand and you're gonna curl it. I know the coil is a bit weird, it's a bit funny. It's a bit funny. But when you do it properly, you'll see that I don't know how to I don't know how to make it in a way that it will
So,
make sense. It's kinda hard to show.
so like you
Yeah.
had your hand like how you had it facing you, what you see? Yeah, like that. And you see it going how your fingers curve in the next direction, so going anti-clockwise.
Has it seen it like that?
Yes, sir.
I'm gonna go let's see it now. They good?
Yeah, we've seen it, sir.
Yes, sir.
Yes, sir. Yes, sir.
Yes,
All right.
sir.
Okay, cool. So let me share back the screen. This session real making me lose here.
Sir, there's somebody in the waiting room now.
No, already add them in.
Yeah,
Okay,
this
okay.
session give him a gray hair, boy.
So what you mean again, your gray hair?
Yeah, boy. Like it's just to show these things. Like, okay, knowing it is one thing, but showing it virtually is a different thing.
Oh yeah, that's real pressure, boy.
Yeah,
I'm
man,
sorry,
so
say it
consider
all.
this is the first time I ever see physics in my life too now.
Oh Lord, Tira. Hi.
Hi, good Nikolai, how are you?
All right, wait. So guys, over here, since I want to oppose the North Pole, I have to create a north over here. And so I'm going to take my thumb and I'm going to align it in this direction. Now, when you curl your fingers, it's gonna curl like this, and the current is gonna be like in this direction. It's real hard to show though. It's really hard to show though. I really tried.
So you're gonna move in an anti-clockwise direction?
Yeah.
So like this way. Then so I don't know if I'm doing it correct.
Wait,
I never realized my thumb finger so long.
So guys, the galvanometer, it will swing in whatever direction the current is going. So the current is going in this direction, yeah? It's going in that direction. And so my galvanometer will deflect in that direction. So will I do this? Will I do that?
No, sir.
No, sir.
No,
Would
sir.
I do this?
No,
No,
sir.
Would I do this?
Yes, sir.
No,
Yes, sir.
sir.
Yes, yeah.
Yeah. Yeah. Guys, let me check the YouTube people. I feel like the YouTube people are so confused.
I always did notice that circular thing. But it's just that I didn't know the name of it. But thanks for showing me now.
No problem. So, here what guys, if I switch up this question, I think I can handle it.
Sir, run it back one more time, please. One more time.
Okay, no problem. So here what, right? The North Pole is going to enter the coil. You see in that? The North Pole, the North is going to enter the coil.
Yes, sir.
Now, according to Lenz's law, if a North Pole is coming in, I'll want to oppose it. So if I want to oppose the change, what pole would I have to create here to oppose the North?
A north pole.
So according to the right-hand grip rule, your thumb is going to be the magnetic field, right? And it always points in the north direction, right? Your thumb always points in the north direction. So I'm gonna try to explain this again. Sorry, people on TikTok have it bad. Right, so let's stay with me, right? Stay with me. So would I point my thumb in this direction? Would I do this
No,
madness?
sir. No,
No, I
sir.
have to go in this direction. So I'm gonna go in this direction, right? Right. So you can see what I'm talking about. Like I'm trying to,
Yes, sir. Yeah.
and you see like you see like okay, watch. So see how the current going?
Yes, sir.
Yeah.
So try not to stress yourself too much. You're too young to get gray hair.
Cause like I'd just be so scared, you know, on the sun and just be like, as can't sleep at night, boy. Like as like it bad, it bad. Like I need to make sure, like, okay, if you come to my library, you come to my classes, I need to make sure you understand. I don't want it to be going telling people this man can't
No,
teach you.
my camera
Like
is not mirrored.
Sir, we could clearly see from how Shana tell us that you doing maths
oh
in your
God.
sleep.
Oh, that's so embarrassing. That's so embarrassing. I just think about all, you know, like I really care that you guys understand.
Nah, sir, that's what we need. A caring teacher. That's what we need.
Amen.
So
Preach.
like I need to make sure they understand. It's like I really can't do it if they don't understand. So here what? I'm going to switch up this question on you guys. Did they switch it up over here? No, they didn't.
Yes, sir. Next part, switch it up, sir.
Did they?
No.
Okay. Let me see what they say, right? So draw on figure 1, the direction of the induced current and the direction of the arrow on the galvanometer as a result. So you guys saw the arrow was in this direction. And if it's in that direction, the galvanometer will indicate that the current is going in that direction. The galvanometer just tells you how the current is flowing. It tells you the direction of the current. Okay, so we okay with our part 1? Explain why an induced current is produced. Why is this happening, guys?
Because there's a
So you are
magnetic
changing
flux.
magnetic flux.
Right, as the
So
magnet falls,
As the magnet
there is a what? There is a
Changing magnetic flux to equal.
change in magnetic flux.
badness. Yeah, so as the magnet falls, okay, watch. I really want you to understand this thing, you know, watch. This is a practical example. As you can see, pretend the magnet falling, right? I can rotate it. But pretend it falling. Oh, look. Right, watch. Pretend the magnet falling. Are you seeing that?
Yes, sir.
Yes, sir.
Cool. Why is it necessary to use a sensitive galvanometer? Guys, if you don't use a sensitive galvanometer, will you see deflect?
No, sir.
No, sir.
No.
Right.
It would be impossible without the sensitive galvanometer.
Right, to see the deflection. Because I'm gonna explain something to you guys. If it's okay, do you think we're generating a very strong current or very weak current? Let me ask
A very weak current, sir. So
exactly.
weak.
A very weak current. If you don't have a sensitive galvanometer, you wouldn't see the deflection. Right? So why is it necessary to use a sensitive galvanometer? To see the deflection caused by the weak induced current. That is why. Cool. The magnet is then pulled out of the coil. Show on figure 2 the direction of the induced current as a result of this motion. Guys, it's real easy. Let me ask you a question, right? If putting the magnet into the coil made the galvanometer go in this direction, what do you suppose pulling out the bar magnet will do?
You can go in the other direction.
That is all.
Because they would want to pull it, sir. It would want to pull the magnet.
Yeah, the
Yeah,
galvanometer is supposed to show you which direction it's going in.
Yeah. Was that hard or that was easy?
That was good, sir.
That was good.
So here what I'm saying, guys. in the first rounds, you want to oppose the North Pole. If you're opposing the North Pole, then over here you're gonna want to generate a North, right? A North Pole magnet. So you use the right hand grip rule. You point your thumb in the direction of the north. You see how your fingers curl, and that's telling you the direction of the current. Cool. This direction, no problem. And so if I am pulling out the magnet, it will go in the other direction. So let me know if you understand that.
Yes, sir.
Yes, sir.
Yes,
And if I wanted to draw the arrows would look something like so. Are you understand that or not?
Yes, sir.
Yes, sir.
yes, sir. Yes,
So
sir.
you see, from since the time you show me the example with the hand and thing, I understand, I
That-
will understand.
That's good.
So,
That's
and
good.
the galvanometer arrows, when you place the virtual transformer circuiting with the voltmeter, you could see when when you pull out the magnet how it changed direction.
Yeah. Watch it. You see that? Okay, let me try to do it a bit slower. You see that? You see how it changes direction?
Yes, sir.
Yeah, watch. All right, cool. Let me try to switch up this question on you guys. Because CXE might do that. So question, guys. If instead of putting the north side in, I had put the south side in. Let me see how you guys will handle that now. So something, guys. According to Lenz's law, if I put in the south side in first, then I would have to create a what here to oppose it?
A South Pole, sir.
A south
South
pole.
Pole.
South Pole.
The South Pole.
A south pole. So remind me, according to the right hand grip rule, your thumb is always in what direction?
Pointed towards the north.
Pointed towards the current.
Towards.
So will I point in this direction, chat?
No,
No.
No,
No.
remind me, the thumb always points in which direction?
the north.
No.
The north.
North.
So immediately, okay, if the thumb is pointing to north, and if I point in the other direction, wouldn't that imply that it's south?
Yes, sir.
Yep.
Yes,
Yes,
sir.
sir.
All right. So again, this is real hard to see. Trying to wait.
I draw it,
Sir,
So I have a question, right? You
Yeah.
can't use your left hand for the south pole if the north
No,
pole is the right hand.
Nah. Let me explain something right here. This is your right hand grip rule, and it's used for induced currents. You can't, nah. You can't do that.
All right, no problem.
Yeah. So when I do that, okay, so like trying to visualize it. The coil is making it really hard, but effectively, what's gonna happen is
So it will be clockwise.
yep.
So and your thumb will be pointing away from you.
It will
Yeah.
be pointing away from you, so it will be clockwise.
Right, watch. I'm not sure if you're seeing this, right? Like, okay. It's real hard to like, okay.
So go ahead, do your thing, sir. Do your thing.
So like my thumb will be pointing away, and like I don't know, like you see, like
Yes,
it
we
coming.
see this, sir.
We understand. We
So we see
understand.
Like
this.
Yes, sir, we understand. Don't stress out
like
yourself.
it coming up, right? It coming up, and so like
Yeah. We understand, sir. We understand.
I feel like I just saying that to just not give my grade here.
No, serious thing.
No,
We
no.
understand. We
serious
understand.
thing. Serious
We
thing.
understand. We understand, sir. We understand.
They don't
If
understand.
we
They
didn't understand, we
we
wouldn't
understand.
say it.
Just now
understand.
Okay, by the way, you don't have no such thing as left hand grip rule, eh? No.
It's
No.
right hand.
It's right-hand grip rule. I think I think all the confusion is with Fleming's left-hand rule and Fleming's right-hand rule. It do
Yes,
have no such thing as left left left-hand grip rule. There's no such thing as that. All right, cool. Hope you understand.
yes, sir. Basically, left hand Flemings with the
Generator.
three fingers.
Yeah, yeah. So here, what? Immediately after this, we're gonna move on to that, right? We're gonna move on to that.
Okay.
State three changes or adjustments that Kevin could make in this experiment to increase the induced EMF. Now, if you want to increase the induced EMF, you need to increase how much times the coil cuts the magnetic field lines. We could do to make the amount of intersections more.
Make more coils.
More
Yeah,
coils.
More coils.
Yeah,
And I could
more
also do what to the intensity of the magnet. Use like a what?
faster
A
or
stronger magnet.
A stronger
strong.
magnet.
So
And
we can increase
Nikolai
the speed at which it go intersection, so.
That's it.
Nikolai just tell me. Increase,
the speed of the magnet.
I would say velocity here because you're moving it back and forth. Increase the velocity at which the magnet moves in and out of the coil. Are you understand that or not?
Yes, sir.
Yes,
Yes,
sir.
sir.
All right, vibes. Describe what will happen if the magnet remains stationary in the coil. Guys, if it remains okay, I was sure, right? Watch. Wait, I was sure. What happened?
Nothing.
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 No voltage,
Zero.
no
Current
EMF
going to.
induced.
Right. If it remains stationary, you could probably talk about what happened to the galvanometer. The galvanometer would remain what?
Zero. It
Would
need
remain
Zero.
I would say would remain undeflected. It would remain undeflected. So the galvanometer, you could do a little diagram for them if you want. Doesn't the galvanometer indicate the direction of current?
Yes, sir.
Yes,
Yes,
sir.
sir.
So like it'd be right here.
Yes,
Well,
sir.
you understand or no?
Excuse sir, one
Yes, sir. Yes,
question.
sir.
And
Yes,
for
sir.
the stronger magnet, you could put the soft iron around it, or you could just get a bigger magnet.
No. Soft iron is not a magnet. It's a highly permeable material that allows magnetic field lines to pass through it very easily. You
No,
could
I mean
probably say use a neodymium magnet because right now they're using a bar magnet, which is most likely a red earth magnet.
oh, okay. No, I meant like you put the soft iron around the magnet, but
Nah.
then
Right, so you can see the galvanometer. Here what? They ask you to describe what will happen if the magnet remains stationary. So they want, like in this question, they literally have a galvanometer. So you are to describe to them what would happen to the galvanometer. The galvanometer will remain undeflected. And that's because there will be no induced what?
EMF.
Voltage or EMF.
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 Right, because and you could say because there's no change in
Magnetic flux.
Magnetic flux.
I'm really proud of how far you guys came. Now all you understand alternating current, direct current, Faraday's law, Lenz's law. All you understand your right hand grip rule. Big up all yourself. And all you understand transformers as well.
yes, sir.
So you're proud of me
Yes,
too,
sir.
right?
Big
You're
up
proud
y'all
of me too.
physics people, boy. Big up y'all physics people. Y'all go smash up the exam tomorrow. I
Oh,
expect a
thank
one
you.
from
Oh, thank you,
Anisha,
Sarah. Thank you.
and I expect a one from Nikolai. Thank you very much.
Girl,
I want that
I
one.
can't guarantee the one, but I will still try my best, okay? I will try my
Right.
best.
So
It's
if
better
the
Exactly.
you
formula for the
try. It's
transformers,
better you try than you fail to try. So keep trying.
Exactly. Always try.
sir,
Yeah, Nikolai?
isn't the transformers equation is N P over NS is equals to VP over VS, which is equals to IS
IS over
over.
IP.
Okay.
Yeah, that's it. 1 second. Where is that, buddy? Ah, here it is. let's do a I want to explain the Fleming's left-hand rule and Fleming's right-hand rule now. Because I think you'll need to understand that. How much of you guys genuinely understand that or not?
Repeat?
Not there.
All right.
So still need a little proof on that.
Oh,
Take a
this.
screenshot of this. Take a screenshot of this. So we're going to look at Fleming's left-hand rule and Fleming's right-hand rule. And we're going to do this fast. Right? So I trust all you have a screenshot.
So that person have a break finger?
Apparently. All right. So when do we use Fleming's left-hand rule? Well, we use it when we're dealing with generators. Right? So when do you use Fleming's left-hand rule? When you are dealing with generators, not when you're dealing with induced currents. If you are inducing a current, what do you use?
Right hand grip.
The right hand.
Well, we learn about the right hand grip rule, but there's also Fleming's left. What's in, boy? There's also Fleming's right hand rule. And we use this for induced currents. So let's look at this first. Guys, I promise you, this is much easier than you think it is. I promise you. I promise you. Right? Stay with me and you'll see how easy it is. So as you can see, we have a what here. That's a what?
DC.
Right?
DC.
Yeah, we have a DC source there. And we have two permanent magnets. And we have a coil. You see this? This is actually a coil, guys. This is a coil. So here's how we're going to do this. Remind me, magnets go from where to where?
From positive to
Positive to negative.
No,
Positive, negative.
Not to south. Not to south.
Not
North
to
to
Yeah,
south.
that's it talking about
Not
this
to
shit,
south.
you know.
Right. So you're talking about electrostatics there. So the magnetic field line would go from north to south. Let me know if you guys are with me.
Yes, sir.
Yes, sir.
Yes, sir.
So
Yes,
here
sir.
what? If we have a positive here and we have a negative here, wouldn't the current flow in this manner?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay,
It will
good.
start from the positive and go
And then-
straight to the negative.
Good. Now here's what I'm saying, guys. They could ask you to describe the thrust felt on AB. They could ask you, would it go up or would it go down? So let me show you what you're gonna do, right? So guys, pop your left hand, your left hand. Your left hand. Now, it's gonna look a bit different, but for everybody, but pop your left hand, right? This is your left hand. If you don't know where your left hand is, part L. So the thumb finger represents thrust, other finger magnetic field, and the other finger what?
The direct.
The current.
Current.
Current. So again, thrust, magnetic field, current. Tell me, what does the thumb represent?
The trust.
Trust.
This
Trust.
represents
Magnetic
Magnetic field.
Magnetic.
Magnetic field.
this represents
Current.
So here what we're
Current.
gonna do. So my magnetic field is literally in this direction. Are you seeing that?
Yes, sir.
Yes, sir.
So I am going to align which finger in this direction? My first finger, my second finger, or my third finger?
First finger. A second.
Third finger.
Wait. The first finger is thrust, you know. The second finger is magnetic field. So we're gonna align our second finger in this direction. Are you with me?
Yes, sir.
Yes, sir.
Okay. And if we're looking at A to B, where's the current going?
From A to B.
Right. So
From
if we
A
were
to
this,
B.
so it does it look like it's going into the paper or coming out?
Into.
All right. So remember, the first finger is thrust, the second finger is magnetic field. I already have that position. What does my third finger represent?
Current.
Direct.
So
Current.
That finger, the third finger, should be pointing where? In the screen or out of the screen?
Into the screen.
Into
In
the
the
screen.
screen?
So let me see. Do I have my second finger in the correct direction? Wait, let me.
think so.
Wait. This. Wait, guys. I have a whiteboard. No, that'll take long. We'll just use this. Oh God, this is so inconvenient to teach, boy. Oh my days.
Yes,
No,
sir.
you're trying, man. You're trying.
Yes, sir. We see. Yes, sir.
What did you?
Yes, sir.
Wait, sir. I'm gonna figure out something. This not
I
working.
don't see it.
It's not working.
This is dedication, guys. He's really trying. This is what we call
Dedication.
dedication.
Wait,
Sir,
sir.
So
Just,
I'll buy
sir,
a
just
black
use the
die,
pic-
right? At the top.
Wait, give me a second.
By the way, sir, you can just use the pictures, the left hand and the right hand, and
Wait,
we'll
sir.
have it rotated.
Wait,
Wait, give me a second.
okay.
So there's an imposter.
Like, oh, we have to win.
Wait, sir.
Adaptation, sir.
Yes, guys. He's trying his best.
That is why I was going to say, sir is dedicated like me. Because if I
200
wasn't
IQ, sir.
dedicated, I would have give up long time, honestly speaking.
Right. Let's see in this, right?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Which finger is this? I mean, which hand is this?
Your left hand.
Your left hand.
Yeah.
Which finger do I need to align with the north or south?
Yeah, first, yeah.
Your thumb.
Index finger.
Index finger.
Right?
Index
And my
finger.
current. Okay, so can you see that my second finger is going from north to south?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Can you see my third finger is going into the paper? Because like the current is, like that?
Yes, sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
It making sense. It making sense. It making sense.
Oh,
So guys, the last finger, well, I'll say the thumb represents thrust. So what will AB feel? Will it feel an upward force or a downward force? Watch it again.
Upward.
Upward force.
Upward.
Upward force.
Upward force.
Right, upward force. Okay, let's try C to D now. So let me tell me if I'm going correct, right? Do I have my second finger aligned properly? This one.
Yes.
Index finger.
Yes, sir.
Yes, sir.
Right? The third finger, should it be going into the screen or should it be coming out?
Out.
Coming out.
Coming out.
Right.
Oh, so it's outward.
Are you seeing that?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Right. So look at it, look at it. So this finger here is going from north to south. I hope you're seeing that.
Yes, sir.
Yes, sir.
And then this finger wiggling here, isn't it in the direction of the current here?
Yes, sir.
Yes, sir.
Yes, sir.
And as a result, my thumb is pointing in one direction.
Downward.
Downward.
Down.
Right. So C to D will experience a force what?
A downward force.
Downward.
Downward.
Let me ask you a question. B to C, will that experience a force?
upward force.
Will you guys see B? Will BC experience a force?
Just say pilot, sir.
Downward force.
No, BC won't. Let me ask you
No,
a
it
question.
wouldn't.
if over here is experiencing an upward force and over here is experiencing a downward force, according to the forces, right? What force would this experience?
No force. It will cancel out.
It can't. Okay, imagine this is 5
It will
newtons
be
and this is
neutral.
minus 5 newtons. What's 5 newtons minus 5 newtons?
Zero.
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 So no force.
It will cancel out,
Zero,
yes.
no force. It will cancel out.
So A to B is going to experience an upward force.
And then
C to D, downward. And you can imagine if this is being pushed upwards and this is being pushed downwards, it's going to cause this part here to what? That's what S. S is the hangman.
Spin.
Yeah, bingo, he got it. Spin. Watch. If I push on this up and I push on this down, wouldn't that spin?
Yes, sir.
Yes,
Yes,
sir.
sir.
it will spin in the other direction.
Right, so let me switch up things on you guys. Next level dedication there.
So you could be seeing how the fingers up in the air kind of thing during them exams, sir. Like,
Yeah, boy.
Oh, so I was be like, hey,
Somebody say you go on this 10 different gangs.
So
let
that
them
again?
exactly judge y'all, bro. Like, y'all do y'all finger things, and so as long as you understand and you get your answer, let all of them look at you however they want.
No shame, people. When I try to find out something and I don't have my calculator, I just use my fingers.
That honestly, that is joke compared to what PE students do for exam. Tell me why you have a cricket with question and we grab a cricket and tell them demonstrate in front.
Wait there. We can unlock. Oh, we locked in right now. We locked in. We need to move on. Right?
Yes, sir.
I don't want to do anything, but we need to move on. So here what? In this instance, what did I do?
you switch the magnets.
So
Switch
how would
magnets.
so would I draw the arrow in this direction still?
No, sir.
No, sir.
No, the other direction.
No, sir.
This direction. Right? And so here what? If we want to figure out the force experienced by AB, am I going to use my left hand or my right hand?
Your left hand, sir.
Your left answer.
Right.
Left
When is
hand.
the only time I'm going to use your right hand?
EMF.
For induced
Induced
current.
Induced current.
Current.
Induced current. I'm back for up. This is dedication, boy.
So what AC generators?
So here we're going to do, right? I want to tell me if I'm correct. So the second finger represents the what?
The
The
direction.
magnetic.
force.
Is it in the correct direction?
Yes, sir.
Yes,
Yes,
sir.
sir.
But remind me, what does the third finger represent?
The current.
The
Current.
current.
You look at the current over here. The current is what?
Going up.
It's going up.
Going up.
Well, I want you to think of it as either going in into the paper or coming out.
Going
Oh.
in. Going in.
Going in. Going in.
Right.
In.
So is this correct?
No, sir.
No.
No.
No, sir.
Is this correct?
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
Yes,
So either.
So can you guys see that my second finger is in line with the magnetic field?
Yes, sir.
Yes, sir.
Yes, sir.
My last finger is like in line with the current, and as a result, my thrust is what?
Downward.
Downwards.
Downwards.
Right, downwards. And automatically, if this is downwards, for it to spin, what kind of force are going to experience here?
An upward force.
Upward force.
Upward force.
Upwards force.
But let me just make sure though. Bam.
Yeah.
Are they seeing it?
Yes, sir.
Yes, sir.
Alright. Okay, we okay with Fleming's left hand rule?
Yes, sir.
Sir.
And again, we use it for generators. And motors. Motors. What's saying by motors? DC motors. So I was mixing up that. Oh my god, I'm so sorry. Yeah. You use it for motors. Motors, guys. So let me give you all something to take a screenshot of.
Are we good now to switch back the camera? Or...
Yeah. Let's take a screenshot. That's possible. I want to explain the other rule quickly. I'll take a screenshot.
Yes, sir. Yes, sir.
Yeah,
Yes,
so
sir.
let me just clarify this madness, right? I was telling you something that kind of sus. What I was saying, boy, I really wasn't thinking, you know. This is for motors, guys. Because, you know, for a generator is an induced current. A generator is an induced current. Right? And I mean, and so like it sees a motor because it's spinning.
Yeah.
Yes, sir.
Yes,
Okay,
sir.
cool. Let's look at Fleming's right hand rule now. So it's more or less the same thing, but you're applying it for your right hand. Stay with me. So, okay. So in this question, you could see we have a rod. Are you seeing the rod?
Yes, sir.
Yes, sir.
Yes, sir.
Right. And we have these dots. What do these dots mean?
When into the
Yeah,
into
coming
the
out.
Coming out.
Coming out. Coming out. All right, cool. So let's read the question. I'll read it one time here. Figure 1 shows a copper rod moving through a uniform magnetic field. The symbol represents the magnetic field coming out of the page. Each end of the rod is connected to leads that are connected to an ammeter, which measures the electric current. The rod is only allowed to move in a horizontal direction, left to right, right to left, while in the magnetic field. So guys, you see this rod here? We are allowed to move it left or right in the magnetic field. Are you understand?
Yes, sir.
Yes, sir.
When I move this conductor in the magnetic field, it's gonna what? It's gonna experience a what?
A magnetic influx.
A what?
Induced current.
Okay, a change in magnetic flux because it's gonna cut. Okay, watch. I'm not sure what you're seeing, but like,
Yes, sir.
Yeah.
Yes,
it
sir.
As a
like
Yes,
change
sir.
in magnetic flux.
is a change in magnetic flux, right? It's gonna experience that. So draw an arrow on the rod to indicate the direction of the induced current when the rod moves to the left. So we're going to move the rod in which direction?
Left.
Left.
So here what? Would you guys say that this is a motor or a case of a generator where you're inducing a current?
Generator.
Right, because a generator, it relies on mechanical movement to generate what?
EMF.
EMF.
Electrical energy. Electrical energy. So here's what we're gonna do. Since this is induced current, I want it to pop on the right hand. Right hand. So it's a similar concept. Thrust, magnetic field, current, right? Thrust is just a force. Let me ask you a question. Since we're moving it to the left, what would finger would that correspond to? Okay, thrust is a force, right? Thrust is a force.
Yes, sir.
In this
Yes, sir.
instance, I'm applying a force to the left.
Yes, sir.
So my thumb would have to be going in which direction?
Left side.
The left.
Right. So my thumb needs to be going in the left, right? What does this finger represent?
The magnetic fields.
Magnet.
But in the question, what did it tell us about the magnetic field?
It's going.
It going in.
It
No,
changing with the rod.
Nah, guys, what is saying?
Coming out.
Coming out.
Coming out.
Right. So my thumb represents thrust. I'm thrusting it to the left and I'm moving it to the left. This represents magnetic field, but the magnetic field is going in or coming out?
Coming out.
Coming out.
So is this correct right now?
No, sir.
Is this correct?
Yes, sir.
No.
Yes, sir.
No,
No,
sir.
sir. Point it.
No.
Face
No,
you.
It
sir.
needs to be
Tilt it
pointing
somewhat.
to you.
It
Is
has to
this
be
correct?
pointing
Yeah.
to you.
Yes, sir.
Yes, sir.
So guys, let's observe what's happening here, right? So my thumb represents how I'm thrusting it. So I'm thrusting the rod in which direction?
To the left.
Left,
Left to the left to the left.
right? My second finger represents the magnetic field. As you can see, the magnetic field is,
Coming out.
and this my last finger tells us the what?
Current.
The
Right.
current.
So my
Current.
current is going to go in this direction, right?
Yes.
Sir.
So
Right.
Oh, but wait. The magnetic field coming out. So how come your hand? So put back your hand how it was.
Right.
Your index finger is not the magnetic field.
Okay. Thrust, magnetic field current. Thrust,
Right.
magnetic field current.
And the magnetic field coming out of the paper, right?
Right. So what's thrust, magnetic field?
Yeah. Oh, you had the paper at the bottom. That's why. Okay, cool. Okay.
Yeah. We understand it?
Yeah, I
Yes, sir.
understand.
So, but I think your index, your finger close to the index finger was looking like it was being disrespectful. Oh, so
Hey,
finger
hey.
so long?
No, that is the chromatic aberration. That's like the distortion of the lens.
Uh-huh.
So I was not going to find out what was that in. Like when your
Yes,
fingers.
so like wait, so like let's look at a slight alteration in this question. So in this instance, I'm going to move it to which direction? What do you guys think? Well, I'll move it to the right this time.
Okay.
Again, this is an induced current. So which rule am I going to use?
The right hand.
The right hand.
The right hand.
Right. So my thumb needs to be pointing in which direction?
You're right.
Like this, right?
Yeah.
My second finger is supposed to be pointing in which direction?
Right.
Coming out.
No, up.
So yeah,
Right,
up.
guys. Remind me, what does the second finger represent?
The magnetic field.
Magnetic field.
Magnetic field.
Right. And
So
consequently, my
which means
last
the finger after the magnetic field is supposed to be pointing towards you.
yeah, this finger.
The magnetic field.
Yeah. So guys, my last finger tells me the what?
The current.
The current.
So the current looks like it's going in which direction?
Downward.
Downwards.
Downwards.
So you draw the arrow then downwards.
Alright, I feel like all you understand Fleming's left hand rule and Fleming's right hand rule.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir. Partially.
Thank you for all the explanations.
Not a problem. Ooh, my back is not. Hey.
So you have to sit down.
As old age.
I think that might be a sign you're getting old now. Not gonna lie.
Hey, why all you so disrespectful? I don't know how old says, but he not that
Don't
old.
worry,
Oh
don't
my
worry.
god.
Uncles could be young too.
It's 22.
Oh god.
Oh, that's so
Good.
disrespectful.
I should kick them out of the Zoom.
Sir,
No,
you
I'm
put
not
no
saying
words in
that
your
we
mouth,
could
you know.
need your film paper once.
And
Ah,
I small thing could go on YouTube.
hey boy. And well, for part 2, name the rule used to determine the direction. What rule I use?
Fleming's right hand
Fleming's
rule.
hand rule. Fleming's right hand rule.
Right, Fleming's
Correct. Yes.
right hand rule.
I said before I forgot I write the right hand rule.
And if you want to know when we use them, look, it's right here. We use the Fleming's right hand rule. Wait. Huh? No.
No, this is not yours.
No.
Sure, right?
Sure. I teach in class. Yeah, so I would use the Fleming's left-hand rule when I'm dealing with what? I did tell all the generators, but that was real wrong. I don't know what I
DC
was thinking.
motors.
When
Right,
you
DC.
Use the
Motors.
use for DC motors.
Right? And Fleming's right-hand rule is used when we are generating EMF. So,
Yeah,
if,
generating EMF.
like we use induced currents,
Yeah.
right?
Would the questions give you like clues to tell you which Fleming's left hand and right hand rule to use?
Nikolai, look at this question, right? When you move a conductor in a magnetic field, what do?
You generate current.
Exactly, you're inducing a current or you're inducing an EMF. So you know you how to do right-hand rule here. Understand?
Yes, sir.
Okay. So here what? Let me look at this question here, the electromagnetic relay. Right? We're gonna move the transformers just now, like in detail.
Yes, sir.
We're nearly done with this topic. After this topic, I want to do nuclear.
Yes, sir.
Yes, sir, please.
And after nuclear, since we did waves and optics and thermal physics in the last lives, we could start past papers.
Yeah.
So one question, sir.
X.
Did you get a chance to look at what I had sent you about that same nuclear question, sir?
Oh no, I didn't get a chance to look at it.
Oh, okay.
Suppose I could look at it today. So let's look at this question blindly.
Wait, sir, I have a question.
Yeah, talk to me.
What do you think? What is the probability of radioactivity coming tomorrow?
Well, I'm sure some radioactivity must come. I'm sure.
It's come every year.
It's come every
Okay.
year. Alright, so let's continue. A magnetic relay is used to switch on a circuit carrying a large current. Figure 11 shows an electromagnet using a magnetic relay to operate the starter motor of a car. So let me try to understand what happened in here, right? The longer terminal is the what? Positive or the negative?
Positive.
Positive.
And this is the negative, right? So how will the current flow?
From the
Positive
positive to the
to
negative.
negative.
Positive.
Are you understand this or not?
Yes, sir.
Are you sure?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Question. Let's
Excuse
try
sir,
ask it.
for the sake of me, I could just move again, please.
Right, so no problem. The longer terminal tells you the what?
The positive side,
Right, and the shorter terminal tells you what?
the negative side.
Right.
Okay.
And so watch. The current is going to flow from the positive to the negative, right?
Yes, sir.
Yes, sir.
You understand or not?
Yes, sir, I understand. Thank you.
All right, so guys, I have a question. Let me see if I truly did only work. Where would be the north side of this magnet? 1 or 2? Use the right hand grip rule to figure that out.
One.
So I think in one.
Two, sir. I
So
think
it's two. So it's two.
it's two.
It's
Two.
two. I think it's two.
They could bring a question like this, and they could ask which is the north pole. Let me show you how this working, right?
It's the thumb is pointing not pull it.
Yep, the thumb is always tell you the north.
Alright.
The tongue does always point upward, so
Right, so let's stay with me, right?
I will go with two.
Here what? I want to coil my fingers around the bar. Does this look like the proper way to coil it?
No, sir.
Nah.
No, sir.
Nah.
No, sir.
No, sir.
I bring it towards you. Yeah, yeah.
Yes, sir.
Right.
I bring it towards you.
Watch. I really trying here, you know. Watch. Like you see how I hold it?
Oh,
Yes, sir.
I do the
Yes,
wrong
sir.
way.
Yes, sir. Understanding.
So I might have me wrong way.
If you notice, it wraps around So like, imagine you're grabbing it, hold it like that.
Yes. So like your fingers going in the direction of the arrows. Like the arrows coming down. So
Let me remove the arrow. Oh, nah. Yeah. So like, okay, I'm gonna explain this, right? Yeah. Your fingers are curling in the direction of the arrows. So like, I'm not sure if you've seen it, you know, like, are you
Yes,
seeing
sir,
it?
I seen it. I seen it.
But
We seen it, sir. We seen it.
because this going behind, you know, it going behind. So like, it going behind like this. Like that. So, for this magnets, this will be the what pole?
North Pole.
North
The
Pole.
North Pole.
And this will be the what?
That is South Pole.
South Pole.
South Pole.
What question I just come on here? Remember me, right?
Yes, sir.
Yes, sir.
Yes, sir.
Alright, this is a good idea with the phone. It's like a multicam setup. When I get like real big and I have like multiple angles, I'll be so cool. We can remember these days when things were dark.
So I wouldn't say
Yes,
it was
sir.
dark, sir. It would just get brighter.
Yeah.
Just get better.
I like that one. I like that one.
That's a good one. So let me ask you a question, right? When I close the switch, the current is going to flow through the coil and it's going to generate a what? As you can see, it's a soft iron core here. So the soft iron core would channel the magnetic field lines and it would form a what? A what magnet? What kind of magnet you call this that is created by electricity?
Magnetic flux.
Electromagnet.
Electromagnetic.
Electromagnets. A magnet created by running a current through a coil wrapped around a soft iron core is an electromagnet.
Oh,
And
okay.
so, question: what's attracted to magnets?
Iron.
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 So let me ask you that question. When we have the current running through this coil, it's gonna, you see this soft iron armature over here?
Mm-hmm.
Yes, sir.
It's gonna latch here
A circuit.
and it's gonna allow the current to now flow. Are you understand that?
So you're talking about the metal contacts, the
What? Talking
soft,
about this.
yes, that part.
Yeah, so like, okay, look at the circuit right now. Does it touch over here right now?
No, sir.
No, so is this an open circuit or a short circuit?
Short?
Open.
No.
Open.
Guys, watch. It's literally open. It's like an open door. It's like open. Now, when I have this switch on here, it's gonna generate a magnetic field, and that's gonna cause the soft iron armature to be snapped into this position. And the current now will be able to flow and complete the circuit, thus starting the starter motor. Do you guys understand the procedure?
Yes, sir.
Right. So somebody tell me, when I start this, when I close the switch for this circuit, it's gonna generate a what?
Electromagnet.
Electromagnetic
field.
Well, it's gonna create. Well, it's gonna create. It's gonna create an electromagnet, which will produce electromagnetic fields, which will attract the soft iron armature to this latch over here, and this would now complete the secondary circuit. So here's a good answer. Somebody read it.
When the switch in the primary circuit is closed, current flows through the coils and the soft iron core becomes an electromagnet. The magnet pulls the soft iron armature and causing the metal contacts in the secondary circuit to close. This completes the high current circuit and allows a large current to flow to the starter motor, causing it to operate.
Are you understand or no?
Yes, sir.
Yes, sir.
Are you sure? At long time I didn't check the people on YouTube. Have anybody on YouTube?
If you're on YouTube, subscribe while you're over there. Get him to 10,000.
Alright, so if you like all you understand relays or no?
Yes, sir.
So you have 244 people watching.
Okay, I wasn't expecting that.
NASA is 229, my bad. We knew it.
That's okay. So here what? Who wanna help me with this question? Any volunteers?
So I'll do it.
I could try.
Oh, on the camera, right? So let's side by side. So everybody that who wanna help me with the question? Who was it?
I think it was somebody. Well, I know it's
It
somebody.
was me.
Who are you?
Sarai.
Ready? Who?
Sarai.
Sarai, okay. Everybody that isn't Sarai, I'll take off all the camera. So Sarai, put on the camera and let me run it, right?
That is bad like that. Jeez. Well,
No, this is not what I want. Now a second. Sarai, start talking there.
sir.
Oh. This is not what I want.
In the meantime, while Phil fixes this, guys, the people on TikTok and YouTube, let's subscribe. We're trying to hit 5K. CXC done.
Yeah, subscribe. So deserves all the subscribers he gets because he works hard.
On TikTok. Let me go to
And
70K on
if
TikTok
you
and
subscribe,
at least 8K on YouTube. Let's go, guys.
We could get the
Yes,
5K, guys. We could get the 5K. We could get our 5K boy.
Yeah.
So we have to go big or go home. So we're gonna pass the 5K, but for now, subscribe and turn on notification after paper 2. We're gonna
10,000,
hit
I think.
Wait, yeah. All right. So, Sarah, you ready?
Yes, sir.
So it's Sarai. Sarai for the girl.
Sarai, okay. State what is observed on the galvanometer. Oh, wait, give me a second. No, that wouldn't make sense. State what is observed on the galvanometer when the wire is moved in the direction shown by the arrows, parallel to the magnetic field. Let me ask that question, right? If it moves parallel to the magnetic field, will it cut the magnetic field lines?
No, sir.
No, it won't. It won't. Watch. I don't know what I see. No, I see it now. But if it moves parallel, will it cut it?
No, sir.
No, sir.
So if it does not cut it, will the galvanometer deflect?
No.
Remember, the galvanometer shows you the direction of the induced current. If there's no change in magnetic flux, is there going to be an induced current?
No, sir.
No. So, the galvanometer is undeflected. And why is that?
Because it have no flux, it doesn't change anything in regards to the current.
Right, there will be, you see, no. Because if you guys recall, flux is the area where the field lines cut a surface. Does the field lines cut the does it cut the rod over here if it's parallel?
No, sir.
I don't think I'll see it on watch. Like if I slide on it, I'll see
Yes,
any.
sir. Not cutting.
Okay, good. So the galvanometer is undeflected and no change in magnetic flux. As a matter of fact, is it even cutting the field lines?
No, sir.
No,
No.
sir.
Right, so all right. Now we're gonna move it upwards through the magnetic field. If I move it upwards, and you can see it cuts in the magnetic field.
They will cut the magnetic field. Yes, sir.
Right. Would you say that this is a DC motor or an induced EMF?
That will be induced EMF.
Right. So which hand should we use? The left hand or the right hand?
The left hand.
Now,
The right hand.
we use the left hand when we're dealing
When
with
we have the DC.
DC motors.
Yeah.
But over here, you see not induced EMF, so you have to use the right hand, right?
Yeah.
Okay. So tell me, which finger is magnetic field again? The first, second, or the third?
The second.
Right, the magnetic field. So if it's from north to south in this direction, should it be like this?
No, sir.
Should it be like this?
Yes, sir.
Next question. They're telling us we're moving it upwards, right? Upwards.
Yes, sir. That means the
So-
thumb should face up.
So I'm thrusting it upward.
Yes, sir.
And so the current is going to flow in this direction.
Yeah, outside the page.
And so how will the galvanometer be deflected? In what direction?
It will to the right.
Are you understand that?
Yes, sir.
Rest of people, are you understand that or no?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Right. In the next one, wait, sir. I don't know what happened here. Right. So if it's upward stream magnetic field, you will say the galvanometer was deflected to the what direction?
To the right.
Right. Okay. Now we're gonna move it downwards. So Tom, is this correct?
No, sir.
Is this correct?
Yes, sir.
I don't know why the contrast be even so, but like watch. Remember, this is thrust, right? And if we're moving it downwards, we're thrusting it downwards. So this needs to point downwards. My second finger is the magnetic field. The magnetic field is literally from north to south. So I need to align it like that, north to south. And so my current looks like it is what?
Going in the page.
Remember, the last finger here, this is current. So the current looks like it's going in the page. So that would be
Yeah.
so it calls my galvanometer to deflect in what direction?
To the left. Yeah, to the left.
Guys, are you understanding this?
Yes, sir.
So I would say the galvanometer was deflected to the what?
To the left.
Are you sure you understand this?
Yes, sir.
Yes, sir.
So anytime it's induced EMF or something like that, which rule we're gonna use? Left hand rule or right hand rule?
Right hand.
Right hand rule.
Right hand rule.
Right hand rule. Right. I hear somebody say left. No. Hey, anytime you see the word induced, right hand rule. Right hand. Fleming's right hand rule. Right?
Yes, sir.
Yes, sir.
Well, they surely understand that.
Yes,
You
sir.
go through it
Yes,
again
sir.
for the people that saying yeah, but they probably say no.
Okay, so guys, anytime you move a conductor in a magnetic field, what is induced in it?
The conductor.
No. If you move a conductor in a magnetic field, it will experience a change in what?
Magnetic flux.
Flux.
And if it experiences a change in magnetic flux, what will be induced in it?
EMF.
EMF.
Right, an EMF.
EMF.
So anytime you see induced EMF, you're going to use Fleming's right hand rule. Do you guys understand or not?
Yes, sir.
Yes, sir.
Sir.
Yes,
Yes, sir.
If I'm dealing with a DC motor, which rule will I use?
Left hand
Left
rule.
hand. Fleming's left hand.
Left
Right.
hand
And I
rule.
could use that to figure out the thrust experienced by the what?
By the DC motor.
No, by the coil. By the coil of the DC motor.
Yeah.
Remember, the coil would be like this, Nikolai. Yeah.
Yes.
All right, cool. Ooh. After the session today, RL bond by RL bonnet. The lives typically will be this intense. Are they feeling
Bro,
the
at least you're
intensity?
trying, bro. You're trying. You're trying. That's the main thing.
Yes, sir, I feel in the intensity.
All right, let me just do a quick summary, right? If you see the word induced, which rule are going to use?
Fleming's right hand.
Fleming's right hand rule.
Right hand.
Fleming's right hand rule.
Right. Your thumb represents what?
The
Thrust.
The
Thrust.
thrust.
The thrust.
The thrust, right? And the
The
thrust
index
is
finger represents the
field.
The electromagnetic
magnetic field.
force.
The magnetic.
electromagnetic field, and the other finger is the current.
Right, the current. Now, here what? It's more or less the same thing as the left hand rule. The only difference here is I am moving it. So when I say thrust, I mean that you thrusting the object. If it says to the up, if it says up, then you are taking the object and you're moving it up. So your thumb will point up. If they say you're moving it down, your thumb will point downwards. Question. If you see an X, that means the current is what?
Into the
Going
paper.
into the page.
Going in.
And if
Going
you see a
into the
dot here,
page.
Out
current
to the
is.
page.
Going
Going
out.
Coming out.
Out.
And which finger would have to point in this case?
Your thumb.
Thumb?
Index finger.
No, your in
Or the
your middle
index
finger.
finger.
Your index.
Remember, guys, thrust, magnetic field, current. Your second finger is the magnetic field.
Okay, so.
And obviously, which finger would I put pointing towards me?
The second finger, so.
Right, which is the index finger. And what does the middle finger represent? No, it does not represent FU. No.
Nobody
No.
wasn't gonna say that, sir.
Really, Sha, I was looking at you now. Does not
What?
represent.
Sir, I wasn't gonna say that.
Not
What?
the
You're trying to
current,
get
sir.
me kicked out? No.
Right, so
Your middle finger will
what
be
does the middle finger represent?
the current.
Current.
The
The
current.
current.
Current. Everybody okay with this?
Yes, sir. Bye,
All right.
Sarah.
Sarah leaving?
Yeah, she said she had to go and study for PE.
Oh, okay.
I have to go. I come to
Bye
support
bye.
y'all.
That's okay.
It was nice having you here. See you
Y'all
back
got
here for
this.
paper
Push
1
through.
month.
I will sell a paper one tomorrow evening.
Amen. So let me at least get my rest from after. Come home now.
Yeah, man, Nikolai. I learned some
I
good
will
lessons
see. I will
tonight. I
see.
learned
Why
some
do I
nice
late night
things
session?
tonight. I learned some
So
coils
guys,
and things.
somebody tell me fast, what is Faraday's law?
I should have paid my voice. Somebody else answer now.
Somebody Faraday's law. What's Faraday's law again?
So is the rate of change of a magnetic flux the rate of change of magnetic flux that is directly proportional to the magnitude of the induced EMF.
Right. And if you say it any other way around, that's fine as well. So if you say the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux, that's fine. If there's no change in magnetic flux, is there induced EMF?
No, sir.
No, sir.
No, sir.
If I have DC current, will I have a change in magnetic flux?
No, sir.
No, sir.
No, sir.
If I have AC, will I have a change in magnetic?
Yes,
Will I have a
sir.
change in magnetic?
Yes, sir.
Okay, good. So we more or less done with this. Are we done with this? Something you guys should remember is this as well. DC motors and AC generators. So for a DC motor, the power source is the battery. In a DC motor, you're converting electrical energy to what?
Mechanical.
Right. Because it's moving, right? It's moving. In an AC generator, you're converting what?
Mechanical to electrical.
Good. For a DC motor, you have a split ring commutator, and for AC generator, you have slip rings. So this is the split ring we're talking about, and these are the slip rings for AC generator. And how to make the motor spin faster? Well, for a DC motor, you just increase the battery voltage. It could increase the number of turns, or you could use a stronger magnet. For AC generator, you could increase the turning force velocity. You could increase the number of turns for the coil, and you could use a stronger magnet. Let me know if you're okay with these things.
Yes, sir.
Yes, sir.
Yes, sir.
Come on fast. For AC generator, what we use? I would use what?
Slip rings.
You're not wrong. But like, if I want to figure out like a magnetic, like figure out the magnetic field or figure out the direction of the current, or
Fleming's right
Right.
hand.
Right hand grip.
Fleming's
Right hand.
and if I deal with a DC motor, what we use?
Left.
Fleming's
Left.
left hand.
Okay, cool. So I trust all you're okay with this now, right?
Yes, sir.
Somebody fast. This is an example of a what?
Electromagnetic.
Electromagnet. Nice. Let me look for a transformer question now. Right, so complete the statement. Oh, let me just give a little crash course on transformers, right? A little crash course. Someone fast, are we not sticking? What do I call this?
Primary.
Primary.
Primary coil.
Coil or winding.
What is this?
Soft iron core.
Iron
Soft iron core.
What is this?
Secondary winding.
Coil.
All right, cool. We good. What are the main formulas? Well, first of all, you need to understand that the power you get in is going to be equal to what?
The power you get out.
Right. Now, if you recall, P in is this. Okay, do you guys remember the formula for power in terms of voltage and current?
Yes.
Yes, sir.
P is equal to what?
V over I.
Nah.
Energy
I-
over
I-
time.
IR.
I just typically say VI, but you could say IV. You know, multiplication is commutative, it doesn't matter. So, in other words, the voltage in the primary by the current in the primary would have to be equal to what?
The voltage in the secondary.
Voltage in the secondary.
Current in the secondary.
Current in the secondary.
Secondary.
And let me show you guys something. If I divide both sides by IP, I'm gonna end up with VP is equal to VS IS all over IP. And if I divide both sides by VS, I'm gonna end up with VP over what?
VS.
Yes.
Yes.
So like I tell you, I just never remember formulas or anything. I just figure it out in the exam. And there's a way it means to figure it out in the exam. If you know that the input power is equal to the output power, then you should know that the primary voltage times the primary current would be equal to the product of the secondary voltage and the secondary current. From here, you could derive that VP over VS is equal to IS over IP. Yeah.
Excuse me. I'm taking your approach and going to exam. Yeah, my approach. We're just figuring it out. I'm gonna do that, yes?
No. But the approach is if you fully if you understand the concept, if you understand the concept, do that. If you don't, just memorize it.
Okay.
So you need to know this one. You should also know that. Okay. VP over VS is equal to what?
IS over I. P.
Oh, we just discussed this one. We just talked about this
Oh,
one.
NP
IS
over
over
S.
IP.
NP over NS.
NP
Over.
over NS.
No. Would it be wrong if I said Vs over Vp is equal to Ns over Np?
No, sir.
No,
No,
sir.
sir.
No, that would not be wrong.
No.
If you do that, that's perfectly fine. That is perfectly fine. Right? That's equally correct. But let's do a quick summary, right? Right. So Vp over Vs is equal to what?
NP over
Current. Summer current.
S
IS.
over IP.
IS over
IS
IS.
Current
over
S
IS.
over current P.
Right. And if you want to remember it like this instead, all you have to remember is that you will not be writing IS. All you write on top, if you want to write it like this.
IP.
IP.
Over,
IP
over
over
IS.
IS.
Good. So it's VP over VS, IS over IP. And if you flip it, it will be VS over VP, IP over IS. Cool. Now tell me, NP over NS is equal to what?
VP over VS.
VP over VS.
VP over VS.
C over PS.
And if you're remembering it the other way, that'll be NS over
NP.
NP
NP.
and VS over VP.
S over VP.
Good. So here what? I think we're ready for a question now, right? And by the way, transformers work on the principle of what?
Oh, I remember it.
No.
That's what I, guys. That's what I. Remember,
Induction.
induction. Yes, induction. Specifically, mutual induction. Let me explain induction fast, right? Because we did it already. You see Faraday's law? It's Faraday's law of induction. So guys, again, if you have a change in magnetic flux, what will that induce in the secondary coil? Guys, I'll say it again.
I don't understand.
If you have
EMF?
okay, when you're working with a transformer, right? What power source do you use? AC or DC?
AC.
And we spoke about this. We use AC because the direction of the current changes what?
With respect to time.
Respect to time.
Right. It changes with respect to time or periodically, right? So therefore, that would generate what type of magnetic field? A constant or a changing?
Changing magnetic.
Changing.
Right. And that is going to cut the what?
Secondary coil.
Secondary
coil.
Secondary coil.
And that will induce a what?
An EMF.
EMF.
Right.
EMF.
That is induction. That is induction. That is induction, right? That process is called induction. But for induction to take place, you need to have a change. You need to have a change in magnetic field, right? And the AC does that because when we're talking about AC power, the current switches directions, and we spoke about this. If the current changes direction, what happens to the direction of the magnetic field?
It also changes.
It will all change.
Right. So hopefully you understand.
It also changes.
So if I have a change in magnetic flux, what's going to happen on the secondary side? We're going to get a what induced?
And induced
Induced
EMF.
Good.
Induced.
Right. So transformers can increase or decrease the what? Can increase or decrease the what?
The voltage.
Right. The voltage.
Yeah.
Magnetic.
So guys, if I am increasing the voltage, what kind of transformer is that?
A step up.
A step up.
A step up.
Step up.
Good. And it would mean that we have more turns in the what?
In
Your
the
secondary coil.
Secondary coil.
Right, more turns in the secondary. Remember, the more turns you have, the induced EMF is going to be
Increased.
going to be greater. Okay. If the voltage is dropping down, if it's dropping,
Step
what's that?
down.
Step down.
Step down.
What is in the primary?
Yeah.
So isn't there assumption for transformers, by the way?
Yeah, an ideal transformer works on the principle that the input power is going to be equal to the output power.
Or it could be 100% efficient.
Right. Okay, Nikolai, if the input power is equal to the output power, what efficiency is that?
100%. Okay.
Right. But that's wrong. If all they do are their bachelor's in electrical engineering, or they go see that transformer has a bunch of losses. You have like resistive losses, you have eddy currents, bunch of losses. So transformers can increase or decrease the voltage with a corresponding decrease or increase in what?
Current.
Current.
Let me explain something earlier. If you're stepping up the voltage, what do you think you're doing with the current?
Increasing it.
Increasing it.
Decreasing.
Decrease.
For everybody that said increasing, where you getting that energy from? I'll ask you that. Let me give you an example, right? Let me give you an example.
So and it in the formula as well.
Yeah, it's in the formula as well. But I'll give them an example, right? Let me just say we have 5 turns here. And we have 10 turns over here. Let me just say the voltage is 9 volts over here. What do you think the voltage in the secondary is going to be?
18
volts, sir.
18 volts.
18 volts, right? Because we have 2 times the number of turns. Okay. Let's just say we had a current at 10 amps over here. How would I calculate the power in the primary? Man, what's the formula for power?
IV.
IV.
What's the current in the primary?
The current is
10 amps.
10.
10 amps.
And what's the voltage?
10.
9.
9 volts.
So how much power we have in the primary?
90.
90.
90.
90.
What?
That also, I was trying to be funny there. I said like 90 watt. 90 watts.
Watts.
90 watts. Yeah. I think I get a joke. 90 watts.
Yeah.
That's so unfunny. It's funny.
No, it's not bad.
So here we're saying now, for the people that saying the current increasing, what are they going to say? The power here is 18 by, I don't know.
18 times 10.
Are they going to say 18 by 10, right? Where you getting that power from? I will ask you that. Where you getting that power from?
The
Here they say.
primary.
No. But how much power are given in primary?
5.
What?
No, 10.
No, I given the primary 90 watts of power.
90 watts.
So where the extra 90 come out from? You understand the problem, right?
Yes, sir.
Okay, sir. Yeah.
The power that I put in must be equal to the power I'm getting.
Oh.
Okay.
So here I was saying, this what's supposed to get for the power over here? Since I put in 90, what's supposed to get?
90
as well. 90 watts.
90 watts.
So by increasing my voltage by 2 times, I decrease my current by
2 times.
2 times.
So from 10 amps it's now going to be what?
5.
5.
Olha, do the math somewhere. Where's 18 by 5?
90.
Yes.
90 watts.
Right, so I hope you understand. If the voltage increases, what happens into the current?
Decrease.
Decreasing.
So, I hope you understand. Because you can't just pull out the power out of nowhere, you know what I mean? If you're given it 90 watts, you have to get 90 watts out. Cool. So transformers can increase or decrease the voltage with a corresponding decrease or increase in current. Are you understand or no?
Yeah.
Yes.
The basic principle behind the working of a transformer is the phenomenon of what? We just spoke about it. Mutual what?
Electromagnetic induction. Mutual induction.
Mutual induction. Yeah, mutual induction.
Mutual induction.
Yeah, that's it. That's the specific terminology they're looking for. Mutual induction. And induction is just the Faraday's law I was telling you guys about.
Sir, what if we just put induction? Would they still get the mark?
I think you would, but for the full thing, mutual induction.
Sir, cool.
Okay. Without looking at anything, right? I'll tell me, it's looking like a step up or a step down.
Step down.
Step down.
Step down.
Step down. Right, so in the experimental setup shown in figure 1, a variable AC voltage source V1 drives the primary winding of an ideal step-down transformer. If it's ideal, then the input power will be equal to the what?
Output.
Output power.
Good. And it has a turns ratio of 3,960 to 600. And we have a resistor 5 ohms connected across the...
Secondary winding.
You all can see that, right?
Yes, sir.
Yes.
Sir.
Right. Use the readings from table 1 to plot a graph of V2 versus V1. I have the graph plotted already. We're not going. I'll take some time. Which one we're gonna plot on the y-axis?
V2.
V2.
V2. And
Whichever one is
V1.
right. I should have the graph somewhere along the way. After this, we have to look at circuits and then be done with this topic.
Sir.
Okay. So again, whichever one is mentioned first, that's going on the y-axis. Cool. So I plot the graph here. Of course, you need to label the axes. You need to put your scale and you need to label the graph. Are you understand?
Yes, sir.
Excuse me.
Yeah.
Even if they don't say best fitted line, you still have to do a line. Depends on what kind of graph it is.
It depends on what type of graph it is.
Okay.
Yeah. Like in this graph, you can clearly see a linear graph.
Yes, sir.
But remember earlier, we got this graph where it looked like this. Are you know what I'm talking about?
Yes, sir.
Yes, sir.
That was clearly not linear, so you couldn't do a best fit there. I mean, if you see like a little point like that on our off, I mean, best fit. But like if you see something that's clearly indicating a curve, can you do best fit there?
No, sir.
No, sir.
No. All right, so we have the graph. In these types of questions, the next question asking you to find gradient. To find gradient, I'm going to read off 2 points that are what? Sure, but the main thing is that I pick points that are what on the line? On the line or not on the line?
On the line.
On the
On
line.
the line.
Some students might try to pick a point that was given to them. You can't do that, eh? Can't do that. You need, after you draw the best fit, you need to look for points and read off those points. Like for instance, I picked this point, and this point was 0.75. Then I picked this point over here, which was 65 and 9.9. So what am I going to do with these 2 points now?
Create gradient.
Find
Make
the
formula
gradient.
Gradient and slope.
What's the gradient formula?
Change
Y
it.
2 minus y1 over x2 minus x1.
Right, so you could label anyone x1, y1 or anyone x2, y2. It doesn't matter. Cool. So using those 2 points, I form a gradient, and they wanted me to call the gradient S. If they want you to call the gradient S, do not write M. You lose a mark. I'll hear what I say, right? If they ask you to find for the slope and the way to call it S, call it S.
Okay.
Everybody okay?
I got 0.15.
Yes, sir.
Yes, sir.
Now I have a question. Typically, when you're doing gradient, you want to stay the units you use. On the y-axis is voltage. On the x-axis, it's also voltage. So what's going to happen with the voltage and the voltage?
Cancel.
Cancel out each other.
And if you notice, this is, okay, on the y-axis, we have V2. Do you think V2 would be the input or the output? Okay, wait. Do you think V2 would be the primary or the secondary?
Secondary.
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 And of course, what do you think V1 would be?
Primary.
Primary.
Cool. So what we have here is really Vs over Vp. And we know that Vs over Vp is equal to what?
IP over IS.
Ip over Is, which is also equal to what?
NS over NP.
Everybody with more now?
Yes, sir.
And if it was Vp over Vs, that'll be equal to what?
IS over IP.
Which is also equal to?
NP over NS.
Cool. What does the slope of your graph represent? Alia,
The ratio between two same units.
isn't this equal to Ns over Np?
Yes, sir.
So that's the what ratio?
The number of turns ratio.
You wouldn't say no. You would just say turns ratio, Nikolai. You wouldn't say number of turns ratio, but yeah,
Alright.
it's fine. So turns ratio. And again, if you want to show them proof, you could just write that.
So is it correct if you you say the ratio between two same units?
Say that again?
Would it be correct if you say the ratio between two same units?
Nah, they're looking for the turns ratio. Right? So if it was Vp over Vs, would it change or would it still be the same thing? Be the same thing, guys.
Same thing. Same thing.
Same thing, right? Turn ratio. Hopefully you understand why we're saying it's the turn ratio, you know, because we have Ns over Np, so that's our ratio. Fractions are ratios. Right, use your graph to determine the value of V2 when V1 is 50. So what am I going to do with my graph now?
You can look for
Look for
V2
V2.
because V1 is 50 volts.
So when I go on V1, am I going to draw a horizontal line or a vertical line?
Vertical.
A vertical line.
Because V1 is on which axis?
X.
X axis.
So I'm gonna look for 50. I'm gonna draw a vertical line and a cuts the graph here. What does that look like?
7.5.
7.5.
0.5.
Don't forget the units. Voltage.
Yes, sir.
Right. Anybody want to help me with part F?
I don't mind. Well, yes,
All
sir.
right. So Nikolai, they want me to calculate what?
I2, which is current for the secondary.
Right. And they're telling us in the secondary winding when V1 is 50 volts.
Yes, sir.
So Nikolai, when V1 is 50 volts, right?
Yes, sir.
What's V2?
V2 is the 7.5 volts, which we found previously.
Okay. So that's one. I mean, let's try to work it like this and see what happens. But I would solve it using V is equal to IR. And the reason for that is because across the secondary, you have a what?
5 ohms.
Yeah. Well, let me calculate it like this and see what happens now. Let's see if it will work out.
Yes, sir.
So remind me, V1 is the voltage in the what?
In the primary.
And V2 represents voltage in the?
Secondary.
Secondary.
So Nikolai, you have any formulas that you know that deals with VP and VS?
Yes, sir. VP over VS.
But you're gonna run into a problem then, Nikolai. Is equal to what?
That'll be 50 over 7.5.
No, yeah, but I know, but like what is that equal to?
Oh, S over IP.
Well, let me ask that question, Nikolai. You know what VP over VS could be? The way to find I2, which is IS. But do you have IP?
No, sir.
No. So what are you gonna do?
We got to use, well, we got to find for I using
Right.
V1 and R1. No, V2 and R2 because the resistance was in the secondary.
Right. Do you guys understand why I wouldn't recommend this approach?
Yes, sir.
Guys, if you want to use this, you would need to know what VP over VS is. We have that. VP is 50 and VS is 7.5. We have that. They want me to find I2, which is the secondary current. Do I know what my primary current is?
No, sir.
No,
It's
sir.
like you're
No,
trying to
sir.
find for one unknown, but it have two unknowns.
And that's our problem. That's a problem. So here what? Let's use V is equal to IR quickly. So if we're using V is equal to IR, we look at the voltage in the secondary and the current in the secondary. Nikolai, what was the resistance in the secondary winding?
5 ohms.
It's 5 ohms. Do we know what the secondary voltage is?
Yes, sir.
That's a 1.5. Do we know what I2 is?
No, sir.
No, sir.
Do we know what the resistance is?
Yes, sir.
Yes,
5.
sir. Yes, sir.
So what should I do then, Nikolai?
Well, we want to get I2, so we divide by 5 throughout.
So I2 would be equal to what?
I got 1.5 amps.
How many of you guys got that?
Yes, sir.
Yes, sir.
Yes, sir. I get it, sir.
Okay, so I have a question. How would we find for I1 now?
Well, we use this same formula now that we have I2, which
Someone want
is
to write?
VP is equals to IP over S.
Wait, take your time. Tell me the wrong thing just now.
Oh, VP over VS is equals to IS over IP.
So we know that, well, VP is 50. VS is what?
7.5.
And that'll be equal to 1.5 over.
IP.
What's 50 over 7.5?
I got 6 point. Oh my goodness. The 6.66 and reoccurring.
Yeah.
6 point reoccurring 6, sir.
So 6.67.
Yes, sir.
All right. And that's equal to 1.5 over IP.
Yes, sir.
Yes, sir.
So we multiply by 1.5 IP.
Yeah.
You can cross multiply, you're gonna put 6.67 IP. It's equal to 1.5. So how am I gonna find for IP then?
Divide by
Divide by
6.67.
6.67.
Now let me ask a little question, right? We are dealing with step down. So where do you think the current would be higher? If we are dropping
the,
voltage,
secondary.
Primary.
nah,
No.
In the secondary,
No, sir.
the secondary
guys,
winding.
you are saying, right? Where will the voltage be higher?
In the primary.
Oh, the primary.
Primary current.
If the voltage is higher here, what will be lower?
The current.
Right, so you have to think about it intuitively.
Yes, sir.
So where's 1.5 over 6.67?
I got 0.2
0.25.
amps.
So guys, did we see that reflected? Like, I mean, we find the secondary current to be 1.5 and we find the primary to be what?
Wait, so how you get 0.25?
Yes, sir. So I get
hear
0.225.
I hear somebody tell me 0.25 just now.
So it's 0.225. That's why.
Oh.
Yeah, but it'll be 0.23.
So let me follow understand. Since it was a step down, the current in the primary was less than the current in the secondary.
Yes, sir.
So this was just a possible question CSEC could bring.
So if you're putting it to two decimal places, it was
So this is come
0.2.
often?
Yeah, it's come often. It come in January 2026. I typically recommend you write your answer to 2DP. Right? Cool. Nikolai, watch. Speaking of the devil, read this for me.
Use the slope of your graph and the equation I1 is equal to S multiplied by I2 to determine the current I1 in the primary winding. But we already find that.
Well, let me see if we get the same thing now. Yeah, watch. Exact same thing, watch.
Yes, sir.
Well, we use it just verify. So I1 would be equal to the gradient multiplied by the current in the secondary. What did we find S to be again? What was the gradient?
0.15.
And what did we find our secondary current to be?
0.23. No, 1.5. My bad.
Why 0.5, 0.15 by 1.5, guys?
I got 0.23, so yeah, same thing.
Did anybody get that as well?
By 1.5, so I guess 0. Yeah.
Yes, sir, I got that too.
All right, cool.
Transformers is a nice subject to do. Seeing that you could understand and you getting like basically good marks.
Yeah, man.
So this question was from 20 to 25.
Question this was
The
from.
last one we just do.
Yeah, this is January 2025.
I know I see that somewhere.
So Nikolai, help with part I now. HI.
Calculate the power. This what? This I pronounce it properly. Dissipated.
Could do it.
Dissipated.
Right.
Dissipated in the resistor R.
Anytime we're talking about power dissipated, what formula are we using here?
P is equals to I squared R. Or no?
Right.
Yeah.
And we want to calculate the power dissipated in the resistor.
Yes, sir.
So would I use the current in the primary or the current in the secondary?
Secondary, because the resistor is in the secondary.
Right, because wouldn't the current in the secondary flow through the resistor?
Yes, sir.
Cool. What was the current in the secondary?
1.5.
So I'm going to say 1.5 squared, and the resistor was 5 ohms.
5.
So plug it into your calculator. Let me know what you're getting.
Can I get level point 25?
11.25, yeah.
And where's the units of power?
Ohms.
No.
Watts.
Watts.
The resistor is ohms. My bad.
Correct. So guys, anytime you see power dissipated, they're talking about power dissipated in form of heat. P is equal to I squared R. And this happens because of resistance.
Yes, sir. And when they ask for power, it's just P is equal to I R or IV?
IV. Again, you're looking at the information provided.
Okay.
Yeah.
Thank you,
Like
sir.
in this question, Nikolai is saying calculate the power dissipated in the resistor R. I wouldn't use P is equal to VI here.
Okay. No, I was just finding out, like, just a reminder, if they was asking for power, if it was V over P is equal to IV or IR.
It do have IR. Nah,
Yeah, I made that mistake there, sorry.
that's okay. Part 2. Determine the power input to the primary windings by the source. So Nikolai, what kind of transformer is this?
There's a step down.
Yeah, but it told us it was a what transformer?
Ideal.
Yeah, Nikolai. They said it was ideal. Let me show you on. Remember we see it was ideal?
Yes, sir.
So if it's ideal, Nikolai, then the power in the output will be equal to the power in the
Input.
So if we found the power that was dissipated in the resistor is 11.25 watts, what do you suppose the input power is?
Level point
11.25 or no?
Right. Because for ideal transformer, P in is equal to what?
P out.
P out.
Right, are they okay with transformers?
Yes, sir.
Yes, sir.
Okay, cool. So here what? We're gonna move on to circuits now.
Sir.
After circuits, or can take a break.
Yes, sir.
So
Yeah,
what
just-
was the answer? Sorry.
The answer was 11.25 watts. Let me explain, right? Let me explain. They want you to determine the power input to the primary windings by the source. Now, in the question, they told us that this was a what type of transformer?
Ideal.
If it's ideal, then the input power will be equal to the what?
Output.
Output power. I'll check the percentage on my iPad.
So, but wouldn't it also be P equals IV?
Yeah.
67.
All right, so let me show you something, right? If you want to do that, it's not a problem. So that would be that'll be I1 by V1, right? Where I1 and V1 is for the primary side. You understand?
Yes, sir.
Okay. Right, so I see in V1 is 50 here. And what was I1?
0.23.
0.23.
Oh, yeah, was 0.23 by 50.
11.25.
11.5.
Well, if you use the exact value and you don't round it off, you get 11.25. But you didn't have to do all of that.
Calculator just gave me 11.5.
Say that again?
The calculator just gave me 11.5.
Yeah, me too.
If you're using the exact value, like, okay, let me show you what I mean.
Also the 0.22 4 thing.
It's like a second. I'm gonna try to use exact values. I don't even see it. Because I had used rounded off values all over. Give me a second. Right. Cool. Okay, it's gonna be slightly inaccurate. Why, buddy? So to get the exact answer.
Then I probably CSEC fault.
No. It can also be the fact that the gradient isn't perfect. Yeah, could be the fact that the gradient isn't perfect. But you're supposed to get the exact same answer. I mean, it's a 1 mark question. For 1 mark questions, you typically do where to do calculations. You see how much marks it give you for 1 mark. I mean, you see how much marks it is give you for a calculation question, like at least 3. But if you did P is equal to IV, that's fine. But here what I was saying, right? Here what I was saying. At the start of the question, they told you it was a what type of transformer?
Ideal.
Ideal. If it's an ideal, then the input power is going to be equal to the what?
Output power.
And if the output power dissipated by the resistor is 11.25 watts, then the input power should be what?
11.25 watts.
Right. Now, I'm not sure if you guys know this, but if you have a resistor in a circuit, it's going to draw current. And the smaller the resistor value, the more current it's going to draw. So, because of this resistor, a current is going to pass through it, and that's going to use a power. That's going to use power in the secondary. And that power used must be equal to the power provided by the primary. So, I hope you understand.
Yes,
So,
sir.
one more time. What is causing the... Okay, so like we have a resistor here, right? The resistor will cause the circuit to draw what?
Power.
Current. Say current.
Current, my bad.
And that would obviously, because we draw in current and it has a voltage across the resistor, power will be drawn. But here we're saying, guys, because the resistor is here, it's going to cause the transformer to draw current. It's going to draw current from the transformer. And so we just found that we were using 11.25 watts. So if we are using 11.25 watts and there are no losses, then how much power would the transformer have supplied?
11.25.
Kylie, you understand?
Yes, sir.
So if I use an 11.25 watts and it's an ideal transformer, then no losses are supposed to get that back in the primary. Okay, let me give a crash course on circuits. Suppose I have a note here. Okay, just go on a new page. Okay, do you guys know the difference between circuits and resistors and parallel and resistors in series?
Yes, sir. In series is have R1 plus R2 plus R3, but in the parallel.
Yeah.
Okay, so in the series, the resistors is added as R1 plus R2 plus R3 and so forth. But in the parallel, it'll be like as in a fraction. So it'll be 1 over R1 is equal to 1 over plus 1 over R2 plus 1 over R3 and so on.
Correct. That's correct.
Because the
Now,
series is going in one direction, the parallel have more than one areas of where the current is going.
yeah, the current could split. So let me give you guys a simple example of what's. And by the way, when you see resistors, do you all see it as a rectangle or do you all see it like a squiggly line?
Sometimes
Rectangle.
Rectangle.
Rectangle, sir.
Or they go for simplifying things for you. No problem.
One question. Would there be questions where they have the resistor with the arrow facing in that direction? Would that be the same resistor or no?
It's
This,
not variable resistor.
yeah, this is a rheostat or variable resistor.
Would they do the same thing or different?
The both of them would, okay, this is a fixed resistor, meaning that the resistance does not change. With this one, you could actually change the resistance.
Ah.
I actually have a bunch of variable resistors. Wait, I have one. I'm gonna show you. Show you what this looks like. And it's a simple circuit I have made. Right, so let's see this thing over here. Right here. This thing over here.
So that bad.
So like this, depending on the position, this is a potentiometer, by the way. It's an example of a variable resistor.
Be rotted.
And this has, okay, depending on how I turn this, the resistance is going to change.
Oh, okay, well, that's very cool.
Variable resistor. Can anybody tell me the experiment you would use? Like there's an experiment where you would use a variable resistor.
Would that be where it's like wires connected and it had the voltmeter and the ammeter or something like that?
Yeah. Yeah. And we use that to determine the what are the wire.
The resistance of the wire or the current? Resistance.
Resistance.
So
All
I
right,
don't
cool.
know why I say the correct thing, but then I changed to the wrong thing.
I don't know. I wonder if I understand the flow of current.
Yes, sir.
Yes, sir.
All right. Does the current ever split?
No, sir. It all goes in one direction.
It all goes in one direction. And so if you want to combine resistors that are in series, one after the other, I mean, it's a series, right? And when you watch a series, it's one episode after another.
Yes, sir.
Yes, sir.
So like a resistor is one after the other. So if you want to find the combined resistance, the RT, for something that is in series, you just add the resistances as well. Not hard.
Yes, sir.
Let me show you a parallel circuit now.
I believe in every household there is a parallel circuit. Well, parallel circuits.
I will explain why, but that's correct. I'm going to draw the direction of current here, and you guys will tell me the point at which it splits.
All right,
Right,
yeah.
so
That
we have
junction.
we have a node here,
So right
and we have a junction here. So at the junction, what's going to happen to the current?
It will split.
You're gonna split.
there.
It'll go right and go down.
Exactly. Anytime you see that the current is splitting, you have an example of a what?
Parallel circuit.
Parallel.
Parallel circuit, right? So anywhere the current is splitting, it's a parallel circuit. Now, did my Apple Pencil die? Yeah, it
It
died.
probably
My
buttons and
days.
white.
Let me use the fake one. That Apple Pencil needs to keep up with me.
So yeah, I get one of them batteryless pens or something. I don't know.
You see, the thing is, I don't understand why Apple wouldn't just make it in such a way that you can use it when it's charging. So dumb. So question. When the current reaches this junction, it's going to split. So you'd say you'd have a total current over here, but when the current splits, wouldn't the current be shared amongst the resistors?
Yes, sir.
Yes, sir.
Right. So they understand that, right?
Yes, sir.
Yes,
And
sir.
when the currents meet back at this junction here, it would sum to give you the what?
The total
The total current.
current.
Right, total current. Cool. If you want to combine resistors that are in parallel, it'll be 1 over RT, 1 over R1 plus 1 over R2. Now, I just tell my students, if you want to find the total resistance, yeah, just do that. See, you add it, then you raise the power negative 1. Because you
Oh, sir,
understand,
so you them identify the inverse.
yeah. Because watch, you'd have to sum this, and you'd get like one answer, like probably, so let's just say 1 over 50, and then you'd have to do what with both sides?
Multiply by 1.
Multiply.
Yeah, but I was looking for the word
And reciprocal.
reciprocates. If you just reciprocate both sides, you get
Yeah.
RT over 1 is equal to 50 over 1, you get your answer.
Okay.
So by me raising it to the power negative 1, I am reciprocating it one time.
Yes, sir.
Okay, cool. So let me explain some fundamentals of series circuits. If this resistor blows, it's going to create a what circuit?
Open circuit.
I open. Well,
An open circuit. If this resistor blows, will there be any way for the current to reach the other side?
No, sir.
No, sir.
No, sir.
No, sir.
So would you want a system like this in your house?
No, sir.
No, sir.
No, sir.
No,
Sir,
like, okay.
that would be like, for example, the Christmas lights.
Yeah, like the Christmas
One blow,
lights.
That's the Christmas light itself. That's the Christmas light itself.
If one blow, the rest won't work.
Right? So this is a property about series circuits. If one quantity goes bad, I mean if one so look at one component, if one component fails, an open circuit is created.
So you have 4. I don't know if you're trying to say fail and you put 4 instead.
If a right fails. A right fails though. Yeah, if one component fails, an open circuit is created. Because is there any way for the current to flow?
No, sir.
No, sir.
No. Right. Let's look at another property about for this circuit. Does the current ever split in a series circuit?
No, sir.
No, sir.
Right. So the current is what?
fixed.
Is fixed and going in one direction.
Current is fixed. Cool. And let me explain something. Anytime you have a resistor, okay, a resistor resists the current, right? And so what will happen is across the resistors, you'll have voltage drops. So across your resistors, you're gonna have voltage drops. So you should know that.
Yes, sir.
Now, somebody said the current is fixed. Now, we know that, eh? But let me ask you a question. Okay. How can I explain this here now with irons? Okay, I feel like we could just stay with that, right? Stick with that. Let me explain parallel now. So let me look at the parallel circuit. If one component goes bad here, will the whole circuit stop working?
No, sir.
No, sir.
No. As you could see, there's still a path for current to flow. So if one component goes bad, circuit is still functional. Now I have a question, right? For a parallel circuit, so the positive is here and the negative is here. Those resistors, okay, across those resistors, the voltage is going to be the same. That's what I'm trying to say. Can you guys see that? Because watch, this is the positive and this is the negative.
Yes, sir.
Watch, the voltage across these resistors is
The same. Positive and negative.
so if over here was 5 volts, then across both of these resistors would be what?
Also 5 volts.
Right. Voltage across resistors in a parallel circuit is what?
The same.
Did you guys know this or no?
Yes, sir.
Did you all know this or no? I only hear Nikolai.
Yes, sir.
Yes, sir. Yes, sir.
Right. So, and the main formula I need to remember here is that V is equal to what?
IR equal to the current and resistor.
Right, V is equal to IR. And also you need to know that P is equal to what?
I over R, or is the same
No.
thing?
No.
IR.
IV.
IV.
My
P is
bad.
equal to IV. Right, so this is the summary. So let me just, I'm going to draw a circuit first, and I want you guys to tell me if it's parallel or series. What type of circuit is this?
Series, sir.
Series.
Series. Series.
Okay, what about this now?
Parallel.
That's a parallel.
Well, okay, I'm going to label the resistors, right?
Got
R1, R2, R3. Which resistors are parallel to each other? Well, actually, this is a bad example, right? No, let me explain something.
So this still look like a series.
Let me explain something, guys. Let me explain something. If you have a resistor here, right?
Yes,
And you
sir.
have a wire connecting here to here, where would the current go? Would the current go through the resistor, or would it just go straight through this path?
Yeah, just go to the
Through the resistor.
It will go through the
There
free
are two
path.
paths.
Wanna go through both ways?
It would go right here, what, right? Here, right? Current likes, this is our oversimplification, but current likes to take the path of least resistance. If you connect here to here directly, like a negligible amount of current will pass through R2. Most of it will just go straight through, like straight through right here. Yeah. So in other words, the resistance here would be what? What would the resistance here be? If it's a fixed wire, it's 0, right?
0.
It's 0.
0.
So if you have something like this, like negligible current will flow through R2, will just go straight through here. And let me show you what I mean. Let's just say R2 was 100 ohm resistor, and I added another resistor, and I say this resistor was 10 ohms. When the current splits, right, where do you suppose most of the current would flow?
So the resistor,
R3.
10.
Through R3.
R3.
Most would flow through R3. Why?
It's the least.
Because it have all the resistance.
Less
A
resistance.
smaller resistor.
Of a smaller resistance. Now, the circuit as it is, which resistor? Let me just change this to R4. Which resistors are in series?
Series it could be R1 and R4.
R3 and R4.
R1, R2, and R4.
Yeah, I gotta be careful, very, very careful. Let me explain this to you guys. You see these two resistors over here?
So they're parallel
Yes, sir.
They are parallel
to each other.
So actually, let me use this as an opportunity. Right? I'll treat this as a question. Let me just say R1 is 7 ohms, R4 is 6 ohms, and the voltage we have here is 10 volts. Okay. If they want, and let me put an ammeter here. Oh, I should probably explain how you just put an ammeter or voltmeter in a circuit. Are you know how to do that?
Yes, sir.
No? I gotta explain that then. Alright, so an ammeter. It's an ammeter, right? I feel like I spelled that wrong.
Oh, actually,
Right.
that's correct, sir.
That's correct?
Yeah, that's correct.
Okay. I just always feel like I'm spelling things wrong. What do you think an ammeter measures?
The current.
So
Measures
voltage.
current. Nah. Ammeter. Ammeter. Amp is current. And this is a voltmeter. What do you think a voltmeter measures?
Voltage.
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 No. Be careful with this, right? Would you say, okay, doesn't current have to flow through the ammeter for it to take a reading?
Yes, sir.
I have a question.
Yes, sir.
Somebody said they had a question.
Yeah, I have a question. So the ammeter, does it thing that's be outside your house? The kind of circle thing, the clear
That's
circle thing?
a wattmeter.
Oh,
It measures voltage and current. And it okay, do you know that power is equal to voltage by current? Well, you guys didn't know IV is the same thing. Do you know that power is equal to current by voltage?
Yep.
Yeah or no?
Yes.
Yeah, so it measures the current and the voltage and multiplies and you get the power. Let me show you guys something, right? A lot of you guys don't know this. So on this charger, it says what?
I was going to say
67
something
watts.
on
67 watts. 67 watts.
Right. So 1 second. Right? It's really, really hard to see, but over here you have like a bunch of specifications.
Yes, sir.
And the one that says 6.7, it says 20 volts and 3.35 amps. I will let you do the maths, right? How do you think they get the 6.7?
Power, which is equals to IV
Exactly, so they multiply any 20 by what?
by the resistance.
No. Remember, power is voltage by current.
Oh, why?
By the
Resistance.
So like on this, it's really hard to see, but they are telling you they get 67 watts when the voltage is 20 volts and the current is 3.35. What is 20 by 3.35?
67.
67, sir. I multiply 20 by the 3.3.
That's it.
Yes, sir.
So here what? If you want to measure current in our circuit, the current has to flow through the ammeter. So you'll hook up the ammeter in series or parallel.
Series.
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 Let me explain. I'll tell you guys probably confused. This is in series. Can we see that if it's in series, the current will flow through it?
Yes, sir.
Yes, sir.
Yes, sir.
Right. So we hook up an ammeter in series. And let me ask you this. If you're adding an ammeter into your circuit, do you want the ammeter to mess with your circuit?
No, sir.
No, sir.
No. So if the current is flowing through the ammeter, do you want to be adding resistance to your circuit?
No, sir.
No.
No,
So
sir.
so an ideal ammeter should have a resistance of what?
0.
0.
Right, because you don't want it to be adding resistance to your circuits. Now, in real life, most ammeters have a very low resistance. Not 0, but very, very low. So let's just do a quick review. An ammeter needs to be hooked up in what?
In series.
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 And it must have a what resistance?
0. For an
Zero.
ideal ammeter.
Zero resistance. Zero resistance.
All right,
So
let's talk about.
ammeter is the capital A that has been the series, right?
Yeah.
Okay.
Let's look at voltmeters now. Voltage is potential difference. When you hear the word potential difference or just difference, isn't difference between 2 points? Like, yeah, you measure a difference between 2 points. So let me show you guys what I'm talking about. Compound circuit here. Power ammeter here. So does everybody understand that based on how the ammeter is in the circuit, the current will flow through the ammeter and give you a reading for current.
Yes, sir.
Yes,
Now,
sir.
does it make any sense for me to measure voltage like this?
No, sir.
No, this makes
No,
no
sir.
sense at all. This makes no sense because I don't know if you all know, but this over here is called a node, and the voltage is going to be the same. And so if you measure voltage like this, you're going to get 0.
Because there is no potential difference.
To measure voltage, it has to be between 2 points. So let me show you what it would look like. Oh, let's see what I'm talking about.
Sir.
Yes, sir.
Right. If I wanted to measure the voltage across the resistor, I would put it like this. Again, before the resistor and after the resistor. Because you know what? Anytime current flows through a resistor, you have a voltage drop.
Yes, sir.
So, guys, this is in series or parallel?
Parallel.
Parallel.
Yeah, parallel.
So could you put any resistor between the two resistors?
Well. You mean to say, could I have put any voltmeter between the two resistors?
Yeah. I think I said that wrong, but
Yeah.
no, like
Let me ask you a question. What would the potential difference across this be? Anybody can tell me?
0.
Is the same length of wire? Is the same
No,
0?
so
Be 0.
I meant from the first resistor at the entry to the second resistor at the exit point.
Here?
Yeah.
Yeah, that's fine. It's fine.
Okay.
And the answer would be whatever the total voltage was. Yeah. Cool. So a voltmeter has to be hooked up in what? Parallel or series?
Parallel.
Parallel.
Okay. Let me ask you a question, right? anytime you have parallel circuits, what happens to the current at the junction?
It is split.
It splits.
It splits. Let me ask you guys a question. Do you want the voltmeter to be stealing current from your circuits?
No.
No, sir.
No. If you don't want it to be stealing current from your circuit, should it have a high resistance or a low resistance?
Low
Low
resistance.
resistance.
High
Okay.
resistance.
Somebody said low resistance. If it have a low resistance over here, hey, most of the current gonna pass through it. No, that's not what we want.
Oh yeah.
If it had a really, really high resistance though, would the current want to pass through the voltmeter?
No, sir.
No, sir.
So, for a voltmeter, you want a very high resistance, right? A very, very high resistance. Do you understand why?
Sir, it's not because the current takes the path of the least resistance.
Yeah, that's an oversimplification, but yes. So if there's if it has a if it have a resistance of infinity over here, will any current be able to pass through it? If it has a infinite resistance, like infinite resistance, no, the current will not be able to pass through it. And if the current isn't passing through it, is it taking any current from the circuit?
No, sir.
Yes, sir.
No. So ideally, a voltmeter should have a resistance of infinity, but ideally, well, realistically, it just has a very high resistance. Yeah. So you understand what I'm saying, right? We don't want the voltmeter to take up the current. So if I give it a very high resistance, most of the current is just going to flow through the component like it should. So the voltmeter should have, ideally, it should have a resistance of what? Infinity. But realistically, it just ends up having a really what resistance?
A really high resistance.
Yeah. Right. I mean, if you guys understand this. Guys, are you with me? I'm gonna follow you. Understand this.
Yes, sir.
Yes, sir.
Yes, sir.
Cool. So here what? Do you guys understand why I place the ammeter in series now?
Yes, sir.
So how will the current look like in this circuit? Well, it'll leave the positive terminal and it'll flow like this. Okay, quickly. A represents the total current or the split current?
The total?
Total
Because
current.
we had resistance was you.
Right, this would represent the total current. So let me show you guys how you tackle a question like this. So first of all, we need to combine all the resistors. So I want you to think of the circuit like it's in parts. Which resistors are clearly in parallel?
R2 and R3.
R2 and R3?
Right. How would I combine R2 and R3?
1 over R plus 1 over... Well, it's 1 over R2 plus 1 over R3.
Now let me show you an easy way to do that. Combining parallel resistors, R2 and R3. Check how easy it has to be, right? I could just say 1 over 100 plus 1 over 10 to what power?
Minus 1.
The negative one.
Right, so plug that into your calculator and let me know what you get.
I get 100 over
100.
Again, tell me what's a decimal.
9.10.
9.10?
Yeah.
Everybody getting that, right? Now, if you did it the long way, where's 1 over 100 plus 1 over 10?
11 over 100. I assume. Yeah.
And then you would reciprocate both sides. Where's 100 over 11, guys?
The same 9.10.
Yeah, the same 9.10. So I'll pick all the poison, right? Either one is fine. All right, cool. So here what? I can now redraw the diagram. Which two resistors did I just combine?
R2 and R3.
R2 and R3.
So instead of drawing all of this, I could just draw what?
1, well, R2 plus 3.
And I'm gonna say that as how much ohms?
9.10.
9.10 ohms.
Yeah. And well, we had R4. That was 6 ohms. So question, guys, question. All these resistors are now in what?
Series.
Series.
Would it be that hard for me to combine them?
No, sir.
No, it would not. Be very easy. So how would I find the combined resistance?
Just
I
add
don't know.
all.
You add all.
Gotta find the sum of them.
That's all. And so if I want to find the combined resistance RT, which is the total resistance of the circuit, that'll be 7 plus the 9.10 plus the what?
E6.
And what would I get for the total resistance?
22.10.
22.1.
20 what?
22.1.
22.1.
So that whole complicated circuit could just be boiled down to this. Let me know if you guys understood how I did this.
Yes, sir.
Yes,
And
sir.
how do you
Yes,
fold
sir.
the ammeter as well?
Yes, sir.
Right, and the ammeter was originally over here.
The
And the
voltage.
ammeter would have asked us to find total current.
So
Now,
it would be voltmeter as well.
no, I didn't put voltmeter in the circuit.
Oh, my apologies, sir. Sorry.
That's okay. And so if they ask you to find the total current in the circuit, you need to find your total resistance first. So question, guys. If I know my total resistance is 22.10 and my voltage is 10 volts, how am I going to find the current?
E is IV.
Equal to I.
Right.
Together.
So V would be 10. Where's the resistance?
22.10.
22.1.
Trying to find for the total current. So what I do on both sides there?
Divide by
Divide by
22.10.
22.1.
So the current would be what? What is 10 over 22.10?
0.5.
That's 0.45.
0.45. I read it to decimal places, no? 0.45 amps.
Okay.
Yes, so 0.45.
You guys understand that?
Yes, sir.
Yes, sir.
So anytime they ask you for total current, you have to find total resistance. So here's my advice. You want to combine the parallel resistors, then sum up everything in series.
Yes, sir. And what we just calculated was for the ammeter.
Yeah, that's for the ammeter.
Okay.
Right, so let's do our CSEC question.
Sir.
Right, and I'll show you guys the current divider law just now. Right, so anybody want to help me with this question? This is the last electrical question we're doing for the night. Well, I would do like a couple more. Yeah. Who wants to help me with it? Shania? Right, no problem. Shania, give it a read. Shania?
Figure 9 shows a circuit diagram which has a combination of 4 resistors and an ammeter. A. Calculate the reading of the ammeter when the switch is open.
Okay, no problem. So here what Shania, my first piece of advice is draw the direction of the current. Conventional current flow says that it goes from the positive terminal to the
negative terminal.
Okay, cool. And I want to figure out the reading on the ammeter when the switch is
open.
no problem. Pick your wrong Apple Pencil up. Yeah, so is anything I'm doing here confusing you?
No, sir.
No, sir.
So, Shania, the current is going to go from the positive to the negative, right?
Yes, sir.
So we have the positive here, and we have the negative here.
Yes, sir.
Somebody said they're real confused. I'm going to try to explain it one more time.
So I could ask you a question, is that? Like, what pass it back?
Not sure what year this is, or not. I'm not sure. Not sure. Somebody remind me. Conventional current flows from where to where?
From the positive to the negative.
Positive to negative.
So here what? Isn't this the positive terminal here?
Yes, sir.
And this is the what? Negative terminal, right?
Negative.
Yes, sir.
So I'm going to go from positive to negative. It isn't hard, guys, I promise. Positive to negative. Watch. When it reaches over here, what's it gonna do? Shania.
It's gonna split.
Sir.
Let me ask that question, Shania. Can it pass through this open circuit over here?
No, sir.
No.
Sir.
Yeah?
This is 2024, May, June.
2024, May, June? Okay.
Yeah, I was not going to say that.
Alright, cool. 2024, May, June. Right. So Shania, the current will pass through the resistor. And the current will continue flowing like this to the negative terminal. Do you understand this?
Yes, sir.
No. If the switch is open, is any current gonna pass through this this node over here?
No, sir.
No. So I could boil down my circuit to make it simpler.
Yes, sir.
So I'll just put the 12 volts over here. Be negative over here. For my 3 ohms here. And here what? Since the switch is open, we know that no current is gonna flow through here. So if no current is flowing through there, can I exclude it from my diagram?
Yes, sir.
I could. So after the 3 ohm, I'm just gonna put a what?
6 ohm.
And then after that, I'm just gonna put a what?
A 1 ohm.
So guys, do you guys understand why I left out the 3 ohm resistor here if the switch is open?
Yes, sir. There's no flow of current if the switch is open.
Exactly. So we could leave out this entire thing. And if we leave out this entire thing, it's gonna leave us with a what circuit?
A series circuit.
Series.
Tell me guys, this current we want to find for, is this a divided current or is it like the total current?
Total current.
Total current.
Right, is the total current. So to find the total current, we must first find the total what? Tell me, Shania.
Total
Resistance.
resistance.
How would I find the total resistance, Shania?
You just add all the resistance in the series circuit.
So that would be 3 plus 6 plus 1, which is?
10 ohms.
Cool. And so how would I find the current?
We'll use V is equal to IR, and we know that V is 12, and that we don't know I, and we know that R is 10, and we can send over the 10 to divide, and that will leave us with I is equal to 12 over 10.
Which is?
1.2.
Nice. Are you understand how I do that question?
Yes, sir.
Are you sure?
Yes, sir.
Okay, now we have to figure out what the reading on the ammeter will be when the switch is closed. Is that a trick question? Even if the switch is closed, right? If the ammeter is placed over here, did the current split? Did the current split before it reached the ammeter?
No, sir.
No, so what will the current still be?
Oh, the 1.2?
12 volts.
Yeah.
Yeah.
Well, actually, no, never mind. I had a, yeah,
Because we
yeah,
didn't
nah,
add in
would be
one
that
of the resistors.
yeah, to combine them. Yeah, it would change. It would change. Yeah, I will explain why though. I'll explain why. So here we are saying, guys, it will not remain the same because this circuit excluded which resistor? Which resistor did this circuit exclude?
The 3 ohms.
But if the switch is closed now, what resistor are we taking into consideration?
3 ohms.
3 ohms.
Because the current of flow now like how it close.
So question. Are you guys seeing any parallel circuits there?
Yes, sir.
Yes, sir.
Yes, sir.
Which resistors are parallel?
The 6
3
ohm and
6 ohm and 3 ohm.
Yeah, and 6 ohm.
So I would have to do what with these resistors?
Yeah, add them.
Add them.
Not add. Right, let me show you. So here what? If I want to combine the resistors that are parallel to each other, what I'm gonna do, I'm gonna say 1/3
1/3
plus
3 plus
1/6.
1/6
So
to the
what?
power minus 1.
Yeah.
Let me know what you guys get for that. So remember, guys, anytime you want to find the total current, you must find the what first?
Total resistance.
Total resistance, yeah. Total resistance.
So I got 2.
Yes, I also got 2, sir.
So here what? This circuit could be boiled down. So I'm put back my meter here. I'm put my 3 ohms. Okay. And instead of putting the 3 ohm and the 6 ohm, what could I replace that with?
The
2 ohm.
Because how did I get that 2 ohm?
The combination of the 3 ohms and the 6 ohm.
Yes. And can we see that it's now a series circuit?
Yes, sir.
Yes, sir.
Because the current is not divided anywhere. It follows one continuous path. So what will be total resistance now?
6 ohm.
Right. So the circuit will boil down because if these resistors are now in series, what could I do with them? What's all I had to do with them?
Yes, add them.
Add?
Just add them. That's literally it. And so if this is the case, and I know that my voltage is still 12, how do I find the current?
12.
I is equal to 12/6.
Right?
These are
And so the voltage is 12 and the resistance is
6.
so your total current will be what?
2.
2.
Do you all understand?
Yes, sir.
Yes, sir.
So I have a question. Yeah.
Yeah? Talk to me.
Initially, this might sound stupid, but initially, how did you figure out that the current was flowing that way? Because there's 2 terminals that say positive and negative. Is it because of the position of the ammeter?
Oh, this is just a trick. Don't study about this. Don't study this. Like all you need to know, like this is the positive and this is negative.
Oh,
So
okay.
don't study this. Just put out the tie up. Right? What they're really doing here is that they're connecting 2 6-volt batteries in series. If I connect 2 6-volt batteries in series, what voltage would that be across it?
12.
12. Yep, 12. Okay,
thank you, sir.
And we're dealing with the conventional current flow here, which assumes that current goes from positive to negative. So the current must take the path of positive to negative. So all here. Yeah. Okay, do you guys... Okay, I want to explain the question back again, right? The ammeter is at a place where it receives the full current. Why am I saying that? Are you guys seeing the current splitting anywhere where the ammeter is?
No, sir.
No, so the ammeter is going to receive the full current. So if the switch here is open, in the first scenario, will any current flow through here?
No, sir.
No, sir.
No, no current will flow through there. None. And so I can simplify my circuit by removing the 3 ohms. And that will leave me with this. Are you guys with me?
Yes, sir.
Yes, sir.
Yes, sir.
The ammeter is going to measure the total current. To find the total current, you need to find the total resistance. As you can see, we have the 3, 6, and the 1 in series. If you have resistors in series and you want to find the total, what do you do?
You add.
You find the current.
Now, if you have resistors in series, it's so like real simple. All you have to do is just add them. Where's 3 plus 6 plus 1? 3 plus 6 plus 1 is?
10.
Okay, and how do we know it's in series? Aren't the resistors one after the other one, like a series?
Yes, sir.
Yes, sir.
Right, so we just add it. So here what? The total resistance is 10 ohms. My voltage is 12. According to V is equal to IR, V is 12. I don't know what I is. My resistance is 10. Dividing both sides by 10 gives me I. I is 1.2 amps. If the switch is closed, what does that change in the circuit? It changes the total what?
Resistance.
Resistance.
And if the total resistance is changed, what would that change as a consequence?
The current.
The current.
Total current. So here what? When you look at this, what kind of circuit is this?
That's a series circuit in
Series
itself.
circuit.
No.
Wouldn't it be parallel?
This is parallel. Watch. If you have trouble seeing it, when you reach this point over here, what's happening to the current?
It is splitting.
It's split.
Anytime you have current splitting, you're dealing with a parallel circuit. So this resistor and this resistor, they are parallel to each other. And if you want to combine parallel resistors, it's just 1 over the value plus 1 over the value, all of that raised to the power negative 1. You get your answer one time. So that's why I said 1 over 3 plus 1 over 6 to the power negative 1, and I got 2 ohms. And that's how you combine resistors that are in parallel. And to see if resistors are in parallel, you look to see if the current is dividing. If the current is dividing, or if it's being split, parallel circuit. So when I combine these 2 resistors, what did I get?
2.
2 ohms. So I can replace this whole thing with what?
2 amps.
I can just
1
2
resistor.
ohms. So I have 3 ohms over here, I have 2 ohms over here, and I have 1 ohms over here. From here, I could just add them. So 3 ohm plus 2 ohm plus 1 ohm is
6.
6 ohms.
So the combined resistance for the entire thing is what?
12 divided by 6.
2.
Well, the combined resistance is 6 ohms and the voltage is 12. So 12 over 6, 2 amps.
2
Do you guys understand this question?
Yes,
Yes,
sir.
sir.
All right. I'm going to add another dimension to the question.
Would that be with the voltmeter, sir?
Nah. The other dimension I'm going to add is with the current splitting.
Sir, and the next part on this question asks us to calculate the power dissipated.
Yep, and power dissipated is given by what?
P equal IV.
P
Nah.
is equal to I square R.
Right. Anytime you do it, power dissipated, that is I squared R.
Oh, okay, sir.
They say that in any other way that would confuse you, or it's just like that?
It's typically say that. Or they might say, find the power wasted as heat.
Okay.
Okay, so here we're going to do, right? Let's say the switch is closed. Let's say that for a second that the switch is closed. We already know that the current is going to what? When it reaches this point over here, what is the current going to do?
It splits into two.
It's going to split.
Splits.
So up to this point, we have the what current? I'll help out the total current. Because at this point over here, right before it didn't split us yet. So up to this point, we have the total current. Wasn't the ammeter measuring the total current?
Yes, sir.
Because the ammeter was before the current split. So here what? If I asked you to find the current over here, it might be a bit tricky. So let me show you guys how we're going to tackle that. You could just use the current divider though. That's it. So let me just say back what I was saying, right? Tell me something, guys. At this point, what's going to happen to my current?
It splits into two.
Split.
So remind me, when the switch was closed, what was the total current?
2 amps.
2 amps.
That's 2 amps, right? At the ammeter here, that is going to be 2 amps. So we have 2 amps of current here, and when it reaches this point, that current is going to be what?
Split into two.
It's going to be split into 2. Let me ask you that question. Where do you think most of the current is going to go? Through the 3 ohm or the 6 ohm?
These 3 ohms.
3 ohm. 3 ohm.
Right. So let me show you this quickly, right? If I want to find the current over here, it's just going to be, okay, and this might confuse you, right? This might confuse you. It's going to be 6 over 3 plus 6 by the total current, which is 2.
The 3 plus the 6 was the 2 ohm, the 3 ohms and 6 ohms.
That's this.
Oh, okay.
So we're going to end up with 6 all over 9 by 2. What is 6 over 9 by 2? Okay, this is the part that might confuse you guys.
1.33.
Some of you all may be wondering, some of them might be wondering, sir, you know, if you're dealing with this resistor, why you gonna put 6 over here? Well, I'll ask you a question. Where does most of the current flow in this parallel circuit? Through the 3 ohm or the 6 ohm?
3 ohms.
3 ohm.
So our question, even though we're dealing with the 3 ohms, should I put the 6 on top or the 3 on top? Okay. If I put 3 over here, would I get a small answer or a big answer?
A small answer.
Small answer.
Yeah, so it makes sense to put the 6 on top. You guys will see. You guys will see it in the end. What is 6 over 9 by 2?
1.33.
1.33.
All right. And I want you to apply the exact same concept, but instead apply it for the 6 ohm resistor. So that is
0.67.
wait,
Yeah.
what would go on top, guys? We're dealing with the 6
3.
ohms. 3.
3 will go over top, sir.
And what would we get?
0.67.
I got 0.6. Yeah, 7.
Let me ask you that question. If you add 0.67 and 1.33, what again?
The 2 amps.
Wasn't that the current that entered the node?
Yes, sir.
Right. I hope it makes sense, you know. If
No,
2 amps,
sir,
if
don't.
it don't make sense?
No, sir, I'm confused. Like,
Okay.
why you adding the 3 and the 6 at the denominator?
We're effectively dividing the current. We're treating this as a fraction. So like, we have 3 ohms over here and 6 ohms, right?
Yes, sir.
If I combine that, that's going to be 9. So out of the 9, what fraction of the 9 does this receive? Let me ask you a question, Shania. Which resistor is bigger here?
The 6 ohm.
Okay, where do you think more current will flow? Through the smaller resistor or the bigger resistor?
The smaller resistor.
Exactly. So out of the 9, the 3 ohms is going to receive the 6. 6 out of 9. 6 over 9 of the total current.
Oh, okay. That makes
And
sense.
the bigger resistor, will more current pass through it or less current pass through it?
Less current.
Right, so out of the 9, 3 out of 9 of the total current is going to pass through that. Make sense now?
Yes, sir. It's kind of
It's-
like unequal sharing.
Yeah, it's like a final ratio. It's like, because you understand, the current here is being divided. And if it's being divided, then obviously the current here will be some ratio with respect to this one. It's going to be some ratio. It's going to be some fraction of the total. If you understand what I mean, like this will have to be some fraction of the total current that entered.
Yes, sir. That makes sense.
And notice the two currents are going to meet back at this point. So when they meet back at the point, the 1.33 and the 0.67 are going to combine. What is 1.33 plus 0.67?
2.
2. And wasn't that the initial current that entered?
Yes, sir.
Right. So hopefully you understand that. So the current that entered was equal to the current that what?
2 amps.
Current that So the current that entered is the same as the current that left.
Yeah.
Yes, sir.
Yeah. So I hope you guys understand that.
Yes, sir.
So let me give you guys another example quickly, just to make sure that we fully understand it. Let's just say we have 9 volts over here. We have a 10 ohm resistor here. I have a 1 ohm resistor over here. First of all, what kind of circuit is this?
Parallel.
Parallel.
A parallel circuit. Why? Because at this point over here,
Because
the
it's
current is going to split. Now, if I wanted to find the total current in the circuit, what would I do?
You find for the total resistance first.
How would I find total resistance?
You find
combination of
1 over 10 plus 1 over 1 in brackets minus 1.
If I wanted to combine these resistors that are in parallel to each other, that would be 1 over 10 plus what?
1 over 1
To the power what?
minus 1.
Let me know what you guys are getting.
0.9.
0.91.
0.91?
Yes, sir.
Yes.
So therefore, my combined circuit, like, okay, if I were to combine the resistors in simplest forms, like in the simplest way possible, this is what my circuit would look like.
Yes, sir.
So I have a voltage of 9 volts, and that 9 volts is across that resistor. And so would I be able to find the current through the resistor?
Yes, sir.
Yes, sir.
Right. So we know I is equal to V over.
R.
R.
Right. What's the voltage?
9 volts.
Voltage is 9.
What's the resistance?
0.91.
What is 9 over 0.91?
I got 9.9.
0.9. Yeah. 9.9.
9.9.
9.9.
That's the exact thing you guys got?
No, it was 9.89.
9.89.
Yeah.
So I'll make it two decimal places.
Okay, so it's just be 9.89.
9.89.
So that would be my total current, right?
Yes, sir.
So before the current gets divided, what's the total current?
9.89.
So over here, if I were to put an ammeter over here, what would the ammeter here read?
9.89.
Yeah, 9.89.
Now, let's just say I put an ammeter over here. Right. And I wanted to find the current here. How would I find the current there?
It would just be 1 over 10 plus 1.
From here.
Well, if I want to find the current here, I call this A1. I just call it A1 so you guys will be able to differentiate it, right?
Yes, sir.
Because like if I just put A right through, it might be a bit confusing. I just put in this just so we can differentiate it. It's not that deep. So let's just find the current by A1. So question, guys, where would most of the current flow? Through the 10 ohm or the 1 ohm?
The 1
The
over
1 ohm.
Right. So if we're treating the whole thing as a fraction, right? Then it's gonna be 10 plus 1, and we understand that less current gonna flow through here, so we're gonna give it 1 out of the 11. And we're gonna multiply this by the total current, because the total current is what's being divided. What's the total current?
9.89.
9.89.
Right, what is 1 over 11 by 9.89?
0.899.
0.899. Yeah.
But it'll just be 0.90.
Okay, cool. I want somebody else to tell me how I'd find the current by A2.
So, sir, you have 10 over 10 plus 1 times 9.89.
Right? And what would I get?
So you're gonna get 8.99.
All right. So we're clearly using rounded off values here, right? We're clearly using rounded off values. Because
So it
when
will
you're
be 99. 8.99 or 9, sure.
wait, so you're getting 8.99999 recurrent?
No, sir. That's 8.990.
And then 0.
Okay, 8.99. So I have a question. Now, theoretically speaking, when the currents merge at this point, it's supposed to add back to give me what?
9.89.
When I add 8.99 and 0.90, what do I get?
9.89.
9.89.
Right.
9.89.
Yeah. Are they okay with this?
Yes, sir.
Yes, sir.
Yes, sir.
All right, when y'all do Unit 2 physics, you learn about KCL and KVL. Kirchhoff's current law and Kirchhoff's voltage law.
Okay.
So like Nikolai, you see how the current entering the node here is equal to the sum of the currents leaving?
Yes, sir.
That's KCL, that's Kirchhoff's current law. So you see how 9.89 amps entered here?
Yes, sir.
One had left, what was it?
It came back to its original value.
Right. And KVL, Kirchhoff's voltage law, just says that the sum of the voltage drops in the circuit would be equal to the source voltage. Or you could just say the sum of the voltages in the circuit adds up to 0. Because if you add up the source voltage and the voltage drops, you get 0.
Oh, okay. Well, that's interesting.
Let me do this question fast. Anybody want to help me with this fast?
Sir.
Alright, so Nikolai.
Sir.
I'll let Nikolai help me with this fast. So Nikolai, I pray that this will come, but if it does come, I have the answer right there. With the aid of a diagram, describe an experiment that may be used to investigate the relationship between current I and potential difference V for a filament lamp. Sketch your expected result. So the answer you're looking for is right here. Would you guys have looked at IV characteristics for diodes, conductors, and filament lamps?
I don't think so.
Yes, sir.
No,
Yes,
sir.
sir.
No, not really.
I didn't do that?
Yes, sir. Well, we were
Yes,
just
we
given
did.
like
Yes,
a
sir.
worksheet with all the properties and stuff.
Okay.
Yes,
For
I
us, it was the diode and the semi diode, but that was it.
Okay. Well, should have it here. You could take a screenshot. IV characteristics. If I don't have it here, I'll just draw it. Oh, look, it's right here. These are the IV characteristics. If you have a ohmic conductor, it means it's a pure metal. And you could get this question tomorrow. They could give you any first question. They could be like, you're given the following readings for voltage and current. Plot the graph. Then state what the gradient is. If you're given a graph of V versus I, what do you think the gradient would be?
a line passing through the center. Oh, wait. Gradient?
What would the gradient represent? V over I.
The change in V, the change in I.
The resistance.
Yeah. A question like this come tomorrow, because I'm alright. But it could give you voltage readings and current readings and tell you to plot the graph and then ask you to state what the gradient represents. If this is the case, the gradient represents resistance. So this is what would happen if you have a pure metal, which is a good conductor. If you use a filament lamp, this is what it's going to look like. You don't need to know copper sulfate electrolyte. And this is what a semiconductor diode looks like.
Do we
Let
need
me
to
explain.
that one?
Yeah, I need to know that one. Let me explain this quickly to you guys. This is what a semiconductor diode looks like. It would only allow current to flow in one direction. Do you think it would allow current to flow in the other direction?
No, sir.
No, sir.
No. So, let me explain what I mean by this. I feel like this is one of the densest parts of physics, boy. Because there's a lot of things we do. Remember, how does current flow again? From where to where?
Positive.
Positive to
With
negative.
negative.
The currents would flow, right? Because it's any direction of the diode. You can imagine that it's kind of like an arrow. Yeah?
Yes, sir.
Yes, sir.
Now here what? I'm going to switch the polarity. When I say switch polarity, what does that mean?
Direction.
Yeah, means you're going from negative to positive.
Well, okay, when I say switch the polarity, I mean that you see the battery? I'm gonna reverse the terminals. So I'm gonna switch the battery. If I switch the battery, right, guys? The direction of current is gonna change.
Yes, sir.
Yes, sir.
Tell me, can the current go past the diode now?
No, sir.
Yes, sir.
No. So let me explain this quickly. When the voltage is positive, the diode is in forward bias, meaning that it could conduct. But when the voltage is negative, what's happening?
Nothing.
Nothing. The current is essentially what?
Zero.
Zero.
Yeah. So
Hey,
hopefully
so,
understand.
so do we draw it exactly how we see it here?
Yeah, you could draw it like
Because
that. It's fine.
I know the X. I know it's supposed to be on the X because the X would show is zero, but it below the X axis.
Because it will never truly be zero. It will always have some leakage current. You don't know about that before you do electrical engineering.
Okay.
Yeah. And truth be told, this graph would go like this, eh? Like over here is your leakage current, over here will be your avalanche current, and over here will be like your reverse voltage. And like over here will be your breakdown voltage. If you like, if you apply too much voltage to a diode, it break the diode and it will allow it to conduct regardless.
Oh, okay.
But all you just need to know about this. Yeah. So the main ones you need to familiarize yourself with is the one for ohmic conductor, a filament lamp, and a semiconductor diode. So store that in memory.
Yes, sir. Wait, can I take a screenshot of this now? Seeing that
Yeah.
you
Take a screenshot first. And by the way, guys, you see the circuit where the diode allow the current to flow?
Yes, sir.
Yes,
They
sir.
call this forward bias. What do you think you call the other one?
Backwards bias or reverse bias.
Ah,
Reverse
boy.
bias.
Reverse bias. All right, cool. Let me get back to the mission. I'll give a break. I feel like I need a break. This is what the filament lamp looks like.
Yes, sir.
This region over here will be the what region?
Negative.
Negative.
No.
Nah, the linear region. The linear region.
It'll just be I over V.
Yeah. Yeah. This is the linear region. And over here, this is non-linear regions.
Yeah.
So if they were to ask us to find the gradients using the filament lamp graph, we'd find it from the linear region.
Yep.
Okay,
Hey, that
cool.
was such a nice question, Blackom. That'd be such a nice question. It would. You have to find the gradient of the linear region.
What was the information?
Oh, this was to measure the resistance. So let me explain. Set up a circuit as shown below, or shown above. Increase the resistance in increments of 5 till 30. From step 2, record the values of current and voltage. Plot the graph of I versus V. So Nikolai, if you wanted to experimentally look at the IV characteristics, this is what you would do. So you'd have a battery here. You'd have an ammeter so you can measure the current. Oh, that ammeter is hooked up in what? Ammeter is hooked up in what? Series. I'd put the filament lamp over here. Across it, I'll put the voltmeter so I can measure the what?
The
voltage.
The
The
input
voltage.
and the output of the current.
Aye, the voltage. The voltage across the filament.
Oh, okay.
And then I would put a rheostat over here. Why are we putting a rheostat? Well,
Resistance.
if I put a rheostat there, wouldn't we be able to get different current readings at different okay, we'll get
Yes,
so
sir.
like guys, if the resistance of your circuit changes, what are the things that change?
Current.
The current.
Yeah, your current will change, and as a result, the voltage across the filament bulb will change as well.
Yes, sir.
And so by varying your resistance, you could actually get a bunch of readings, and then you could plot your graph. You understand?
Yes, sir.
So that's the purpose of the rheostat over here, to get different readings for current and voltage. So you can go and plot your graph. Take a screenshot of this. I wonder if it have anybody on YouTube. Wow, it have like nearly 300 people on YouTube. I'm fully barbecued. No, I did not eat. Alright, I'm gonna follow okay with this.
Yes, sir.
Yes, sir.
Somebody tell me fast, what is the purpose of the rheostat in this circuit?
To check for the different resistance and the current.
I wouldn't say it like that. Somebody else give it a try.
To be able to change the resistance of the circuits, you'll get variable readings.
Alright, now that's better. So the purpose of the rheostat is to change the resistance in the circuit, so you'll get varying results for ammeter, for current and voltage. If you have different readings for current and voltage, you can then plot a
graph.
Right. So the purpose of the rheostat is to change the resistance of the circuit So you can get varying results for current and voltage. So you can plot a graph. That is it.
Yes, sir.
All right, so Nikolai, read 5B for me.
The power supplied shown for the circuit in figure 4 provides a current of 1 mega amp.
Nah. Correct yourself. That is what?
Meter amp or something? Meter amp?
Nah. This is our prefix.
Billy.
Yeah.
Milli? Okay.
So milli means 10 to what power?
-3.
-6 -3.
Nikolai, if you know what milli means, and if you know it's 10 to the power -3, I would cry if you say it's meters. Because you know what milli means. You know what milli means. You know milli is 10 to the power -3.
Yes, sir.
I will literally cry. I'll crash out.
Okay, so I'll read it back. The power supplied shown for the circuit in figure 4 provides a current of 1 milliamps to the rest of the current. Assuming
The rest of the circuit.
Oh, my bad. Circuit. Assuming negligible losses in the connecting wires, calculate the required potential difference of the supply.
Okay. All right, are you ready?
Yes, sir.
It's a nice question, boy. So, Nikolai, in the question, what are they providing for us?
They provide any current. And
So they're giving us the current. They're giving us the current. Lovely. They're giving us the current. Bam. The current they're giving us is
1 milliamp, which is 1 times 10 to the power -3.
So here what earlier. They're giving us the current, and in this circuit, what are you seeing?
The resistors, the ohms.
They're giving us resistance. But we should know if you want to find voltage for the whole circuit, you gotta find what? Or what?
Total resistance.
Total resistance. Could we find total resistance from a circuit?
Yes, sir.
Yeah, we could. Could do that. And if you have I and RT, what you could do?
Find for V.
You can find the voltage.
Right, because V is equal to
IR.
IR.
That's extravagant news. Are you understand the concept?
Yes, sir.
Yes, sir.
All right, so here what? Nikolai, which resistors in series?
None. But I'm in parallel.
Well, actually, the sum of when you combine these two, it will be in series with what?
Oh, it will be series with the one.
Right. Which two resistors are in parallel?
The 3 and the 2. The 2 and the 3.
Right. So
23, yes, sir.
and obviously, to do this, you need to close the circuit, right? So Nikolai, remind me, how does current flow from where to where?
From positive to negative, sir.
So when we reach this point, what happens to the current?
It will be divided into 2. It will split into 2.
And at that point, it will merge back.
And go to the negative side.
Right. So Nikolai, let's combine the parallel resistors. I really feel like I need more space. Anybody sponsoring food or?
Unfortunately, no, sir.
Hey, buddy.
Unfortunately, I get food.
All right, so I have space now. Yeah, so Nikolai, which two resistors are in parallel?
The 2 and the 3. So I could buy food if you wanted to. We could just go out and get some.
What? All them a car fixing. Otherwise, I'll run by food. All right, so if you want to combine R2 and R3, the real simple, Nikolai. You don't know the trick.
Yes, sir. In brackets 1/3 plus 1/5.
Whoa. We just talked about this prefix thing. Somebody tell Nikolai what we're going on.
It's in kilo ohms. So you have to multiply the 3 and the 5 by 10 to the power of 3.
Nikolai, you see that kilo ohms, eh, boy? You see that kilo ohms?
What, sir?
You see any kilo ohms?
Yes, sir.
What does kilo mean?
Well, kilo ohms, that is 10 to the power of 3.
Yeah. See, I don't forget that. So it'll be 1 over 3 by 10 to the power 3
Yes, sir.
plus 1 over what?
1 over 5 times 10 to the power 3.
And if I want to get my answer one time, I could just raise this to what power?
Minus 1.
Yep.
We got 1,875.
Anybody else get out? 1,875?
Yes, sir.
Yes, sir.
So I run it back again for people on YouTube. Oh, yeah. Any question, they give me current. If we want to find the potential difference or the voltage for the circuit, we need to find the what? We gotta find. We got the current, you know.
The total resistance.
Total.
We gotta find the total resistance. You look at this circuit. The current is being divided over here. So that would make these two resistors what? These two resistors will be what?
Parallel.
Parallel. Anytime you have two parallel resistors, it's real simple, you know. You're just gonna write 1 over what the resistor is, so 1 over the 3000 plus 1 over the 5000. Adding that and you're raising that whole thing to the power -1. You get your answer.
Yes, sir.
So Nikolai, when I combine R2 and R3, that's just what?
That would just be R2 plus 3 plus
Which
the
is?
R1.
And that is what?
That would just be 1,875 plus, I can't see you on top. Oh, 2 kilo ohms, which is 2 times 10 to the power 3.
Okay, I really hope nobody. Let me check on YouTube because I feel like people are real confused by it. People in Zoom, are they confused or they understand?
No, so we good.
Partially.
Alright. Are they understand or not?
Yes, sir.
Yes, sir.
Partially, sir.
So the circuit now, I boil down R2 and R3 to one resistor. 1,875 ohms, yeah?
So Jared don't understand.
Alright, Jared, do you know how to identify parallel resistors? Jared, if you don't talk to Mark, I help you, you know.
No, sir.
Alright, so Jared. To identify parallel resistors, you're looking to see where the current splits. So the current is going to leave the positive and is going to flow to the negative terminal. When the current reaches this point, what's going to happen, Jared?
It's gonna block off.
That is going to split. So at this point over here, watch, it's going to split. You're not seeing it?
Yeah, I see it.
Right. Okay, so like imagine I share money between two people, right? Over here, will be the total amount of money. And after here, I split the money. Right.
Oh, yeah.
So this will be the total current. And at this point, the current is divided. So some current goes through the R2 and some current goes through R3. So therefore, these resistors are parallel because, as you can see, the current splits over here. It's divided. And so
Okay, sir.
anytime you have parallel resistors and you want to combine them, it's just 1 over the resistor plus 1 over the other resistor to the power -1. And if you put that into your calculator and you do everything correct, you should get 1875. That's how you combine parallel resistors. So we just combine these two. And Jared, when we combine these two resistors, what do we get? Jared? Can I hear Jared? But when I combine these two resistors, guys, what do we get?
We get 1,875 ohms.
Correct. So I merged these into one. So that's the 1875, and we had that with 2K.
Yes, sir.
So what kind of circuit this is now?
It will be a series circuit.
Yeah, series circuit. So what will be the total resistance?
It
They
was
will
just
add a one. Oh,
no, go ahead.
they will add a 1,875 plus 2.
Add any 1,875 to what? Tell me.
Oh, 2 to the 10 to the third power.
2 by 10 to the power 3.
Okay.
And what I end up with, guys? I should get 3,875.
75 ohms, yeah.
So that is the total resistance. Now here what? In this question, did we have a current?
Yes, sir. We had a current of 1 milliamperes.
Right, 1 milliamperes. And so here what? We have the total resistance, check. We have the total current that's being provided to the circuit. That's 1 by 10 to the power -3 amps. What's the only thing I'm missing?
Volts.
Voltage.
And to find voltage is just a product between I and R.
Yes, sir.
Yes, sir.
So that'll be 3,875 by 1 by 10 to the power -3, and what we get in chat? Should be like 3.875. Oh no. Yeah, let me know what I get.
Yes, sir. 3.875 volts. Well, watts. No, volts.
And if I round it off to 2 decimal pieces, what that'll be?
By 3.88 volts.
Are you understand anything?
Yes, sir.
Right,
Yes,
because
sir.
voltage is just the product between the current and the resistance. So 3,875 by 10 to the power -3, 3.88. Cool. And that's the answer to the question.
Yes, sir.
So again, the hint in the question, right? They're asking you for potential difference. Potential difference is just a fancy way of saying what?
Take a voltage.
The voltage, right? So when you read the question and they ask you for potential difference, I want you to look at what you have. In the question, they're giving you current. The way to find voltage, and in the question, they're giving you the resistors. Is it hard to combine the resistors?
No, sir.
No, you could combine the resistors, find the total resistance, and then use V is equal to IR, and you get your answer. Right. So guys, let me answer the other question. Huh? Calculate the current in the 5 kilo ohm resistor. We just handled that question like this. Anybody want to tell me how we can do that?
Yes, sir.
Talk to me, right? What should do?
So we'll do 3 kilo ohms over 3 kilo ohms plus 5 kilo ohms multiply by the total current.
And I suppose we could call that here what? Probably call this I1, probably call this I2, probably call this I3. So they want me to find the current in the 5 kilo ohm resistor, right? So we be dealing with I3. So tell me how I'll find I3.
3 kilo ohms over 3 kilo ohms plus 5 kilo ohms.
So that'll be 8 by 10 to the power 3.
Yes, sir.
Multiply by
multiply by the total current.
What is the total current?
Was it?
It was 1 milliamp.
Yeah, 1
So,
minute.
so let me run it back again for anybody that might be confused. This is the current divider law. What did I do? Well, they want me to find the current through R3. So we added up the two resistors and I put in the denominator. 3,000 plus 5,000 is just 8,000, all right? 8 by 10 to the power 3. We want to find the current through the R3. If I want to do that, let me ask you that question, right? Where would more current flow? Through R3 or R2?
R3.
R2.
R2.
Remind me, guys. More current would flow.
R2 because it has less resistance.
Exactly. So question. When we are writing the current as a ratio, right, as a fraction, am I going to put 3 over the total or 5 over the total if we're dealing with R3?
3 over the total.
Right, because less current is going to pass through this, right?
Yes, sir.
If I put 5 on top, wouldn't that mean I get more?
Yes, sir. And you'd
Yes,
be
sir.
dividing 3.
Exactly. So I'll explain it back again. If you are dealing with if you're dealing with a situation like this when you have a parallel circuit, I had to figure out the current through one of the resistors. You have to add up the resistors first, and that's how I got 8 by 10 to the power 3. And we are interested in finding the current through R3. So I say the other one over that. So I say 3 by 10 to the power 3 over the 8 by 10 to the power 3. And I'm multiplying that by the total current because the current is splitting. What are we getting?
I got 3.75 times 10 to the power negative 1. No, 4.
Negative 4. Yeah. Yes, I got the same thing.
3.75 by 10 to the power negative 4 what?
Amperes, because it's
Amperes.
current we're dealing with.
Cool. I have a question for you guys. Let's just say I wanted to find for I2 while we're at it. How would I find for I2? I do not.
It would just be 5 times 10 to the power 3 divided by 8 times 10 to the power 3 multiplied by 1 times 10 to the power negative 3.
Let me know what you're getting, guys. You should get like 6.25 or something. So
Yes, sir. 6.25 times 10 to the power negative 4
and
amperes.
I'm asking that question, right? When you add this up, what are you supposed to get?
The 8 times 10 to the power 3.
Nah. You're supposed to get the total current, which was 1 by 10 to the power negative.
Oh. Okay.
So I have a question. So
Yeah.
if you wanted to, you could have just minus the 3.75 from the total amps and you'll be able to find I2.
Yep. Because the current entering a node is
Okay.
equal to the current leaving the node. That's Kirchhoff's current law. Yeah. But I'm just showing you guys now how to use the current divider law. Yeah. I was
Yeah,
just
no
showing
problem.
people how to do that. So I'm running back one more time for anybody that might be confused. If I want to find the current through R3, it's going to be, I know it's a bit confusing, but I'm not going to use R3 on top. I'm actually going to say R2 all over R2 plus R3 multiplied by the what?
The
The what
total
current?
difference.
And if I wanted to find the current here, it'd be what?
R3 by R2 plus R3.
Multiplied by?
I
Total current.
total current.
Good. And well, we get the answer for part 2, right? The answer for part 2 is just this.
Yes, sir.
I feel like, okay, right now I feel like so much people confused. Is that true? Like, are they genuinely understand?
Well, I understand, sir.
Yes,
No, sir, I understand.
All right. So let me answer part 3 now. So Nikolai, if the 2 kilo ohm resistor burns out, what current now flows in the 5 kilo ohm resistor? So Nikolai, the 2 kilo ohm resistor here burn out. Nikolai, if that burn out, what happen in the circuit?
It will just be open.
Yeah, it will be open. Let me ask you that question, right? If R2 burns out, will the current be able to pass through R2?
No, sir.
No, sir.
No, sir.
No. And so the circuit will be what?
Open.
Open.
Exactly.
Open.
So the current that flows through the 5K is what? Nikolai, if it's an open circuit, the current will be what?
0.
0? Yeah.
Yes, sir.
Oh, that was 1 mark. Wait, is it 1 mark?
Yeah, it's 1 mark.
Oh, okay.
Good. All right. So I'll call it a day with electrical questions, right? We looked at a lot.
Wait, sir.
Say that again?
Oh, wait. Sir, why would it be 0 if it already
0
the current
amps?
already passed through the
Right. Okay, let me explain that, right? So talk to me. If the 2 kilo ohm resistor burns out, it's now gonna have a gap in the circuit, you know. It's gonna have a gap in the circuit. So the current is gonna flow as per usual. You know, the current gonna flow. But when it reaches this point over here, will it be able to now make it past this region?
No, sir.
No. And if the current can't make it back to the battery, will any current flow in the circuit?
No.
Okay, I feel like that confused you. So here what? Imagine R2 was never there. If it blew out, it's not there. Alright. So cool. Good notes. Are you playing up for, boy? Hey, boy. Yeah. So look at the circuit, right? If there is a gap here in the circuit, will the current be able to make it past the gap?
No, sir. It won't be able to make it back to the battery.
Exactly. And if it can't make it back to the battery, then the current flowing through the circuit is really what?
None. Zero.
None. 0. So the current flowing through any of these resistors is,
0.
yeah, I understand that, right?
So
Okay, sir.
Right, so now we're going to move on to nuclear physics. Let's take a little break though. How long of a break do I want?
Sir, how long is the break?
How long will the break to be? Nuclear physics? Nuclear
15,
physics.
20 minutes.
How long?
Shallow 15 or 20 minutes.
I'll give all that 20 minutes break. When we come back, we're going to nuclear physics. Nuclear physics, you're not going to break any sweats for that. That's real easy. That's real easy. I tell you, that's real easy. Right? After we finish nuclear physics, I anticipate we're going to finish in an hour and a half. We're going to be jamming past papers. Right? True.
yes, sir.
Right down to the line. It's going to be good. It's going to be good. Yeah.
Okay, sir.
Right?
Sorry, think electromagnetism might come for this year, sir?
Yeah, we'll come. So, like, the reason why I focus so much on this, because the people that was with me for the previous lives, we'd have finished thermal physics. Then we'd have do waves and optics. So,
Yes, sir.
we only had a couple of sections to look at. After we look at nuclear, we just had to look at mechanics, and you're fine.
Yes, sir.
Yeah. Right, so, I want everybody to come back at 10:31 Trinidad time.
Same time for Guyana.
Why is he fake Apple Pencil behaving so? I will see some more tomorrow. I want to do like a little paper one live for maths. Do a little paper one live.
So no problem.
What time they say?
What time
Probably
it
like,
is though?
probably like 6 o'clock.
Okay. Let's see if I can get a sleep as soon as I come home.
Right. Ollie, remember, tell the people on YouTube to watch. Tell the people on YouTube to
Like
watch.
and subscribe.
Like and
Like and subscribe.
subscribe.
Turn on those
Like and
notifications. We're gonna
subscribe.
run paper
Like
Then
ones.
I
Alright, please
notification bell.
subscribe to the like button, like the subscribe button, and ring that notification bell. Ding a ling
Right.
a ling ling.
Ding a ling a ling. Ollie, because
Ding-a-ling-a-ling.
right now we are 4.79. So close to 5. So close to 5. Yet so far.
Yes, guys, put it to 5.
Guys, if you're not subscribed already, go subscribe.
Wanna get to 6.7.
Subscribe. Bad boys to the world.
Oof. I need to go get something to eat now. Yeah.
Charge whichever pen it is in the meantime.
I like that. That's some good advice. That's some proper advice.
Also put the tab to charge it on 37.
Ahead of you. Yeah.
We can't have the equipment failing us this early.
No. It's too early into the night, you know. We're going to 4, you know. Yeah.
So,
I know.
unfortunately, I might have to stop at 12
That's not a
or
problem.
11, whichever one. As long as I get to see all what I want to see to make sure I remember everything, and then I'll go to sleep.
That's not a problem. Oh, somebody's mic is unmuted. Right.
I'm gonna be real honest. I did not understand, well, some of electrical physics before you tonight. Like, this is just a generational lock-in.
Yeah, it is a generational lucky. Definitely. This luckiness crazy.
You should go and get your thing to eat. You sit down here, just, I don't know, fixing your hair like a mermaid man. Go eat.
No, somebody's asked my question. Yeah, boy. Alright, well, I'm gonna go ahead all day. I want to sleep, right? Good night.
So say you gonna sleep, yes?
Yeah, but
That's what I said.
So how are you feeling for the physics tomorrow?
Yeah.
real good, real good.
Less cooks.
Real good.
I mean, chemistry was cake. So I don't expect physics to be cake. I not
But
doing bio, but I hear bio was cake.
Biology
I
is
have
easy.
something to say though.
Honestly, bio was food, right? I watched his solutions when it came out CMD, and I kid you not, I only get like 2 things wrong. So total, I have about 80 something to like 90 flat on that paper.
Yeah, me too. Me too. I realized I get something wrong.
I'm not ready for physics though. I don't know.
I don't wanna
I
say I'm ready for it,
pumping
and
for that physics.
when I go and I see the paper and I start to, get nervous. I don't
Mash up
wanna
that physics.
just wanna try my best.
Just
Just wanna
trusting
see
Uncle Rajiv and we had our physics.
I will kick you out of the Zoom,
I'm
Uncle
so
Reggie.
So you can't do that, sir. I just son, you know.
Then they come up,
While it's still here, you like Mellow during that sitting with Fat Man Bob from Map Vibes.
Fat man Bob is my partner, but he eats all my food. That's why I
Mhm.
Up to now, Fat Man Bob still didn't lose weight. What
Oh,
diet you on, boy?
hold on. Fat Man Bob, he home. He ain't working out these days, but he eating real good.
Tell him enjoy the big back activities for me.
Yes, indeed, I will. But yeah, guys, the people on YouTube, people on TikTok, or they could jump across on YouTube, subscribe, or they turn on your notifications. Because said after we finish up paper twos this week, from tomorrow or the day after tomorrow, we're gonna hit paper two, hit me paper twos, we're gonna hit paper ones.
MVP right there. No worry, eating food, don't worry. But big up, big up.
So, after the break, what we gonna be doing?
Nuclear physics.
Alright.
I'm not
Nuclear
sure if I
physics.
was
Wait.
here or not, but did you go through logic gates already?
No. I'm not gonna treat it as a priority. I'm looking not really fun. But
I think
I
for
guess I
me
could
last 2
skip.
years.
I really doubtful, but I can skim through it fast.
I saw somebody predict that it's gonna come, but I'm not sure because I don't really understand logic gates at all.
Better now.
Logic gate.
Better now like coming.
So logic gate is like no or
Yep.
and NAND.
So what do you think coming?
Thermal physics, optics, electrical physics. And question on mechanics, probably like kinetic energy,
Yeah.
potential energy.
So did you ask Claude to make a predicted paper yet, or?
Nah, boy. I pay for Claude, right? 20 USD a month. And if
Did
I
I buy
use
it
that,
yesterday?
and if I use them that for like what, less than an hour, I'll wait for like the evening to use it again.
Why?
Because like Claude is very intensive on resources and like there's real micromanage. It's like with ChatGPT, if you're paying fit, you can use it nearly any point in time throughout the day.
Yeah.
If you
Yeah.
use Claude for like 20 minutes, they're gonna tell you your outer messages. Wait till the evening.
You're not paying for Claude?
I'm paying for Claude.
So the paid version have a limit?
Yeah.
Mine's never do that yet.
Probably didn't use it intensively enough.
Oh. How much is the limit like?
Like I use it around 4 and tell me I'll wait till 7.
Oh. Alright.
I could do some fried chicken right now, boy. Some nice fried chicken.
Don't forget the garlic sauce.
I don't eat sauce on my food.
I know, I just say
Criminal, that is
it's a
criminal,
song, it's
sir.
a song.
Claude say mechanics, thermophysics, waves and lights, electricity, and atom, and magnetism probably.
Yep. That logic is not gonna come.
Yeah.
Imagine it just come now.
Imagine. Expect the unexpected.
Well, for the people in the group chat, I did send my notes, and in my notes for logic gates, it have the easiest way to memorize it. So it'll be fine.
Okay, thank
Big up, big up.
you.
Big up, big up.
Rich man uses expensive gadgets.
I have some stuff on logic gates I should. Wait. Logic gates. Logic gates anyway. Logic gate is so buns. But yeah, logic it's really simple.
I just have a feeling in my soul that paper is gonna be ridiculously easy, but it's gonna bring the most unexpected topics.
Nah, it'll be easy. Go right here. Are you ready to start back? Well, let's allow some time. I don't know.
Yes, sir.
Now we want energy. What's going on? Kinetic energy. Go fast. Kinetic
Half
energy.
mv squared.
Right? What's the formula for potential energy?
mgh, mass multiplied by gravity multiplied by height.
As the height increases, what happens to the potential energy?
It increases.
Yeah. If something is at the top of a shelf, what is at its maximum? The potential energy or the kinetic energy?
Potential.
Potential.
As it falls, the potential energy gets converted to what?
Gravitational.
Gravitational potential energy.
Right. Cool. Are they okay with moments?
Yes, sir. Moments is cake.
It is. Moment is genuinely cake. It says that the anti-clockwise moment, so the sum of the anti-clockwise moments is equal to what?
The sum of the
The sum of the
anti-clockwise
clock.
moments.
Moment.
Clockwise moments. I don't know how to ask. Sum of anti-clockwise would be equal to what?
The sum of the clockwise.
Sum of clockwise.
About the same pivot.
Clockwise.
Yeah, about the same pivot. If something is at the pivot, what is its turning force? Remember,
Never heard that
turning,
one before.
remember, turning force is equal to F by D. So if it's at the pivot, what's the distance from the pivot? Guys, if
Zero.
something is,
Zero.
If it
yeah,
add the pivot is zero.
and as a result, the turning force would be,
Zero.
yeah, they could ask you that.
That makes sense, you know, sir.
Yeah, because if something is at the
Even
pivot,
yes,
current
sir. Yeah.
movement,
That's like trying to push our door closer to the hinge, then at the doorknob, it'll be harder to
exactly, it's a
push.
lot harder, a lot harder. Physics is like the everyday things, you know.
Just
So
like how maths is everyday thing.
a couple of people wanted to know what we're doing for the rest of the night until 4.
After we're done with nuclear physics, we're going to do 2026 January, 2025 June. After we're done with those, I'll take any requests. Anything you want me to do. Is there any topic in particular that you guys have trouble with?
Sir, moments.
Okay, no problem.
Honestly, have trouble, but I want to know if I amplitude and waves.
Waves, okay, no problem.
So another thing, when I was telling them about the paper ones, a couple of people wanted to know what day exactly is starting the paper ones and what time, roughly.
My schedule is very unpredictable, but I'm trying to have the paper ones consistently at 4 p.m. till whenever, every night. I need
Right,
to
guys,
figure out,
I heard the man. Subscribe now, turn on those notifications.
yeah.
Ding ding.
All right,
And I think it's Sapphire, as her name. She said in the chat for the Zoom that electromagnetism. She want if you could go back through that.
Maybe a bit tough to go back through. We do that real in detail, but we'll see. The night is still young.
And to be fair, we pushing the work quick, so we shall see.
By my standards, yeah, we're moving fast. Because that's typically move a lot slower to explain everything extremely in depth. But like the physics syllabus is a lot. But we still have time. Try to help out as much as I could. All right, so it's time to start back. Are you ready?
Yes.
Yes, sir.
Let's
sir.
I'm gonna start you live on TikTok. TikTok finally unbanned me, so now I could go live on TikTok from a laptop.
Finally, sir.
Yeah, boy. I don't know what TikTok problem is, you know.
So, yeah, I'm careful what you're saying. Remember, you just get easily offended.
Oh, yes, sir. And two, you can't say YouTube on TikTok.
I tell you, they're really in the feelings, alright?
You literally can't say
Yes.
YouTube.
They will get offended.
That's ridiculous. All right, let me continue. Give me 1 second. All right. What percentage did it reach? 94? Okay, we'll work with that. One moment. All right, so let me give all you a quick. Let me just test the waters. Alpha particles are what's in nature? Alpha particles are what's in nature? What are they? Are they here more no?
So
Yes,
repeat that
sir.
again.
Yes, sir.
Yes, sir.
I have something to say about it if it's correct.
Okay,
Say
things are.
repeat.
All right. An alpha particle is a helium nucleus. 42. All right. A beta particle is what?
A fast moving electron.
Right, is an electron. And a gamma radiation. Wait, is it again? Some weird symbol. Yeah. What's gamma? Is it a particle? That's the question. Is it a particle? Let me
No,
distinguish that
sir.
first.
So it's a ray.
Is it a
No,
wave?
sir. It's an
No.
It's a ray.
electromagnetic wave.
Yeah, it's a EM wave. It's a EM wave.
Yeah,
Right.
am wave.
So the alpha particle is what charged? Positively charged or negatively charged?
Positively.
Positively charged. The beta is a literal electron. So what that will be?
Negative.
Negative.
Charge.
And since gamma is literally radiation, something from the EM
Zero.
spectrum, it is not a particle, right? So it can't be charged. It's zero. Which one is the lightest here? Which one is the lightest?
So you're supposed to be sharing the screen?
Oh, you're not seeing the screen?
No, we only
I thought you
seeing
were just
here.
giving
So we
us
see the
trivia, you know.
gates.
I didn't know you were sharing your screen.
So we see the gates, gate symbols.
Oh my.
Yeah, that's all.
No wonder they were so confused because I was writing on the screen.
Is it better?
Come on.
I see the screen.
Wait, they will see the screen in 5, 4, 3, 2. Okay, nice.
Only we on
I
italic.
real seriously giving us trivia, not knowing this man sharing his screen.
Yeah.
I don't know why that was like it was saying you are sharing screen on I don't know. Right, but anyways, helium is alpha particle, positively charged. Beta is an electron. Electrons are negatively charged. Gamma is radiation, right from the EM spectrum, not charged. Which one is which one is heavier? Alpha particles or beta particles?
Alpha.
Alpha.
Alpha, alpha particles are a lot heavier, actually. You guys will see it just now. But that was just a quick run through. Cool. So yeah, I don't know here. So gamma. It's not a particle, has no charge. Alpha. It exists as a helium nucleus, 42He. Beta. It's a fast moving electron, 0 -1. Did you guys know that?
Yeah.
Yes,
Well,
sir.
kinda doing chem too now, so
Okay, nice. As a result, which one would have the strongest ionizing effect? The
Alpha.
strongest ionizing effect. Alpha.
Alpha.
Which one would have the second strongest ionizing effect?
beta.
Would have the weakest
Beta.
ionizing effect?
Gamma.
Gamma, because it's literally uncharged, right? It's literally uncharged.
Carries back.
All right, nice. So let me erase this quickly. All right, so let's fill out this table quickly, right? So Nikolai, radioactive emissions there. Let me just leave the Zoom. Mazen. I leave the Zoom there. I hate hearing myself. I echo thing. I deal with that. People on TikTok, are they hearing me? People on TikTok, are you all hearing me? TikTok people, are they hearing me?
Let me check it out.
Wonder why they're not hearing me, boy. Somebody could go on TikTok and let me know if you're hearing me.
I'm going to know, sir.
Yeah, so we have radioactive emissions here. And the first one says nature, electromagnetic radiation. What's that? Come on, guys, what's that?
Gamma.
It's gamma. And gamma is stopped by what? What is gamma stopped by?
Thick lead.
Lead.
Yeah, a thick layer of lead.
So I'm hearing myself, but I'm not hearing you.
That's weird. Give me a second. After tonight, boy, I'm gonna sleep. How will you feel to
Right,
prepare
sir, I go for my physics pass. My physics test.
You'll get through it.
After my physics exam, I can sleep in peace.
Hey, after my physics exam, I'm not sleeping because I have paper wants to do. I see them that are nuts. That too not acceptable.
Yeah, that's not
And we
acceptable.
had English on 26.
Econ paper, one had to carry my whole econ mark.
Yeah, I
Yeah,
know
but
that, but
really,
I'm not really going and sleep after the physics. Oh my goodness. I wait until all these exams done so I could finally sleep on my bed without having to get up to study for anything.
Mastercon. Audio bit rates. I TikTok gave us so much trouble with
TikTok being TikTok.
settings. Yo, sound check 1-1. Sound check 1-1. Okay, never mind. I just had to go live from a phone again. TikTok.
Oh, it was on your laptop.
Yeah. That's how back to live. You guys will let me know when you're seeing the screen. I think you're seeing it. Seeing it now?
Yes, sir.
Yeah, so finish that up for my guys.
Okay,
Finish up.
the
Before
second one is alpha.
Right, so it will be stopped by thick lead. All right. Helium nucleus. What is a helium nucleus in nature?
Alpha.
Alpha.
And what is its range and aim?
A few centimeters.
Yep, a few centimeters. An electron. What exists as an electron?
Beta.
Beta.
Right. And beta is stopped by what?
aluminum.
Right. A very thin sheet of aluminum.
Yeah, aluminum.
Not thick at all.
So I just say a paper boy gives lead and that's how I just remember it.
A paper.
A paper boy gives lead. So alpha, paper, beta, and I just had to remember that's the aluminum sheet, and then gives is lead.
Yeah, that's also a good way of remembering it. A
Ooh.
paper boy gives lead.
So that sounds like a murder scene. Gives lead.
Nikolai, not boy. Gives lead.
Nikolai, oh my gosh.
Nikolai, what wrong with you, boy? Nikolai deadly.
So when you say give lead, what else you think, sir?
Okay, why
I'm
you
not
took it?
thinking that.
You
I'm not
tryna,
thinking
you
that.
tryna, you
I'm not
tryna,
thinking.
Nikolai, you tryna get so banned.
Nikolai, you good, bro?
When I think of lead, I think of a
I feel like
pencil.
physics.
Tiredness affecting him, guys.
Excuse me, sir,
Right.
can you walk up to the table so I can take a picture, please?
Sure. Take a picture there.
Thank you.
Wait, I have a question. How do you guys draw a gamma? Is it like, okay, is it like this? Or is it like this?
I feel it's like that.
Second
That
one.
one, sir, that one.
The first, I just do the
The
first
first
one.
one I do.
Let's do the first one. Let's do the first
I
At
one.
this
just put the
point,
Y because I don't think there's deduct marks for it just putting Y.
alright, so could anybody, Harry, can people here tell me something fast with the isotope?
Nah,
Yeah,
so
Yeah,
look,
isotope is
look
an
what the
atom of the
chemistry.
same
Atoms are
element.
atoms of the
Equal
same
At the
element.
same number of neutrons.
Hey,
Whoa.
calm down.
I volunteer.
Yeah. Shania, let them know what it is.
Right. Isotopes, atoms of the same element with the same atomic number but different mass number.
First stop.
Atoms of the same element that have the same number of protons. That's
Yeah, the same number of protons. same number of neutrons, different electrons.
No.
No, it's the other way around.
If it had a different amount of electrons, it would not be the same element.
Different neutrons.
Same
Right?
protons, different neutrons.
Same
Yeah.
protons,
Electrons,
different
yeah.
neutrons. All right,
And so
all right, all
atoms of the same element that have the same number of protons, but different number of neutrons.
So my bad. I was just trying to help out.
That's okay.
That's
Have a
okay.
question.
You're still trying to help.
Still try.
Thank you.
So the main thing you should understand is that they have the same number of protons, but they have different number of neutrons. That's the main thing you gotta know.
Because you gotta remember the mass number is both. So if that was the same, then it wouldn't really work out.
Exactly.
Right. Okay.
So the mass
So,
number is protons plus neutrons, and this 46 represents what?
And atomic number?
Yeah, atomic number.
Atomic number.
Well, we just typically say atomic mass.
Atomic mass.
Yeah. Can people enter? They just say that?
Yes,
They just say the atomic number, or some people they say just the proton number.
Atomic number and atomic mass.
Yeah.
Atomic mass, right? So here what? The atomic mass is just the number of what?
Number of protons.
Number of
Yeah, protons.
Right. So let me just give you all I'll run through. So the number on top is the what number?
The mass number.
Mass number.
What is
Mass
the number?
number.
It's like the sum of what two things?
The sum of the
Protons
protons
and
and
neutrons.
neutrons.
Sum of protons and neutrons.
Right? And the bottom tells us the what?
Number of
Protons.
Number of protons. That's the atomic mass.
And it tells us the number of protons. Right?
Protons.
Protons.
And so if I wanted to find the number of neutrons, what would I do?
Mass number minus the number of protons.
Right, exactly. So in this question, if I wanted to find the number of neutrons, I would say what?
106 minus 46.
46.
46.
What is 106 minus 46?
60.
60. Good. So an isotope has the same number of
Same number of protons.
different number of
Neutrons.
right. Cool.
So I have a question, right? So
Yeah.
you see how this short definition was with 3 marks. So you might have a other part to the isotope definition where let's talk about I can't remember if it's carbon 12 or something.
What is stability?
Yeah, something like that. I just know it have
Derivation.
an extended part. Like,
With ratio to the proton or neutron?
yeah, wait, I can't. It's
Because I
some
think that's what you're
112
talking about, you know.
something. So when I find this, I will let you know. But
Okay. Well, like, as far as my knowledge, I feel like this is fine. Yeah.
Yes,
Alright,
take it.
alright,
Yeah.
so cool.
I feel like this is fine. You don't have to put an extra part. They don't expect that. They don't expect
Once
that.
you include all the key points, I do is that I look out for is getting marks.
Yeah. Right, so this one, they say in the structure of the atom of an element Y, show the number of neutrons N, protons P, and electrons E is represented in figure 11. State the mass number and atomic number of this atom. So what is the mass number?
11.
11.
Right.
11.
Because that is the sum of protons and neutrons.
Mm-hmm.
When you add it, mass number. What's 11? What's the atomic number?
5.
5.
Because this is just the number of what?
Protons.
Protons.
Okay, everybody okay with this?
Yes, sir.
Yeah.
Yes, sir.
Yes, sir.
Very easy. Right. Write the symbol for another possible isotope of element Y. So again, if it's an isotope, which number is going to remain the same?
Protons.
Protons.
Proton.
Atomic number.
Yeah, the protons.
Atomic number is going to remain the same, but the number on top is going to change. So
Yes, sir.
give me, and we calling this element Y. So an isotope for this, I would have to write back the same atomic number. So I have to write back what?
5.
Right, so I have to write back 5. And what you guys want to write on top?
12.
11.
11.
Nah, you can't say 11.
It's 12.
Well,
13. What's
Like
that, man?
12 or
12.
13 or something.
Probably say 13 or something. If you go and write 11, isn't that the exact same element?
No, sir, I thought you was writing it back and then we was gonna
Yeah.
change it. That's why I said 11.
Oh, nah. Since it's the same element, it'll be Y as well, right? But this element over here is 11.5. Now the isotope for that would have the same number of protons but different number of neutrons. So the mass number would change. You guys okay with that?
Yes, sir.
Yes,
Like
Yes, sir.
you just had to change this. Okay. Somebody get a read.
A polonium 210 nucleus decays by alpha particle emission to a lead Pb nucleus. Complete the equation for the decay of polonium 210.
All right. So Nikolai, it is decaying by what?
By alpha particle emission.
Right. Do you remember what alpha look alpha? Okay, remind me. Alpha is a what in nature? Nikolai, some fast. Alpha is what in
Helium.
helium. And helium has a mass number of what?
4.
And an atomic number of what?
2.
Right. So when we talk about alpha, we're really talking about helium, right? A helium nucleus.
Yes, sir.
Okay. And so it's really simple. All you have to do is just make sure the numbers add up. When you add them, they're supposed to add up like a regular equation. And this would give you a lead nucleus. Pb is lead. So we'll say Pb. And again, Nikolai, the numbers here must add up to 210. So what would that be?
It'll just be minus
406.
206.
And
And Nikolai, these
82.
numbers here, yeah, must add up to 84, so 82. I think that's hard or easy.
Easy, sir. Wait,
No,
is
we don't
this
finish
the
yet,
plus? Oh,
right? See you gonna say again, Nikolai.
no, I was going to say we not finished yet.
You sure?
Yeah,
I
we're
feel like
supposed to plus energy.
no, that's fine.
Oh,
That's
okay.
fine.
Well then,
No, I think you're mixing it up with fission and fusion.
wait.
I think you're mixing it up. So like all that's happening here, you just have a decay. So it's yeah, but it okay. So the nucleus decays by alpha particle, and that's just 42He, right? And you're gonna have lead. So it decays into a helium nucleus, and the remainder is just in lead. That's it. Easy 3 marks.
Helium.
Honestly, I feel like CSEC should just be giving away marks, boy. Does everybody understand that an alpha particle is a helium nucleus in nature?
Yes, sir.
Okay, so when I say 42He, it means that it is a alpha particle. This is the alpha particle.
Sir, so how do you know what to add? Other than you subtract it, but how do you know what will it be?
So in the question, they said polonium decayed to what? It decayed to what?
Alpha particle emission.
It decays by alpha particle emission. I was talking to the girl.
Oh, my bad. Sorry.
Alpha particle emission to a what? To a what? To a what?
I don't see what you're talking about.
Okay, read the question. I'll wait to read the question from her.
Oh, I
Outcome.
see it. I see it. I see it.
So they're telling us it decays by alpha particle emission to a lead nucleus. So then this has to be PB, and the numbers must add up to give you 210. So this is going to be 206, and the numbers here must add up to give you 84. So this is going to be 82. Let me know if you're okay with that.
Yes, sir.
Okay. Right, so polonium-210 has a half-life of 138 days. Okay, you guys need to know what half-life is. Half-life is just the time it takes for some quantity to be halved. Halved, that's all. So Nikolai, I know you had problem with half-life, so give the question a read for me.
What's this, sir?
I know you had problems with half-life, so give the question a read.
Polonium-210 has a half-life of 138 days. At a certain time, a sample contains 6.4 times 10 to the power 6 polonium nuclei. Calculate the number of polonium nuclei remaining after 552 days.
So Nikolai, every 138 days, what is happening?
A sample contains all 6.4 times 10 to the power 6 polonium nuclei.
No, okay. Somebody, please don't draw on the screen.
Don't draw on the
Yes, sir.
screen.
Sorry, that
Remember
was
that
my
answer
bad.
feel
That was
blood
my bad.
pressure.
Sorry.
Wait, yeah, otherwise I'd have to disable that feature. Well, I mean, nobody does really use that, so I could just disable it one time. How do you disable that? Anyways, I'm gonna stop that. I do know how to disable that. Yeah, so Nikolai, what is half-life? Half-life is just the time it takes for a quantity to be halved. So Nikolai, if I'm telling you it has a half-life of 138 days, that means if 138 days go by, the amount, okay, the amount of polonium nuclei is going to be what?
Half its value?
Exactly. So here what? We're going to start off at day 0. At day 0, how much polonium nuclei does the sample contain?
6.4 times 10 to the power 6.
Everybody understands that, right? Initially, it would have this amount of polonium nuclei. Very simple.
Yes, sir.
So Nikolai, after 138 days, how much polonium nuclei is going to be?
3.2 times 10 to the power 6. Or
Yep, that's correct. Okay, if we go another 138 days, that's going to be day what?
wait, we are at the 138 plus the 138?
Correct. What's 138 plus 138?
276.
And at day 276, what's going to happen to that 3.2 by 10 to the power 6?
It'll be divided into half again.
And what would that be?
Will it be 1.6 times 10 to the power 6?
Okay, let's keep going. There's an easier way to do this question, but it's like okay, I wouldn't say easiest, you gotta remember a formula, but this is the most intuitive way to answer it.
Yes, sir, that was the formula I showed you on the message. And I want to know if that would have worked with every other thing.
I would tell you.
Yes,
So
sir.
Nikolai, if you add 138 days to 270, again.
414.
Okay, and it's gonna be half again. It's gonna now be what?
0.8 times 10 to the power 6.
Right? And then if we add 138 days again, that's gonna take us to what?
252.
252. Nah, take your time.
I mean 552. My bad.
So that'll
So
be
when
0.
you're done, somebody in the Zoom chat and a few people on YouTube say they don't understand. So if you could run it back after.
Okay, that's not a problem. Yeah, so Nikolai, after that, right? After the whole process, we reach day 552. How much polonium nuclei do we remain with?
0.4 times 10 to the power 6.
That's the answer.
Wait, that is it?
Yeah, that's it. This is
Oh.
one of the easiest topics in physics. All right, I want somebody that is confused to come on board and let's tackle it together.
Marley.
Ophelia. That's you?
Kind of. So they say I want easiest way to do it.
This is the most straightforward, easiest way to do it. The other way would involve a formula.
Oh, okay, sir.
All right, so let me explain something, right? Ophelia. They're telling us it has a half-life of 138 days. What is half-life, Ollie? Half-life is just the time it would take for quantity to be halved. So, Ophelia, were you one of the people that was confused?
Not really, sir. I was just watching.
Okay, I want somebody that is confused to unmute their mic so we can run through together. Because this is not hard. It's really.
So
Guys?
it's me, but we kind of afraid to talk.
That's okay. That's okay. Come. Let me tackle it together. So, Tamale, that's you?
Yes, sir.
Right. So, do you know what half-life is?
Not exactly.
Okay, no problem. So, the half-life is the time it would take. So, the time taken for a quantity to be halved. So, Tamale, according to the question, what is the half-life of polonium?
138 days.
So every 138 days that passes by, the amount of polonium nuclei is going to be what?
Is it 6.4 times 10 to the 6 4?
Okay, so half-life tells us how long it would take for like the quantity to be reduced by half the amount. So Tamale, let me use
Yes,
simpler.
sir.
I'm going to give you a simple example with eggs. All right, let me just use eggs, right? Let me just say the half-life of eggs is 2 days, right? And let me
Yes,
just say
sir.
we start off with 16 eggs, right? We start off with 16 eggs. What does this mean? So Tamale, it means that every 2 days, the amount of eggs are halved.
Will decrease by a half.
Exactly. So at day 0, how much eggs we have? At day 0, how much eggs we have?
Hold on, sir.
So that's the initial, that's like the starting point. Nobody had touched the eggs as yet. Right? How much eggs we have?
6, it still have to be 16.
It still be 16. Now here what? If 2 days pass by, we're gonna be on day 2. And so if 2 days pass by, they're saying the half-life of the egg is 2 days. So at 16 is gonna be what?
8 egg.
Exactly, it's gonna turn to 8. Okay. And let's just say I want you to go until we reach 1 egg. You with me?
Yes, sir.
Right, let me keep going. So if another 2 days pass, we're gonna be on day what now?
Day 4.
We'll be on day 4. Correct. We'll be on day 4. And that 8 eggs will now be what? That now turn to what?
4 eggs.
People that was previously confused, are they understand the concept? Or no?
Yes, sir. So
Sir,
far.
yes, sir. We are understanding the concept.
And Timali, if 2 days pass again, we're gonna be on day what now?
Day 6.
And the eggs will turn to what? What the number of eggs turn to?
2.
Did the eggs reach 1 as yet?
No, sir.
Nah. So we're gonna keep going. 2 days are gonna pass by again, and that's gonna carry us to day what?
8
What happened to the 2x?
becomes 1x, sir.
Exactly. So could you tell me the period of time for which it take for the eggs to be reduced to 1 egg?
8 days?
Correct, 8 days. That's it? Tamale. How do I use it?
Yes. Repeat
Double
what you
using-
said, sir.
It was how
It
I
was,
was.
it's not bad, sir.
It's not bad, it's not bad. I was using the chat for Tamale. Big up Tamale one time. Right? So here
Alright,
what?
thank you, sir.
Tamale. We're gonna apply that same concept to this question now. The exact same concept. You hear me? The exact same concept. Right?
Alright, sir.
So Tamale, what is the
Yes.
half-life for polonium-210?
138 days.
Good. And they are saying at a certain time, the sample contains how much nuclei?
6.4 times 10 to the 6th power.
Cool. Now this particle, I have a question, guys. I think polonium is stable. I think polonium is stable.
No.
No.
No, sir.
If the
No.
number of nuclei is decreasing, isn't it clearly unstable and is trying to reach stability by
Yes, sir.
undergoing decay?
Yes, sir.
So, Tamale, we starting off with how much polonium nuclei?
How much? 210?
Nah.
Ah.
So they're telling us the sample initially contains how much polonium nuclei?
Oh, 6.4 times 10 to the 6.
So that's what we're starting off, right? You hear me? That we're starting off with.
Okay, sir.
And that would be day what? If we're starting off with that, that'll be day what?
Today 138?
Nah, that'll be day 0. That'll be day
Yeah.
0.
Oh.
Because Tamale, we starting at that. So Tamale,
Yes, sir.
at a certain time, the sample would contain that. This is the original amount it contains. That's the original
Yes.
amount of nuclei. It's clearly an unstable element. So as time passes by, it's going to undergo decay to reach stability. So what's saying Tamale? Over time, you're going to see the number of nuclei decreasing. Now, they told us had a half-life of 138 days. So Tamale, every 138 days, the amount of nuclei going to be what?
Cut by half?
Exactly. The same thing like with the eggs. The same thing. I ain't trying to trick you. I'm trying to trick you. Same thing. So here what?
Ah.
Check it. If 138 days go by, that would be day what?
No 138 days, sir, or day 1?
Day,
Oh,
day 100.
138 days.
Right. And since the half-life was 138 days, this amount is now going to be what?
I believe 3.2 times 10 to the 6.
Yes. If we go another half-life, remind me, Tamale, what's the half-life of this element?
138 days.
So if we go another 138 days, the number of nuclei is going to be what now?
1.6 times 10 to the 6 power.
W is in the chat for Tamale. Tamale, sound like you get a day. Right? And this
Yes.
would be day what now? This will be day what now?
Day 276.
Yeah. So here what, right? Here what, Tamale? They want us to calculate the number of polonium nuclei remaining after how much days?
Oh, 552 days.
So we're gonna keep going until we reach what day?
552 days, sir.
Right. Big up. So I'm gonna go another how much days?
Next 138 days, sir.
Right, because that's the half-life of the polonium nuclei. So that would carry us to day what?
I believe a 4.
That'll be 414.
414.
Right? And what's gonna happen when it's 1.6 by 10 to the power 6? What's gonna happen with that?
You got dropped by half, sir.
So what would it become?
8.0 times 10 to the fifth power.
So half of 1.6 is 0.8, eh? 0.8. Did we reach 552 as yet?
No, sir.
Nah, so we had to go another what?
Another 138 days, sir.
Aha. What's 414 plus 138?
552.
Yeah?
552 days, sir. Sorry.
That's okay. That's okay, Tamale. I'm here to help all you. Right? I understand that not everybody at the same level and will learn at the same rate, and that's fine. I'm here to help all you in a non-judgmental environment. Because it's fine. I know it's like to be scared to ask a question and thing in a class. Because I've scared people think I don't know anything. I know it's fine. You're okay. It's a safe space. Math Vibes is a safe space.
Okay, sir.
So Tamale, we're gonna have only 0.8 now.
It will cut by half again, sir. So I got 0.4 times 10 to the 6.
And we would have reached what date?
The final day, which is 552 days, sir.
Bam. So after 552 days, we have how much polonium nuclei?
0.4 times 10 to the 6.
Bam. You genuinely understand it now?
Yes, sir.
Nice, man.
100%. But sir, quick question. The part where I got 0.8, for my calculator, it showed me 8,000. I was converting it to the base, sir. But what if I put 8.0 to the power of 5?
That's
Would I be
okay.
wrong?
That's okay, right? It's just that to go in line with the pattern, I just kept dividing the number by 2. So here what? Now I'm actually gonna plug this into my calculator to see what I get. You should get 400,000. I'll make it verify again, 400,000.
Yes, sir.
According to the power. Let me know if you guys getting 400,000.
Yes, sir.
Just move the decimal place 6 times to your right.
Are they getting this correct now, guys? Talk to
Yes,
me.
sir. One question, sir. Should I resend the message that I've sent you about the questionnaire I want to talk about?
That's fine. I think I know the formula you're talking about.
Oh,
And
okay.
I'll show you how to derive it as well.
Yes, sir.
I need somebody to stay on YouTube and let me know what people are saying, right? Because when I'm teaching
Yes, sir.
okay,
Well, I'll
people
check the YouTube then.
people understanding or not? People that was in the Zoom, people that in the Zoom right now, or they understand what happening or they confused.
Understand, sir.
Understand,
sir.
Right, so guys, do we understand a half-life? It's just the time it will take for something to be what?
Half
Cutting
its
out?
quantity or value.
To be cut in,
Half.
to be half. Yes.
Thank you, sir. I appreciate it.
Not a problem. Which country representing?
Jamaica.
Big up Jamaica one time. Right?
All right.
Wake up a sister island.
You know, I when I first met Renisha, I thought Renisha was from Jamaica. Low key.
I honestly thought she was.
Yeah, boy.
I
Something
would
about
like to
Renisha.
say, since you're over there, tell my cousin I love her and God bless her.
Oh, he's supposed to know your cousin.
Who
No,
Who
she's a
knows?
dentist over there.
Oh, okay.
She is from Trinidad. She went over there to do her dentistry in Uwimuna. And
Clock it, big up your sister, boy. Hey.
Renisha, some of the people want to know where you're from.
Trinidad, born and raised.
Right.
Yeah, boy.
So
We have
Renisha, she sound like you know these girls with on TikTok, man. Everett, something like that, man. They're from Trinidad.
sound like
She
what?
sound like you know these girls, these three girls
I get
with
that a
on TikTok
lot.
from Trinidad, man. Everett, I don't want any
when I was
Everett,
in primary
Joel,
school,
or something.
When you was in
when I
primary
was
school, talk to me.
when I was
I
in
find-
primary school,
yeah.
if you didn't know me when I was in primary school, people used to tell me I used to look and speak like an American child.
Yeah, low key, like you have a slight accent, low key. Yeah.
Oh God, hey,
Okay,
well, I am
sir,
not
and
from
But like,
America.
the Trinity come out now. The Trinity like here. Oh God, away. You know what I mean? Like,
don't even get started on when you shall laugh. Okay,
Oh
so
shit.
2 questions, right?
yeah.
One, some of the people want to know if we gonna get a next break, when that break will be, and somebody want to know if you think motors gonna come.
I don't know. I don't know if motor's gonna come, but like if it does come, I think you guys will be fine. I showed you guys. Okay, let me just quick recap. If you're dealing with DC motors, are you going to use Fleming's left hand rule or Fleming's right hand rule?
Left hand rule.
Left hand.
Left hand rule, right? Left hand
And
rule.
rule. Ding a ling ding.
And okay, you'll have 2 magnets here, 2 permanent magnets, and then you'll have a coil here, and you hook it up to a DC power source. Remind me fast. How does the magnetic field lines looks like? It goes
North
from
to
where to where?
south. North to south.
North to south.
South.
North or south.
Depending on the terminals here, the current would flow in accordance to that.
Yes, sir, and it will rotate
From
anti-clockwise.
positive to right.
Right. I call this A, I call this B, I call this C, I call this D. Here what? If A to be going up automatically, did you see how to be going what?
Down.
Down.
And you use Fleming's left hand rule to verify this.
Yes, sir.
Yeah. If it come, well, you should be able to handle that, man. I know you'll have that.
Sir, I have a question.
Wait, if it does come, I'll take a screenshot of this for quick reference. Take a screenshot.
I have a question, sir. I have a question.
Yeah. Talk to me.
All right. All right. Even though you're predicting these topics that will come in paper 2, but what about paper 1? Will they come in paper 1 as well?
I'll
Or they will
paper
test you on
one is
everything?
paper one is just repeats, guys. Hey, paper one is just repeats.
Renisha, I love you, girl, right now, but not the paper one. Let me pass paper 2 first.
Okay,
Yeah.
okay.
Yes, sir. Not too sure what year the past paper question was on, but I'll look at to see which part it came from to just let you know.
Okay, no problem. So here what, guys? Let me show
So,
you all.
people want to know if they could join the Zoom. They're asking.
When I teach it, it's just me. So I don't really have a way of letting people in, right? And we don't know for sure if people just go and come and troll and type 6 up on and thing. You don't know, right? So unfortunately not. Due to the constraints, unfortunately not. Not at this point in time. Yeah.
Okay, so the past paper question was on 2021, and it was like the last question.
Okay, no problem. Well, I'll look at that just now. Let me show you guys the alternative route you could take. Guys, let me ask you that question. So, from day 0 to 138, it's going to be halved. Then it's going to be halved again. Then it's going to be halved again. Then it's going to be halved again. If it's being halved 4 times, then I could just raise this half to what power?
4.
Exactly. And
Four.
here what? If I wanted to figure out the number of half-lives, all I would have to do is take the 552 and divide it by what?
By the half to the power
1
4.
to the 8.
Yeah.
1 to the 8. 1 to the 8.
By 1 to the 8.
So this is another way you could answer the question, right? So you could find the number of half-lives. Nikolai, think about it. Think about it logically, Nikolai. How much days are given us?
552 days.
And we want to figure out how much half-lives it have in that. How much is one half-life?
138 days.
Does this make sense then?
Yes, sir.
Right. And the formula typically looks like it's just going to be over T.
Oh, okay.
As well. So it's going to be the time they give you divided by 1 half-life. Do you guys understand this logically?
Yes,
Or
sir.
Yes, sir.
because here what? 552 days. Now you know that one half-life is 138 days, so it makes sense to divide to find how much half-life you're dealing with. So when you divide this, what do you get?
You get
Sir,
4.
I got 4.
Now let me think about this logically. If it's 4 half-lives, then our sample is gonna be halved how much times?
4 times.
So it's
4
gonna be
times?
halved 4 times. So we can raise half to what power?
4.
4.
4.
And this would tell us how much times the original sample was reduced by. So what would you get for this? 1 over what? 2 to the power 4 is
32.
1 over 16.
right.
Is
1 over
So 1
16.
over 16.
So guys, after 4 half-lives, your sample is going to be reduced to 1/16 of its original amount. So we can multiply what by 1 over 16?
The 6.4 times 10 to the power 6.
yeah.
And that would give you the same answer of 400,000. And the formula looks like this. It's just going to be n is equal to NO, where NO is the initial number, right? All over, well, no, a half to the power n. That's all.
Yeah,
could,
yes, sir.
so I
That's
could
the equation I asked you about.
So
Yeah.
one, the people on YouTube, a few of them want to know if after this, on the same topic, if you could do the graph for this. But also, the people on the YouTube chat that are speaking about cheating, don't do that. You can get banned and they will fail you for all your exams.
Yeah, don't do that.
As a
And
teacher tell
5 years
me,
until you can do
ungraded
that.
is still a mark, eh?
No,
If you
no, no.
want,
No,
Wait, Renisha,
They
Renisha.
fail you and ban you from writing CXE.
For 5 years.
wow.
All right, let me continue now. So, I just never tell students to just memorize. I want them to actually understand what you're doing. So here what? Are they understand how we could find number of half-lives? Logically.
Yes, sir.
Sir.
Yes.
Yes,
It
sir.
is it is just the
Even
time
better now.
Yes,
it's
sir.
just the time they give me divided by 1 half-life. And that would tell me what n is. So n would be equal to 4. The number of half-lives is 4. Now logically, if 4 half-lives happened, then you'd have multiplied by a half how much times?
4 times.
4.
4 times. Do you guys understand why we're saying a half to the power 4?
Yes, sir.
Yes, sir.
And this would tell us the fraction that the original was reduced by. So the original was reduced to 1/16 of the original. So we can multiply the original, which is given by NO, by the 1 over 16, and that would give us 400,000. And you could see that summarized in the formula. NO is the initial amount of the nuclei, right? A half, because we're dealing with half-life, and n is just the number of half-lives. Isn't that what we did over here?
Yes, sir. But I have something to say.
What's
I
that?
would have I would have never think of it that way. I would have done it. I would have done it. The first, the first, the first way. The
Well,
first.
the first way is a long way, but this is just a generalization of what we noticed in the first scenario. Yeah. Feeling tired, boy. Wow.
The first one is better.
Tell me about this.
Yeah, Nicola.
Way better, sir.
Sorry, even though the first one ain't no formula, right? You'd still get full mark, right?
Yeah, that's 100% correct. That's 100% correct.
Either way, whichever way you do it, it's still the same answer. But I
Exactly.
find the first one is the better way to do it. So you go keep the track of what you use already, so you wouldn't use it over again.
Yep. But like, I wouldn't say it's hard, right? I wouldn't say it's hard. If it was up to me, I'd do this if I was in a pinch. They're real efficient. You find the number of half-lives, and the number of half-lives will tell you how much times you multiply by a half. And that will tell you what the original amount was reduced by. So you multiply that by the original, and you get an answer one time. So Nikolai, does this help you in any way?
Yes, I feel like we should do the question that I talked about, but one question, sir. The N at the original of the formula, what that stands for?
Wait, sir. You have a bunch of N's. You gotta be specific. Capital
The
N,
capital
comma
N.
N.
The
So you
capital.
could pause, I could say something.
Wait, give me a second. Let me just explain this fast. All right, so the capital N would tell us, it would just tell us what it was reduced to. So Nikolai, after the 552 days, after N half-lives, N would tell us what's remaining. So it would tell us the remaining nuclei.
Okay.
Okay, watch. Here, what, right, Nikolai? If you find N, you understand a little N tells you the number of half-lives.
Yes, sir.
Okay. And it tells you how much times you're going to multiply by half. And NO, it is the initial amount of the nuclei. So Nikolai, what was the initial amount of nuclei we had?
6.4 times 10 to the power 6.
Right, 6.4 by 10 to the power 6. And I'm going to multiply that by a half to the power 4. So Nikolai, when I work this out, what do you think I'll get?
You'll get the 400,000.
Good. So the capital N just tells me the nuclei after N half-lives.
Oh, I understand now. Thank you.
No problem. Yes,
All
and
right,
use
so right, so before you move on, so the people on the YouTube chat that are complaining that we have been on Half-Life, if you all want somebody that will not explain things properly and move fast, please, there are other people to look at. If you are here, we are going to run through the work, but in grave detail.
Yeah. People don't understand that, like it have a bunch of YouTubers that good, but I trying to do something different. It's like I know a large number of people in the Caribbean, they struggle real bad. And like most people don't get the help they need. I try and tell people that struggle, like the average person, not just like the exemplary students, but like the people that are struggling and was going to fail anyways. But now they have a chance of passing because they understand some things. Right?
Yes,
My
sir.
channel is about caring, like in-depth explanations, and not just connecting with like the people that are gonna get grade ones, but like people that was gonna fail, but now they have a chance of passing. You understand?
Yes, sir, but the people that are actually interested, they want to know after this to do the Half-Life graph.
I will do that. I will do that. Don't worry. I will do that. Yeah. So what do you guys prefer, the intuitive method or like the formulas?
I feel like I would like to try the two. See, not the first one is just a clarification, and the second one. But if it
Same here.
depends on time, I'll go with the second one.
The same here.
Nikolai, that 2021 you was talking about, is it June or January?
I think it's January.
January. I have June.
It was like the last question, question 6. Oh no, it's June. Yeah, this is it.
Alright, so Nikolai, this is real simple. So half-life is just the time it takes for an original quantity to be what?
Half its value.
To be halved. Right. So part 2. At a certain time, a sample contains 8.0 by 10 to the power 8 radium nuclei. Calculate the number of alpha particles emitted by the radium nuclei in the next 4,800 days. And at the start of the question, they told us that radium has a what?
A half-life of 1,600 years.
So guys, every 1,600 years, the amount of nuclei is going to be what?
Half its value.
Exactly. It's going to be halved. So here what? At day 0, Nikolai, at day 0, how much nuclei are you going to have?
We will
Eight
have
times
8 plus 0,
8
10,
times
10
to the 10 to the
Right?
no times 10 to the 8.
And if one half-life passes by, which is 1,600, we're going to end up at day 1,600. And that amount is going to be what, Nikolai?
half its value, so it will be 4 times 10 to the power 8.
Cool. And if 1,600 days goes by again, it's going to take us to what day?
3,200 days.
And that's going to half it again. So it's into what?
2 times 10 to the power 8.
Good. And we didn't reach 4,800 yet, so we had to go another 1,600. And that would take us to
The 4,800 days.
Right, and we'd have to half 2 by 10 to the power 8. What would we get?
That will be 1 times 10 to the power of 8.
Cool. That's the answer. Let me show you how you would do it. You understand, right?
Yes, sir.
Guys, are you getting this for marks? Please tell me yes.
So we getting this 4 marks.
Yes, sir.
Yes, sir.
Tamale, you getting it?
So where they get the 1,600 from?
Oh, read that for me.
Okay, so yes, sir, definitely.
Nice, man. So let me show you guys the formula approach. In the formula approach, you'd have to find the number of half-lives first. So we'd have to find the number of half-lives. And so Nikolai, how much years are they talking about? How much years?
4,800 years.
Okay. And what is one half-life?
1,600 years.
So how much half-lives are we gonna have?
That will be 3 into 1.
Right, and if we want to find the amount of nuclei that is remaining, it's going to be the original amount multiplied by half to the power n, and n is just the number of half-lives. But I hope you understand the formula now, because Nikolai, if 3 half-lives passes by, you'll effectively multiply by a half how much times?
3 times.
And then that would tell you how much you're reducing the original amount by. So if we use that formula, it's just going to be the original. The original is 8 by 10 to the power 8.
Yes, sir.
And I'm going to multiply a half. Well, I'm going to raise a half to the power 3. And when you work that out, you should get 1 by 10 to the power 8.
Yes, sir.
Right. Are they okay with this?
Yes, sir.
Yes, sir.
Nice. So Nikolai, read part 3 for me.
How much more time will elapse before the number of radium nuclei remaining falls to 0.5 times 10 to the power of 8?
Alright, easy, Nikolai. So how much time again will pass for it to turn to 0.5 by 10 to the power 8?
That will be the next 1,600 years.
Yep. Nikolai, boy, you're getting these marks, right?
Yes, sir. I just need to clarify, seeing that there was a long way and then there was a short way. I think I use of the same formula for that to get the 1,600 years.
You don't have to do all that. You don't have to do all that. But if you wanted, you could use the formula, you know. But like it makes no sense. It's 1 mark. It's 1 mark, guys. Although, if they're asking us how much more time will pass for it to reach 0.5 by 10 to the power 8, could everybody see that if you go another 1,600, what I would turn to?
0.5 times 10 to the power 8.
Yeah. So there's no need to use the formula. But if you did want to use the formula, then when you work it out, it'll tell you the total amount of years. So then you'll have to subtract that from the 4,800 to get the 1,600. That don't make any sense.
Yes, sir.
Right.
So,
Yeah, Nikolai, that's it. That's it there. Not real easy.
Yes, sir. Renisha has her hand up, sir.
All right, Renisha, talk to me.
So I will try one. If Nikolai could do it, so can I. I'll try one.
That is the spirit. All right, so let me tackle this question. So guys, do you all know about background radiation? Yeah or no, background radiation?
No.
Yes, sir. Isn't that you minus in the
Somebody.
radiation at the beginning from the amount of time, well, the distance you walk at?
Not quite. Background radiation is just the typical radiation levels that's always is there. That is always there. Yeah. Somebody was saying something?
So somebody wanted to know the question with the radioactive decay where I think the answer is 1/16. If you could go through that.
I wouldn't be able to go through it because like I want to be in depth, but we also have to leverage because they could go back in the video. You know what I mean? They could go back in the video.
Press the red thing with the running on to go back and it will go back.
Yeah, yeah, because I did explain it several times in the past, so it don't make sense to be back again. Yeah.
Figure 5 shows a radioactive source which was placed in front of a radioactive detector. The average background count rate is 5 counts per second. With the source in place, the rate rises to 69 counts per second. After an hour, the count rate drops to 21 counts per second. Determine the corrected count rates for the activities of the source.
Right. Renisha.
Yes, sir.
So the background radiation, it is there all the time. 100% of the time, it's just there.
Okay.
If it's just there, would I want it in my measurements?
No. Yes.
Okay, let me give you an example, right? Let me just say, yeah, I'm gonna think of an example. Huh.
So
Okay.
it's always
Wait,
there would
wait. Thought about an example. Let me just explain this fast. So, Renisha,
Yes, sir.
take this for instance. Imagine you had a beaker here, right?
Yes, Abika. Yes.
And in the beaker, it had 10 centimeters cube of water, right?
Okay.
If you fill it to 50 centimeters cube,
Mhm.
are you going to say the increase in volume is 50 centimeters cube?
No.
What would the increase in volume be?
10?
40.
40.
Oh, 40.
Right, so Renisha, we had 10 already. 10 was there already. 10 was there already.
Oh,
And I pour
sorry.
more water, and now it's at 50. So, what would
Oh,
it be now?
you would need 40. 40.
40. So
Because 40 plus 1 is 50. So we'll need 40.
So it's the exact same concept here, guys. With background radiation, you want to take it away from your reading for it to be accurate. I'll understand this example, right? Like, okay, if you had a beaker and you had 10 centimeters cube of water in it already, then when you pour water and you reach 50, what's the real reading? What amount of water did you put in?
40.
40. Good. So here I was saying, Renisha, the
Yes, sir.
average background count is 5 counts per second. So all my readings are to do what with it?
5 counts per
Well,
second.
no, my bad.
Tell me, Renisha, how to do what with it?
Okay. So, you have to, I'm thinking that you have to count per second.
Nah.
So,
It's okay. Wait. Yeah.
what do you be got to do with this?
Say that again?
What do you be
That was
got to
just
do
an
with this?
example.
No, the beaker was just an example, right? Like it's the exact same concept. It's literally the exact same concept. Leon, if you
Yeah.
have a beaker and there was 10 centimeters cube of water in it, right? 10
Yeah.
centimeters cube of water. And you fill it up to 50. Are you going to say fill it with 50 centimeters cube of water?
Nah, 40.
Exactly. So here I was saying, the background radiation is always there. It's always there. So anytime you take a reading, if you want to find how much it actually increased by, we would have to do.
Subtract 5?
Exactly. Renisha, I hope you understand that. Because Renisha,
Yes, sir.
the five is always there, it's always there. So if
Yeah,
you
the
conduct
5
a
always
test
there.
now, if you actually conduct a test now and you want to figure out how much it rise by, you need to take away the 5 from it because the 5 was always there. Are you understand that or no?
Yeah.
Yes, sir.
Yes, so this
Take
was
away the
just
5.
similarity. It's a concept.
Alright.
Take the 5 from the 69.
Right? So that's going to be 69 minus 5 and now turn to what?
Okay, 69 minus 5 will turn to
Right.
64
Right, so that'll be 64 counts per second.
counts per second.
And then we had another reading, which was after an hour. And that was
After
21. So we gotta
that
do
was
what with
20.
20.
Subtract.
Alright, subtract 5 from that, and what do you get?
When you subtract 5 from 21, you will get 16. 16 counts per second.
So do you guys understand why the corrected readings are just the measured readings minus the background? Because the background was always there.
Yeah.
All right.
Yes, sir. Sir, question.
Talk to me.
So, we will always use the background count rate and subtract it from the count rate that we get after.
Correct. Correct.
All right, sir. Thank you.
No problem. So they want us to calculate the half-life of the source. So Renisha, we
Yes,
started off with how much counts per second?
64.
Start off with 64, right?
Yes.
We start off with 64. And after an hour,
We had 16.
we had 16. Okay. So we know that from 64 to 16, this took an hour, right?
Yes, sir.
Now, half-life is the time it takes for something to be what? To be what?
Half?
Half.
To be halved. So let me ask that question, Renisha. What's half of 64?
Yes. Half of 64. Half of 64 is
You can use a calculator. That's fine. Use a calculator. Renisha.
half of 64 is it 32?
Yes, 32. And half of 32 is? Half of 32 will be 16. Half of 32 will be 16. So
16.
in a calculator, all you will have to do is just divide it by 2. So 64 divided by 2, that will give you 32. And 32 divided by 2 will give you 16.
Right.
So let me ask you guys a question.
I was using my brain mentally. I wasn't using the calculator. That's why I was taking so long. Sorry.
Nah, you use a calculator. Use a calculator because time is limited. So how much
Okay.
half-lives? How much half-lives we have between 64 and 16?
2.
Yeah.
2.
So Renisha, if 2 time and a halves, the time and a half is half-life, right? If 2 time and a half took an hour, what would 1 half-life? Okay, what would that be?
1
From Renisha.
half-life.
Yeah.
A half divided by 16.
Nah. If 2 half-lives is an hour, then 1 half-life would be half of an hour. Half of an hour would
Half
be how
of an
much minutes?
hour.
30 minutes?
30
30.
minutes.
Oh, half of 60. Half of 60 is 30 minutes.
Nisha, so every number you're just gonna divide it by 2, basically.
Yeah, because they were half.
Okay.
Because half-life means that it is decreasing by a half. It's being divided by 2. Yeah.
Okay.
And here I say, to go from 64 all the way to 16, it took two half-lives, and it also took 1 hour. So 2 half-lives is an hour. So if 2 half-lives is an hour,
Half of
then
an hour is 30 minutes.
right. But do we leave our answer in minutes, or do we write it in the SI units for time?
We write it in the SI units for time.
So I'd have to multiply 30 by what?
60.
60.
And I would get what?
1,800
Yeah,
1,800
1,800 seconds.
seconds.
Right. Let
that's
me know if you guys genuinely understood that.
Yes,
I
sir.
understand.
Yes,
Yes, sir.
Nice. Now, if you
Although
did
I was
not,
moving slow, I still understand.
the point is to try and you learn, as he means it.
Yeah.
Right? All you
Okay.
must learn from Anisha, like you can't give up. You can't give up. You just gotta keep going. You gotta try. You gotta try.
All you don't make me cry now.
Right? But you would not have gotten through if you didn't correct your count rates first. And remind me, guys, if you want to correct your count rates, you have to take away the background from the
time that you have.
From the time that you have.
from the measured results.
The measure results.
Measure results.
So I measured 69 counts per second, and then I measured 21 counts per second. So to correct that, I would have had to take away the 5 from that to get the actual reading, which is
So this
64
would
and
be
60.
the actual background, sir.
Say that again?
Would this be the actual background?
Oh, no, this is not the background, Nikolai. This is not the background. Nikolai, here what I was saying, right? In the atmosphere, there's background radiation. There's already radiation. So, Nikolai, when I place the radioactive source in place, so okay, Nikolai, if I have no radioactive source, where's my radiation? If I have no radioactive source, where's the radiation?
69.
Nah. The 69 is when I add the radioactive source. Where's the radioactive source if
the
I just
64.
how much?
64.
No. Alright, so like I said, guys, we have background radiation all around us.
Yeah.
So the radiation that is always there is the background radiation. So Nikolai, what is the background radiation?
The 5.
Yes, and the 5 is always there. So here I say, Nikolai, if the 5 was always there, and now I put down my radioactive source, you see that it now rises to what?
The 69.
But Nikolai, if the 5 was always there, how much does it really increase by?
Minusing the 5 from the 69.
So it really increased by what?
By 64.
Yeah. And after an hour, the radioactive source would probably decay, and you see that it dropped to what?
21.
But Nikolai, this 21 includes the background count in it. So if you actually wanted to find the actual reading, you'd have to do what?
Minus the 5 from the 21.
Correct. You understand it?
Yes, sir.
And so Nikolai, they wanted us to find half-life. So we know we went from 64 to what? 64 counts per second to what?
16.
How long did that take, Nikolai?
There was our interval in between.
An hour. Now we know that half-life is the time it takes for something to be what?
Halved.
Right. So if one half-life passes by, 64 gone into what?
32.
And 32 gone into what?
16.
So Nikolai, from 64 to 16, we had how much half-lives?
We had a total of 2.
2 half-lives, and that took place over a duration of what?
1 hour.
So if 2 half-lives is an hour, then 1 half-life is just 30 minutes, which is 1800 seconds.
Yes, sir.
You genuinely understand?
Yes, sir.
Okay. The rest of you guys, are they okay?
Yes, sir.
Yes, sir.
Yes, sir.
So is this
Yes,
question
sir.
under the same topic?
Yeah. All of this is nuclear physics. Right. So in this question, they're saying a block of lead is then placed between the source and the detector. The results of the count rates are recorded in table 2. So what I'll do, right? So Renisha, between the source and the detector. So like you have the source, right? So you have the source here, and you have the
Right.
detector. By the way, the detector is called a Geiger-Müller tube. That is the detector.
Geiger-Müller tube. Okay.
They place a lead block in the middle. Guys, if they place a lead block in the middle, you think the radioactive source will be able to pass through that?
No, sir.
No,
So
sir.
So we think it's
is
going to
lead
take
we talking about?
lead we talking about, right? So the Geiger-Müller tube will measure what? That's how bad it is, right? It will measure what still? It will still measure what?
The distance of where the radioactive source reach.
It does not measure distance. This measures the counts per second. It measures the radiation.
Oh, the counts per second.
Yeah, that
Is it
measures
lead
radiation.
tech?
So I'll measure 5.
It will measure 5. It will measure 5.
5.
Because no, if you have nothing there, the Geiger-Müller tube will still record 5 because that's the radiation that's always present. So let's see what happens here.
Okay.
So the count rate with the source in place is 69 counts per second. The count rate with the source and block in place is 32. And they want me to figure out the count rate with the source and the block removed. So I remove everything. What am I gonna measure?
5.
5.
5.
Because that 5 is always there. Is the background radiation. Now, all you notice something, right? Even when I put the lead block in place, it still had some radiation.
Yes, sir.
That had to be some powerful radiation. What kind of radiation will pass through lead?
Gamma.
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 The source is known to emit one type of radiation only. Deduce what type of radiation it is. This had to be gamma.
Gamma is the answer.
Yep, gamma is the answer. Do you all understand that?
Yes, sir. Yes, sir.
Yes, sir.
All right, so number 1. I think any and any. If I like cars, not really. I like car audio though. Right, so here what, guys? Anybody can tell me why I think it's gamma?
The power of the radiation of where it passed through the
Oh,
block.
the radiation as the pass through the block. Well, when it is.
Sorry, pass through lead.
Yeah, that's the main thing. It passed through lead.
Oh.
It passed through lead. That's like a dead giveaway. Now what? Okay, you see. Okay, if I say it passed through lead, that is a qualitative analysis. That's not quantifiable. So this is the qualitative part. Could we state a quantitative part? Okay, quantitative just means like a number, like numerical
So
proof.
would you look on from the table?
Yes, I would look at the table, and I would say that when the block was added,
It was 32.
It was 22.
it dropped from 69 to 32. Now, if it was anything other than gamma, it would have dropped to what?
Half of it?
Half of that.
Nah.
So I dropped to 0. 5.
5?
The background.
5.
Yeah, I would understand that, right? Because like saying it partially lead is one thing, but you gotta say why you say that. Why? How you know that? Well, even after I put the lead block in place, and that's still getting some counts per second.
Yeah, you're still getting counts per second. So,
Yeah,
which
okay.
means you have to tell them the reason why you choose.
Yeah, so I had to tell them when the block was added, it dropped from 69 to 32 instead of 5. Guys, if it was something like alpha or beta, until I completely block that radiation.
Yes, sir.
Yes, alpha especially.
Yeah,
Alpha
and you'd just be
especially.
measuring the background radiation. The background radiation is just 5. So I probably understand.
Yes, sir.
Right. Describe an experiment to compare the ranges of beta and gamma emissions in aluminum. So I have something nice for you here. So you will set up the detector. By the way, guys, what do we use to measure radiation?
To measure
A
radiation.
radiometer.
Nah. A Geiger Mueller
A-
tube.
A gaga. Tongue twister.
A
A
Geiger
gaga
Mueller.
Mueller tube. Right.
Or it's also called a Geiger counter. Right?
Geiger counter.
Mueller.
Ooh, I like that word
Geiger.
better.
So here, this is the setup. You want to set up the detector. So you're going to clamp the GM tube securely on a stand. You don't have to be so specific, right? It's just like a model answer. You're going to clamp the GM tube securely on a stand. You want to place the beta source at a fixed distance from the GM tube. You want to make sure everything is aligned so you can slide aluminum sheets between source and detector without changing the distance. So you're going to measure background radiation. Remember, we need to figure out what the background radiation is. Right? You want to measure the background radiation with no source present. So guys, if I measure the background radiation, any measured values are fine. What do I do?
Subtract them from 5.
Subtract the background radiation?
Not from 5, but subtract from the background radiation. Well, you have to subtract the background radiation from the measured value. Then you want to measure the beta counts without aluminum. So you want to place the beta source at a fixed distance. You want to record the count for the same fixed time. And of course, you have to subtract the background to get the net beta count rate. Then you want to insert aluminum sheets. You're going to place the thinnest aluminum sheet first. You're going to record it. And you're going to increase thickness. You're going to record. And you're going to keep doing this until you can't record anything anymore. And you're going to repeat this process for alpha and gamma. So let me show you guys what I'm talking about. This is what I'm talking about. So can you guys see we have a lead box over here? Oh, they say beta and gamma, no problem. So guys, can you guys see that I have a lead box over here?
Yes, sir.
Right. You're gonna place your beta or your gamma source over here, and they are going to emit what? Well, they are going to experience radioactive decay, and they are going to emit radioactive. They're gonna okay, when they decay, they're gonna emit alpha rays or gamma rays. I was saying beta rays or gamma rays, right? No. You want to measure it without the aluminum sheet, and then you're gonna put aluminum sheets until they get a reading on what in the GM tube.
The background information.
Exactly, and you wanna put sheets until they get in only the background radiation, and this would kind of give you a gauge as to how powerful the beta or the gamma source is. Question: which one do you think is gonna need more aluminum sheets to stop it, beta or gamma?
Gamma.
Gamma.
Right. Do you guys understand the experiment?
Yes, sir.
Yes, sir.
Right. So what do we use to measure radiation, guys?
Gaga too.
Geiger counter.
You can say
Geiger
Geiger counter.
counter.
You could say Geiger counter or Geiger-Müller tube.
So, sir,
Geiger
that-
Müller
who-
tube.
whoever said
Geiger
that-
Müller tube.
Sir, excuse sir, whoever said that sound like they was gargling water or something before they said the words.
Bubbles crack me up with your laugh. Oh Lord.
Oh my gosh.
Like a like say gargling water.
Get away.
Because I hear the word, I was like, what?
Yeah,
Geiger
so tonight.
Müller tube. That is scientific.
Nikolai, I
word.
think you need to get your ears checked, you know.
No, I hear that too. I hear that too. I hear Geiger. So, we nearly finished with nuclear physics, and don't worry, I did not forget. We'll do our radioactive. If I have any specific questions or any years, you can tell me fast. Tell me so I can do it.
Oh, sir, I will try this one. I will try this one. I will try this one.
So I don't have a year, but I have 2 topics.
Okay.
They say moments of a force, like with the fulcrum, the diagrams, those questions, and well, they say the radioactive decay graphs, like what to do and what not to do.
Okay. Well, in the meantime, while I'm doing this question, I want some. Wait, they're real questions, boy. I like the questions, but like, whoa. Here what I'm saying, right? While I do any question, I want somebody to be looking for a radioactive decay question, so I could explain our question, right? Do that for me.
Well, somebody better do that. I'm monitoring the YouTube chat.
Yeah,
Right?
somebody do that because I'm going to answer the question.
Okay.
Well, Renisha, you answered the previous question, so I'm gonna give somebody else to answer this question now.
Can I try?
Okay, no problem.
Yeah, you could try. Who's this?
Amelia.
All right. Hey, Amelia, you good?
Yeah.
All right, Amelia, don't worry. This question real easy. This mass defect question, real simple. I promise. I promise. All right. So, give the question I read.
A liquid fluoride thorium reactor is said to be the new green nuclear reactor. Rewrite the nuclear sequence to show how thorium-232 becomes uranium-233, a nuclear fuel, by calculating the numerical values of X, Y, U, V, and Z.
Okay. Now, before we even start here, right? Right, Amelia.
Yeah,
In maths, whatever you have on your left-hand side is equal to.
the right-hand side.
So it's the same concept over here. 1 plus 2 to the 2 is?
1 plus 2 to the 2?
Yeah.
1 plus 2. Oh.
It's not trick. I'm not trying to trick. I'm not trying to trick all you. I'm not. It's real straightforward.
5. 1 plus 2 to 5?
No. Watch. 1 plus 232.
Oh, 232.
Nah, 233.
233.
And we had to do the same thing. By the way, guys, what we call the number here? The what?
The mass number?
Mass number.
And it tells us the protons plus the what?
The neutron.
Neutrons.
And what does this tell us?
Proton.
Atomic mass.
Atomic mass, yeah.
Protons.
Good. Yeah, so like I was saying, the mass, well, the atomic masses need to be the same. So, well, when you add it up now, the 0 plus 9 is supposed to give you this. So, Amelia, what do you suppose this is?
Y 90.
90. Hey, physics so much easier than any other thing, you know. Like it's one of the most straightforward things, I promise. So, Amelia, let me do it here now. So, Amelia, we just find x to be what?
233.
And we just find y to be what?
90.
And what? Like I just tell you, I want the left hand side have to be equal to the right hand side. So you have 0 here, and you have u. We had to add to 0 to get back 233.
233.
That's it. 233. Over here you're seeing minus 1. Okay. What would I have to add to minus 1 to get back 90? What minus 1 will give me back 90?
91.
Yep. Nikolai, I see you have your hand raised. Talk to me.
Just to let you know, I found 2 good questions that we could try, both in
That's
January.
good. Hey, W in chat for Nikolai. Right? And let's continue, Amelia. So Amelia, we just find u to be what?
233.
And we find v to be?
91.
Cool. Remember what I tell you? It must add up. So, what do you think I'll put for z?
92.
I mean, if you guys understand this. 5 marks. Really easy. 5
Yes,
marks.
sir. Yes, sir. Yes, sir. Good
Guys.
job, girly. Good job. You deserve it. Clock it.
Hey, CSEC, girl, your marks like the same can, boy.
Yes, everybody understand this, right?
Yes, sir.
Yes, sir. Of course.
So I'm kind of lost.
Okay, no problem. I will explain it back to you. You know,
So
I'll be real tell you, right? Like out of all the lives I ever did, I'm breaking the most sweats in this live, boy. Like, ooh. I had to arch my back and like show like oh, this life was intense. Boy.
I
So
think
that's
it's because we actually put in more work, and not only that, because somebody, how I'm monitoring the YouTube chat now, people actually asking the questions.
Yeah.
okay, that's good, that's good. So here what? I can't really explain this.
Is this radioactive decay?
Yeah, it is.
Because I see a question with fission in it.
Don't worry, that question real simple. Okay, I know I'm saying this simple, but I mean it. Like, okay, you see how Fleming's right hand rule and like the right hand grip rule and thing was a little complicated? This is not complicated. This is easy.
Okay.
So, Tamale, let me run it through real fast, right, Tamale? Real fast. Tamale, it's real
So
simple.
I
What?
understand the top part, sir, but they probably keep on adding 1 to the 90, sir. I thought you after you add the 1 to the 90, I would have when you go back down to the V, you'd have just add the 91 to it same way.
No, let me show you something, right? Let me show you something. So, Tamale, I
Yes, sir.
must. Okay, so I have 1 here and I have 232. 1 and 232. What was I supposed to get here?
Yes. 233.
Bam. I have 0 here and I have 90. Where's 0 plus 90?
90.
Okay. So X here would be what?
233.
Y would be what?
90, sir.
Cool. And let me ask that question. If over here is 233, then what would I have to add to 0 to get back 233?
233.
Yep, 233. Okay, what would I add? Okay, I have negative 1 here, right? Now tell me,
Yes, sir.
Tamale, I had to get back 90. You seeing that?
Yes, sir.
What minus 1 would give me back 90?
91.
Yeah. And so over here, I'm going to put 233.
Oh, because you pull that from up there, come back down here, the 91. You want to get back the 91 when you add it to the -1. So you add one more to it, give you 92.
Yep. Got it?
I see, sir.
You get
All right,
85
thanks, sir.
marks. Let's come up with like 85 marks, eh?
So, question, sir. Would they have these right here?
So
Or the black numbers and letters?
You mean like X, Y, U, V, and Z?
Yes, sir.
What about them?
So would they still have, without the blue writing, like your writing, of course, would they have them on the paper already?
I would say X is equal to 233. I would say Y is equal to 90. I would say U is equal to 233. I would say V is equal to 91. I would say Z is equal to 92. I'd write this. Let me know if you understand. I would actually write this in like a space. You understand? Can I hear them?
Partial.
All right. Do you understand how we got the answers?
Yes, sir.
Right. So they want me to state the numeric values of X, Y, U, V, and Z. So what was X?
233.
233.
Right, so I put X is equal to 33. What is Y?
90.
So I put Y is equal to 90. What is U?
233.
Yes, I'll just state any values. That's all.
V is 91 and C is 92.
Okay, I want to understand which part confuses me.
No, I was just asking if alright. Like the 1 and these right here, would they already be on the paper by themselves?
Like the 1, 0, and plus 2 to the 290, like this.
Yeah.
So like what you're saying is like in the exam, you worried that it would just be this?
No, without none of these.
Okay. What you're trying to say is you worry that you might have to remember it yourself, like
Yeah,
alpha
right.
is
All the numerals, all the
beta is
numbers.
0 minus 1.
Yes, sir.
Ah, I understand. I understand. Well, you should still remember it. Alpha is 4, 2, beta is 0 minus 1, and gamma is 0, 0. Those are the ones you have to remember. If it's like a neutron, they would give you that, but a neutron is just 1, 0. Yeah.
Yes, sir. Other than this question, it had a question, I think it was from last year, I'm not sure, that they brought a question, but they never put, they just put one.
Yeah, what? When we reach our paper, we will do it. We will do our
Okay.
paper. Yeah, because that's on the agenda. That is on
I
the
have
agenda.
a specific question that you would like to do if you want.
Which question?
2017 question 3, part C.
Okay, Nikolai. So, okay, you telling me May, June, or January?
June. I say June.
June 2017, question 3.
Part C.
Right, Nikolai, you were telling me what?
There was 2 papers in January 2020 and 2021 with question number 6.
All right, cool.
The quick question, right? The live that we did yesterday, mind just telling the people that are listening what we did yesterday and the live that the day before? Like, what was the topics?
All right, so in the live we did yesterday, we looked at all the gas laws. We looked at all our waves and optics. So if you need help with lenses, you need help with Snell's law, refraction, diffraction, everything is there. if you need help understanding longitudinal waves, transverse waves, displacement distance graph, displacement time graph, so like amplitude, all that is there. And in live before that, we looked at thermal physics. So like all our thermal physics is there from like latent heat fusion, latent heat vaporization, specific heat capacity, the units, passive properties like if something is dull, if it's black, if it's white, if it's shiny. Yeah, we looked at all of that.
Next question. Somebody want to know if you could do the parallelogram law.
Okay, no problem. I guess there's a lot of things, but wow. Ooh,
Sorry, to do the half-life graph.
we gotta like limit the questions, low key. We gotta limit the questions.
Yes, I feel tired reading the questions.
Here what? Let me just finish this question. Let me finish the questions. Let me finish this question. I want somebody to come on with the question more. I need the energy.
Yes, sir, there you go. There.
Right. So Nikolai, you're telling us the equation representing the fission. Okay, when you hear fission, right? That means that a large nuclei is what?
Divided into two identical daughter cells or something like that. Something to that aspect, or no?
Yeah, something to that aspect. Like you just split one big nuclei into two smaller nuclei, in simplest terms.
Okay.
That's fission. And that process releases energy.
Yes, sir.
So that's what I was saying. I think it was confusing where the decay with this.
Yes, I assume so, yeah.
Right. So Nikolai. And so like you see everything here? This will be the mass before. This will be the mass before the reaction. Before the fission, this will be the mass what?
After the fission.
Right, this is the mass after the fission. Now here what? Before and after, there's a mass defect, meaning that some mass is actually lost, and that mass is released in the form of energy. Do you know that?
Yes, sir.
Okay, good. And if you want to find the mass defect, it is the mass before minus the mass after. So calculate the energy released in the fission of 23392U. Cool, not a problem. What's a problem? So let me tackle this question fast. So the main formula I had to use here, I'm going to call one friend Einstein. What's the main formula to use here?
E is equals to mc squared.
Now, we get the mass by finding the mass defect. And well, we should know that C is the speed of what?
Light.
C is the speed of light. Correct. So to find M, it's going to be mass before minus what?
The mass after.
Right, so you gotta be real careful here, Nikolai. Like, very, very careful. So when you're adding the mass before, you're looking at the table they give you here. Typically, they will give you tables, right? So Nikolai, we have 23392U. What is the atomic mass for that?
233.03964.
Right. So here what? Let me find the mass before. The mass before is going to be 233.03964.
Yeah, 3964.
And don't forget, that's U, eh?
Yes, sir.
Nikolai, you think we'd actually be able to represent atomic mass? Like write it on paper?
Nah.
Nah, so what we just do is we just write it in terms of U, which is like an incredibly small prefix.
Yes, sir.
And we need to add the mass of the one neutron.
That is 1.008.
Whoa. Whoa, why we keep seeing this number, buddy?
So please don't stop that. The
I'm
YouTube
fed up,
chat is gonna stop.
Oh, yeah. So we're not add that again. Again, guys.
Yeah, well, 234. But the rest.
Yeah, let's say the full thing. It is if this is one topic in physics, yeah, let's say the full thing. So that'll be 234.0 what?
There. There's a 0.
4831.
4831, yes, that's correct.
You know, I just literally do the maths, you know. Like sometimes I'll make mistakes on purpose to see if I'll correct. But like I look at these things I could do in my head. But like I want to give a little chance.
That is incredible, but thank you.
Now, like all you have to do the thing on yourself.
Yes, sir.
Like find the mass after now. So the mass after is all of this. You gotta add all of this. So Nikolai, we're looking at SB. We're looking at NB. NB is over here. So we'll say 132. So you'll say 132.91525 U plus what?
The 97.9091033 plus 3 times the neutron.
Now here what? If all I realize it's 3 times the neutron, so you gotta multiply the neutron by what?
By 3.
Yeah, by 3. So you'll say plus 3 by the 1.00867. So you can plug all of that into your calculator and let me know what you get.
I got 233 point.
Wait. 8519.
Nah, you miss out a number there, sir.
85159.
That is correct.
So 233.85159 U.
Yes, sir.
Cool.
So what is the
This is going to be the mass after.
Yes, sir.
So if we want to find the mass defect M, it's just going to be the mass before, which was the 234.04831, minus what?
The mass after.
The mass after.
Which is this. It is looking real complicated, but it's actually very, very simple. Eh? Like, guys, all you had to do, right? All you had to do, go in the table, add, watch, U is this, and you add it to this. Simple. That is the mass before. And after the reaction, you're just looking for everything in the table, and then just add them. That is all. And then you want to find the mass defect M, so you subtract the mass after from the mass before. And what are we getting?
I got 0.1967. Yes.
2.
Yes, sir. But that is not our answer.
That's not our answer, right? Remember, we want to find the energy. So the energy is going to be this mass. But again,
So you must well, are we? Wait, are you going to say what I'm going to say or not yet?
you will see, you will see.
He's gonna say it.
So wait. Alia, do you think we could write the atomic mass on paper?
No.
No. So like a convenient solution we come up with is just we could use this prefix over here, U. But U is actually incredibly small. So what is U? They should have tell it somewhere.
I was not going to say we're supposed to multiply now.
Don't worry, Nikolai. It's a good thing you know that though. So we're going to multiply 0.19672 by the, I think it was 1.66
Yeah,
by
10
10 to
to
the
the
power.
power negative 27.
Right, so that's the mass there. And we're going to multiply by the speed of light squared. So 3 by 10 to the power 8 squared. Plug that into the calculator and let me know what all I get.
Oh, I thought you wanted the full answer, or you wanted to break it down for if you want to explain it again.
Nah, put it in the calculator.
Okay.
So long story short, guys, this is not the mass in kg. To convert this to kg, you see this little u over here? What does that u represent? That u is actually 1.66 by 10 to the power minus 27 kg. So if you do any calculation with this mass, you need to multiply this by 1.66 by 10 to the power negative 27.
Yes, sir. My answer, I got 2.9. Well, should I write out the full thing?
The two decimal places.
Well, it'll just be 2.934 times 10 to the power of negative
Two
11.
decimal places. Two decimal places.
Yeah.
There's some 3 decimal places.
Oh, my bad. Sorry about that. Yeah, so it will be 2.9 times 10 to the power negative 11.
Wait, that's 2 decimal places. Now you tell them about 1 decimal place.
Huh? Wouldn't it be just 2.94?
Yeah, it should be 2.94.
Yeah, but I said that before. I mean, I said when I asked the question if you were supposed to put it, well, simplify it or put in the full value, but then I said 2.94.
I
But
can
then you
ask
told me
you 2.934.
Yeah. No.
I swear I hear that. And that'll be by 10 to what power?
Negative 11. I was going to say out the full value, which was 2.93899968.
Nah, just 2 decimal places. That is a day.
Excuse you.
Talk to me.
Somebody wanna know if we could just go over it one more time because I didn't understand.
If you don't understand, unmute and let me run it together. That's the only way you go understand. Because looking at
That's
me,
not it's not somebody from the Zoom, it's the YouTube.
oh, anybody on the Zoom confused?
Yes, sir.
All right.
Yes, sir.
All right. So Tamale, let me run it now. So Tamale, we have an element here.
Yes, sir.
And it undergoes fission. You know what fission is?
Yes, sir.
All right. So imagine you have a big nuclei. After a fission, this thing splits into what?
Energy?
Into 2 smaller nuclei. 2 smaller, lighter nuclei. No, what saying is, so Tamale, this over here will be the mass before or the mass after?
Before.
And this could be the mass if I add up this. That'll be the mass.
After.
Now here what I'm saying. During this process, we actually lose some mass, you know. We actually lose some mass. So here what I'm saying, right? Here what I'm saying. Stay with me. This over here, this is the equation representing the fission. So, Tamale, let me know if you're seeing. All right, so you see we're starting off with, I think that's uranium, right?
Yes, sir.
And after we end up with what two, I don't know what 2 elements is that, but Sb and Nb. So you see how it's split into two lighter nuclei?
Yes, sir.
Watch. We start off with uranium, and this end up splitting into Sb and Nb. And it release some neutrons and release some energy. So here we're saying, right, Tamale, in nuclear fission, you have a big nuclei, you split it into 2 lighter nuclei. In this process, some mass is lost, and that mass is converted to what?
Energy?
Yes, energy. So Tamale, can you identify that this is the mass before?
Yes, sir.
And this will be the what?
The mass after.
Good. Now they want us to calculate the energy released. Now in these types of questions, you're going to use E is equal to mc squared, where m is the mass defect. It's just the mass before minus the mass after. Because like I said, we will lose some mass.
Yes,
And
sir.
that mass that we lose will be converted to energy. So how do I find the mass before? So Tamale, we starting off with 233 U92, right? What is
Yes,
the
sir.
atomic mass for that?
233.03964.
Good. So we have the atomic mass for that. It's over here.
Oh.
And we need to add that to what? That's not the only thing over here. What else we have over here?
The N10, which is the bottom one, it's 1.00867.
So all you had to do, it's not hard, guys. I'm telling you, this is not hard. All you had to do is just add this and add this. Are you understand that? Now.
Yes, sir.
And of course, you're not going to write kg here. The atomic mass here is given in terms of U. So,
U.
yeah. So, Tamali. So, hear what, Tamali? You think you're going to write? You think you're going to write the mass of an atom on paper? You think?
No, sir.
No, you can't do that. That's madman thing. However, you could write it as some crazy small prefix. Hey, big up Richard, boy. Yeah. So, Timali, I hope you understand that. Atom is
Yes,
way too
sir.
small. You can't write down paper. So, what we just do is, we just add a crazy small prefix, which is U. And U is actually 1.66 by 10 to what power?
Negative 27.
kg, right? Good.
Yes, sir.
So, does everybody in the Zoom understand how you'll find mass before?
Yes, sir.
Good. And that mass will be in terms of what? In terms of what? kg or U?
U.
U. Good. So the mass before is just the 233.03964 plus the 1.000867 U. And that gave us 234.048331 U. Are they with more or no?
Yes, sir.
Now it is the exact same process for the mass after. So Tamali, over here is seeing SP, over seeing NB, and it's seeing 3 by what? It's seeing 3 by what?
The 1N0. So you got times it by 3.
Yeah, that's all. So Tamali, to get the mass after, you're gonna, you notice I have SP in it. So you gotta say this, plus how much times this?
3.
Exactly. I'll understand what I'm doing, right? I'll just add this to this, and I'll multiply this by 3, because they're saying 3 times that. I'll add those 3 things together, and I'll get the mass after. Are you all with me?
Yes, sir.
Yes, sir.
And so, can you guys see that there's a very slight difference in mass?
Yes, sir.
By one.
Yeah,
No.
there's like a very slight difference that we're seeing. So that is actually going to be what we call the mass defect, which is the mass before minus the mass after. So I'm just going to subtract those two, and I'll get M. Let me know if you're with me.
Yes, sir. And then you got times M by U, which is the 1.66 times 10 to the negative 27.
Big
And
up
this.
yourself. Big up yourself, Somali boy. Big up yourself. Big up yourself.
All right. Yes, sir.
Right.
Thanks much.
Yeah, you have it. So, like, guys, are you seeing kg anywhere? Are you seeing kg anywhere?
No, sir.
Are you seeing kg anywhere?
No, sir.
No, see, you have to remember this, right? You have to remember that U is actually 1.66 by 10 to the power minus 27 kg. So before you could work with M, you first had to multiply M by the 1.66 by the 10 to the power minus 27. So I hope you understand that.
Yes, sir.
And that would be the mass. And then we need to multiply that by the speed of light squared. And they give you the speed of light. So you just have to square that. Right. Now I'm going to explain that back. I feel like I really explain that.
Thanks much, sir.
You understand it?
Yes, sir. Definitely. Thanks much.
No problem. This is guaranteed marks, guys. If this comes, this is guaranteed marks. So we have to get the marks.
Yes, sir.
Let me know if you're okay with this.
Yes, sir.
Yes, sir.
So, like, all I had to... Okay, somebody run me through the process. You had to find the mass what? You had to find the mass?
Before, then you find the mass after, then you subtract.
And then you multiply that by what? You had to
The
multiply...
U.
Right.
And then you times it by the C, the given C, that is 3.0. What is it? Yeah, 3.0 times 10 to the negative. No, 10 to the 8.
Yeah, and you square that. And you square that. You square that.
Yes.
Double using the chat, boy. People on YouTube, Hard luck today. If you're still confused, look back at the recording. I mean, look back at the video. You will understand it. You will understand it. I
Forward
promise.
ever, backward never.
Where you
Right. So,
getting 234 from?
well, I get the what?
234.
I get the 234 by adding. Okay, so what? So, Risha, we have U here, and I have 10n, which is 1.00867. So all I did, I just added it. And that's how I get the 234.04831.
Okay. Thanks, sir.
No problem.
Yes, sir.
This is the only other thing I think could come other than the radioactive decay, like with the graph.
Actually,
So
sir,
yeah.
that is the same question I'm talking about in 2021.
Oh well, we're covering it here one time. So we're gonna look at the gold foil experiment. Let me ask you a question. If I have alpha particles here, alpha particles are what in nature? They are what?
Helium.
And they are what charged?
Negatively charged. I mean, positively charged, sorry.
Positive.
Positively charged.
Now, the whole purpose of this experiment is to prove the concept of the nucleus and, well, the electrons. Because, you know, until normally Plum put in model.
Yes, sir.
Yeah, yeah. I think at a point in time, they believe that, like, some weird stuff.
Yeah, and
And
then
this was, so, like, what this shows us is that the atom is mostly made up of what space?
atomic space?
Empty.
Nah, empty space. Empty space.
Oh, empty.
Yeah, let me draw the structure of our atom. Draw the structure of our atom now. See, I have the orbital shell there, and what you have here. Guys, we have here. What do you call this again?
The nucleus.
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 And what does it contain in the nucleus?
Protons and
Proton and neutron.
neutrons.
Right, protons and neutrons. And what kind of element is looking like, guys?
Helium.
Yeah, this is looking like
Helium.
This is looking like helium, which is alpha particle in nature. Whoa.
Yes, sir.
So you go have 4, 2. So 2 will be the number of what?
Protons.
And 4 will be the what?
Atomic number.
4 would be, well, it would have 2 protons and 2 neutrons, right?
So there's only 4 atomic number?
Yeah, yeah. Well, no, the 4 was not the 4 was mass number. The 4 was mass number.
Oh, mass.
Because remember, this is
Just
mass number.
remember, just remember both of them mass, atomic, protons only.
That's what I was gonna say. In order for you to get the mass number, you have to add 2 plus 2. You get 4.
Right, because mass number is protons plus neutrons. So let me ask you that question, right? If the nucleus here and the valence shell over here, what do you have in the middle?
Nothing.
Have anything, right? And this experiment proved that. So let's observe what happened. So you have a thin sheet of gold foil. Why does it need to be thin?
For it to pass through.
For it to pass through. Good. Now you realize that most of the emissions, most of the alpha particles, what?
Went through undeviated.
Pass through it.
And that would tell us that most of the atom is made up of what?
Empty space.
Empty space.
Empty space. Empty space. So most alpha particles travel straight through undeflected. And this tells us it's mostly empty space. Now, in the instances where it was completely deflected, it would encounter what?
The outside, the layers of the detector or something like that.
No. So Nikolai, what happened in here, right? So the alpha particles, it passing through the atoms of the gold foil. And we just say that, the atom comprises of a dense nucleus, and in the nucleus you have protons and neutrons,
Yes,
and on
sir.
the outside you have electrons, right?
Yes, sir.
So most of it will have passed straight through the gold foil because our atom is mostly empty space. And in what condition do you think it would completely be deflected back? Thermal Nikolai. So again, alpha particles are what in nature, Nikolai? Positive or negative?
Positive.
So, Nikolai, where would the alpha particle encounter another positive charge when it hits the what?
The gold foil.
Nah, when it hits the nucleus of the gold atom.
Sorry, my bad.
Because Nikolai, we have a nucleus.
Protons and neutrons.
Protons. So nucleus is what charged? Nucleus is what charged?
Positively charged.
Positive charge.
So if an alpha particle hits here, what will we do? Since it's also
Deflect.
positively charged. So Nikolai, since the alpha particles are positively charged, if it encounters the nucleus, which is also positively charged, what do you think gonna happen?
It will repel because it's like.
It will be completely deflected.
Yes, sir.
Because it's like both of them is the same charge. So that's why I'm saying occasionally an alpha particle travels back from the foil. But why? This is because the nucleus carries most of the atom's mass, and well, you know, in the nucleus you have you have a positive charge, you have protons. Do you understand now, no?
Yes, sir.
Yeah.
And well, some alpha particles are deflected by small angles. And let me explain this. So Nikolai, if an alpha particle hit the nucleus head on, what happened?
Wow.
Remember, the alpha particle is positively charged. So
Yeah.
they hit the nucleus head on, what happened?
It will cause friction.
What happened?
But not only friction, but due to the like charges, it will repel.
It would completely repel. It would completely repel. Now, Nikolai, what happens now if the alpha particle goes close to the nucleus?
Yeah, kind of like it will like graze, but not fully. It will not fully go straight.
To be
It will
pushed
like
away.
go from one direction.
All right. So wait, Nikolai. So the nucleus is what charge? Is what charge?
Positively charged.
And alpha particles are what charge?
Positively charged.
So if it goes close to the nucleus will what?
Well, it will repel because
Yeah.
it's charges. Yeah.
So every once in a while, you will see some alpha particles are deflected by small angles. Why this happening, Nikolai? This happening because the nucleus is positively charged and as in the alpha particle. So if I go close to the nucleus, since the alpha particle is also positively charged, it's going to be slightly deflected. You
Yes,
understand
sir.
anything? Or no?
Yes, sir. I understand, sir.
All right. So you have to remember this.
Yes,
This
sir.
might
Yeah, and the question is definitely about this.
I had to explain some other things for you guys.
One question before we continue. Sorry to interrupt, but do they have questions that you have to label the parts or anything like that?
Label the parts, what you mean?
So we gotta draw this.
Yeah,
Yeah,
like
you might have to draw this. You might have to draw the whole thing.
When did the last time this come?
Scratch.
Nikolai, when was the last time it come? Because the question you can't tell me. I suppose it deals with this.
It was 2021.
Okay.
It
I think
wasn't
it
anything to draw. It was more like describe or anything like that.
Oh, it's not hard to draw. It's not hard to draw. Watch. What hard to draw about this? I don't have to
Don't
draw,
forget the
guys.
binocular. Don't forget the eye.
The eye, yeah, the person that's viewing it.
Yeah, I know.
But
I
like,
know you might take out some marks for that.
I don't think so, you know. If you look up the goal for the experiment on Google, I think you can see eye.
Yeah.
Yeah, I don't see an eye. I don't see an eye. That's not even mean the eye is not so important. Eye is not important. Watch. I'll look up this online. You seen any eye here?
Nah. Alright, well. Sir, that exact picture you show me there is very close to comparison as the 2021 question.
Okay. You better use that. You better use that. So
Probably.
summary, right? Alpha particles are what in nature? What charge?
Positively charged.
Positively charged.
Generally speaking, most times it's going to pass straight through the gold foil undeflected.
Yes,
And
sir.
that is because what? Why? What's the inference there?
That they have empty space.
Right. Atoms are made up of mainly empty space. Every once in a while, you go have a total reflection. It go just bounce back. Hit the wall. So what would I infer there? What would I infer?
Because they experience other atoms that have the same charge, meaning that they reflect.
Nah.
Or repel.
Not atoms. Not atoms.
Particles.
Particles.
Nah. It would hit the what of the atom?
The nucleus.
The nucleus.
Yeah. So Nikolai, for total deflection to happen, I said reflection just for some moment ago, my bad. For total deflection to happen, the alpha particle needs to hit the what of the gold atom?
The nucleus.
The nucleus. Because in the nucleus is what? What's the nucleus?
Positively charged.
And if it make a direct collision, it's gonna just be deflected.
Totally.
So you had it, Nikolai, you had to tell them the alpha particles occasionally will collide with the nucleus of the what atom?
The gold foil atom.
Right. And sometimes, it passes through the gold foil, but it is deflected slightly. Why is that?
Because it didn't collide totally to the nucleus of the gold foil.
It just passed.
It just barely passed it. But it will still be reflected due to the fact that the both of them is positively charged.
I don't say reflected, I say deflected.
Deflected. My bad. Deflected.
Yeah. Cool. Are you feel like are you okay with the gold foil experiment?
Yes, sir.
If this come on, like get the marks,
Yes,
get
sir.
the marks.
Of
Come on,
course.
but you don't get
Of
the marks.
course.
Sir, you gonna see that drawing real neat.
I hope so. I would hope so after all of this.
Of course.
Let me look at 2021 now. Nikolai, you said May, June, or January?
No, January.
Ooh, January.
I'll send you the paper if you don't have it.
Do I have that? You guys send me to know.
Yes, sir. I'll send it one time.
I keep telling them January, but January. Baby. Okay, anybody, Nikolai, send me January.
It's sending, like it taking, for some reason it taking long to load. I can't understand why.
So was the charge on your Apple Pen?
It's charging right now, as a matter of fact, as we speak.
Okay.
It's charged.
So, what time we finishing this again?
4 o'clock in the morning. Yeah.
I'll bet that manageable.
Right.
Yes, it's sending now.
Send, okay.
It's
People,
only one megabyte and it takes so long to load.
no, but that's May, June 2019, though.
Huh?
It's on May, June 2019.
So I'll send it.
All right.
Oh my goodness. All
Nikolai,
that time
like you're,
I'll send
like
you
you're
I'll send
sleeping,
it.
boy.
All that time when it was May, June.
That's crazy.
You get?
Liam, have everything unlocked, boy. Liam is the man, yeah?
Yes, sir.
Look at Chinese girl. Look at Chinese girl all there.
What?
Chinese girl.
So without context, that sounds so bad.
Oh, I need to remember. I need to remember that even though like we're from Trinidad and we just like say things like joke in a joking manner, um, a lot of the foreign audience mightn't understand that. Yeah, boy. And like I need to realize that, I get a little more popular. I need to watch what's saying. People
Well,
might
actually,
say,
sir, you jump, you reach 4.83K now.
ah, so close, guys. After this
That's how
live,
the advertising works.
after this live, make it 5 now, Ollie. Make it 5, make it 5. Stop sticking, guys. After this live, make it 5. All right, let me just send this to myself. PDF file.
Wait, what that Chinese girl question was about?
You will see, you will see, you will see, you will see, you will see.
You shall see.
Like literally, the eyes are, you know. Woo. It's like real small eyes now. So yeah.
So I need after exams when I home, I'm gonna just dig up, remember all the inside jokes for math vibes, and I will design some logos. Cause why not?
Nah, that's all good. That's all good.
So you need to drop some merch.
I would drop some words like Fat Man
I
Bob.
made a logo with Fat Man Bob, right?
I see that. I see that. So
Yes.
we had to make like some inside jokes now. Like make like a shit that say Fat Man Bob. Fat Man Bob walking around the longer part of the vector to lose some weight.
Yeah, yeah, hoodie with Romano catchphrase on it.
Absolute cinema.
Yes.
So,
Yeah,
what about
it's a nice paper, boy. It's a nice
Meanwhile,
paper.
Brian.
Chinese.
Olio, that look like a look at him. Hey, next thing you think I'm racist something. I'm not.
Nah, I am
Next
Chinese. I
thing.
endorse this.
Big up.
All right.
Olio, these are a nice paper, boy. Low-key, they're a nice paper.
So I
Right.
feel like the John papers is be easier because like
Yeah, look
how
at this.
they gotta do the labs.
Wait, these people are looking familiar, boy.
So here what? State the conclusions that were deduced from each of the following observations made from the alpha particle scattering experiment. Yeah, it looks really similar. All right, so most of the alpha particles pass through gold foil on the. What's the answer? What's the answer? What is the answer? I'm waiting, Olio. I'm waiting. What's the answer?
Because they did not hit the because they have empty
There are
space.
more.
Right, because
There's more
Atoms
the
are
empty
mostly
space
contained of
in
empty
the
space.
atom. Empty spaces.
atoms mainly comprise of empty space, so the alpha particles would have passed through. Part 2, a few alpha particles were deflected from their path but continued through the gold foil.
The positive alpha particles hit the positive nucleus of the
No,
gold foil.
did not hit.
Deflect off.
Not deflect. Okay, it's so
They didn't even touch.
it didn't even touch the alpha particles. The alpha particles experienced a repulsion
Yeah.
upon being in close proximity to the nucleus of the gold atom.
Alright.
So because it was in close proximity to the nucleus of the gold atom, it was slightly deflected. Because like charges, what? What do like charges do?
Repel.
Like charges repel. A smaller number of alpha particles rebounded. So what would happen here? Nikolai, tell me fast. If like some alpha particles completely rebounded means like it like hit the other, it like didn't even make it through the foil. What I mean?
Because they hit other. No, because they hit the positive charge of the gold foil. The nucleus, my bad. Nucleus.
Yeah, you gotta be more specific. You gotta say the alpha particles would have collided
With
with the
the
nucleus.
of the positively charged gold foil.
No, the gold foil is not positively charged, Okay.
I was saying that before and you said okay. I
Yeah.
did not know that was wrong.
Guys, The nucleus is what's positively charged, no, not the atom. Right? Not the atom. I'll say a proper answer. Please remember. In these instances, the alpha particles would have collided with the nucleus of the gold. It would have collided with the nucleus of the atom. What's the boy? Long story short, it would have collided with the nucleus of the gold atom. Because the nucleus is positively charged, it would repel the alpha particle completely. And this also has to do with the fact that the nucleus is very heavy. Most of our most of our atoms mass comes from the what? Most of yeah. Guys, do you all know how light electrons are? Wait, let me show you guys. Let me show you guys this.
1/1 to the 836.
And even with a cup, I don't remember. I don't remember.
That is correct.
Oh, it was 1/1840.
So
Am I wrong?
I see in that the atomic mass. Okay, this is not wow.
That was for beta I was talking about. Sorry, sir.
Oh, we also have to look at this. We also have to look at this cloud chambers and deflection of radiation along electric and magnetic fields. We'll look at this as well.
Yes, sir. The year before, the year before, I had a question like that.
Oh, and every once in a while, they go ask you for some uses of radioactive isotopes. They go ask you for this sometimes.
Okay.
But there's accident chemistry too.
Yep. 1 second. Oh, they're like, I reached this stage, like we're like internally crashing out. Internally.
Yes, sir, I reach it too.
Yeah, boy. Had too much sweats in the session. Mass.
Was gonna suggest a 10-minute break and we resume at 1, but I don't know.
Man might fall asleep.
That is true.
Okay, we need to lock in, guys. This is the generational lock-in we've been talking about.
Yes, sir.
The caffeine now started hitting me there.
Caffeine is not
You
good.
lucky you have caffeine. What I have is a bottle of Coca-Cola, and that is what we doing right now.
Now why you drinking?
She sounded like she going crazy just now, sir. Yeah, she said that.
No, I'm not. No, I'm not.
And I'm running on no energy drink and I'm surprisingly awake.
Oh my God, you sounded like you're about to. You
I have
sounded like if you
ChatGPT.
close your eyes, you're gonna KO on us.
I'm actually not tired.
So I'm going to send you the document now. We'll have the question that you said we will look at after.
No problem. Guys, what is the mass of an electron? Like right there. Is the mass of an electron?
9.11
9.11
times 10 to the minus 31
1 kilograms. Sir,
kg.
would they give this on the paper?
I don't think so. Think they expect you to know this. They expect you to know this.
What?
Yeah, and if we're talking about a proton, well, a proton is 1.6. What again with a 6.7? So here what? We're comparing an electron to a proton, right? A proton. Because remember, okay, an electron is very, 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 very light. A proton, however, guys, would you say a proton is heavier?
Yes.
So I would think so.
I would think so. Watch. One is to the power negative 31 and the other one is to the power negative 27. Which one has a greater mass?
The proton.
The proton, for sure. The proton, for sure. Right? And here what? Let me look at alpha particles, right? Alpha particles is 6.64 by 10 to the power minus 27 kg. Do we have beta there? Well, beta is just an electron, right? All right, so cool. Let me ask another question. So, where do you think most of the mass is for atom? Is it in the shells, the orbitals, or is it in the nucleus?
I think it's in the nucleus.
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 Right, and that's another reason for why occasionally, some alpha particles will be completely rebounded. You know why? Because it's gonna hit a really dense nucleus that has a lot of mass, in addition to the fact that it's positively charged, which will cause it to repel it. I don't know how I'm gonna do these lives when I get a little older, boy. Not sure. Not sure, man. Not
You
sure.
gotta change your channel name to Unk Vibes.
Hey. And I go had a
Careful,
really
careful. He don't like when we call him uncle, no.
like that. Like that. When you think of unk, you think about somebody with like a big belly, they're losing here, and like they have like a all uncles just have like this one thing where like they're missing here around here. You know what I'm talking about? I don't.
Yeah.
And they have like this mustache. All of that is mustache. Oh God.
Sir, and they just have the hair loss, sir. Some of them. Nah, not some of them. Most of them.
I don't want that for me. I help it so much. And that's
Sir,
all they want for
I
me.
never seen
Nah,
none of
oh,
them
nah,
things.
sir.
No,
You
Nah,
sir,
sir,
talk,
it's
we
all
sir.
never
jokes.
see
It's all
that.
You talk,
This
jokes.
is your
talk,
true
sir.
inside children here, sir. They
It's
will
all
never say
jokes.
nothing like that. All these outside children saying of bad negativity.
But yeah,
It's crazy. Hey, I gotta make it in life, you know. Like if I start losing here, I go in Turkey one time, you know. I go in Turkey one time. I gotta do
Turkey,
something.
sir.
Like, you know,
Why?
like
Like Turkey.
hair transplants.
Oh,
Yeah,
was
boy.
now saying that we get my little hair transplant. He'll be good.
I don't want to lose my hair. I cannot. But like what I do into my body, like I've been going every single night for like 8 hours, more or less
Well,
8 hours every night. Like it's tough, it's
well,
tough.
so apparently, some I forget what it is, but the for biology, they say if you could grow a good beard, is a high chance you can go bald.
Yeah,
If you could
yeah.
grow,
That has to do with testosterone and what's the other hormone? DMT. DMT. I think that's it. Like people take DMT inhibitors to prevent losing hair.
well, all the stress, sir.
DHT.
Oh,
DHT.
sir, you're gonna make it. But another thing too, that means I'm not gonna lose no hair.
Hey,
So,
boy.
fact, you're very much more likely to lose it because you have a full grown beard because of the DHT.
Although, let me not manifest that
Sir,
negative.
you see all these negative
22.
outside children,
I
sir.
feel
See,
we should be
Not
manifesting our one
manifest.
in
Let
physics.
me not
sir.
manifest that. Although, let me stick to the physics.
Yeah,
Right? Let me
and
stick to the
manifest our
physics
one.
and not manifest going bald. Because right now, I feel to just end this life, boy. And it hurts my feelings, but
Sir, that is how the outside children does behave, sir.
never.
That's how the outside children does behave, so you had to expect them thing.
I had to expect
As our
them.
inside child, boy.
Nicola use the same person and nearly get so banned just now. Calm down.
Whoa.
Led.
No, but think logically though. Like,
Wait,
I
what you
was
say
eh?
not
about
thinking
lead?
about that, Nikolai. When
Wait,
Nobody was thinking about that but
nobody
wait,
you.
was thinking about that.
what you say about lead?
No, you're trying
They
to
don't
get
want
mad
to.
now. Nah.
Anyways, let me look at the things we didn't do as yet. So cloud chamber. I want to ask a lot question, right? Which one had the strongest ionizing power? Alpha, beta, or gamma?
Beta.
Grandma?
Beta. No, alpha, guys. Alpha.
Alpha?
Alpha. Remember?
Alpha had the strongest and gamma had the weakest.
Okay, alpha is very positively charged. It's very positively charged. If it's very positively charged, okay, when we talk about ionization, we talk about ions. For
Oh
something
yeah,
to,
nice.
wait, for something to be an ion, it needs to have a charge imbalance. Like, I don't really like chemistry, but like, you have cations and anions, right? I
Yes.
believe cations is when you have more electrons, and it's always be like the opposites, or I'm mixing up with electrolysis. But like, the point is, if you deal with ions, is like positively and negatively charged. So for something to have a great ionization effect, it itself needs to be charged. So alpha is very positively charged. It's very positively charged. Beta is negatively charged, and gamma is not even isn't even a particle. Gamma is what? Where's gamma? Gamma is not a particle. What is it?
A
It's gamma.
electromagnetic wave.
Exactly, it's an electromagnetic wave. So this have a charge at what?
0.
0.
So will it have a strong ionization effect?
Nope.
No, it's the weakest.
Exactly. So I'll understand it now. So here what? For alpha, it's gonna produce thick, dense trails. I would probably hey, let's see like how the deep died in the boys latest
Yeah,
episode.
yeah, yeah, yeah.
Nah, sir.
Bro,
Sir,
bro.
nah, sir.
See, how they remember it have certain people who never watch it yet.
Come on, nah,
Okay.
sir.
Hey boy.
The
Oh
peak.
man, I
Kind of remind me of meiosis.
Rest in peace, the peak.
Hey
So
boy.
it does look like meiosis.
That's like how it was like hey, let's see the new Mortal Kombat movie release.
Yes, sir.
But I don't think it's gonna
There
be
was even
big.
something
Also,
like that.
sir, what did deep dive had to do with physics?
Okay, like you see this?
Yeah.
Like it remind more of like like how we died like
Nah,
like
nah, boy.
yeah.
What?
Like low key, high key. Like
Like
we
low
kind
key,
of
like a
Nah, boy, sir, boy.
low key,
Wait,
low key.
sir. We talking about
Let
high
me move on. Let me
quality
move on.
and
So you know
We
where the
have to
tentacle went?
we have to move on to physics. You have to let me move on. Let's stick in. Let's stick in. I don't know what wrong with all.
sir. I don't think I was there.
Nikolai, physics. Come on, physics, Nikolai,
Physics. Physics.
Yeah. Beta.
So alpha has the strongest ionization strength, so it's going to produce thick, dense trails. Beta it has a weaker ionization strength, so it's going to produce jagged, broken trails, and well, gamma is going to produce scattered spots. So let me just pick all the up quickly.
Do they give questions that we have to draw these things?
Yep, they come on here.
Oh, okay.
Guys, what is this?
Beta.
That the beta. No, that the alpha.
And I thought you would do better.
That the alpha.
That's
No, look at
Guys, that's
Yeah,
gamma.
oh my days.
okay, your spot's not looking like spotted.
So that
So
more looking like
Exactly,
that was
there's an
more looking like the
spot.
beta was kind of like
yes, sir.
separated, but more
That
close.
looking
to the
that
edge.
looking like gamma
But
now.
that
That
looking
looking like
like
gamma
Very
now.
good, very good, much better.
We happy now?
Yes,
Yes,
What is it looking like?
Alpha.
that's
That is
alpha.
Alpha.
That the deep.
Why? So, hey.
Nikolai, do question. What is it looking like?
That would have been
That'll be beta then.
All right, cool. I don't understand anything. Nice. Right, deflection of radiation along electric and magnetic fields. So, okay, this one really easy to understand. All right, so remind me, guys, alpha is what charged?
Positively charged.
Positive.
charged.
Gamma is how much charge 0, and beta how much charge what?
Negative.
-1.
Now you're gonna realize that beta is deflected a lot more.
Yes,
Can
sir.
anybody tell me why?
Because
It's attracted towards the positive as it's negative.
Positive side.
Okay, but and by that logic, alpha is supposed to deflect the same amount?
Yes, sir. It depends on how much negative charges the beta has.
No, like okay.
Was it lighter?
It's lighter. That is why.
Lighter.
If it's lighter, it's going to resist change in motion less. It's going to be less inertia. Right? It's just going to be deflected. Okay, question. If something is lighter and it's easier to move,
Yes, sir.
Correct.
I would think so.
So basically getting peer pressured right now.
okay. I have this. Wait, I'm gonna show them on physics, bro. It's physics. Right. I'm going to our episode paper here. Oh, the thing that's hard to move?
Nah.
No.
Wait. 1 second. That wasn't hard. Yeah, I got into this
Nah.
one. Did it move much?
Nah.
No, sir.
No, sir.
No. So like imagine this is like it deflecting as a result of being in like a positive or negative charge. And so as you can see, the greater the mass of the particle, the less it's going to want to move. Because, again, inertia. Inertia is a object's ability to resist a change in motion. So if it's heavier, it's going to resist that change a lot more than if it's something that's lighter. Again, which one is lighter, beta or alpha?
Beta.
Beta.
So, Alia, don't just try to memorize it, try to understand it. So, I can put positive here. I can put negative here. Where's this one?
Gamma.
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 Which one is this?
Beta.
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 Which one is this?
Alpha.
Alpha.
Which one was deflected more, beta or alpha?
Beta.
Right. If you do this in the exam, no, you're not gonna get a mark. You're not gonna get it. Right. Okay. This one is a bit harder to explain. So let's look at it again. So over here, you have, okay, what does the X represent again, guys?
The X. Oh, that is where you're going into the paper.
This is okay. So this is where you have a magnetic field going into the paper, right? You have a magnetic field going into the paper. So again, gamma is uncharged, it just goes straight through. Guys, it's more or less the same thing, Beta gets deflected very, very like to a great degree. Alpha gets deflected, but not as much. Like it is more or less the same concept. It's more or less the same concept. Like over here, it's okay because here, right? The magnetic field is going to, you have like north to south. Like, okay, let me try to see if I can explain this to you guys in a simple manner. Like you should be able to prove this using Fleming. It was Fleming's, I think it was.
I think it's the right hand rule and also I forget too.
Well, I think so because you have a magnetic field and you have something passing through the magnetic field. So anytime you have something passing through the magnetic field, it's going to experience a what? If it's passing through a magnetic field, what's gonna happen? What's gonna be induced in it? Since it's passing through a magnetic field. Induced EMF. So check something. Okay.
Was it on the left hand or the right?
No, right hand, right. Time
Yeah.
with induced right hand. Here. I'm not entirely sure. I'm being honest. I don't want to tell you anything wrong, but the answer here. But you would have to use Fleming's right hand rule though. You would have to use Fleming's right hand rule. I presume that if it's positive, then okay, I'm really not sure. I can't say I'm sure about this one. But it's right here. I wouldn't say it's hard to remember. Just remember that alpha gets deflected to the left and beta to the right. Right. But this one is easy to understand. It's very, very easy to understand.
I was not going to ask if either side would have worked as long as you understand that beta would have been deflected much easily than the alpha.
Nah,
Because
any side wouldn't work. Let me explain something. If you had the magnetic field coming out of the paper now, what would change?
or the direction of the magnet. No, the magnetic field.
Yeah. And as a result, it's going to deflect in the opposite way.
Oh, so I did have to watch the. Oh, I wasn't watching the X. I thought like you could have just draw it any different direction as long as you draw it properly. No.
Nah, you gotta be careful. I don't think this is gonna come though. Don't think so.
It's still good to know and remember it.
For sure.
Yes.
So I feel like we can move on to the isotope question now. Yeah. Anybody have any isotope questions?
Isotope questions.
Yeah.
So wait, we didn't do the question that I sent you on via WhatsApp.
How's it 2021?
Yeah,
I don't
January.
I don't think you had an isotope question in that, you know.
No, I'm talking about the same thing that you told us that it may or may not come.
What was that, boy?
With the same alpha, beta, and gamma.
Oh, and you just went through it?
Yeah, but you said that we would have went through the question.
What, this one?
Huh? No.
I went through that one.
No, I sent you a new one.
A new one?
Yeah. No,
Um,
not 2021, it was 2020. My bad.
oh, yeah, see, this is what we call a true crash course, boy. This is what we call a crash course.
I finna crash just now.
Yeah, boy. Let me see if I have 2020. I think I have it here. 2024. I need to sort this out when I get time. Because I give maths and odd maths all the love, you know. And pure maths hardly give physics much love. I'm just telling it to myself.
He the godfather of the sciences, and they give him no love. On.
I love physics though. It's just I prefer. Obviously, I prefer.
Numbers more than words.
Yeah, for sure.
Yeah, the only thing with physics is the definitions. You have to put it at T. It comes like biology.
Yeah, I don't like that. I don't like no definitions on it. I like pure theory. I can use your brain to figure it out. Gotta remember things, a liability. All right, so Nikolai, which question?
I think it was lower down, like a question 6 as well.
Hey, look.
Our next Chinese boy.
Wait. This Dave.
I like how they're showing us the fish and you ball like an extra.
Oh,
Yeah,
look,
yeah.
hey, watch this. Oh, let me use question fast now.
This are Jan or May June?
January.
So, like, it gonna go. Oh, what would that be?
Gamma.
Gamma.
Right? What would this be?
Beta.
Beta.
Are you sure about that?
No, that alpha because it going in that direction, yeah. Is alpha. That's the negative sign. And
And
that
that
is the positive sign, which is beta.
yeah,
Oh.
direction matters here. The direction matters. Okay. The magnetic field is replaced by an electric field, as shown in Figure 6. Draw the three rays to represent the path of each of the three emissions on Figure 6 as they pass through the electric field. Right, so which one is this?
Gamma.
Right? Which one is this?
That's beta.
Beta.
I'm gonna deflect it a bit more. Which one is this?
Beta.
No, that
Beta.
alpha.
No, that alpha.
Right, alpha, but how is beta
The
so
negative
high?
side.
All right, so
Maybe
Nikolai,
it's
we have over here. We have over here.
positive,
Exactly. We have over here.
negative.
They just put us to confuse you know, Nikolai.
Yeah, but isn't that the beta lighter?
Yeah, that's why I deflect the beta a lot more.
Oh, because it's easier to move. Oh.
Yeah, because it would resist a change in motion less.
Oh.
No, like, okay, so like the previous one where the beta was very low, or all layers on the positive side as well.
Okay, I see what you mean. But
Yeah,
like they would take that, you know. This is fine. It's
okay.
fine. It's fine.
But then that means the alpha got to be bigger because the alpha is much more heavier than the beta.
No. Okay, Nikolai. If the alpha is more heavier, then it's going to resist the change in motion a lot more. So the deflection is going to die down quickly, and it's not going to be as potent.
Okay.
Nikolai, if something heavy is going to be easier to move or harder to move?
Harder to move.
Exactly. So if this is heavier, is it going to be as easy to deflect or harder to deflect?
Harder to deflect.
Exactly. So it's going to deflect less.
Okay, now I understand the situation now.
The beta is a lot lighter, so it's going to deflect very easily.
Okay, sir.
Oh, again, that's 6 marks. 6 marks? What? What?
Yes,
Shh,
6 marks are
don't
my
complain about the
life.
marks. Don't complain about the marks. It's 6 marks and we bag.
That's crazy.
So, fella, see you clocking all day.
Are you clocking out?
Nah, somebody in chat here.
Oh, okay. I'll final isotope question now. I think I have one in 2025.
So the 2017 question.
Say that again?
The 2017 question.
2017. June?
May, June. Number number 3. Which country?
This question?
Yeah, that one, the one with the box.
Oh, this one over here.
Yeah.
Oh, we just look at this.
Yeah.
Yeah, we just look at this. It is more or less the exact same question all I watch. Like it's like literally. Like I feel like they copy and paste it though. I feel like they copy and paste it. Like you're not even joking. Because it was
Okay,
uranium.
So
I will
it's
explain back to you.
Yeah, it was uranium, but they used different values this time.
Ah. Okay, so I'll explain it quickly, right? Talk to me. Unmute yourself fast. Let me run through this fast. Who is this? Talk to
The
me.
person
it's
who was
Priyanka.
speaking, yeah, I'm not going to say that's Priyanka.
Priyanka,
So
okay, no problem.
yes,
So
please.
Priyanka, state the value of P. So let me see how this is gonna run, right? So whatever on the left hand side had to be equal to whatever on the right hand side. So you see how we have 238, 1?
Yeah.
When I add 238 and 1 again.
239.
When I add 139, 97 and 1, what do you think I'm gonna get?
239.
Make sure there is something here to trick you guys. But add it. Let me know where you're going. So 139 plus 97 plus 1.
I got it. 237.
237. Let me verify that. So 139 plus 97 plus 1. That makes sense because after fission, okay, over here we have nuclear fusion. It's looking like nuclear fusion, right? So they say we have nuclear fusion here, right? During nuclear fusion and fission, what happens after? What happens after, guys? Like you have mass before and you have mass after. What happens to somebody mass?
It gets
Somebody
lost.
mass is lost, but like still, this is a bit sus. It's a bit sus. This is a bit sus. Let me check something. Well, you had to multiply by 3. I don't think you multiply by 3.
Yes,
One.
I was about to ask her.
The whole time she was saying 1, and I was like, am I crazy or is there 3 watching me?
Yeah, I said the same thing.
No, like remember when I was looking at the
I
question,
didn't
I see like you gotta look at the 3. So like okay, if you have 3 neutrons, you have to multiply by 3. So when you add up 238 and 1, where you getting Priyanka?
239.
When you add up 139, 97 and 3 by 1, where you getting?
239.
Okay, so number one I was saying, right? The same concept will apply for the atomic number. So you have 92 and you have 0 here. What's 92 plus 0?
92.
Right? And then when I add up P36 and 0, I'm supposed to get what?
You should get 92, so you could just say 92 take away 36, and that would be P.
So what that will be?
56.
Everybody okay with this?
Yes, sir.
Yes, sir.
All right.
Yes, sir.
So Priyanka, they already say the value of P as 56. State the meaning of C in Einstein's equation. What is C? What's C?
The speed of light.
C is the speed of light. And the speed of light is equal to what?
3 by 10 to the 8 meters per second.
It's right here.
Oh,
Calculate the total mass of the elements formed after the reaction. So the total mass of the elements formed after the reaction. So Priyanka, okay, question, right? What do you think this would be? Before or after?
After?
This is after. So all you had to do, right, Priyanka? So here what, right? Barium. This is mass of barium here, right?
Yeah.
What are we gonna add to that? What are we gonna add to that?
KR.
Which is this?
Yeah, and
how much neutrons?
3.
3. So you gotta multiply this by
3.
right. And when you plug that into your calculator, you'll get the mass after. Let me know if you want more.
So I'll get the total mass after.
Correct.
Okay.
So all you have to do is just add up barium, add it to krypton, and then add it to 3 times neutron. And you get an answer.
Okay, understand.
Nikolai, I see you raise your hand.
I found an isotope question. It was on 2019 May June.
Okay, good. And
question 6.
Priyanka, in this question, I want us to calculate the energy released in the reaction. So what formula are we going to use here? Anytime you want to calculate the energy released in the reaction, and you deal with fission and fusion.
E equal mc squared.
Yep, E is equal to mc squared. Priyanka, remember this formula.
Okay.
And this is the formula you use to calculate the energy released in fission or fusion. Understand?
Understand.
So mass, this M over, how do you find that? That's just the mass after, I'm saying, there's the mass before minus the mass after. So here, I do the question first. So, Priyanka, if I want to find the total mass of the elements formed after the reaction, tell me what how to add. Speed. Light speed. Come on, tell me fast.
Right, yeah, so B8 beryllium. So 232.560 by 10 to the power negative 27, close brackets, plus 152.620.
Right. Plus the
152.60 by 10 to the power negative 27. Close brackets, plus 3 by brackets.
1 point. 1 point. Priyanka, you did. I'm to Priyanka, boy. You don't want to say them two numbers. Okay, 1.67 by 10 to the power negative 27. Priyanka, you there with us? Can I hear Priyanka, but like guys, the mass after will be this 3.9019 by 10 to the power minus 25 kg. Is anybody confused at all by this?
sir. Also like cake.
Like cake, right? And what should also find then? What should also find?
The mass before.
The mass before.
To find the mass before, well, what two things are gonna add?
Uranium and 1 neutron.
One neutron, my bad. I said electron by mistake.
Say him and all the incidents can I died on now.
Yeah, I hear it. Yeah. So I'm gonna add everything. I got 3.9019 by 10 to the power minus 25, right? And what is the mass? We had to calculate mass before, right? When we do these type of questions, you're finding mass before and mass after. So how would I find the mass after? What's the invite? How would I find the mass before?
Yeah, add uranium and neutron.
So that'll be 1 point.
670 by 10 to the power negative 27.
Tell me, where's the mass greater? Before or after?
Before.
Yeah, and this is always the case because after fission or fusion, you lose some mass, and this mass is given off in the form of energy, which is a direct conversion of mass to energy. That's called the mass defect. So, Priyanka, you understand everything so far?
Yes, sir.
So, how am I going to find n? Well, that's going to be the mass. That's just going to be the mass before minus the mass after. So, that's going to be, well, I can probably do it here. M would just be 4.0002 by 10 to the power minus 25 minus 3.9019 by 10 to the power minus 25. What would that be? Okay, again, 9.83.
And get 9.83 times 10 to the negative 27.
Priyanka, are you with us? And Priyanka, boy. But that's just going to be that mass we find 9.83 by 10 to the power minus 27. By what?
By C square.
All right, by 3 by 10 to the power 8. Power 2. Yeah, let me know if you guys get that.
So then did you
Yes,
see
sir.
follow-up question?
Talk to me.
The value for C.
Yes, sir, I get that.
C is given to us. C is 3 by 10 to the power 8.
Oh, okay, sir.
Right, so that's how you tackle a question like this. State one use of the energy released from the reaction. We're going to use this energy for. Let me give my example.
Heat.
Yeah, you could use it. Well, you could use the heat for like heat water, but like generally speaking, and we have like nuclear reactor facilities.
Oh,
Yes, sir.
What would you use the energy for?
Or like
for power.
Yeah,
or for electricity.
state one use
For electricity.
can be used. Well, here what? You'd have to convert the heat energy. You'd have to convert heat energy because that energy can be released in the form of heat. You can convert this into electrical energy, and this could be used to power power homes or like power. That's what I'm looking for.
Machinery.
Power machinery, yeah, you can say that. Or
Electrical devices.
Electricity.
yeah, well the main use is that you can convert the heat energy to electrical energy. That's right, and you can use that electrical energy for however you want. That's the main use. That one mark. So Priyanka, let me know if you're okay with this.
Yes, sir.
Make it real simple. Alright, so Nikolai, what was the question? Yeah, you said 2019 and
Yes, sir, Major. Question
Sir.
6.
Sir,
Yeah.
After I think it run through land and sea breeze, that might come.
Land and sea breeze. Think
Yeah,
that gonna
yeah,
come?
yeah. Huh?
You think that gonna come?
Yeah, get predicted for like high.
Okay, no problem. Because like,
But
I'm not seeing an isotope question. I want like the graph question. I'm looking for like the graph question.
Like graphs.
Yeah,
Ew.
like the graph question where it's like,
Oh.
so like 100 here, I'll go for 50, then I'll go for 25.
Ah, like that. Radioactivity.
Yeah.
Oh, well, this one doesn't have it, but it have like to draw it and all kind of stuff.
I want to look for a question. I must find question somewhere here. Questions carefully. Very good.
So try 2022. 2022. May, June.
Months.
Sorry for you or
I know how the solutions right here. Are the solutions. So we can run through this fast then. Are the solutions.
yeah.
All right. So guys, for those of you guys that wanted these type of questions, all right, pay attention now. If you wanted to see how to find half-life from the graphs, pay attention now. Have anybody in the Zoom that want to see how this going to work out?
Yes, sir.
Me, I do, sir.
All right. So again, what
Sir.
is half-life? What is half-life?
The time taken
You
for
tame it.
a radioactive substance to decay to half its original value.
Yes. Time it takes for it to decay to half its original value. Right? Half. So they're saying use the grid provided in figure 1, plot a graph of activity versus time. What are we going to plot on our y-axis?
Activity.
Whichever one is mentioned first is going to go on the y-axis. So activities on the y-axis. What's going to go on the x-axis then?
Time.
Time, as a matter of fact, time always goes on the x-axis. By the way, watch. The time it takes for the active mass or activity to be half, right? Half, that's what half-life is. So on the y-axis, I have activity per minute, and I have time in minutes. What do you think I'm going to label my graph then?
Activity versus time.
Activity versus time. Simple. Let me see if we can come up with our scale quickly. I mean, I already do the graph, right? But I think coming up with our scale is something that's give a little trouble. Right? Think I need to
Kinda.
work on that.
Stop watching the scales.
Oh yeah, what are you looking at that for? Yeah, so we're gonna go on the x-axis, guys.
Oh.
2 centimeters is
Centimeters
1.
Wait, what going on the x-axis? Tell me that. What going on the x-axis?
Activity. No,
Time.
wait.
Wait, time does always go on the x-axis. Time always go on the x-axis. So we had to go from 0 to 6. And how much divisions we have here?
18.
18. I see in 16.
16. Oh, my bad.
So question, guys. Your graph in physics must occupy what? Must occupy what?
3/4.
More than half.
5%.
More than half, right? More than half. If I use every one represents one, would that work?
No, sir.
No.
Ah,
Nah. So where's the next other scale I could use?
2
Every
centimeters.
2
to
cm equal
one.
1.
Like I say, 1, 2, 3, 4, 5. Is that occupying more than half the graph?
Yes, sir.
Yes, sir.
I could use that then, right? And then on the y-axis, we gotta go from 4 to 80. Okay, don't look at the scale earlier. Well, yeah. We gotta go from 0 to 80. Any suggestions?
So
So
I
if you
think I
count
two.
every 2 centimeters is 10.
But I think I 2 to 10 skill working.
Let me see.
Just I
10,
guess though.
20, 30, 40, 50,
If
60.
not, you how to do every 2 cm equal like 5.
That working, because it's 80. Doesn't that occupy more than half the page?
Yes, sir.
Right. So therefore, on the x-axis, we are going to say every 2 centimeter represents 1 what?
Second.
Activity.
Nope. Nope.
Oh, no,
One.
time. Second.
Seconds.
Is it second?
Or minutes.
It's how easy it is to lose marks.
Yeah,
So,
but
well,
sir,
it dress small, so I can see.
sir, isn't time in seconds?
I know, but look at the
But they gave
units.
it
But
in
the graph
minutes.
telling you that is minutes, so you gotta work with them.
Yeah. Right? And activity, guys, the proper unit here is becquerels, eh? Oh, you know that or no? BQ.
Nah, you know that.
Becquerels.
Never heard
So,
it.
That's okay. That's okay.
so you have to give the half-life answer in seconds, though? Or minutes?
You give it in seconds, but we'll convert it after, as you'll see.
Right.
So on the y-axis, we're saying every 2 centimeters is what?
10 becquerels.
10.
You could say 10 BQ, or you could say, yeah, you could just say disintegrations per minute. But that is really BQ. That's what it is, becquerels. Right? Disintegrations per minute is BQ. So are you okay with the scale?
Yes, sir.
Yes, sir.
Right, so I'm gonna plot the graph now. Wait. Nice. What was our initial activity?
80.
So you plot that graph real fast, boy.
I know, I just dive out. Barry Allen, Reno and Regine Vareka. I mean,
Yes, sir.
so the original activity was 80 disintegrations per minute. What would half of that be?
40.
40.
40.
So I'm going to go here, look at 40. And I'm going to take a read off. This will tell Mama what?
The amount of time taken for it to reach 40.
Right, so this will tell me the first time and a half.
So you gotta use 3, right?
You don't necessarily have to use 3. But you try to do as much as you could to take average.
Oh, really?
Yeah. But you need enough to take average. You need to do it as much as possible. As you'll see. So the first time and a half looking like what?
1.6.
1.6.
1.6. So next up, we're gonna look at half of 40, which is
20.
you wanna go to jail. What? What? Why am I doing that? It's crazy. Reggie not supposed to yawn. Right? Yeah. We're gonna call it 3.2, right? For the sake of simplification. Are you okay with that?
Yes, sir.
Yes,
Yeah.
sir.
Right. Now let me ask you a question, right? It's a mistake students make. Students are going to measure from here to here and say that this is the second time and a half.
No, it's the 1.6 to the 3.2.
Right, because how much time would have passed since the first half-life?
1.6 minutes.
Yeah, next 1.6.
1.6.
1.6 minutes.
So you had a measure here, guys. You had a measure here. And this is going to give you a second time and a half. All you understand?
Yes, sir.
Yes, sir.
Right. So the first time and a half looking like what?
1.6.
1.6 minutes.
The second time and a half looking like what?
Our next 1.6 minutes.
Is it possible for me to take another time and a half?
Yes, sir.
You can take one more.
Yeah.
One more?
Take the 10.
10, yeah.
Yes, sir.
That's it. If there's one thing I hope I realize, like if I gotta rewrite physics or something, I hope not. I'll see how easy it is. Physics don't want to be hard. Don't want to be hard at all. And
It
guys,
only hard when you make it hard.
exactly. Am I going to do that?
Nah, sir.
No.
That's bad.
It's very bad. I'll do this. I'll do this. We have 4.5 here. We have 3.2. What would the difference in the middle be?
Would be the same 1.6.
Is it 1.6?
Is it 1.6? Nikolai, where's 4.5?
Nah.
3.2.
No,
I say it's 1.3.
1.3.
Yeah, so I said it would have been.
Oh. Okay. Nikolai gonna make a good lawyer. Huh?
So why you put
For
that time in
real.
on Tuesday?
What? What? What did you? Best I just end this live, boy. Nah, boy. Wait.
Nah, sir.
Wait, boy. So here what? If I make a mistake like that, I worry about it tomorrow. Cause like I gonna get sleep after this live, man. I'm not gonna get sleep after this live. What are you gonna do in the exam? I'm concerned.
So for that maths, I had to splash my face with water during halfway through the
Every
exam.
can you whole night.
After that whole all night live.
So I have a next question. If I wanted to find another half-life, how would I do that?
You go
Right
to
now,
5.
go to 5. There's just being extra, right? I just being extra at this point. That looking like it's over here. Give or take. That looking like what? 5 point.
5.7.
So I hope I understand that we are long blue line I draw there. That is not the half-life, and
That's a
this
big no-no.
this is the half-life.
That looking like a 1.2.
Yeah.
We could go next one. 2.5.
No, relax yourself, Nikolai. Relax yourself. Relax.
Let me stick to whole numbers.
Nikolai, how are you gonna do that, boy? How are you gonna do that, Nikolai? How are you doing that? You tell me how I doing that.
That time and a half could be infinite.
Nah, Nikolai.
Lead.
Aye, look at it.
Nikolai, take a nap.
Nikolai, take all the time out, man. Take all
I
the
still don't get the
time.
lead thing. I still don't get the lead thing.
How you do?
Don't worry about it. Do not
Don't
worry.
worry about it. I'm not forgiving Nikolai for that though.
So, Alia, here what, right? From your graph on page 5, calculate the average half-life of the radioactive substance. Do you guys understand? To find average, you just need more than one.
Mm-hmm.
You understand that, right? To find average, you
Yes,
just
sir.
need more than one. How much time
Mm-hmm.
and halves are fine?
You get 4.
4.
So
And you
I have
add
one.
them up and you divide
And
them
divide
by
them by
4
4.
to
I have
get
one.
the AVG.
Right. I have the first time and a half there, 1 T and a half. I have 2 times T and a half, 3 T and a half, and I'll have 4 T and a half. So to find the T average, right? So I say average T and a half. What that will be?
That'll be all of it
1.6,
plus and divided by
1.6,
the number.
1.3 divided by what?
Divided by 4.
4.
What we getting?
1.43 rounded off to 2 decimal places.
I realize this is like my good solution. This is my good solutions. I erase the whole thing. It's like reference solutions.
Wait, so you didn't copy it?
It's fine. Make it back. It's fine. I will use these things to help the future generation of kids when they're writing physics. It's fine.
Yes, sir.
I did back these things anyways.
So that you saying it's fine, it's not sounding like it's fine.
It's fine. What we getting, guys? 1.1.
1.43 rounded off to 2 decimal places.
1.53?
No,
4.3.
4.3, sir.
So couldn't you just divided the 5.7 by 4?
Yeah.
Well, I mean, you add up everything and divide it by 4, right? Oh, you're
Yeah, you
talking
just
like
find
from
some
Yeah,
history?
parts with
I was
and
watching
divide
the
by
whole
4.
line as a thing.
You could do that. You could do that. You could do that. Because that would be a summation of all the previous time and a halves. That's a good observation. But see, I still want to see that, They want to see,
I'm not going to
They
say they
want to
want to
see
see you
working. They
working.
want to see working.
right? But that's a brilliant observation. I like what you're thinking. I like what you're thinking. 1.43. Yeah. So the average time and a half is 1.43. You know what? I would advise you to convert that to,
Seconds.
yeah. Because the SI unit for time is
Seconds.
Seconds.
Yeah, multiplied by 60.
it's 1.43 by
85,
85.8.
85.8 seconds.
Yeah. Are you okay with that?
Yes,
Yeah.
sir.
Yes, sir.
It's 5 marks for that? That's ridiculous.
Hey,
That's
sir, don't jump about the marks. It's 5 marks we have.
So, on your graph on page 5, use dotted lines to determine how long it would take for your activity of the sample to reduce to 10 disintegrations per minute from its original activity level. So, the way to figure out how long it would take to drop down to 10 disintegrations. I think we have that. We have that. 10 disintegrations as well.
4.5.
Yeah, we have that already. Are you okay with that?
Yes, sir.
Yes, sir.
Then nuclear fission. Nuclear fission is the process by which a heavy unstable nuclei is split into 2 or more lighter fragments, thus releasing energy in the process. And if you wanted to find the energy from this, what formula you will use?
E equals C squared.
Bam. Cool. Easy. Very, very easy. I think somebody wanted me to explain this to them.
Yes, sir, but I'm not sure if
So
this
I,
still here.
so I just always get an answer size and never know what to do.
Okay, no problem. Here you want to do, right? I will show you the formula method and the one with the always mix it up.
Oh, you need a protractor. Wait. No, it's a
Protractor.
compass. It's a compass.
Yes, it's a compass.
The thing with the pointy thing.
Like as a math teacher, I should know,
Yes,
but
a compass.
I'm
look
looking
at
straight
this.
some
Look at this.
advanced.
What does this look like, guys? What does this look like?
It
Does it
does
not
A
look like
taco.
a taco, man? Say a taco. Right. So you would take, here we're going to do, right? You're going to take your compass. You're going to open it out to the length here, right? Are you with me?
Yeah, so
Yes, sir.
Then you're going to place it at A, and you're going to draw an arc.
how long you had to open it up?
You're basically opening the compass from point O to B. You're measuring that distance and you put the compass point on E. When you put it on E, you're not going to change the length and then you have to draw the arc.
You had to strike a arc.
You know what?
Correct.
I will actually show that.
Oh, and you open the length at A, put it at B and strike an X arc.
Right. You're getting it.
Oh, yeah. I smart enough.
Yeah, everybody locked in.
And then the point at intersection, you draw the line.
And the resultant is the line in between, like inside the object.
Diagonal.
The length of it?
Yeah, the length of it. You just measure it and that's the answer there.
Are you ready?
Way.
I like
Yes, sir.
the energy. I love the energy we gain. Love the energy. You gonna take one compass?
Hey, compass real small, sir.
No good to say that.
It just maths.
Nikolai, don't hit Nikolai,
I feel like Nikolai.
Nikolai saying some sketch stuff, Nikolai saying some sketch.
Nikolai a little salty about what went on earlier with that lead now.
Yeah, boy, it seems so.
Huh?
Like Nikolai can't give us some lead, boy.
I still curious about the lead.
All right. So here we're going to write it down.
Yes, sir.
We're going to take the sharp point of our compass, and we're going to open it out to the distance of O to B, which is your base, right?
Mm-hmm.
Then you're gonna take your oh my days. Then you're gonna put a sharp point at A, right? You with
Yes,
myself,
sir.
or you're lost.
Now, sir, I did.
And you're gonna
Yeah,
draw.
strike that arc here.
Then you go into, oh my days.
Nah, so okay, get there now, sir.
Then you're gonna measure the distance of O to A, right? Right,
Mm-hmm.
Ida?
Yeah.
You're gonna take this
And
and
put
place it.
that B. And strike
Right.
that next arc.
Bam.
And where it intersect, you gotta draw some lines.
I know, sir, every time that question moves, sir, want to crash out.
Now he'll give it
Polypod
like,
acting up, sir.
Yeah, it's exactly now.
sir, wait. Remember, sir, if anytime something given sir trouble, he just want to shoot it up in a shooting mode.
Nikolai, you calm yourself, but you calm yourself. You
I
calm
tell
yourself.
them Nikolai salting hard right now, boy.
Honestly, it's the most emotion I hear out of Nikolai.
All you understand anything?
Yes, sir.
Yes,
Yeah.
sir.
So this over here would give you
Yes,
the
sir.
what? That's what R. It would give you the what?
The
Resultant
resultant for it.
vector.
Right. This is the resultant.
And whoever you measure that is your answer.
Yeah, the magnitude of this will give you the resultant. So all you have to just measure. So like, I should have a ruler somewhere. Nikolai, don't get me started ruler, but do.
Huh? Sir, I wasn't
Nah,
even about to say
that
anything.
ruler big.
All right, so let me what are looking like, guys?
I got good 16 cm.
Yeah, 16.
Yes, sir.
So easy, right? Like in this.
Yes, sir.
For
Yes,
sure.
sir.
But
Yes,
here
sir.
what?
Of course.
They're asking you to determine the magnitude of the resultant velocity in meters per second. So what are gonna be?
16 meters per second.
Cool. And they always just figure out the direction in degrees from the wind velocity OB. So we need to measure the angle from OB to the what?
To the resultant line.
Exactly.
Huh?
Yeah, to bring your little thingy, the half a circle.
Like this.
My
The
brain
taco.
blank. My brain blank come out with that name.
The taco.
Compass.
Hello. We just I this is the most amount of sweat. Like I don't think I
Polypod,
Sir,
boy.
sir, at least you're sure we get in the physics. We don't need to get anything else right now.
Hello, what is it looking like?
Like
Well,
more than
if you put
40.
it more, it would have been
Looking like
more like
our 15. If you raise it up, it'll be
42.
like a little.
been
No,
13 or like
47.
14.
I think in our
Oh
14.
my god.
I thinking probably like a 40.
A 40.
Yeah, because it's not directly on the
14.5. 14.5.
Yeah, ask me
47.
47.
Sir, remember it's not exactly on the zero. Watch it
Somebody
properly.
say 47.
Yes, that was what I'm going to
I
say.
think they meant the
It gone,
other
it
part.
gone.
Okay, let me explain the thing, right? So earlier,
40.65.
wait, me personally, I would say, boy. Let's see if I can rotate this
Why is
portion.
it fixed on that point?
Why are you moving so far?
It's just polypod, sir.
Sir, do not get frustrated with it.
Let me just call the thing
It's got
13 and done.
14.
Let me call it 13 and done.
Alright, no
Because like,
scene.
if we were to like move it up a little bit,
So, and it would have a range of values you could have getting anyways.
yeah. Let me just say 13 and done. Okay, you understand?
Everybody answer wouldn't be exactly the same.
It's looking like around 14 and 30. 14 and 30. Around there. You understand that?
Yes, sir.
Yes, sir.
Yes, sir.
Sir, question before you move on.
Yeah.
Okay, my bad. laptop was dying, so I had to go for the charger, sir. So I didn't see how you get the there's something out there so with the compass.
Okay, can I run it back one more time?
Thank you, sir.
Well, I think I'll be a good father in terms of patience.
Yes, sir.
No.
Yes, sir.
I hope so.
Not gonna lie, sir. I
No.
don't know if you'd still have here by then.
Pushing negativity.
So if you're using all the patients in one place, how can you use it the next?
No, think about it, right? When you have children, you'll be seeing them every single day, week in, hour. When CCB is just for a couple hours, it's not the whole day.
I've been
Nah, but
seeing you guys. I've been
students
seeing.
be seeing me every day.
Hey, I've been seeing you guys more than I've been seeing Mrs. Matt Rhymes or my family, bro.
Don't worry, you'll see her soon again.
Wait,
That's
so what
rough,
kind of thing
buddy.
is that? Ain't you?
That's
Wait, eh? So here what I was saying, right? What's his name again? The guy from Jamaica. I remember bringing short.
Tamale.
It's tamale.
Me?
Tamale? No, I don't think it was tamale. Was it? Oh yeah, it was tamale. It was tamale.
Yes, sir. Timorley.
I have another student from Jamaica called Dimali. Dimali. Yeah.
So what about Bob Marley?
Bob Marley is my
Yeah.
dog. Bob Marley is my brethren. I know Bob Marley long time. I know Bob when he was fat.
What?
That's interesting.
Comedy.
You know Fat Man Bob. Or you know Fat Man Bob. Fat Man Bob fat. That Bob Marley, you know, that Bob Marley. Bob Marley, you dead, you know. He just get a little fat. Nobody can recognize him now. I mean, he wants to be on the download. You want to download, guys. Yeah. So, Tamale, I'm going
Yes,
to
sir.
place my compass from O to B. Then I'm going to place it at A, and I'm going to strike an arc. Gonna strike, and then
Yes, sir.
I'm gonna put it from O to A.
A, and then a strike arc again.
Yes. Oh my days. Ugh.
So no need to. I get it. No, thanks much.
No problem. And then in the next question, well, my blood pressure is so high right now. So, and then in the next question, they said to state its direction in degrees from the wind's velocity OB. So we have to measure the angle with reference to what? So what?
Wings OB.
OB. Right, so I'm gonna take my
Taco.
taco and I'm gonna line it up. And look, it line up properly this time.
Yes.
Yeah, looking like
It didn't
Look
even
like
line.
Molly
It
13.
still didn't line up properly.
we taking this. We taking this.
We could take it. It's the way the taco crumbles.
I want to see how my brain crumbling. But yeah, guys, the answer was 16 meters per second, and this was for the resultant vector. And the angle, call it 13 degrees. Are you okay?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
That's 5 marks.
What?
All right. Hear what? I feel like I should just start pass papers now, you know.
It's like full pass papers, Dread.
Yeah, just do a full
I
pass.
find I agree with that.
I was waiting
Yes,
for that,
sir.
honestly. I was waiting for that.
Do a full pass paper. Right, January
I
2026.
agree with doing the full pass paper, and we do all the questions. If we come up across something, we check.
Stick with the land series.
So did you do a prediction in this paper, by the way? In physics?
So Claude predict that might come. So and life lesson teacher too.
Yeah.
This is only 2.5 hours. Are you serious?
I'm explaining it to you fast.
Yeah, it's a gadget.
Alright, by the way, a lot of you guys don't know this, but A is actually a what? That's what F. A is actually a what? That's what F.
A force.
Yep.
Nah, not a force. It's a fluid.
No, why I think that.
Power
It's a fluid. It's a fluid. It's
or
a fluid.
fluid because it's a gas. Yeah, gas and yes.
Oh yeah, because then that comes back to Bernoulli's principle.
You know what Bernoulli's principle?
Sir, I'm a cadet. We learned that in cadets.
Okay, that's really cool.
We have with the airplanes, we have to learn it like Bernoulli's principle and Newton's third law in relation to lift flight.
That's actually really cool. That's actually really cool. Not gonna lie. Like one of the courses at the UE, we had to actually do Bernoulli's principle questions. A lot of it was fluid dynamics something. I didn't like that course. Didn't like that course. Yeah, didn't like that course. Because I did electrical engineering, why doing that? You know what I mean? But
Oh, well,
yeah,
that is very
it's
interesting.
good to know about us. It's good to know about that stuff. But basically, what I'm trying to say is hot air what? What does hot air do?
Rises.
Rise.
Rises.
Yeah.
Hot air rises.
Because it's less dense?
Exactly, because it's less dense. You know why? Because when you heat something, kinetic theory of matter says that the particles would gain kinetic energy, they'd start to move about, and if it's moving about and it's occupying a greater volume, but it's the same amount of particles, what comes to the density?
It would be less
Density
dense.
is equal to mass over volume. If it's the same mass but taking up more volume, but what happens to density?
Density will get
Less
big.
dense.
Less dense. So the hot air rises because, like he says, less dense, and the cold air would what?
Sink.
Cool. I'll ever feel like the sun real hot, but when you go into the beach, it's cold.
Yeah.
Yeah, kind of so.
That
That why we
has-
are AC. That why we are AC close to the ceiling.
What?
The thing about this, right? We are
No.
AC.
You have a point, you have a point, but there's also
Yeah.
some other factors, right? Yeah, because cold air sinks and it would occupy the space in your room. That's fair. But some other factors too. Like, why would you put a AC on the ground? A lot of AC, like, I literally have my AC right here. Is a window unit, literally in the window. Would I
I like
break
them
it?
old time things. So.
Yeah, why? You're so man insulting, my boy. But it's work good, it's work good. Hey, I save up real hard and get I know. I save up so hard and get a AC. Don't bother with that AC, boy. But like, are you going to break the wall to put AC on the ground? No, you would not, and that wouldn't make any sense. You'd put the AC closer up to the top, right? Closer up to the top, so that the cold air would sink and it would occupy the room.
Basically, that's the way you're saying it with the AC just remind me of diffusion, basically.
Similar, it's a similar concept. Do you guys know about water potential hunting? By people, are you know about that? Anybody know about water potential?
I think no.
Yeah, I'd agree.
Like, it look like this.
So I remember it from where you told us last time about it, sir.
Oh yeah, and I was explaining osmosis.
Yes, sir.
All right, so we understand hot air rises and cold air sinks, and we understand that water has an extremely high specific heat capacity. So you need a lot of energy if you want to raise the temperature of a large body of water. So the sea generally remains what? Hot or cold?
Cold.
Cold.
So when the hot air goes over the sea, it gets what? What does it get? What I'm saying?
Cold.
It gets hot or it gets cold?
Cool.
It gets cool.
So let me explain the full concept over here. And by the way, this example are convectional currents, right? Because okay, let me explain convection currents real fast. If I realize when you're cooking something, you see like currents. You ever see that?
Yeah.
Yes, sir. When the air is look bendy and
Right. So here what? The bottom of the pan is closer in proximity to the hot plate. Could somebody tell me fast what mode of heat transfer is this?
Conduction.
Conduction. This direct contact. Anytime it's direct contact, conduction. Over here though, inside the pot, it's what?
Convection.
Convection, cool. So this is closer in proximity to the hot plate. So everything over here is going to get really, really hot. And if it's getting really, really hot, what's going to happen to the density?
Again, less dense.
Lowers.
Decrease.
And the kinetic energy will rise.
Okay, if the density decreases, then it would want to go. Where would it want to go? If the density is decreasing,
up.
It would want to go up. It would go up, and as it cools, it becomes what?
It sinks.
Denser.
More
dense.
So it sinks.
And then it gets hot again. Then it gets hot again, and it rises back up, so on and so forth.
So it's
Easy?
like a cycle, basically.
It's a cycle. It's a cycle.
So evaporation, condensation, and repeat.
Yeah. So sea breeze is another example of convection currents. Note the diagram below and compare it to the heated metal pan above. So, Leon,
Yeah,
the ocean is cooler than land or hotter than land?
cooler.
Right. So here what? When the hot air will sink, right? The hot air will sink, agreed?
Yeah.
Hot air will sink and it will go really close to the sea, and as it passes over the sea, it's gonna become what? Cooler.
Yeah.
And this is gonna sink and is going to go on land. When it
And
goes
rise
on
again.
land, what will the land do to the cool air?
Rise.
It will heat it up because the land is what? The land is what?
Hotter than the sea.
Exactly, it's hotter than the sea. I don't understand what I'm saying, right? Like on land,
Yes, sir.
it's gonna be hot. And so when the cool breeze blows on the land, the air is gonna get heated again. And if it gets heated again, what happen?
Less dense.
Less dense, it rises. And when it goes up to the top, you know what the clouds is, it would start to what?
Become more dense.
Right, it would get cool again, and it would start to fall. What's saying, boy? No, that's a bad example. Bad example. So like, okay, I'll understand the part where the sea cools it, right?
Yeah.
I'll understand that part.
Yes, sir.
So
It goes on the land, it gets hot, it rises. It rises. Okay, cool. It rises. Now it must why does that hot air want to come down?
Because it's near the sea.
Because it have like less pressure below it, so you can pull down. Because the other air going towards the land.
Now we want to talk about convectional currents here. So here what I'm saying, right? Over here is really hot. So okay, as soon as the air comes off the ground, is it gonna experience that same level of heat?
Nah.
No. So the air here is gonna start to what? The air here is gonna start to cool, right? And when it goes, but it's still a little hot, right? And then it's gonna go against it's gonna blow on the sea, and then it's gonna cool it even more. It's gonna go on land. The land is gonna heat it up. If it heats up the air, it's gonna rise. In the sky, it's not in direct contact with the hot land, and so it starts to cool.
Yeah, cool
Right? It
enough
starts to
to
cool.
get enough density to sink.
Exactly. It's a whole process. I understand?
Yeah.
Yes, sir.
So like when the air so here what? You have hot air, right? The hot air would what? Hot air would what?
Hot air rises.
Sink.
Okay.
I mean, nice, yeah.
That was a trick question.
Rises.
If you're looking at this question, we know that hot air rises. Now when the hot air leaves the ground and it's in the sky, what will happen to it?
Cooler.
It will cool.
It will cool, and when it starts to cool, it'll start to
It will start to sink or go down. Sink.
and when it brushes against the sea is gonna cool it even more.
Yes, sir.
And now that's gonna go on land. On land, the temperature is lower or higher?
High.
High. So it's gonna do what to the air?
Make it rise.
Less dense.
It's gonna heat it up, right? It's gonna heat it up. And so it's gonna cause the density to decrease. And it's gonna start to rise again. Since it's not in direct contact with the ground, it's gonna start to what?
To cool.
It's gonna start to cool, and then it's gonna start to sink.
So it's a cycle.
It is a cycle. So somebody explain it to me.
Okay, so I want to explain.
Explain it.
So as the air goes over the land, it gains heat, it heats up and rises. But when it touches, as it goes up, it isn't in contact with the land anymore, so it cools. And because it cools, it becomes more dense and sinks back to the sea level. The sea level is also cool, so it pushes it onto the land, and then it gets back hot, so it goes up again, and the cycle continues.
That's an excellent explanation. I'll clap.
Chat.
That's a
Yes,
W
sir.
explanation. That's a
Clock
W.
it, clock it.
Yeah. Right, so everybody feel like they understand CB. I don't think it's gonna come, but like if it doesn't,
Of
I don't know. But
course.
convection
I
currents.
feel like
Yep.
what would come really and truly is the convection, conduction, and radiation. You know, where is either when you touch something, what is that? If it's convection,
Yep.
something
But
like
I'm not hard. I'm not hard, guys. I really see what I'm saying, right?
So, what you guys had covered in the first physics live?
Thermal energy.
Energy. No, we cover
Heat.
Thermal physics. My
thermal
bad.
physics.
Heat. Yeah.
We cover like those
Okay.
calculation questions, like like if somebody leaves ice exposed and they come back and it's on liquid water at 27 degrees Celsius, calculate the energy it would take to become to melt, then the energy to heat up to 27 degrees Celsius. Say the total energy, that kind of thing.
Degrees is heat capacity and specific heat capacity, and the change in state is the latent heat of vaporization and fusion.
Correct. We looked at cooling curves and heating curves as well.
Mm-hmm.
All right. So are you ready to start the question?
Yes, sir.
Yes, sir.
All right. Let me see how much I know. Your phone dying. Thing dying. I dying. Because
And we all
I'll be mean to my boy.
So that's your
tough,
that's
Here's a
the
little joke.
outside people.
tough love, tough
Is
love.
that
Nicola, you're balling is the outside chair and you salting the most right now.
all right? Are you ready? Let me start now. Let me start.
Of
So,
course.
a class is investigating. Wait. Yeah. A class is investigating whether the amount of insulation around a container affects the rate at which a liquid cools. Now, logically, if you're insulated, right? If you're insulated plenty, would it take a longer time to cool or
Yes,
what?
sir.
Yes, it will take longer.
Yes.
It will take a longer time to cool.
Okay, what is one of the best insulators?
Styrofoam.
Styrofoam, but we have something better than that. Have something better than that.
Calorimeter.
Air, guys, air.
Yeah.
A vacuum.
I feel like a vacuum flask might come in on low key and they might ask you to explain.
So I was now going to say something like that. Like when you're putting something hot, it'll stay hot for a very long period of time.
Yeah, because a vacuum flask has a vacuum.
Yes,
Between
sir.
the inner and outer layer, you have a vacuum. Yeah, so remember that. Cool. So if something is insulated, it'll maintain its temperature for a longer period of time. For this experiment, two test tubes A and B were set up as shown in figure 1. Test tube A has insulation of a given thickness around it. The insulation around test tube B, which was made of the same material as the insulation around test tube A, was much thicker. So which one is going to maintain its temperature for a longer period of time?
B. Because the insulation thicker.
Exactly. They might ask us a question on that. Procedure. Hot water was poured into test tube A and test tube B, up to the level of the top of the insulation. The initial temperature, theta, of the water in each test tube was recorded and the stop clock was immediately started. Temperature recordings were taken from both test tubes A and B at a what? This is important, I feel.
30-second interval.
30 seconds intervals.
So every 30 seconds, what are you going to do?
You take the
Take
reading.
Take a reading.
Take a reading. Cool. Over a
But
period of 240 seconds. So going from 0 seconds to what?
240.
240.
Good. Let me answer the first question.
Die 8 readings.
Wait, sir. We had answer this one. A student touched the bottom of each test tube and exclaimed that they were very hot. Well, who tell it to touch it, dog? Who tell it to touch it? Right?
Those who don't hear this had
This
them
come like
please.
this come like Jeremy. This come like Jeremy and the oil. What Jeremy was doing, boy?
So
What
that
Jeremy?
is stupidity at its finest.
Yeah, boy. This is
You
Jeremy.
know what?
Jeremy touched the bottom of the each tube and exclaimed that they were very hot. State the method of heat transfer by which heat was transmitted from the test tube to the student's hand. That's direct contact. What's that?
Conduction.
Induction.
Right, conduction. Easy. Let me tackle this question now.
Oh, this is a hybrid exam.
Hybrid exam, yeah. So like you had like this handout. I make this handout. I use Claude to make this handout. Right? But you don't have something like this. And you don't have to look at the exam and write on the handout. Which make no sense. Which make no sense. How do I make any sense? But anyways,
CXC just trying to experiment.
who am I to talk about CXC? Alright, so remind me. It said every what interval?
30 seconds.
So what do you think this could be?
30.
30.
What do you think this can be?
90.
90.
What do you think this can be?
120.
This?
180.
180. The next one will be 221.
210.
210.
Oh, 210, my bad.
240.
240.
Yeah, I'll again the marks. 3 marks. 3 marks!
Of course.
Nah, they should have make that more. Like a
They
4
should have get
mark.
a mark for
Like
everything
an
you
8 mark. 1 mark for each entry.
Yo, 8 marks is for the graph. You know what? Yeah.
Right. On the grid below, plot a graph of temperature against time and draw a line of best fit for test tube A only. In the interest of time, I already give all you a scale, right? Interest of time. So, I really don't like this hybrid thing, you know. You gotta be going back and forth, back and forth. Make no sense.
At that point in time, they said they was gonna do it fully online. Things like maths and things, man, I would have cried.
Yeah, what you gonna do that online for? But anyways, we had to plot temperature versus time. Therefore, you can see temperature is on which axis.
Is on the y-axis.
Y.
And time is always going which axis?
The X.
Alright. Now we are plotting for test tube A only. I know somebody would not read this. Oh, you gotta do test tube B. I know that. I know that. Are they think I'm lying or that's true?
Lion.
I lying? Nah, that's
Me
true.
I
That's
know,
true.
sir. Me I know.
No, it's true.
So
So,
it's so
okay.
obvious.
So the first point would be 0.0, 71.0. So where that gonna be? That looking like it'll be over here.
Yeah.
Because 71 will be in the middle of what?
70 and 72.
Oh, wait, so there's gonna be like a cooling thing. Like it gonna keep going down.
Well, this is a coolant curve, so yes. But there would be no phase change. But it would be a coolant curve. It'd have a negative gradient. That's a good observation. You don't go and get distinction in physics. Chemistry too, but physics, yeah.
Thanks,
The next one is 3069. Are they lost or are they understanding?
That's we
Understand,
did,
sir.
we
Now
did.
we understand.
Next one gonna be 6066.
So what graph you think coming tomorrow?
Probably V and I.
That's actually done.
That's nice. Wait, what? Wait.
Yeah, wait, either V and I or sin I over sin R. I
Both
feel
of them straight dynamic.
yeah.
Alright.
Well, it
A
depends on
refractive
what
index
IV.
might be nice.
It depends on what IV characteristic you're dealing with. For ohmic conductor, it'll be linear. If it's
So
a
let me say
filament,
the points you give is like 0.003. I could put on the access of that like 3 to the power by 10 to the power minus 3. And let's put the whole numbers.
yes, you can do that.
Alright.
That's completely fine.
Alright.
I have a feeling like somebody knows something and they're sharing it. Like, all
I
this.
don't mean to say anything, but apparently people were
Yeah,
saying that the
yeah,
quotation.
men spinning rumors how the people
No,
getting
here, no. So I had message and I said that if I found good information, I would tell her. So apparently, quotations, because I'm studying fine out, they say the paper leak. And then some people saying that, oh, they have the paper message if it were the paper. But I'm not taking that risk because if it is the paper, I could get in real trouble for that. So
Men
we
lying,
know.
boy. Men
Alright,
lying.
alright, don't talk about on my YouTube live. Next thing I get in trouble, boy. Say I harboring some
Who says I message
physics
them?
person.
So I won't message them.
So that's why I said quotations allegedly.
Okay, thank you. Let me continue now. Focus on the physics.
Of course.
58.5, 58.5, looking like these are real funny scale cloud maker, but I will put it. 210, 56.
Is a linear graph? Well, no,
This
it's
is
not
a linear,
linear.
this is a linear graph. Anytime I see best fit, what I mean?
Linear.
Linear. And then 240, 54.
One question, sir. I overheard that you talked about I over V, right? That was with transformations or no?
Wait, I guys give me a second. I'm gonna do this first. When I say I and V, I think in IV characteristics, maybe like a filament lamp might come.
A filament lamp. Ah,
And they
okay.
might ask you to draw a best fit line for the linear region.
Okay.
But I don't know.
So I taking your predictions, or well, it
All
may
all
be
you
a
need to
come, but
all you
still,
need to think for yourself, guys. Okay, that looking like a decent best fits. Or
yeah.
like,
Yeah. I mean, it's very close to the points, though.
I think we take that.
Yeah, we could take that because it has some nice points that we could take and use for gradient if they ever ask.
Yeah.
Well, they obviously ask.
Right. Everybody okay with that?
Yes, sir.
And obviously, you know, when you do that physics graph, you're supposed to say it's your title. What the title for this could be?
Temperature test tube A versus time.
Temperature, theta, in degrees Celsius versus time. Yeah, I'm gonna follow okay with this.
And the scale. Like the box for the scale.
Yeah, you gotta put that. So in this instance, we said every one block on the x-axis, or you say 1 centimeter, let it be equal to 30
30
seconds.
seconds.
On the y-axis, we said every 1 centimeter was equal to what?
10, 5.
Not 2
Oh, my bad. 2.
degrees Celsius. Right. Let's see what's able to calculate. I tried the best fit. Cool. Using your graph, calculate the gradient g of the line. Show clearly on the graph line the coordinates used to obtain the gradient. So, like I see in this point over here, look nice. What are looking like? Somebody tell me what are looking like.
So it's looking like 150, 60.
Okay, let me look for another nice point. Could probably use this point here. They're looking like well, I see in 1, 2, 3, 5 divisions, so each division will be what?
Well, each one will be 6.
6.
So that would be 12.
So like, yeah, we 12. Let's be 12. Because watch. If you're confused, I'm telling you it have 5 blocks and each is equal to 30. Divide both sides by 5. Again 6. So then this would be what? 12, comma what?
6.
70.
No, 70, my bad.
Which one do I want to call x1, y1?
The
12 70.
And the gradient would be what? Well, here what? In this question, they want me to call the gradient what?
G. Did they? Yeah,
What?
G.
G, capital G.
People on the TikTok. I don't
So,
even TikTok anyways. But my phone dead. Oh boy.
but is it changing Y or will it change in X?
Yeah. Yeah, what we call it G, right? So I'll say G.
Yes, sir.
I'll again a mark for the right any formula, eh?
Yes, sir.
Really?
Formula
Yeah.
is very important for physics.
Yeah,
So
you
it's
gotta write the
Any
formulas
any
like
equation, any equation with maths is got a mark for the formula, substitution, answer.
yeah,
and
you need to put
units.
the formula. So
And
to find for G, that's gonna be 60 minus what?
70
Then they're gonna be x2, which is 150
150
minus 1.
minus 12.
Again, since it's a cooling, I'll like to see that this is a cooling curve. Like as time passes by, the temperature drops.
Of course.
Right? This is a cooling curve we're dealing with. Well, it's not really a cooling curve, but here what? If you had let me just give you a quick crash course, right? Let me just say that over here was liquid, and over here was solid. What this point over here is? They call that.
The change of state.
Right. This is where you're changing state. And since you change it from liquid to solid, this would be specific latent heat or what?
Fusion.
Fusion. You're right. Fusion. So I would say E is
So it's a
equal to MLF.
so it's a straight line because um you can't change temperature and state at the same time.
Exactly. That region over there is energy being used to change the atomic structure into a solid. And so there's no change in temperature there. And I would refer to this as the what point. The what point. What point is that? What point is that, guys?
Freezing point.
Nah, the melting point.
So how would melting and going from liquid to solid?
Okay. If you were going backwards, right? If you were okay, liquid to solid, right? Liquid to solid. Let's just say we're going backwards. This temperature over here is the temperature at which it would melt. Melting means liquid to solid or solid, vice versa. Vice versa. I don't know if you understand what I mean. Like there were questions before.
Yes, sir.
Okay, this temperature over here, if it was a solid, when I reach that temperature, what happens to it?
It will melt.
It will melt. Yeah, it will melt. Right? So that's the melting point. And further above that, if this is the melting, what is going to be?
The boiling.
Boiling. Right? Cool. Right, so what's the gradient, guys? Some of us.
Say because the thing about how the graph is a
so I
straight
got
line.
-5/60, so
Say because the thing about how the graph is a straight line since there's no change in state.
Yeah, there's no change in state here. And we didn't think it would happen because it's just water thermally insulated. Tom, what's our decimal?
I got 0.07.
You should get minus 0. Oh, let's tell fast. Fast.
0.7, sir.
7.
Right? And what units are we going to put? Well, to figure that out, you look at what we have on the y-axis. What do we have on the y-axis?
Temperature.
Right? That's degrees Celsius. What do we have on the x-axis?
Time in seconds.
Right. So this is going to be degrees Celsius per what?
Second.
Seconds.
Are you understand that or no?
Of course.
Yes, sir.
All right. Cool. How we do this one? What physical quantity does a gradient represent? Well, as you can see, this will be the rate at which we are what? The rate at which we are doing what to the liquid. Like I said, this was our what curve?
Cooling.
Cooling curve.
So this is the rate at which what? This is the rate of what?
It cools down to
Yeah. So this is the rate of cooling.
when they ask physical quantity, it's just what you see what the graph is doing.
Exactly. So like look at this for yourself. Every second, the temperature in degrees Celsius drops by what?
0.07.
Understand? Okay, what does this mean? This means that every 1 second passes by, the
It'll
temperature drops
drop
by what?
by 0.07 degrees Celsius.
Right, so it represents the cooling, the rate of cooling. Yeah? Understand?
Yes, sir.
The magnitude of the gradient for test tube B is less than that for test tube A. State how thickness of insulation affects the rate at which the water cools. Give a reason for your answer. Right. So, okay, so let me explain this, right? So they're saying the magnitude of the gradient for test tube B is less than that for test tube A. If it is less, and the rate of cooling is... Okay, here, I understand why I'm confused.
Lower.
Let me show you two different scenarios, right? In which
It'll be lower.
scenario is the cooling happening at a greater rate? One or two?
Say that again, sir.
In which scenario is the liquid being cooled at a faster, at a greater rate?
One.
One. So in this question, it's saying the magnitude of the gradient for the graph of test tube B is less. So if it's less, it's cooling at a faster rate or a slower rate?
Slower rate.
Slower rate. And this makes sense because if you look at test tube B, it's more what?
Thicker.
It's more insulated, yes. Yeah. So let me write the answer first. So
I could give an answer.
wait, yeah.
So I was gonna say this is what the how the thickness of insulation affects the rate at which water cools. I would say the thicker the insulation is, there's more medium to work with, and it's harder to conduct heat through a thicker medium than a thinner medium. Good.
I wouldn't. Okay, medium. I hear what you're saying. It makes sense. It makes sense. I probably wouldn't have phrased it like that.
Yeah, I know here, and I need to rephrase that.
So I go on write the answer and I'll tell me if it makes sense. So a greater thickness of insulation. See these answers here whether right, I hate it. As a calculation type of guy. A greater thickness of insulation decreases the rate at which water what?
Cools.
Cool.
Yeah. And I'll justify my answer. So like, isn't there proof for this? Like, okay, there's proof, right? Let me explain. There's proof.
So
There's proof. From 0 to 240 seconds. What was the delta theta for test tube A? Delta theta just means change in temperature, guys.
changing temp.
What was the change in temperature for test tube B?
71 minus 54.
71 minus 54. Should be 17.
Yeah. Yes, sir.
Right?
Yes, sir.
So the delta theta here was 17 degrees Celsius. What was it over here?
71 minus 60.5.
Which is 8.5? No, 9.5. 9.5?
So I get 10.5.
10.5. So here what? Guys, from this, we can make a clear observation. In the same 240 seconds, which one cooled at a greater degree?
The tube A.
Tube A.
Because there was a greater difference in temperature. I feel like right now just Nikolai and Aiden are up.
NASA still up.
Yeah, I was off.
Over the
Yeah, because
240 second span, Test tube. I don't have enough space here, boy. Claude, what you do, boy? Claude do nonsense. I tell Claude leave some space. This is not enough space. Don't know what wrong with Claude.
So Claude thinking that's space enough.
Claude, what you feel I is, boy? Oh my days. AI,
So what if
yes.
God think is AI too? What if they think you're gonna type it out?
You can't type it out on this.
Still, there's not enough space. The amount of information we have just to answer that question with 2 marks.
And the thing is, it leaves the same amount of space for everything, you know.
Yep.
This is like going on for infinity.
This is real DIY.
Yeah, boy.
Could you imagine if you could do the star question?
That would be extravagant news.
Just cover it. It's not if I can't see it, nobody could see it.
No, but these days now, they just scan it and facial all that. Which I find is nonsense, like the AI could say a question wrong when it really right in a sense.
That is, I feel like AI shouldn't be marking nobody paper, boy.
I agree.
Listen,
Also, like, what about the people, like, different people handwriting and thing too, you know?
AI can miscalculate it as something else.
AI shouldn't be correcting nobody paper. All right, so the answer for this, oh my days, it's so frustrating. Right, so a greater thickness of insulation decreases the rate at which water cools. Over the 240-second span, test tube
A.
A. What the chill had a delta theta, a change in temperature equal to what?
17 degrees.
Whereas
B is 10.5 degrees.
So
doesn't this prove that it had a it doesn't this prove that it decreased the rate at which it was cooled?
yes,
Yes,
sir.
sir.
This is an observable reason, right? This is an observable reason. Yeah, so a greater thickness of insulation decreases the rate at which water cools. Over the 240-second span, test tube A had a delta of 17 degrees Celsius, whereas test tube B had a delta of 10.5 degrees Celsius. So let them take that. All
Take
right.
it or leave it. I mean, it's 2 marks.
So I was trying to
What
fabricate
complex?
this, right?
Mm-hmm.
The increasing the thickness of the insulation decreases the rate at which water cools because heat is conducted more slowly through a thicker insulating material than a thinner insulating material.
That is correct. That is correct. You can say that.
Look
But like,
it.
that's a good explanation. But when it's a reason, okay, like you make that statement, what make him make that statement? If you understand what I mean, like what make him make that statement? Well, it's a practical example. The delta in temperature was, like one was more than the other one. That's like a reason. So you
Yeah,
you state something
that
and then you give him a reason. Part G. State two actions that the students would have taken to ensure that the temperature readings was accurate as possible. Right.
Reading the thermometer at eye level to avoid parallax.
Right. So number one, eye level.
Do not let the thermometer touch the beaker or the underneath of it.
Wait.
Not the beaker, the test tube.
That is okay because you want the thermometer to be enveloped. You want it to be
want it in the
fully in
fluid.
the fluid. So I hear what you're saying. But I feel like what I'll probably do is I'll probably give like the test tube a little shake now. A little shake to make sure like the temperature is like homogeneous. So I'd probably say probably like stir it before reading. So like stirring before reading.
Okay, makes sense.
Because like let me ask that question, right? As we know, okay, like you insulating the sides, right? Are you insulating the bottom?
No, sir.
No, so like generally speaking, the bottom is gonna be what?
At a different
At
temperature.
different temperature.
Yeah.
It's gonna be cooler, it's gonna be cooler, right? So if you stir it, then you're like making sure
It'll
the
kind of even it out.
correct.
It's
So I would
like
say stir it before reading,
osmosis. It's like
right?
osmosis until evenly distributed.
Mm, I wouldn't say,
Not osmosis, that would be diffusion.
yeah, diffusion. And I hope you understand this. This is just to make sure, this is to
The
ensure that you have
temperature
an even
readings
temperature.
are accurate.
Why is it not erasing? Oh my god. Ensure an even temperature. Sure.
So tonight you actually make me like physics.
That's good. That's good. That's good. Love to
Like
hear
I
that.
good in it, but I never enjoy it, but I enjoying it.
Same
To
here.
hear that. All right, part H. Suggest two improvements to the apparatus or procedures to ensure the investigation is more reliable. Okay. Should he use different test tubes?
No.
Okay, if you want to get a very accurate reading or a very accurate experiment, wouldn't you want to have okay, the only factor you should have manipulated was the insulation. Everything else should have been what?
The same.
The same
Same.
constant.
So what I would say is I would say use identical what?
Test tubes and thermometers.
Right.
Okay,
And
yeah.
I'll probably fed up here this, right? You could do multiple experiments and just take average.
Yes, sir.
Yeah.
It
So I
also.
was gonna say carry the experiment for a longer period of time.
So does the
To
height
get a
matter?
say that again?
Does the height matter?
Not really. How you say that? How you say that?
Okay, so like when you have a thing at a specific point, air rises, cool air falls, so like different degree, like different temperatures in the atmosphere would change.
Yeah, I hear what you're saying, but like we sealing this thing off. It's sealed off.
Oh, it is sealed.
Yeah, it's
Okay.
sealed.
But it's sealed with the stopper.
Right?
Aye.
Yeah, you could carry out experiment for longer duration, because if you carry it for a longer duration, you get to see a more conclusive result.
That's
Yeah,
true.
everybody
Because you
okay
have
with this question?
more
So
yes, sir.
Yes, sir.
Yes, sir.
um so distinguish between gravitational potential energy and kinetic energy. Right, first things first, what's the difference? Like with formula.
For kinetic energy is Ek is equals to a half mv squared. Gravitational potential energy is the height by gravitation by the mass. No,
MGH.
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 Right.
MGH.
EP. Right. Yeah. Cool. Now, kinetic energy is the energy a body possesses by virtue of its what?
Movement.
Motion.
Motion. Yeah. Yeah, motion. Movement is just something. Is like normal something. And the potential is
The
generated
energy
kinetic
in
energy.
relation, the attraction due to gravity.
Um, I I would more so say it's the energy stored in an object due to its position in a gravitational field. Because like
That sound more like it, yeah.
because
Yes,
like
sir.
on Earth, we have a gravitational field because of the core of the Earth.
9.81.
Yeah.
Is
So
it 9.81?
say that again?
Roll it off to 10 for the gravity.
Yes.
Yeah.
10
10 ms
ms.
minus 2.
Yeah.
We just round it off. So I would probably say energy stored in an object
Due to its position.
due to its position.
In a gravitational field.
Yep. Cool. Now you could add this if you want. Kinetic energy increases if the object what?
Object motion increases.
Nah, look at the formula, right? If V increases, what happen?
The mass increases.
Nah. If V increases, then the final answer will be bigger. So this would
course.
increase. So this would
Yes, so like,
increase when velocity increases.
So you're saying basically if it faster, it will move more.
Well, yeah, like it'd be harder to stop. Right? Because this is the energy our body possesses by virtue of its motion.
And for EP, you'll say the higher it is, the more energy you have.
Yep. So I would say increases as height increases. Everybody with me so far, like, are they confused?
Yes, sir.
Yes, sir. How many marks also?
3 marks. You don't have to put all of that, you know. I would advise you to put the formula and just state what it is. Right? But I give you a good answer there. A baggage handler at an airport lifts suitcases from the carriage that brings them from the plane and places them on a conveyor belt. The moving belt then transfers the suitcases to the passengers. Figure 3 shows the position of the suitcase at different stages of its motion. So, okay, initially, right? Okay, if it is on the ground, the potential energy is what?
Zero.
Zero. Nothing
At
happens.
rest.
Potential energy. The potential energy is at 0, and the kinetic energy is what?
Zero.
Zero as well.
Because is it moving?
No,
Nah,
sir.
it's at rest.
What's it? I understand that. Like, if something is okay, if something is on the ground and its height is what?
Zero. Well, it could be
Zero.
0. So mass by gravity by 0 is just 0. And if it's not moving, its energy is what?
zero as well.
Zero.
Exactly. 0 as well. Okay, if you lift it up now, what is going to increase?
The gravitational potential energy.
So EP is going to increase. All right, so EP increases. The kinetic energy. If you take it and you move it in this position, is it moving right now?
Yes.
Technically,
Yes,
yes.
sir.
Okay,
Well,
so like,
the height increases. Well, the height has
okay,
changed.
hear what I'm saying, right? So like, yeah, we move it at some point, right? Move it
Yeah.
at some point. But like, you're holding it there. You're holding it there, right?
If you just hold it still, then they wouldn't have any
Right.
kinetic energy.
So you could say while it is moving, the kinetic energy increases, but once it's held at that position, the kinetic energy goes back to what?
Zero.
Right? But here what? They're talking specifically about B. So that implies that it's already moved there. So if it's already moved there and it's at B, it's not moving right now. So technically speaking, EK is what?
Zero.
Because it's not moving right now, right? It's not moving right now. And the baggage handler then places the suitcase on the conveyor belt. Right. So K, B to C. Right, any suggestions? Oh wait, let me see what they ask. So describe our total energy at position A compared to the total energy at position B. So A to B. Okay, we answer that. The suitcase is at rest on the ground. If it's at rest on the ground, we said that EP was equal to 0 joules.
Zero.
And EK was equal to 0 joules. Then they're saying describe how the total. Okay, so we answer that. And now we have to compare it with the total energy at position B. So over here, this was for what? This was for what?
Position A.
Right? At B now, EP increases and EK is still 0. You understand?
Mm-hmm.
Now, describe how the total energy at position D compares to the total energy at position C. So we're comparing D versus C. Okay, not a problem. Right. So at position C, it has just been placed on the conveyor belt. Okay, so it's placed on the conveyor belt. Did it move as yet though?
Nah, so
Nah. Let's see, did it move as yet?
if it only conveyor belt, will EP still be the same or 0?
Well, the potential energy. Well, okay, let me ask you that question, right? If I place the suitcase on a horizontal surface and it's now on a horizontal surface, what is EP?
Will be 0.
Because it's like on something, it's on a
Because
surface.
it's not suspended in the air or anything.
Exactly. Right?
So it can't fall. Yeah, I understand.
Right. Okay, so how would we describe this? So let me talk about C first. So at C, I just placed the suitcase on the stationary conveyor belt. I haven't seen it moving as yet. So placed on stationary. It's not moving as yet. And so tell me what happens to K. So what would
EP
happen
0,
to
EK 0.
well, yeah. But like you see the EP parts? Kinda on the fence about it. I kinda on the fence about it. Let me explain something. If let's check this, right? I think it will still have EP. If this is me about to jump off this cliff, because earlier, right?
Whoa.
What kind of energy do I have here? Even though I'm standing on ground, what kind of energy do I still have?
0.
Potential
Oh,
energy.
yes, sir.
I still have potential energy. I mean,
Because
I'm on the ground.
because of the
I'm on
height.
exactly. So like, yeah, we can't say EK, we can't say EP is 0. You understand?
Okay.
Because we don't have a value for it.
So here we go see. EP is the same
as B.
Because I'm asking that question. Did I change the heights?
No.
No, sir.
EP is the same as B. Is it moving as yet?
No.
No,
So
sir.
EK is 0.
Because it didn't
No.
move as yet. Not moving.
Mm-hmm.
Yeah. So like you have to be careful. You have to be careful. Like even though it is on the conveyor belt, it's still some distance away from the ground. Understand?
Mm-hmm.
Okay. And from C to D, what happened?
There is movement. The
So
height has changed. The potential energy change. Well, the EP actually.
no.
Yeah, well, the
No.
height is not changing.
EP
The
remains the same, but
Yeah, it
the
remains the
kinetic
same.
energy changes. The
So
increase.
again, I would say that EP is the same. But however, since it's now moving, so they're saying the suitcase slides on the conveyor belt and is picked up by the passenger. So it's sliding, it's moving. If it's moving now, what would it now have?
Kinetic energy.
EK increases as suitcase what?
Movement
Is
increases.
moved by the conveyor belt.
I feel like it's only all week, you know.
I feel so.
Yeah.
Tamale still here, so.
And so I'm multitasking. I listening to you and taking in this and the notes from the 17-hour marathon. I reading that.
Nice. Big up you. Big up you. So let me know if you understand this.
Yes,
Of
sir.
course.
Yes, sir.
Right, so C. I placed on the stationary conveyor belt. EP is the same as B because it's still the same vertical height. EK is 0 joules, so it didn't start moving as yet. At D, EP is the same, but EK increases as the suitcase is moved by the conveyor belt. Right, I wouldn't say this was a hard question. This was a hard question.
That's marks we have.
Sponge cake.
So we would have answered 1 and 2. Okay, a calculation question. Let me go. This is my time to shine.
Of course.
Right.
You mean it's our time to shine?
Sorry.
In maths, vibes out maths.
Sorry. As soon as I see a calculation question, I get excited. You know what I mean? Me, I like them writing questions. I'm writing questions, Loki buns.
So I look prefer the
Especially
writing
when it's on
questions.
6 marks writing questions. Nah, burn that.
Yes, sir.
So here what, Aaron, they're saying the motor lifts the luggage with a current of 5 amps, a voltage of 110, and a time for 2.5 seconds. So when I read this, immediately, I thinking about V is equal to IR. I don't know if they ask us that though, but like I got ready for me I'm thinking about. I see in V is equal to IR because they give me current and they give me voltage, right? So I could find
V is
resistance.
current. V is current by resistance. Okay, cool.
I also
They
see
give
in
us time.
they also given us current and time, what we could also find for.
Coulombs. Q is IT.
Charge.
Q equal IT.
And we could also find energy. Let me explain. I want to just remind you guys about something. Power is equal to what? What over what?
Energy over time.
Over time.
So if I were to make energy the subject of the formula, I'd multiply both sides by
T.
And energy will be what?
Power
P
by T.
equal P times T.
Good. I think we have everything on lock. I don't think they could bring anything that would confuse us. Calculate the electrical energy transferred to the motor as it lifts the mass. So they want us to find for energy here. Not a problem. Is there a formula we looked at that has energy in it?
Yes, sir.
Yes, sir.
Right. So energy is equal to power
By
by
time.
time. Now let me ask a question. For power, they're giving us current and voltage. So is there any way I could find for power?
Yes, sir.
Yes, sir.
It's IT. IV.
IV. Good. So the power, all you should know, you shouldn't have two equal signs, but I just write in this because I kind of lack in space, right? Chlora again.
Sir.
The current is 5.
To make
So
up for that, when you put the equal sign.
Let's breaking up there.
550.
500, 550. And that'll be in what?
What?
Watts.
It'll be in what?
Watts. Power. So that'll
In
be
what?
550 by what? Power is measured in watts. Power is measured in watts.
By
Watts.
Whole watts. Watts. And time is 2.5.
So
2.5 seconds.
plug in take
552.5. Oh, no, sir. No.
1375.
Yes, 1375.
Oh, so what I was saying was when you like me, like the same way how you put it, and we're not supposed to have two equal signs. On the second equal side, I just put like a little arrowhead.
Or like this.
Yeah, so I just showing what steps I was going.
I just do that too.
Oh, they should have enough space in the exam, right? Let me continue.
Of course.
The motor lifts a 30 kilogram suitcase to a height of 75 centimeters. Calculate the gravitational potential energy gained. First of all, what's the formula for EP?
MGH.
Right? MGH. Of course, The mass needs to be in kilograms. The height needs to
Yeah.
be in what?
Meters.
Meters.
So I'm going to divide this by what?
100.
100.
And I got into what?
0.75.
0.75.
I will have a dread conversation with Claude. I'll tell Claude you didn't leave enough space. I waste my
And
time.
they get the kg.
And
30.
well, and we know gravity is, should I give you that somewhere?
It's 10
Gravity is 10.
ms.
They didn't specify that though. Typically, they didn't specify it, you know.
But it's another
Like,
thing you must know.
It could be either
like
9.81 or 10.
Like here, what CXC usually specifies it. They go tell you they use 9.8. Like you know in maths, you go tell you to use pi as 22 over 7.
Oh,
Like, yeah, it's that kind of thing. That kind of thing. But I'm not seeing it
but
now.
if it unspecified,
You
should
10.
it
You 10.
default to 10?
Should default to 10, yeah. And well, we know that G is equal to 10. 10
30 by
ms. So it's gonna be equal to the mass. The mass is 30 kg. The gravity is 10 and the height is what?
10, 0.75.
So what we're gonna get. Had so much people energy, you know, when we started past paper, like I don't know what of them went.
I get 2.25.
2.25. No, I get 225.
Yes, sir. I got the same thing.
I can double check.
Yes, I get that too.
Right, so here what? We had to calculate the efficiency of the motor. So let me ask you a question. How much energy, how much energy was transferred to the motor to lift the mass? How much energy left?
225 joules. Is it?
1375, right? 1375.
Oh.
How much was actually used? How much was actually used?
The 225.
225.
Okay.
So if you want to find efficiency,
Will it be the difference?
No, it's like the percentage, sir. Is it?
That's it. It's going to be right. So here what? What was the total energy we consumed to do this?
1,375.
And what was the useful energy? Like, oh, what did we actually
225.
225.
So was that symbol?
Efficiency.
Oh, okay.
Like, again, to the habit of using that, I will show you what I mean. I will show you something. So, like, when I doing thermal calculations,
So unfortunately, I have to clock out.
what? Wait,
Yeah.
Way bye.
Well, so I had to go at a certain time. I had to wake up to revise this physics, sir.
Wait. All right.
Yeah, it was nice though. I enjoyed the class. It was very helpful.
That's good to hear.
I get to talk to new people, although they kinda on the scene here, but I got to
Wow.
again.
Nicola, you toting feelings, okay?
No. I
Yeah,
wouldn't be
so
crying. I
I
wouldn't be
wonder
crying, but
what led you to that.
hey.
Speak. Peak reference.
Good luck, everyone. Well,
Good luck, Nikolai. Go get some
Yeah,
rest.
of course, you too.
Good luck.
Let me get back to this. Finish this first. Keep on along, you know.
So, what you just take for these late nights? Like, you take any, like, medicine or anything?
Not to take anything. I literally just don't. Like, look,
Serious?
YouTube, we're not talking about substances.
Look at this. I just look at this and I just tell myself, I can't feel. I just
So
tell
I have
myself,
a book. Let me look for it. On the front of my book, I have a quote. Hold on, wait.
So, I
It
be
says,
free, I nearly fall asleep in the maths exam. I asked the examiner, I want to splash my face with water. That actually wake me up, you know, honestly. And when I reach home, knockout cold.
I have a nice
Imagine
quote.
physics was in the evening, no. That'd be nice if
Hear
physics was
this,
in the
right?
evening.
I have a nice quote for the people that are weak. Studying now is better than leaving the examination room wishing you studied.
that's a good one.
Yes.
Honestly, I like this night studying also. When I study the night before I go and sleep, it's tend to stick in my brain.
It's
Also,
all right.
I have a short-term memory. That's what I found out.
Nah, you sound like you're real smart. You sound like you're real smart. I feel like you don't underestimate his abilities. So let me continue.
The answer is 16.36.
Percent.
Yeah.
16. Badness. So here what's again, right? What was the total energy I used for this process? What was the total energy I used?
1375.
1375.
Out of that, what I actually use?
The 225.
225.
So like you would see the formula. There's like a tertiary level symbol. I guess of course I'm using it in thermal physics.
So
I mean, it's
how
like
form 6 physics is
fun. It's fun. If you want to write the
fun
actual formula, it is useful. It's useful energy
over total energy used.
output all over total energy input. Multiply by what?
100 over 1.
Right. And this makes sense logically, right? It's the
Yes.
amount you actually use over the total amount. Easy. All again, this marks, right?
Of course.
Of course.
Right. Claude, I can do this shipping this forward.
So don't puff up Claude too much. Claude is love you and help you plenty.
True. Although, I really will this thing fast now. So what do I call this chat? What's the name of this? This is the what?
The soft iron core.
Soft.
iron core.
This is our what?
A resistor.
State resistance.
Whoa.
A fixed resistor.
No.
Yeah, a fixed resistor.
No, this, my friends, is our fuse.
Oh wait,
Fuse.
the line going through it, you know. I don't
Yeah,
see.
so like if we're using too much current, this is why I go burn and I go break. It will heat up and it will
And
break.
then when it burn, you can't use it back. You gotta fix it. You gotta replace it.
Exactly. So that's our fuse. What is this?
AC.
AC supply.
Right. This is the what? What side?
The primary.
Primary.
Coil.
Say primary winding as well. This is the what?
Secondary.
Winder or coil.
Question. Is it looking like a step up or a step down?
Step
A
down.
step down.
Step down.
Yeah, because like the number of turns in the secondary is less. Can like a step down, if you ask me. Right? Explain the meaning of alternating current. What I mean, guys, we do have plenty times.
The current changes due respect to time.
Right. It changes periodically. I go with that. Right? So I want to write a really good answer. It is an electric current
That changes periodically.
that changes direction.
Periodically.
Okay, that only gonna get that 2 marks for sure, right?
So I be doing them same thing.
Yes, sir.
Yes. Yeah.
Adding one set of words and definitions.
It's all posh.
Yeah.
State 2 features of the core of the transformer. Alright, so we know about this. What allows me to channel the magnetic flux created by the AC waveform? The what?
The soft iron fluid.
Yeah, the soft iron core.
Soft iron fluid.
So I'd say the core is made of soft iron. This is the scrappiest I ever write in my life. The scrappiest.
So you right-handed?
Yeah, right-handed.
Yeah, I could tell. That's not a bad thing. That
What
is
that's
not a
supposed to
bad thing.
mean?
It's
Well,
not a. Hold on, let me clarify. I am ambidextrous, so like, so over time, I just know if somebody right-handed or left-handed.
ambidextrous for those of you guys that don't know if you somebody that carry both hands.
Well, I
Yeah,
left-handed. I don't like to be left-handed.
I could write it both, but I prefer my left hand. Not only that, people who right-handed, naturally, because the way they have to move the hand, the letters just come kind of slant.
Right, so the core is made of soft iron. This channel is on concentrating magnetic flux. That's the simplest answer I could see for that one. Wait, this is another one. I never told you this before, but the core is actually laminated. And
Isn't it laminated with graphite or something?
no.
No.
Okay, so it's
Why
like
I
though?
think it was something else.
to avoid eddy currents. To avoid eddy currents, you can look that up.
Okay.
And all right, I don't know if you're seeing what I'm talking about. Like, is it like one big
It's
block of?
shiny.
Is it one big block of soft iron, or is it like a bunch of plates?
It's a bunch
Plates.
of plates.
A bunch
Bunch
of
of
plates, right?
plates.
Very thin plates.
And these are laminated.
Ah.
Mm-hmm.
My room is just like a whole electrical lab.
Funny enough, because I'm cadets and I dealing with planes, you know those RC planes on them?
Yeah,
I actually made a few, but I don't have them here.
that's actually really cool. Like you send it to me. Like I want to do some physics projects, like with students.
Cool.
Actually, some like cool physics projects. Not like basic stuff that kind of boring, but like really cool stuff. Like surely I want to make really cool stuff.
Mm-hmm. If you like technology, it have something called a cyber deck, which is basically a mini computer from old parts. You could make that too.
I see that. That's so
Okay,
cool.
you know real ball boy. You know about the Raspberry Pi?
Raspberry Pi, I was
That
about to
is
say
it.
so.
That is it.
You know like a
Linux.
Arduino. You know about like a Arduino Mini?
Yes.
Yeah. I mean, I literally do my bachelor's in electrical engineering. We had to like make our project with that.
I
Well,
want to do
not that.
electrical. I wanted to do electrical engineering, but studying the money and the schooling, so I don't mind doing teaching.
Money is not a problem because you know Gates will fund you. Yeah, but if you fail courses,
True.
you fail courses, well, as on you. Yeah, boy. Right.
Yeah.
Right. So part two. Another property is the core.
Is laminated.
Laminated.
Why is this? And what does this mean? That means that it is made of. Is it one big block of metal?
It's
Many.
multiple
No,
sheets.
multiple plates.
Right, made of thin
Stacked plates.
of iron insulated from each other. Right. And well, I mean, if you want to like be extra, you could say reduces eddy current losses. Right. So just why the transformer is classified as a step-down transformer.
Because
Guys,
the number of primary cores are more than the number of secondary.
that's it. That's it. Number of turns. Guys, if you want to be like real like straightforward with it, you could just say NS is what?
More than N. Wait, what? No, less than NP.
Yeah. So let me take that. Let me take that.
Is
NS is
one
less
mark.
than. Yeah. Describe how the output voltage is induced in the secondary coil. I don't have enough. I gotta make space. Come on a second.
So funny enough, normally by now, it is knockout. Every time when you're doing the last topic, I knock out. And I start to go back and watch it. But weirdly enough, because I enjoying this up and awake.
I like that. I like that. Physics is vibes, you know. Physics is real vibes on it.
Physics will sleep.
Physics one is one of the cooler subjects because you can actually apply it in your life. Maths, I mean, you literally applying maths everywhere over here, but you don't like that. Right.
So the only maths that I actually apply You know the question where they tell you had to find, like, when you're trying to buy the better deal on something. I was trying to
Oh,
buy a coffee and I was trying to find the volume of that for 1 gram.
oh yeah. Let's do that too. Let's do that too. So I got right answer fast. So like describe how the output voltage is induced in the secondary coil. All you gotta know. Are we dealing with our alternating current source, so that will produce a change in magnetic flux. And because there's a change in magnetic field or magnetic flux, it's going to induce a current in the what?
It's used to.
In the what? So like, okay, again, it's alternating current means that the direction of the current is changing. If the direction of the current changes, then so will the direction of the magnetic field lines, and this would produce a change in magnetic flux experienced by the secondary coil, which would induce an EMF in the secondary coil.
Yes, sir.
All right. So
It's used to.
yeah, you know.
So we had go through Transformers in this life. I'd leave for a little bit, then I came back.
Yeah, we did.
Okay, I had to watch that back then. I'll if you this topic, but I'll just review it. I'll be alright.
Should be all right.
Sir,
Just
what
looking
time
straightforward.
What time?
you're ending the life, sir?
When we finish this paper.
Okay, sir.
Right, so the alternating current in the primary coil creates a continuously changing what you done. Since it's alternating current, here what you done, right? Here what you done. Here the full thing. Alternating current means that the direction of the current changes every so often, right? Periodically. And if the direction of the current changes, here what? Anytime you have a current flowing through a wire, around the wire, you're gonna have a current. Well, you're gonna have a magnetic field around it. Watch. So like is in your right hand grip rule, you go see the current, right? This is the direction of the magnetic field.
Of course, sir.
If I
Yeah.
switch it around, watch, you see enough?
Yeah.
Like the direction of the magnetic field changes. So what I'm saying is, if there's a change in if there's a change in magnetic flux, watch. Watch this fast. That cotton the what? What that cotton? Cotton the what? So watch. You have an alternating current in the primary coil, and this is going to
Yeah.
generate a magnetic field.
Mm-hmm,
And that
yeah.
cotton the what? What that cotton?
The
Like you literally cutting it.
yeah, because in the
Cutting
other
the
one.
It cut
Yeah.
in the windings in the secondary coil. And
Yeah.
because it's an alternating current, the magnetic field is gonna change. And anytime you have a change in magnetic flux, you have an induced EMF. So we just had to write that now. So the alternating current in the primary coil creates a continuously changing magnetic field. Right? In the soft iron core. So the alternating current in the primary coils create a continuously changing magnetic field in the soft iron core. Cool. I hope I understand that. And we should know that the magnetic fields generated is going to flow, is going to be channeled through the soft iron core because it has a high magnetic permeability. Meaning it's going to let the magnetic field pass through it very easy. Like okay. Essentially the magnetic field lines are going to prefer passing through the soft iron core as opposed to air. That's what I'm saying.
Yeah.
Because it's more permeable for the magnetic field lines.
Yeah.
And then we're gonna say this change in magnetic flux, right? Links with the what coil? So you have a change in magnetic flux, and I will interact with what coil?
The secondary one.
Exactly. So this change in magnetic flux links with the secondary coil. My days. And by Faraday's law of electromagnetic induction, induces an alternating EMF across the what? So guys, since we have a change in magnetic flux being experienced by the secondary coil, what's gonna be induced in the secondary coil? I think everybody's sleeping, you know.
Repeat
No,
what you
I'm
said.
thinking, I'm thinking.
Right, so this change in magnetic flux links with the secondary coil, and by Faraday's law of electromagnetic induction induces an alternating current across the which coil?
The secondary coil.
Yeah.
So they just not my favorite topic.
I understand. There's a lot, lots of prerequisites here, I don't know. Given the output voltage is 6 volts, calculate the number of turns on the secondary coil. Okay, let's write the information given to us. If we're talking about the output voltage, will that be in the primary side or the secondary side?
Secondary.
Secondary.
So
Secondary.
VS is 6 volts. Earlier in the question, they told us, well, they told us that they told us, we know that
That VP.
VP is, what's VP?
240
240.
voltage.
240 volts, and we know that the number of turns in the primary is
8,000.
800. 8,000, yeah, my man.
8,000. So this is what we have. Is there any formula we could think of with VS and VP and NP that we could use to find number of turns in the secondary? So we had to find for NS.
NP over NS equal to VS. I mean VP over VS.
Yeah, you could use this, or if you wanted, you could use NS over NP. Either one is fine. NS over NP is equal to VS over VP. Either way is fine. Either one works. Bro, good notes. Try to cooperate with me now.
So
Which one
stop
looks
buffing them up. They work for you.
that'll work better? And so which one I want to use? NP over NS or VS? Same thing. Which one I want to use?
I say the first one.
Second one.
Can I use the first one? So where's NP? I just put something both.
8,000.
So let's say 8,000 all over.
NS
Don't know what that is.
equal
To
sec
two,
what 240
240
over
over 6.
Where's 6 over 240, chat?
40.
So we could cross multiply first. So I cross multiply, gonna end up with 40 NS is equal to what?
8,000.
What do I do next?
Divide 8,000 by 40.
Oh, yeah.
200.
200.
yeah 200.
So NS is 200.
Yep. Well, you find that was hard?
Nah.
No sir.
That was not hard. That was not hard at all. Right. Now we move on to this fuse question over here. What is the function of the fuse? You have a fuse in the primary coil. What's the purpose of that? Okay, for those of you guys that don't know how our fuses do, in the event they have a short in your circuit and there's excessive current draw, the current will pass through the thin wire in the fuse, and if it exceeds the rating, the wire inside the fuse will melt and it'll break, preventing the flow of current if the current is exceeded. That's what it's doing. So it's really just there to protect the device. So what's the function of the fuse? Protects the circuit.
That's basically when like current trip, except it's not like a
from excess
breakaway
current.
could put it back on.
Right. It protects the circuit, right, from damage caused by excessive current. Right? And we're talking about like overload. So like let me just say overload the transformer. Transformer will get hot. Transformers have ratings. Overload or short circuit. Right. If you want it to be extra, if the current is exceeded, what happens to the wire inside the fuse?
It would burn.
It would burn.
And you'll create a what circuit?
A broken circuit.
We typically say open circuit.
An open circuit.
If the current exceeds the fuse rating, it will melt and create an open circuit. So easy paper so far. Real easy. A current of 150 milliamp flows in a primary coil. Okay, so they're giving us IP here. And that'll be 150 by 10 to what power?
Paper 3.
3? Yeah, sure. It's milli. It's milli.
Minus 3.
Minus 3.
And that's in primary, right? Assuming the transformer is ideal. If it's ideal, then the input power will be equal to what?
The
output.
Oh,
I remember that.
Right, good. So here what? They want me to find calculate in amperes the current through the secondary coil. No problem.
So we find an IS.
Now you have to take your time, right? So it goes like this. VP over VS is equal to what? Don't mix it up.
IS over VP. I mean,
IS. Right. Well, VP over VS, we know that is what? What is VP over VS? I just
40.
that's 40, right? That's 40. IS, we don't know what IS is.
IP is 150 times 10 to the minus 3.
So you gotta multiply both sides by what?
150 times 10 to the minus 3.
And they're gonna give you IS. So IS is gonna be 40.
40 by 158 times 10 to the minus 3.
What do we get?
I guess 6.
Well, you get 6 ohms.
Yes, sir.
Now let me look at this intuitively, right? In a transformer, okay, diagram not here. Here what, right? If you're lowering the voltage, right, what would have to increase consequently?
The current.
And over here the voltage is more, but the current is
Less.
right. And we saw this because they told me, or they tell me that the current in the primary is 150 milliamps, but in the secondary is what?
6 amps.
Right. So if the voltage decreasing, the current will rise. Vice versa. So if the voltage is increasing, the current will drop. And if the voltage dropping is a step down. Okay, and if the voltage rising is a what?
Step up.
Step up.
Right, step up. Draw the line from each type of electromagnetic wave to match it with its use.
This is more my style.
Okay. So gamma rays. What are looking like?
Oh, the last one?
Last one, yeah.
I think gamma. I was think gamma. I was think
Grammar.
like cancer or something. And cancer is
So,
medical.
but I thought that was X-rays.
Yeah, but you could also use gamma rays. Yeah.
And that's how Bruce Banner turned into the Hulk.
Yeah. So like that's what Bruce Banner turned to the Hulk, like he said. Microwaves. What would I use microwaves for?
The communication.
Satellite communication.
Yeah. I didn't know that stuff, boy.
Infrared is
Thermal imaging.
Thermal
Thermal,
imaging, and I'd say
you
ultraviolet is the fake
ultraviolet,
banknotes.
Yeah. I mean,
yeah,
is
yeah.
it
UV.
use it, right? You literally use it to detect
Is
fake
it UV
banknotes.
like black light as well?
Yeah, let's call it
What
that.
they call a black light?
Yeah. I have one now. I've like a bunch of UV lamps. Just like chilling.
So wait, what the extra one for? It's just the
It's just there.
optical.
Confusion.
To throw us off.
CXA love to make you
Watch.
overthink.
It's really lamp.
Exactly.
Yeah, so them I don't think
Wow.
about. I just always wonder how then this thing is be purple, but they say how the sun does emit UV rays, and the sun white.
Sun
This
isn't
one
white.
white?
Sun not white.
Neil deGrasse Tyson said the
Okay,
sun
never
is
use that.
white. Neil
Hey,
deGrasse Tyson said if the sun was yellow, snow would have been yellow, and snow reflects light. The sun is white, emits white light.
Well, the visible light it does emit is white light because it's a spectrum. RGB is on a spectrum. All right, figure 5 shows circular wave fronts. Okay, this is a nice question. We did this question already.
Oh yeah, they're
I did
fool.
this question already with my glass. So guys, figure 5. Okay, we nearly finished, Nearly finished. Figure 5 shows a circular wave fronts produced at the center of a wave pool. Two paddle boats, P and Q, float on the water in the pool. Boat P is on the crest of a wave at the instant shown in figure 5. Let me explain something. So, crest is the watery waveform. Top or the bottom?
The top,
The top.
And lazy what?
the
There's a
trough.
trough.
Now, what type of waveform has crests and troughs? Transverse or longitudinal?
Transverse.
Transverse.
If you all remember, if you watch my video,
Longitudinal is a series of compressions and refractions.
right? And
Correct.
compressions would be areas of high pressure or low pressure.
High pressure.
High pressure.
High pressure.
Right. A little impressive, boy. Okay.
Appreciate it.
So I used to drill railways.
That's good.
I hated waves.
Yeah, that's why I drill it.
So here, the first thing that we want to do is define the wavelength. The wavelength is just the distance
between two successive
trough.
crests or two successive troughs.
Right.
So you don't write it out. You don't write it out.
So wait, what would be in like terms of a longitudinal wave?
Just like the same thing, but for compressions and refractions.
So the distance between two successive compressions.
Or two successive refractions.
All right.
So I have a question, right? When I say successive, do I mean like here to here? You mean
No,
that?
so right after
No, sir.
Well, for some funny enough, I find this looking like
the deep. The deep.
So hold on, let me screenshot this. Hold on.
Rest in peace, the deep.
Right, I got
That finale was crazy.
Look who this look like? The one villain from SpongeBob earlier.
Mermaid Man.
Man
I forget his name, Man Ray.
It looked like him, eh? It really looked like him.
So you just need two little the little ears. Yeah, I didn't see it.
Mm-hmm.
Yeah, boy. Artist, I was actually drawing. I was showing my drawing today. But this and this would not be a successive crest. The successive crest for this would be here.
Yeah. Smiley face.
right? And if we're talking about two successive troughs, it'd be here to here.
Yeah, the frowny face.
Cool.
Cosine.
And yeah, cosine and sine. Big up the advanced people. Is sine. Is cosine. Period. Where's that period?
The time it takes a full oscillation.
Alright, the time it takes for one full oscillation. Bam.
Sine lambda is the symbol for wavelength.
Yeah. And
That
capital T is
that
period.
equation you said during
Yeah,
this
yeah,
meeting,
yeah.
I forget what it. Something
V
what
is equal
if
to
you use
what?
F lambda.
Yeah,
F
boy.
lambda.
Peak boy, big up yourself. And
F is
T is equal to what?
frequency.
Well,
1 over
1
F.
over F.
and F is equal to
1 over T.
1 over T.
easy peasy, lemon squeezy. You know what they say, let's go. Alright.
Of course.
If you want, you could say that this is measured in what? If it's wavelength, it's measured in what?
Meters.
And if it's period, I'm measured in what?
Seconds.
Seconds.
Bam. Boom. Real easy thing, right? Real easy thing. Using figure 6 and or other information, calculate the period of the wave. There we go. So before we do anything, I think we could find the wavelength for this.
Yeah, of course.
Yes, sir.
What are wavelength looking like, chat?
7.
6.
5 is looking like
3.
6.
Yeah, that's 6.
11.
Five.
11 minus 5, 6.
Yeah.
Huh? Oh, yeah.
It's clearly 6, guys. Clearly 6. And if you have trust issues, you could always check it here too. What's the difference between 2 and 8?
6.
So I realize people that do in science have a lot of trust issues.
Yeah, they do.
Wait,
They
wait,
do.
physics.
So, like, Ole, when I do an exam for NUE, I just plug in 1 plus 1 into my calculator, no? Telling you.
I just put everything in my calculator.
I don't want to take any chances.
Now why
It
paper
is a
one
bit
so
safer
scary
than
for
sorry.
now why maths paper one is so scary, you know.
No calculator to rely. But I'll show you tricks, don't worry. Show you tricks. Right, part 2. Yeah, we had to figure out the period, guys. We had to figure out the period. So here what? In the question, they said the wave takes 0.95 seconds to move from boat P to boat Q. This is a very, very important information. So to go from here to here, how long did it take?
0.95.
0.95 seconds.
So if it takes 0.95 seconds to go from there to there,
You
tell
double
me,
it.
guys, tell me, what is this distance from here to here?
Half.
That's
half a
Yeah,
wavelength.
3.
That's 3, right? Now 3
3.
is half of the wavelength. So like if you wanted to find for a full waveform, you gotta multiply that by what?
2.
2.
Oh,
You gotta multiply this by 2.
you get the
So
6.
the period, that's just gonna be 0.95 by what?
By 2.
What are we getting for that?
1.9
1.9 what?
seconds.
Seconds.
Yeah, seconds. Now they want me to find the frequency of the wave. Bet. We know V is equal to what?
V is F
F
lambda.
lambda.
If I make frequency the subject of the formula, that would be what?
F equals
So you gotta divide both sides by lambda.
V over lambda.
V over lambda.
Now, here what? You know how to do all that, eh? I'm not realizing this doesn't make any sense. If you want to figure this out, remember, frequency is 1 over T, guys.
1 over T.
Oh yeah.
So that'll be
1 over
1
1 yeah.
which is
1.95. I mean 1 point yeah, my bad. I thought the seconds was half 5.
well again 1 over 1.9 is what?
0.53.
Yeah, 0.526. Yeah.
0.53.
Yeah, to 2
Yes, sir.
decimal places.
Hertz.
Right. Remember, frequency is measured in hertz.
Mm-hmm.
Every time I see this, I just remember that one Machine Gun Kelly and Camila Cabello's. When it hurts, but it hurts
MGK.
good, can you?
MGK. That's the guy
Yeah,
who's like 30, but he's look like 19.
yeah. The one that have beef with Eminem. You know who I'm talking about.
Oh, I know that. Oh, yeah, I know you're talking about.
Yeah,
That's some crazy beef.
yeah, crazy beef. I kind of relax right now, you know, like these questions too easy, bro. Too
Of
easy.
course.
Too easy.
So
I
somebody on
don't know.
YouTube asked why I
The
multiply by 2.
All right. So the period is the time it takes for one full what?
Oscillation.
Right.
Oscillation.
Now, one full oscillation happens from one crest to another crest. So one full oscillation is how much how much meters? So this is one full oscillation, right? This is one full oscillation, and one full oscillation is how much meters?
6 meters.
Meters?
6 meters.
6 meters.
6 meters, right? And the period is the time it takes for?
One full oscillation.
So yeah, what I was saying now then. One full oscillation takes place over what distance?
From one
6.
crest to another,
Right,
which would be 6.
6 meters. In the question, it told us it took 0.95 seconds to move from P to Q. So to go from P to Q, that took 0.95 seconds. Now, coincidentally, that's actually what are the wavelength?
Half of the wavelength.
Half.
Yeah, watch. So we know one full oscillation takes place over 6 meters. This is 0.95 seconds and it takes place over 3
3
meters.
meters.
So if I wanted to find a full oscillation, which happens over 6 meters, I'd have to multiply 0.95 by 2. I just add 0.95 to 0.95.
1.9.
Are you okay with that?
Of course.
Yes, sir.
Yes, sir.
Okay. So I hope the person on YouTube understands it. Now we have to calculate the speed of the waveform. So speed, what's another word we just typically use for speed?
Velocity.
Velocity.
So I want you guys to think. We just find
V
frequency.
equals F lambda.
V equals F lambda.
What's the frequency?
0.53
Hertz.
by 6.
So give me a second. I'm gonna pull up the calculator on my phone so I can just do this thing fast. Make sure cross-reference all the calculations.
So
Yeah,
on the YouTube chat, we have 119 people.
that's a decent amount. For like the time it is.
For real, huh?
Yeah. Don't worry, just now, one day Mac Vibes will make it. For sure. But I low-key feel like I'm making it already. But like more. I wanna help more kids. A lot of kids need to see how cool science could be, you know what I mean? And they don't see that. They just
Oh
see
my
things.
God. So you literally reached 4.85K.
Oh, I wanted to hear something like 4.9. This is okay.
No, I'm pretty sure by as soon as the day we start paper, when we gonna see that 5K.
I hope so. But
So
like,
you doing paper ones for months tomorrow?
yeah, maybe. But like here what I was saying, right? Last year, December, I was struggling to cross 1K, guys. I was struggling. And then bam. Yeah,
Yes.
and the wavelength. What was the wavelength, guys?
6 meters.
6 meters.
And this over here is the wavelength I'm talking about. It's the wavelength. 0.53 by 6.
3.18.
Now, if you find the exact thing, if you say 1 over 1.9 and then multiply by 6, you're actually going to get 3.16. Watch. They do the exact thing.
Oh, I see.
That's the exact value. And I will say ms what?
-1.
I don't understand the exact, like, if, okay, if I use 1 over 1.9 by the 6, I get the exact value, which is 3.16
Yes,
ms.
sir.
I don't think CSEC can't take away marks for that, but just show the proper thing. Right. People on YouTube, I hope they're understanding. So here what, right? In the first part, I find the period. I use that to find the frequency, because I know frequency is 1 over the period. Bam, sorry, frequency. Another one to find for velocity. We know velocity is frequency by the wavelength. When we just find the frequency, the exact frequency is going to be 1 over 1.9. And my wavelength is just the distance between two successive crests or two successive drops, which is 6. So I will say 0.53 by 6. And I get 3.16. Yippee. All right, let me tackle this question now. A student investigates the refraction of light when it travels from the glass to air. Figure 7 shows the arrangement of the apparatus for the investigation. Let's label this quickly. Guys, which one is the incident ray?
The glass ray.
The
Yeah.
I mean,
G, yeah.
the line
Now
will
the
come out of
incident,
the
I like
box.
to think of the incident ray as the one that's going to the point here. It's incoming.
And what's coming out is a refracted ray.
The reflected ray.
Refracted. And this could be the angle of what?
Incidence.
Incident.
And what would I call this ray here?
The refracted ray.
Refracted ray.
And this is the angle of what?
The angle of refraction.
Okay, now let me explain something. The boundary is a line that separates the two mediums. As you can see, we have air over here, and we have glass over here. Boundary line separates. This, what you're seeing here, is called the normal, and it's always perpendicular.
Perpendicular.
Quickly, if I'm going from a more dense to a less dense, I would bend what? You remember?
Away from the normal.
Away.
Right? Alish? Yeah, that's correct. Bend away. Yeah, that's correct. I think I remember this from a live the other day. And if I'm going from a less dense,
you went towards. That makes sense.
It does make sense because when you look at
like
total
they'll be slower.
yeah. And when you look at critical angle and total internal reflection, you'll see that, like, if you're going from water to air, like the bigger the angle is, the more it's going to move away from the normal until it's like 90 degrees. That's the critical angle. And when you pass the critical angle, it will dip into water, and that's total internal reflection. Bend away from, I'm not saying, but bend towards. I want it to always be like fact checking yourself. If you say something that don't make sense, correct yourself one time.
Of course.
Have trust issues. That's what I'm trying to say.
Of course.
Don't rely on your ex and think to get your trust issues. Give yourself trust. Yeah. Or did I read yellow something?
If only your man was it. Yeah, all the exes.
No, it's Nikolai had the exes.
Oh yes, Nikolai who had all the exes.
So let me answer the question first. Now it's an easy question.
Of course.
They were we to calculate the refractive index of the glass. Now the formula I prefer to use is Ni sin I is equal to NR sin.
To NR sin R.
And this works when you're going from any medium to any medium. So here what? Let's tell them A is 48 degrees. This is 48 degrees here. And let's tell them that G is 27.5.
27.5.
And we know that the refractive index for A is what?
It is 1.
Right, and we're trying to find for the refractive index of glass.
Of glass.
So, I can write Ni sin I is equal to NR sin R. If you want, I can make it look a bit simpler for you. The incident ray is in which medium?
The glass.
The
So
glass.
this is
equals to
And the refracted ray is in which medium?
Air.
the air.
So I could say, cool. We're trying to find the refractive index of glass, which is this N over here.
Mm-hmm.
What's the angular incidence?
27.5.
Yeah.
And
What
that
is
is equal to 1 by 48, which is for sine 48.
so I'm trying to find for the refractive index of glass. So I gotta divide both sides by what?
Sine 27.
Sine 27.5.
And just like that again on subchat, this is not hard. This is not hard. It's real easy. So like I'm gonna want to get for the answer.
Ooh, 1.61. I'm not sure. Anybody else get on?
Putting it in right now.
Getting 1.61.
Yeah, I got
Yeah, I
1.6.
get us too.
Yeah, I get the same thing.
A pencil that again, boy. What's not? You're playing up. You're playing up. Why are you doing that for?
So why are the deep as in profile picture?
I don't know. Because I'm in deep into the physics. Are you guys getting 1.61?
Yes,
Yes, sir.
Yes, sir.
Approximately, yeah.
Okay, cool. That's the answer. Right. So I kind of calculated here, so I'm gonna just copy and paste it here into the answer sheet.
The notes look so cool. But it look too finicky at the same time.
This is like the worst notes I've ever do in my life. What you saying here? The worst.
So doesn't it have an app where like Apple have a built-in calculator? So like if you write out like an equation.
Yeah, but it kind of useless. I don't really use it. Can't remember the last time.
Mm.
Right, so now we're on to thermal physics. Great. Question 5 out of 6.
When all this paper was food.
It was it real easy. Hopefully you see how easy physics is then. They're real putting effort into these diagrams, boy. Okay. Okay. Let's see it.
I
See you
hope the
next year.
person that draw
I
that
sure
get
it
paid good, yeah?
I sure it didn't look like that in the exam. I sure it looked like a splotchy mess.
I don't know. So I read that from my facts.
Figure 8 shows a standing steam iron which Caleb uses in his laundromat. The tank is filled with water, and the steam iron is used until 80% of the water has been converted to steam and released through the ironing plates.
Ooh. I try to understand this. So if I heat an element here. So here what? If I see a heat an element, I already thinking about like P is
Conduction.
equal to IV. I thinking about P is equal to IV and thinking power, kind of thing.
Oh.
Yeah, because like we go see. I don't know. I didn't do the question yet.
I see copper.
We have a heating element here. The heating element, you'll have to supply electric power to it, and it will convert the electric power to what?
Heat the water.
Heat energy.
Heat
Heat
energy.
energy.
So
So
here
that's
what?
that.
Yeah? So that
Yeah.
again?
No, man.
All right. So hopefully you understand everything so far.
Mm.
Now, the water that's in
Yes, sir.
contact here with the heating element is gonna what's gonna happen to it?
It's gonna get heated by
Heat up.
conduction.
It's gonna get heated up quickly. And so the water at the bottom is gonna become hot faster than the water at the top.
And rise to the top.
And it's gonna rise to the top. And then it's gonna cool here. Then it's gonna like
Sink.
inside here, what you have what currents?
Convection.
Yeah, convection currents.
Convection. So a convection is not only just air. Is any fluid.
Is any fluid.
So gas is on liquid. I thought it was like conduction, but nah. That makes sense though. So like conduction is seen if it's like contact with solids.
Conduction is like in contact.
Okay.
Explain how the water in the tank of the standing steam ion is heated by the process of convection. We call that. 'Cause I never do this paper before, right? But I mean, you could like read these questions on. It's not.
As the element temperature increases, the surrounding water is heated and rises. Then the cold water sinks, and then is heated and rises.
Let me see if I can write answer like real short. Where's the heating element situated?
At near bottom.
Right. The heating element at the bottom of the tank heats the water. Correct. Perfect. This water would what? The water that's
Rise.
directly above the heating element, this water would what?
Heat or increase in temperature and rise.
But why? You have to say that this water what? This water starts with E. Remember, like, okay, if I apply kinetic energy to particles, it's
But there is
gonna
more
become more
frequent
energetic.
collision.
more energetic, so it's gonna
More
want to
thick.
occupy. It's gonna want to occupy more area.
More area.
So it starts with E. If you occupy more area, you're what? You're what? You're what?
Expanding.
Expanding.
All right. So the water expands, and if it expands, it's gonna become what?
Yes.
Less dense
Less than
and rise.
and rises. Bam. Cool.
So
The
if it rises, it would displace the cooler water, making it sink down. Or you could say that.
that is also correct. You could say that as well. That is also correct because if you're pushing water up, it's gonna push the water down. That's a
Yeah.
Iran, you're real smart, boy. You're real smart. Iran is real think. Yeah, now who sound like you know? Who sound like you? I hope you aura like you and you think like you know what I mean?
Of
Guys,
course.
don't let Nikolai hear this.
Oh yeah, Nikolai go. Hey, Nikolai blood go. Boy. Romano too. Romano real cool too. Right?
Was the word people place animal and thing.
Yeah, boy. The cooler, denser air what?
Sinks.
At the top.
Yeah.
Top 6. Right. This cycle continues. And is called convection currents. I really tried to just get a fast answer there. So the heating element at the bottom heats the water directly above it. This water expands, becomes less dense, and then rises. The cooler, denser air at the top. What's the air, boy? Ugh.
Water.
Coconut water. I look the guy young, you know. I know. I know all the latest
I didn't even know that one.
You had to know.
Coconut water.
Nah, I just think
Coconut water.
it too cringy for me.
When I hear that song, I thought it was Nicki, no. I thought it was Nicki.
Nah, sir, you're pushing it.
No, I well thought that was Nicki. I'm not even lying. I thought that was Nicki.
Oh, that next question is cake. Oh my days.
Say the name of the process by which water is converted to steam?
Evaporation.
No.
Vaporization.
Oh my days.
Let me
Vaporization.
take this chance to distinguish between
Latent heat of
evaporation.
vaporization.
Let me take this
That
chance to
occurs
discuss.
throughout and one occurs on the surface.
Yes. And I have more, I have more.
I appreciate
So,
this.
evaporation, it occurs at the surface.
Because it's actually the same thing with boiling.
So wait, let me explain something. So like, Aaron, you do bio?
Yeah. Oh, if I do in bio, no.
Yeah. Oh, I want to talk about transpiration and how it is increased, when the wind is stronger. But like, okay, anyways, Aaron, imagine you have a shallow pool of water, right? When wind blows by, occasionally it's gonna it's gonna give some particles at the surface of the water enough energy to break away from the bond and be like it'll go into the air essentially. This would happen on
Yeah.
the surface only. This would only happen on the surface.
Mm-hmm.
Right? So some particles, the particles with enough energy would go to the surface, and if you get a
So
light,
you're trying to say vaporization happens to the whole body.
vaporization happens throughout, but it has to happen
Throughout
at a
this.
specific temperature.
So the
Evaporation,
whole okay.
evaporation occurs at the surface and at any temperature. Are we saying so? What do you mean by that? Let me ask that question. If you spill water in your room with AC, that water can't stay there forever?
Ah.
If you spill, okay, if you have a room with AC and you spill water, if you leave it for like 3 days or something, it evaporate less than 3 days. And then eventually evaporates.
Yeah, so
Yes, evaporation takes place at any temperature and it only occurs at the surface. Vaporization occurs where?
Throughout the body.
The whole body of liquid or water.
I wouldn't say throughout the body, I would say throughout
The whole medium.
liquid. Or you could say fluid if you want. Occurs throughout the liquid, and it happens at a specific temperature. Specifically, the boiling point. So this is a good opportunity there to discuss evaporation versus vaporization. That come tomorrow, big up, big up. So this is vaporization. And I should know this because when you're doing thermal physics, you have LV and you have LF. Isn't okay, the definition of specifically is a heat of vaporization. Isn't that the amount of energy you need to convert 1 kg of a substance from solid to liquid?
Liquid to gas.
Liquid to
What's it?
liquid.
What's it? Solid to liquid, but
Vaporization.
sorry. Liquid to gas or vice versa. You just learn that. You just learn that. And it's called latent heat of vaporization for a reason. Right. All you understand that?
Yes, sir.
Yes, sir.
Yes, sir.
Right. Using the kinetic theory of matter, fully describe the process named in B part 1. Oh my days.
So much yapping.
I hate this
Particles.
question.
Matter
Oh
is
my.
always in constant motion. Something like that.
Jesus.
Shut up. I hate these type of questions. It's so buns, like, come
Yeah,
on, man.
lap.
I don't want to
lap.
write.